In this video series, we're building a high-performance stock exchange in C++ from scratch. At its core, a stock exchange has to do this: accept orders from buyers and sellers, decide which ones should trade, and publish the results. Conceptually, that's simple. The challenge, however, is that it has to make those decisions millions of times under constant load while remaining completely deterministic. It can't occasionally pause because memory needed to grow, a log was contested, a network message arrived in pieces, or two parts of the system disagreed about what happened. That's what turns this simple idea into a high-performance system. To achieve that, we need to represent prices and orders safely, build an order book that enforces price-time priority, and implement a matching engine that correctly handles partial fills, cancels, modifications, market orders, IOC, FOK, stop and stop limit orders, icebergs, and post-only orders. And that's what we'll build in this video. In future videos, we'll build everything around that engine. We'll implement a binary TCP gateway that brings orders into the exchange, a pre-trade risk gateway that checks limits, ownership, price collars, and kill switches before an order can affect the market, and a sequencer that assigns every accepted order a global sequence number while writing it to a journal so the exchange can recover and replay its state after a crash. We'll also build a market data system that publishes an itch-inspired UDP feed, detects missing packets, and recovers clients using snapshots. We'll build a trader terminal as well that tracks orders, fills, positions, and PNL, along with a liquidity bot that keeps the market active. Finally, we'll connect every component into one live exchange. The important part here isn't what we're building. It is important, but what's more important is how we're building it. Performance isn't something that we're just adding towards the end. It is designed into the system from the very beginning through fixed point prices, fixed layout messages, pre-allocated memory pools, intrusive order queues, cache-aware SPSC ring buffers, bounded back pressure, logical timestamps, and hot paths that avoid surprise allocations and lock contention. You don't need any prior finance knowledge to continue along with this video. We'll introduce every concept as we need it. On the C++ side, you should be comfortable with functions, classes, templates, and the standard library. That's all. We'll be using C++20 throughout the series, so ensure you have that installed. By the end of the series, you'll have built a complete runnable trading system, one that can accept the order, manage the risk, preserve its history, match the trades, publish market data, update the clients, and more importantly, it gives you an understanding of why low latency C++ systems are designed the way they are. Let's get started by building the foundational types, zero allocation infrastructure, the order book, and the matching engine in this video. The first step for us is to set up a project. To set up a project, first we obviously need to create a folder. Once we've created a folder, we're going to add a CMake lists.txt file. What is that? It is just an instruction manual for building the software project. You know, what language do you want to use? C, C++, Fortran. We want to use C++ obviously. Then what C++ version number do you want to use? 17, 11, 20. And then all the dependencies we'll need, all of the files that are present in our system. We need all of that. Okay. So we'll add that to the CMake list.txt file. And then it will just tell a tool called CMake exactly how the code should be compiled and put together. I'll talk more about the CMake build system in a while, but yeah, that's what we want to do to set up a project. So let's go ahead and create a folder. So I'll go to the desktop where I'm going to create a folder. After that, I'm going to call make directory. MKDIR stands for make directory. And then I'll pass in stock exchange because that's what we're trying to create. After that, I'll cd into the stock exchange and then hit enter. After that, I want to open this up in Cursor, VS Code, whatever one you prefer. I'll just open it up in Cursor. Okay. So let's just go ahead. We're not using the AI feature here. I've also set the tab completion to false. So we'll not be using that because it will just get annoying in the demo when I'm writing out the code. So yeah, now I'm going to create a new file called CMake lists.txt file. And here we're going to specify how our entire thing is going to work, right? What we need is, first of all, what is the CMake minimum version required? That's what we want to specify. But first, what even is CMake? CMake is the build system. This single file, cmakelist.txt, is the recipe that will turn the entire source tree into runnable programs. So if we add a main.cpp here or any other CPP file, it's just a CPP file. But what we want is to convert it into a runnable program. And we want to ensure that all the C++ files are connected to each other. For example, if I have a C++ file that includes another C++ file, we want that entire source tree to be connected, right? And for that, we need the build system. You can obviously go ahead and just use CMake or G++ just like that in the terminal and compile it. But when we start to have 10, 20, 30, 100 C++ files, it gets a bit annoying. So that's why we're maintaining the cmakelist.txt file. This cmakelist.txt file is going to be kept very simple. We are not going to do much more than that. It's just like we're going to specify the files that we need and one small dependency module. Nothing too complex. So the first thing we need is what's the CMake minimum required version. We'll be using version 3.24. Now, why are we using version 3.24? Why not 3.23, 3.25 or any other version? Well, that's because the older CMake version had a clunkier fetch content behavior, and fetch content is how this project pulls in third-party code without rendering Git submodules. I'll talk more about fetch content in a bit when we add fetch content related stuff, which is just the next line or next fourth line or something. But yeah, we need this version 3.24 because the previous versions had clunkier fetch content. If you want to switch to a newer version, go ahead, try it out, see what happens. Also, one thing I forgot to mention is that you need to have CMake installed in your system. If you want to install it, you can just do brew install CMake on macOS, or you can find it on your distribution on Linux. You can just search the web or ask ChatGPT how to install CMake. I'm not going to get into that. The next thing we're going to have is project exchange languages CXX, which is basically C++. So this is giving the project a name which is called exchange. You can also call it stock exchange, whatever you want to call it. Then we have languages, what languages are we going to use? And we're using CXX, C++. So we are strictly telling CMake that, hey, we're not a C project. We're not a Fortran project. We're not a mixed project. We just want C++. By default, CMake will have C and C++. If you want to specify Fortran, just for context, you can just go ahead and do Fortran here and it will have the Fortran compiler baked in. But we just want the C++ version, not the C, which is by default, we are going to have C and C++. So we are strictly telling we just want C++. After that, we're going to specify anything we need from CMake itself. In the initial version, when I was creating the project by myself, I had included the C test line here. So something like include C test, that was present. But now we're not going to add testing here. So I'm not going to include it. But what I am going to include is fetch content. So let me just have include fetch content. So what is this fetch content? Fetch content is the modern dependency mechanism. It will clone an external Git repository during configuration. It will build it as part of the project and expose its targets to us as if they had been written here. So it does not go to the Git repository and try to fetch it in real time, which would probably lead to latency issues and we would have to be connected to a network or whatever. What it does, it goes to the dependency that we need, its GitHub repository. Then it will fetch that Git repository during the configuration. It will build it as if it is a part of a project. Like we have all of these files created here. It will just treat them like that and then expose its targets to us, like we have written here. That's how fetch content works. It will just lead to a better system, which is less latency, less complexity. All it's doing is just cloning it into our system. Great. Now the next thing we want to specify is the C++ standard. What version are we using and how our compiler should behave if it does not find that version. Also, by the way, this file is looking very plain because it doesn't have any syntax highlighting. It's not giving us any auto typing features. So what I'm going to do is go to this extensions tab. If you're in VS Code, you'll be able to see this. Just type in CMake. You'll find some extension similar to this. Just install it. I'll trust publisher and install. And once it's installed, this will look much better. I just don't want to see a plain white file, you know. Okay, great. So now that we need to set up a C++ standard, these are the 3 lines I'm going to paste in. The first one is set CMake C++ standard to 20. So we'll be using version number 20. And we're deliberately using this. If you use 17, it will not work in this project. If you use 11, it will not work. We need strictly 20 because in this project, we'll be using C++ 20 related features like standard span. This is a feature that was introduced in C++ 20. And almost every function that we create will return a list of events, and it returns a span over a reusable buffer. I'll talk more about that when we get to it, but yeah, that's what we're going to have. We're also going to have attributes like this, where you have, you know, like something like this, where you have likely and then unlikely if you're likely to use it, unlikely to use it, so that we can optimize how it's laid out in the instructions of assembly. Okay, so yeah, these are all of the features that are present in C++ 20, and we do need to use them. Several of these features are not present in C++ 17, so we cannot use that. The next thing is CMake C++ standard required on. This means if the compiler does not support C++ 20, we want to fail loudly, not fail silently during configuration. Without it, CMake would silently fall back to C++ 17 if it does not have C++ 20. And then half the code base would fail to compile with, you know, cryptic errors showing up, which you'll not be able to figure out. Or you might be able to figure it out. You can just ask Claude or chat, whatever. So anyways, the point of this is that it will just fail clearly. The last thing we have in the C++ standard is CMake C++ extensions set to off. What does that mean? Well, first of all, what does extension even mean? It means that your compiler is only allowed to accept official C++ language features, not extra features that are invented by the compiler. Think of this C++ language as a rulebook. There's a C++ standard written somewhere, C++ 20 standard written somewhere. So the C++ version 20 has a certain standard, and that is the official rulebook. But there are many compilers like GCC, Clang, Microsoft has their own called MSVC, I believe. So sometimes they add their own extra rules, and those are called extensions. For example, there's a GCC extension called something like type of, similar to how it's in Python, right? So what's type of XY, right? So this might compile in GCC, but it will fail in MSVC because type of is not a part of standard C++ 20. It is part of the GCC compiler. So what we're saying here is that, hey, you cannot have compiler features. You can only have C++ features. So with this line, you are sacrificing on something, which is convenience. You can have multiple features that would not make you write, like, let's say 3 lines of code, you could just write 1. But you are getting portability because what you write in this C++ project will be used across all the compilers because all the compilers definitely support C++ 20. So yeah, that is a deliberate decision we're making here. The next thing we need is the build option. For the build option, the thing is I had 2 toggles here when I was building it. The first one was, do we want to enable tests? And yes, we did have tests in the initial version, or, you know, when I was building it. But now we don't really have unit tests. The other thing I had was benchmarking. Is something we're not going to add in this system. I know it sounds very weird that in a stock exchange where speed is the biggest factor, we're not adding something that is going to test how the speed is affected with each feature that we add, each thing we do. But yeah, I don't want to make this project too long. The duration should not be too large. So I'm not going to get into most of these features, right? We're going to focus on the main stock exchange part, and rest of the things, you can build it out yourself because those are dev tools, right? Benchmarking is a dev tool. So you can add it yourself, see, and when you try to expand this project, well, you'll have to read more about how to ensure that the code you're writing is efficient code, and you'll have to research yourself. And when you do that, you have some hypotheses, you can just add benchmarking in. And once you've added benchmarking, add your own feature, and then you'll be able to see the difference that your feature causes. Most of the time, it's just going to be noise. If you're having, you're just doing maybe something like time.now. I'm just using Python here, but like time.now, and you just have some code present here. Okay. So with this, what you've done is, well, before the code starts, you've measured how much time it is, after the code how much time it is, and then you subtract both of the times and you'll get how much time it takes to execute this code. And in the benchmarking, you'll have to run it maybe 10 times, 5 times, so that you can take an average. Otherwise, it will just give you a lot of noise, because we're out here measuring in microseconds, milliseconds, sometimes even nanoseconds. So it's obviously going to be a lot of noise that you'll face. Or if you find a better way to benchmark, let me know in the comments. I've not researched much on that. Anyways, we're going to ignore the build options for now. The next thing we're going to add is dependencies. And this is what we're going to add. What this means is that we are going to include the file cmake/dependencies.cmake. So something like cmake dependencies.cmake. So we are including this file as if its contents were here. It will keep the third-party stuff out of the main file, and we will look at that file in just a moment. But yeah, what it does is it's just clean. You can shift all the dependencies to this dependencies.cmake and just have the main configuration options here, and the dependencies will be maintained in a different file. So if you want to add more dependencies in the future, you just have to edit that file, not the txt file anymore. So that's what it is. CMake current source directory, which is what directory we are in, /CMake. And then we include dependencies. Cool. The next thing is the core library target. So we add this line where we say we're adding the library exchange project interface. So this single line is kind of the structural decision that will shape everything else. So what is this line doing? To understand that, first we will need to understand how does C++ normally build. In a normal C++ project, you might have seen there are two kinds of files. You have header files, .h, which holds the kind of the announcement that this function exists, this class exists, etc. Then you have the source files, the .cpp files, which holds the real code, the actual function bodies. So the compiler takes each .cpp file that's present, it compiles it into a chunk of machine code, and then a step called linking glues all those chunks together into one runnable program. A library in this normal world is just a pre-compiled chunk of machine code that you can reuse. So I hope we are clear until now. Header files, source files, and the library. We know what all of that means. Now, what is this project doing instead? This project is header only. There's one CPP file that we're going to have. Rest everything is going to be in header file. So the real code isn't split out between CPP and header files. Everything is just in header file. And as I said, there's only one CPP file called main.cpp, and that's the program's starting point. Now remember, this hash include that we have, this hash include line at the top you might have seen in C++ code, it's just a dumb copy paste. So when the main.cpp includes the engine's headers, the entire engine's real code gets copy pasted straight into it and compiled right there all at once. So this kills the idea of having a normal library, right? A normal library is a pre-compiled chunk of code. But here, there's no code sitting in C++ files waiting to be compiled ahead of time. It's all in the headers, and headers only turn into machine code at the moment they're copy-pasted into a program that uses them. So if I have a program like, main.cpp and I'm including, let's say, an order book there. So it will just go ahead and paste the code of the order book right there and there. And then we can have other parts of our main.cpp like this one, correct? There's literally nothing to precompile into a .a or .so file that would generally happen. A traditional add library where we would specify static or shared here instead of interface would be an empty, pointless file because there's literally no code. We are having headers there. However, we still do need shared settings, right? Even with no code to compile, every program in the project still needs to agree on things, like where do we find all those header files so that hashed include will work? Which C++ standard should we use? Which compiler flags do we apply? You don't want to repeat that setup in every program by hand. You want one place that holds it. And this is what this line does. The interface keyword says that, hey, we want to make a library that contains no compile code. It only has settings to hand out. It's the settings bundle from before. It produces no file. It just holds the include paths, the C++ standard, the flags, and whatever else is needed. So when the main.cpp file will say, hey, I want to use this Exchange project library, it's not pulling in machine code because there is no machine code. It's inheriting those settings so that it knows that, hey, yeah, where are the headers, where are the flags? And then it will compile itself and it will copy paste the whole header only engine as it goes. So to summarize, what this line is doing is that since the engine will live entirely in headers, there's nothing to pre-compile into a real library. Interface makes a code-free bundle of settings instead, and the single CPP file that we have main.cpp will inherit those settings and absorb the whole engine via hash include when it builds. After that, we are going to add this line, target include directories, Exchange project, interface, and then the source folder. So when something links Exchange project, we're just saying, hey, you get the source folder on the include path. So hash, maybe we're going to create a file called types.h, which will just have all of the type structures present. So if you do something like hash include, something like core/types.h, this will work because the compiler resolves that to something like src/core/types.h. This is the only reason the includes look clean across the code base. We don't have to specify this source. We can just do core/types.h and it will automatically add that source. The next thing we need is the compile features. So we'll have the compile features of Exchange project, interface, C++ standard 20. So even if some downstream sub-target tried to compile against, Exchange project library, this library, and let's stop the agent, Exchange project library with C++ 17, this will propagate the C++ 20 requirement that we have. After that, we're going to add the compiler flags, and these are the things we're going to have. Exchange project library, interface, and these are the 4 flags that we are setting. The first one is WALL, which is enabling most warnings. It stands for warnings all. So it will enable most warnings like, unused variables, signed or unsigned comparisons, missing return statements, like all of the basic stuff. It will add all of that. Then we have warnings extra. It will add more like empty bodies, unused parameters, unused results, suspicious comparison, all of that. Then we have warnings pedantic, which is we want to warn on anything that uses non-standard C++ features. So this is kind of going with the CMake C++ extensions off. We don't want to use any non-standard C++ features, right? So yeah. And finally, we have if no exceptions. It is an unusual one and it will deserve kind of a long explanation. So the point of this is that we are disabling the C++ exceptions. Now, why are we disabling the C++ exceptions? Well, that's because C++ exceptions like throw, try, catch, they're a mechanism for error handling. So when something goes wrong, you throw an exception and the runtime walks up the call stack looking for the catch block to handle it, right? let's take a code example. We have try, then we have some code here, and then we have catch, where we have, let's say, an exception. And yeah, so once you've got something, it throws an exception from here. The runtime walks up the call stack looking for the catch block to handle it. It will destroy the local objects along the way. And this is convenient, but it is also expensive in 3 ways that will matter for a stock exchange. The first one is unpredictable latency. So when an exception is thrown, for example, an exception is thrown here, the runtime walks up the stack. It finds the destructors to call so that, whatever is constructed will be deconstructed. All the proper cleanup will happen. It will find the right catch block, and then it will transfer the control. This can take microseconds. On a hot path, by hot path, I mean path that matters to us in terms of latency, the code that is most often used in the stock exchange. If we do that on a hot path, every order will have to take this extra microseconds. And occasionally it will take 100 times longer because something exceptional happened, and well, we don't want to do that. It is just the wrong shape. The second is there's a hidden control flow. Any function that might throw creates an invisible exit path. Let's take an example for that too. So let's say we have something like auto value is equal to, maybe we have some map dot at, and then we are trying to get a key. Okay. So we are just getting a value from some map. Now, if the key is missing, this at will throw. The function you're reading might suddenly exit through a different door. For a system whose main loop is process every accepted order in deterministic replayable order, the invisible exits that we have are a problem. We want all the control flow visible in the source code. We don't want any hidden control flow here. So that's the second thing. The third thing is the binary size and the instruction cache pressure. To make exceptions work, the compiler emits unwind tables. What are unwind tables? They are metadata sections in the binary describing for every code address how to restore the registers, which destructors to call, which catch handlers match. Just to give you an example, let's say the table is like a map, okay? And in this map, what we have is some metadata sections describing for every code address. Maybe your code address is some hex like this, okay? Maybe this is your code address. Now in this, it will describe how to restore the registers. Maybe it has another kind of map here. Obviously this is not in a map, these are all in binary. I don't know how they're displayed, but just for visualization, this is how they are. And in there, they have how to restore the register, and then it contains how to restore them. Then maybe there's all the destructors that should be called. Because all of that knowledge needs to be stored somewhere, right? And that's what the binary is doing. And it contains all of these instructions. And these tables, well, they just sit alongside your code in the binary. Because of that, the binary size increases. Now, to really understand why this matters, you need to know how a modern CPU will fetch code. So the CPU has an instruction cache. Okay, what is an instruction cache? It is just a tiny kind of scratch pad of recently used instructions sitting right next to the execution units. And this is the diagram for that, okay? You have the main memory, L3 cache, L2 cache. What we are interested in is the L1I cache, because that's the L1 instruction cache. And we are going to talk about L1D cache and L1I cache more in the future. But know this L1I cache, which is typically around 32 kilobytes on, let's say, a modern x86 processor. So this is a tiny scratch pad that contains recently used instructions, which is sitting right next to the execution unit, right? If the next instruction the CPU wants is in the L1I cache, the fetch will take about 1 nanosecond because it's so close to the execution unit, right? So if it has to go to L2, for example, which is typically bigger storage unit. It has about 256 kilobyte to 1 megabyte. So it will take obviously 10 nanoseconds, just more than the L1I cache. If it has to go to the RAM, which is the main memory here, it will take 100 nanoseconds. So as you can see, the difference is like 100x. The hot path of the exchange, the part that I said will run millions of times per second, is small enough to fit comfortably in L1, 32 kilobytes. The point is, it can fit comfortably in L1 if we keep it lean. But once the binary starts pulling in exception, unwind tables, runtime exception support code, and throwing variants of standard library functions, the hot path starts to compete with all of the machinery for the same cache lines that would be stored in L1I cache, and the CPU starts missing more often. Your matching loop, which fits in L1 when you measure it in isolation, will no longer fit when it shares the cache with exception infrastructure that we've built out, or not we've built out, but that's present in the binary. So to just make it more concrete, let's say we have something like this. Maybe our L1 cache would be, and why is this small? Let me make it big. So let's say our L1 cache would be something like 1 nanosecond for L1I cache. Okay, this is I cache, not the D cache. D cache is the data cache. We're talking about the instruction cache. If this L1 cache is hit, it's 1 nanosecond. If L2 is hit, it will take 10. If let's say L3 is hit, that's maybe 30. If the RAM is hit, that's 100, right? So as you can see, it just gets bigger and bigger. And if we just have the hot path size, so let's say we have hot path size and let's make that bigger. So if we just have the hot path size, where the size is, let's say, small, or maybe we can say it's maybe 20 kilobytes, okay? And then you add the exception tables on top of that. If we add the exception tables, we'll have, let's say, 10 KB more. Then we have the runtime helpers for these exception handling. That will add, let's say, 10 KB more. These are all figures I made on the top of my mind. This is not all true, but it's just to prove a point that when this happens, you're adding more size to the binary. You're just increasing the size. So what could have fit in this L1 cache, which was 32 kilobytes, will now not fit because it's 40 kilobyte. So the CPU will have a miss here, a miss there, and the fast engine will suddenly run at the L2 speed, not the L1 speed, which is 10 times slower. And this is what people mean, when they say like exceptions cost predictability. By disabling exceptions entirely, every error will become either a return value, so you'll either have a boolean, an optional returned, an enum class, all of that, or it will be a terminal standard abort, because the condition is a startup bug that should never happen in production. So you'll see both these patterns, like a return value of boolean or optional, or abort just happening, and this will happen in our code. And it will look scary. The abort especially looks scary, but inside of, our philosophy here is that this can never happen unless capacity was misconfigured at startup. It's better to crash a single test run than to silently corrupt all of the market state. That's why we're doing what we're doing. So I hope that's understandable. After this, we are just going to go ahead and paste these 3 things in. The first one is add executable, exchange source exchange main.cpp. This is a main.cpp file. The executable I said there would be, which is just the one source file that we have. This is only possible because everything else is in headers. Exchange main.cpp includes them and instantiates them. Then you have target link libraries, where you just say that this exchange that we have will be linked to the exchange project that we defined up here, where all of our headers are going to live. And then we have the set target properties, where we say that, hey, this exchange that we have, the properties it has is this, the output name. Well, that's going to be called exchange, And the runtime output directory of this is going to be, well, something like build/source/exchange instead of, having build/exchange or whatever. That is why when we try to run it, we'll be using ./build/src/exchange rather than anything else. And the same pattern will also repeat for the trader terminal and the liquidity bot that we have. So let me paste in this thing. The trader terminal is just, the nice terminal user interface that we're trying to create so that the user can interact. It has nothing really to do with our engine as such. The engine and the exchange is this part. This is just a nice TUI that I thought like we'll just add on top of what we have so that we have a nice demo to give. So we have trader terminal, which lives in tools/traderterminal.cpp. Then we link the library to the exchange project. And then the trader terminal, the output name is this, and it will live in this /tools. And similarly, we're also going to do it for liquidity bot. We'll talk about liquidity bot when we get there. But the point of this bot is just to, feel like there's liquidity in the market. If you understand that, well, good. If you don't, we'll talk about it later when we try to build the liquidity bot. But for now, I'll just copy paste it here. Again, similar thing. We have liquidity bot. It's present in tools/liquidity bot. Then we link the library exchange project. Then the output name is liquidity bot and the output directory is the same one as the above trader terminal. Okay, I'll just minimize this a little bit so that you can see all of these things at a glance. So yeah, this is how it looks. After you've understood this, I'll just maximize it again and let's move forward if there's anything else to add, because other things I had were related to benchmark toggling here. And since we don't have benchmarks, we don't need to add those things. But the point here I was adding, just in case you want to know, is that we also add the executable, link libraries, set target properties for the benchmark. And for that, we link the libraries of exchange project, but we also add the histogram. It's called the HDR histogram library that we're trying to use. This will just give us a nice histogram output just to visualize stuff properly. Then we use the matching bench library, which links the Google's benchmark so that we can just, do the benchmarking clearly, properly, all of that. And yeah, that's pretty much it. That's the entire CMake list.txt file that we have. The next thing I want to add is, if you remember, I told we also have a dependencies.cmake file, and that is present in the CMake folder. So here we go, we have dependencies.cmake. And now that I realize we don't really need the dependencies.cmake because the dependencies that we wanted to add go within the unit tests. We wanted to have a unit test framework or library, and then we needed the Google benchmark that I talked about. Well, we don't have either one of them, so we can directly just remove this, and in the CMake, I can go ahead and say that the dependencies part, where we add dependencies, where is it? Oh yeah, this is where it is. And we just go ahead and remove this line because, well, we don't have that anymore. So yeah, this should be enough. Now I'll just go ahead and create this exchange main.cpp file. And if you remember, we need to do that within source. So we have source exchange main.cpp. And here I'm going to do the simplest thing ever. We are going to have int main. And then I'm just going to do standard cout hello world. And then I'll have standard endl. And then obviously we need to go ahead and have hashtag include, and then we have IO stream, then we have using namespace std, and yeah, that should be enough. Now, how do we go ahead and build this project? So there's two steps. The first one is configuration. So the CMake build system will read the project and write out a detailed build plan. And the second one is the build, a tool that will follow the plan and actually compile everything. So to configure, the command we'll be using is this, So open up your terminal, then you have CMake, which runs the CMake tool. Then we have -G Ninja, which will generate the plan in Ninja format. What is Ninja? Ninja is a fast build tool. You're telling CMake to write instructions that Ninja understands. Other options exist as well, like make files, but Ninja is just quick. Now you might say, hey, I thought CMake is the build tool, not Ninja. Well, that is a common confusion. No, CMake doesn't compile anything. CMake never compiles your code, not a single line. CMake is a translator. It figures out what needs to happen and writes the instructions down. Then a different tool actually does the building work. So people call this a build system generator or a meta build tool. It builds the plan, not the program. So Ninja is the fast modern version of the build system. There's also other things, as I mentioned, like you can also use the make, which is the most common one as well. And yeah, you can use that, but Ninja is just fast. Why would you use anything else? I mean, sure, you can. And what this flag here is doing is that it's just telling, hey, CMake, translate my project into Ninja's language. If you'd written -G, let's say Unix make files instead, CMake would have written instructions for make, and you'd then run make instead of using Ninja. That is the next step, okay? So now that we have -G Ninja, after that, we're going to specify the build type. So do you want to build in release mode, meaning we want to optimize for speed? The alternative is debug, which is slower but easier to troubleshoot. -D that we've added in the first just means, hey, we want to set a setting, and the setting's name is CMake build type. And what are we trying to set it to? Well, that's release. So we can have release because we're trying to optimize for speed. Then we have -S, which is, where is our source file? And our source file is here. So I'll just say dot in the current folder. After that, by the way, our source file is here, meaning the CMake list.txt file is here. That's what we are concerned about. After that, we have the build file. So we have -B, and then we have the build. Where's our build directory? Well, in the build directory, just put it there. This will keep the generated code separate from the actual code, which is great for us. So let's hit enter now. And we have an error because we do not have tools trader terminal, tools liquidity bot. And yeah, that's obviously going to give an error, right? So let's just create it now and we'll populate it later on so that we get rid of these errors. So let's go ahead and have our file, tools trader terminal. Then the next thing is tools liquidity bot.cpp. So let's have that too. And well, let's try to run it again. And it says build files have been written to stock exchange build. As you saw, this is really fast. And we have our build files here where we have CMake files, source, tools, it copies our entire folder structure. It contains instructions for Ninja. And yeah, that's all good. The next thing we want to do is build it. We'll build it using Ninja. If you'd using something like make, CMake, whatever, you would have to do make here. But now we'll just do Ninja. And then we'll say, hey, we want to change into the build folder first, right? And then follow the instructions CMake left there. So we'll have -C build. So this is the step that will read all of your headers, compile the exchange main.cpp, all the thing about the header only engine, like we discussed before. All of that will happen here and it will produce the runnable program. So this is usually the slow step. And we do have an error because Trader Tools terminal does not really have anything. To fix that, what we can do is just copy paste everything in the Trader terminal and the liquidity bot. Now let's try to run those two commands again. So I'll just clear off everything. And now what we need to run is we'll go to the build folder, then we'll go to the source folder and we have our exchange here. So I can just do ./build/source/exchange and there's a hello world. If you want to do it for liquidity bot trader terminal, you can do it. As you can see, we only had to type in exchange because in the CMake list.txt, that's what we had specified is the name of this thing, right? Where we have exchange. Great. So everything here is completed. If you want to add unit tests, which I would actually recommend you to do, you can just go ahead and add it. The next thing we're interested in now is, well, we'll go to the source. Here we're going to create a new folder called core, within which we're going to have a types.h file. I told you we're going to specify all of our common types in this particular header file, which will contain, things like what is the price going to be? It's going to be a 64-bit integer. So we're going to specify that. Then how is our structure for all of the things that we're going to use look like? And yeah, we're going to dive into all of that now. So let's get started. Before we get into the types.h and what we need to write in there, first let me make sure that, all the C++20 features are activated for cursor. And to do that, we'll have to go back to our CMake list.txt file, and here we'll have to add this line in. CMake export compile commands on. What this will do is create a file called commands.json or compile commands.json in the build folder that will allow cursor and similar IDEs to know that C++20 is being used, and we'll be able to see all of the features in place. Also, one thing you'll have to do is open up the terminal, and here you will have to run the following command again. So the commands we ran to build up our system, we'll just run those again and ensure that, everything's working. I'll also print out the hello world again just to see everything's working. And now we'll be able to use the C++20 features. Otherwise, if you remove that line, rebuild the system, you'll see that whatever we type in that is specifically C++20 will not show up. Okay. Now, having understood that, let's try to understand what types.h is. So this, you can think of this as like one of the most important files in the project because, this is the shared vocabulary that every file will use. We're going to specify the types. We're going to specify certain structures. We're going to specify the enums that will be used throughout the entire project, and also kind of lay a roadmap or a mind map of how things are going to work. So this is very important. There's nothing clever going on here. Maybe a few things that you might not have seen before, but it's relatively straightforward. So the first thing we want to do is just have all the imports in place, and also obviously have the pragma ones. One thing you'll notice is that we have algorithm array, C standard int, string view, type traits, but we don't have anything related to, allocation, vectors, maps. None of that is present here. The whole file is about types, not containers. So we're not getting into that. The next thing we have is, everything will be wrapped in a namespace, obviously. So we'll be having an exchange core namespace being used. Classic C++, nothing too strange going on here. And this is called core, by the way. Most of the subsystems we'll create will live in subnum namespaces. So we have exchange core here. We'll also have exchange matching, exchange risk when we get to risk and surveillance. So yeah, all of that. But when they import the names, they'll import it from exchange core namespace. Okay. And just to ensure everybody's on the same page, we use namespace so that none of the functions we create, in one file or in one namespace, they don't collide with other namespaces. Had there been no namespace and we just defined functions like that, there could be a possibility that there are multiple functions that collide with each other, and that will cause confusion, and we obviously don't want that. So we have a namespace that directly creates, or where we can create a bunch of functions, and that will help us out. Okay, great. The next thing we'll do is set up this structure. So using price is equal to standard int 64t. So this line is the most important decision that we're taking throughout this project. Okay, we are representing price as a 64-bit integer. Understand this, it's a 64-bit integer. Generally, prices, especially on the stock market, they're not integers. They're floating point or double, right? And here we are representing that as integer. So if you have a stock price, let's say the stock price's value is something like 150.25, you'll represent that as something like 150.2500. Okay. If you have something like, let's say 0.0001, you'll represent that as something like this. It will be 1. And so on. So if you have 1.000, that will be 10,000. So we are multiplying it by a scale of 10,000, and we'll be storing that integer as well called price scale. All of our operations are going to multiply the real value of the stock with 10,000 so that we get them in an integer format. Now, why are we using the integer format? Why are we not using floating point? And why are we using 10,000, right? All the integers represent the money in units of 1/10,000th of a dollar, or whatever the local currency is that you're building the stock exchange for. Why are we using integers? Why not just use double? I would like to show you something in the C++ compiler. So let me just type out something like this. Double A is equal to 0.1. Then we have double B, which is equal to 0.2. Then double C, which is equal to A plus B. And then I'll just print out this C. And then, yeah. What do you think the output of this is going to be? It's going to be 0.3 because standard cout doesn't have kind of like a precision. It will just round it off at 6 decimal points. So you'll still get 0.3. But let's say I do something like this. So we have standard set precision of 17. And then I'll also add an endl, and let's run it. And we run into this error because I forgot to do the hash include. Let me just put the hash include in. As you can see, the output here is 0.3 and multiple zeros and 4, right? Why is that happening? Why is it not giving us 0.3? Why is it giving us 0.3 and so many zeros and a 4? And also, this is the reason why we're not using floating points or decimals. We're using integers here. The reason for that is something like this. So you might think that when we write double A is equal to 0.1, computer stores exactly 0.1, but it doesn't. Computer stores number in binary. We know that, not in decimal. And the problem is that some fractions cannot be represented exactly. In decimal, we can write, let's say, we can have 1/2, which is 0.5, or we can have 1/4, which is equal to 0.25. But if you have something like 1/3, that is 0.33333 recurring, right? There is no finite decimal representation for 1/3. We don't consider that a bug in decimal notation. It's simply a limitation of the number system, right? And the same thing happens in binary. We know binary uses a power of 2, right? It uses 0 or 1 to represent all the things. So if you have to represent, 0.1 with the base 2, that is equal to half, right? Because 0.1 will represent half. If you have 0.01, what do you think you will have? 1/4, right? If you have 0.001, then you'll have 1/8, and so on. Because what you'll have is 1 multiplied by 2 to the power -1. So that's 1/2. Over here, you'll have 1 multiplied by 0. So you'll just have 0 plus 1 multiplied by 2 to the power -2. Because this 1 is at decimal position -2, right? It's to the right side and it's at second position. So that's 1 divided by 4 and so on. So you'll get 1/8. And some fractions are exact in binary like we had here, correct? But the decimal 0.1, which is 1/10, let's try to have 1/10 here. So if you have a decimal point like 1/10, its binary representation goes something like this. It will be 0.0001, 10011001101, and so on. Okay, this pattern will continue happening, this 0011 pattern. And in decimal representation, we had 1/3 that kept repeating forever in decimal, right? The 1/3 was 0.333. Similarly, 1/10 in binary will have this repeating format. And the problem is that this double has a limited space. I told you that a double is 64 bits. And that sounds huge, but it is still finite. You can store 2 to the power 64 numbers in it. And since this 1/10 never ends, you will have to cut it off somewhere so that you can store it in double in 64 bits. So the computer is actually rounding this off and storing it in double. The same happens with 0.2. And so 0.1 is not exactly stored as 0.1. It would be stored something like 0.1, 000, and maybe there's like a 55. That's how I think it goes. You can actually print this out. So you can just try to do A and then try to see what it's like. Yeah, it's 1. And if you try to do B, you'll be able to see how 0.2 is stored. Yeah. Or if I increase the precision, let's see what shows up. And yeah, you can see more numbers are there. So it's not exactly storing 0.2. It's storing an approximation to 0.2. And when you add these approximations, the computer is just getting the nearest approximation to 0.1 plus 0.2. And this is why we're not storing in doubles or floats, we're using integers, because in integers, when we have 150250, or in our example, let's say if it's 0.1, we will have something like 1,000 that's present here, right? We'll just multiply 0.1 multiplied by 10,000. We'll multiply 0.2 with 10,000. So you'll have something like 2,000, and then you add it. So you have 1,000 added to 2,000. So that's 3,000. And then you'll again divide it by, 10,000 if you want to display it somewhere, or you just know that 3,000 represents 0.3. So we are just elevating the entire price scale on the order of 10,000, and everything will be in 10,000s, or thousands if it's decimal point. But the core thing here is that we're using integers everywhere so that there's no loss of digits. And also, just to tell you, this standard set precision was done because cout will hide these tiny errors that show up, and they'll just display 0.3 or 0.2. So if I just do standard cout B, they'll just represent 0.2 exactly as it is. And if we do C as well, it will represent it exactly as it is. But the actual value that's being stored, or actually let me change that. The actual value that's being stored in C is not 0.3. So if we try to do any other operation on it, we might lose out on some accuracy, and we cannot do that in a stock exchange, right? So that's why I had done set precision in cout so that, we'll be able to see the correct output. Just to make this more formal, the reason we are doing integers everywhere is not just for, one reason that we're losing out on accuracy. The first main reason is determinism. So suppose we have to recover from a crash, and we have to replay the journal. We'll be storing a journal, by the way, so that, every accepted order is logged into that journal. And if any machine goes, like we're not doing distributed systems here, but let's just say even our system crashes, we'll be able to replay that journal so that every accepted order on the machine will show up and replay through everything. We'll talk more about that architecture later on. But the core point here is that, let's say if the original run rounded something like 0.1 multiplied by 3, we did multiply it by 3 because we have 3 orders or something at $0.1 price. It will have 0.3, and we saw how many zeros and then a 4, right? And the replay will round it as 0.3 because let's say, we're using different machines, or we have a different compiler used, or a different optimization level used. All of that will make sure that the resulting state just diverges, right? So your recovery exchange after your machine had gone down, after your machine crashed, it disagrees with the original about who owns what. And, obviously stock exchanges are regulated. If in a regulatory environment you're doing stuff like this, that's not good, I would assume. And the second thing is for order matching. First one was determinism. We have now proper determinism that 0.1 plus 0.3 will equal to 0.3 and not, 0.3004. The second thing is for order matching. So let's say you have 2 participants that sent a buy order at the same price. With doubles, the same price that we have is fragile, right? 2 different numerical paths may produce values that compare equal in math but differ in their last bit. The matching engine sees them as different prices, places one above the other, and the wrong trader will win the next match. The participants will not be able to see why. From the outside, the matching is unfair, and obviously that is another big problem in a regulatory environment, and also it's just unfair. Your exchange is guaranteeing that the best price, the best order will win, but even though at the same price, two participants had participated, the other one won and the first one that put in the price did not win. And the sole reason for that was a bug in our system, because for one guy it translated to 0.3 and for the other one it pointed to 0.3004, and as a result this was considered the better price even though this came in first, and both of these numbers mean the same thing, but we had a bug in our code. So that's why we'll be using these integers. And we've already seen that how these numbers can help us, because I just showed you the example. 0.1 will be converted to 1000, 0.2 will be converted to 2000, you add them and you have 3000, right? And that is 0.3. The cost, the trade-off of this approach is that we lose convenience. You cannot write 0.1 directly, you cannot write 0.2 directly. You need to write that big thing. Now the next question you might have in mind is, why are we using a scale of 10,000? Why not 100,000? Why not a million? Why not 100? Why not 10? Why a scale of 10,000? Well, that's just based on observation. You know, if you are in a stock exchange, 4 digits is just plenty. Most of the stock you might have seen will be like 150 or 0.35, and that's enough. And we're also gathering, let's say you have some stock right now that's going at 2100. There are certain stocks that are booming that are priced at 2100 point, let's say 25. So these will be converted properly as well, correct? So basically the 4 digits that we have, the 4 decimal digits, they are plenty. If you're building up something like a crypto exchange or, for FX, you will have to have more decimals because that's how crypto markets work. You would need a finer scale for projects like that. But in our case, it's just based on observation. If the later, results change, maybe stocks seem to have a different value, which is very unlikely. But let's say they want you to have 5 digits now based on observation, you'll be switching it to 5 digits, not just 4 digits. But this is good enough for our project and for stock exchanges over the world, I would assume. The next question you might have is, why are we using this signed 64-bit integer here? So why is it signed? Well, it is signed because intermediate calculations in a few places will be required. So let's say you're trying to do P&L, profit and loss, or you're trying to find out position deltas. We'll learn more about all of this, but they can legitimately be negative. Let's take the most obvious example, profit and loss. Loss is obviously negative, right? If you bought a stock at 150 and the price drops to 140, your unrealized loss, okay? Realized loss means you've sold the stock and you've essentially, you had 150, you have sold it at 140. So your realized loss is $10. But let's say you bought a stock at 150 and the price drops to 140, then your unrealized loss is $10 because the stock might still go up, right? So you've not realized that loss, it's still unrealized loss. If you've lost $10, well, it will be in our systems being stored as minus 10 multiplied by 10,000. So that's something like this, I think. I think I have the right number of digits. I'm not so sure. Anyways, like you get the point. It would be around like 1 million or something. I don't know. Yeah, I hope this is 1 million. But anyways, this is the reason why we have a signed integer, not just an unsigned integer. This allows us to have negative values. An unsigned type, if we use that, would wrap around instead of producing a sane negative number. And why are we having 64 bits? It's just for the headroom. Like if you try to do the math, 64 bits is able to store like 9 something. I don't even know what that is. So let me just paste it in here from Google. Yeah, That looks about right. This is what you can have with signed 64-bit integer. Okay, if you have unsigned, obviously this will be something like 18 because you can have double the number stored. Right now what's happening is that in signed, you have 9 these many numbers in positive and then 9 these numbers in negative that can be stored, right? But if you have an unsigned, you don't have negative values, so everything is just double. So this will be 18, 446, something like that. And let's say this is the max value that we can hit. Now we divide it by a price scale, which is, 10,000. So let's say you have something like this, where you have let's just say it's something like 0.5807. Okay, so that's about $922 trillion ish, and we know that the total US stock market cap is $70 trillion, and $922 trillion is quite a lot. So you don't need to worry about us hitting that number. There are many cases where you'll find that you've not given enough bits to an integer and you just get overflow errors, which crashes the entire system. Has happened, but here we've done the math. It looks about right. As long as the US stock market doesn't hit $920 trillion, we're good. If we used, let's say, 32-bit integer, we would have something around $214,000. Now you might say, hey, $214,000 is quite a lot as well. You cannot have one stock with like $214,000, right? Well, if you just go to a single share of Berkshire Hathaway Class A, not Class B. Class B will show you a decent amount, but if you go to Class A, it trades above $700,000. So obviously 32 bits is not enough for share prices like that, and we don't want to have that. Otherwise, I told you, we can have big crashes that take down the entire system for such a small reason. The next thing we'll have here is the quantity. The quantity is a 32-bit integer. I spent a lot of time on price, but now I'll be quick. Quantity is unsigned. Just note that it's not a signed integer because you cannot have a negative number of shares, right? How can you say I want minus 100 shares of that company? What does that even mean? You can have positive shares only. So the quantity, how many shares you have, is always going to be positive. So you're specifying 32 bits, more than enough. You're not going to buy more than 32 bits or, whatever that number is. I'm not going to find that out. I can tell you though that we are not having 16 bits here because some real trades will exceed 65,000 shares. 16-bit will only allow you to store like 65,535, I believe it is. So some real trades can exceed that many shares. But 32 is good enough. And why not 64? Well, that's because we'll never hit that. And if we can save on byte budgets, that would be good because that will help us in the hot path. The hot path, if you remember, is the path where stock exchange will hit like 1,000,000 times and you want it to be super fast. We'll talk more about this and also why this is 32 bits. It's going to help us in our system as well. That's the level of optimization that will help us because these integers will help us keep it cache friendly. We'll talk more about that later on. Then we have the order ID, which is an unsigned 64-bit integer. Order ID is just a unique identifier for one order. So when a client wants to cancel, modify, they'll reference the same ID. 64 bits gives us so many IDs that, if there's a busy exchange today, maybe some IPO went out and they're issuing tens of millions of IDs per day, it's more than enough. 64 bits is enough. And also this is unsigned again because order ID is maintained by us. It's always going to go up. The next thing we have is a sequence number, and that is an unsigned 64-bit integer as well. So what is a sequence number? So every state changing event in the system will get a monotonically increasing sequence number. What is monotonically increasing number? It just means that, the graph of that is going to look something like this. It's always going to go up. It's not going to be something like this. It's going to be this. It always goes up. This is also increasing, but it decreases at certain points. But overall, it is increasing. Monotonically increasing is that it's always increasing. This sequence number will be used for every state changing event. So event 1 happened before event 2 happened, and event 2 happened before event 3 happened. Always, there's no ambiguity. So that is going to help us. And this will help us in event sourcing, which we'll explore much later in the tutorial. We have a lot more to go over before that. And event sourcing is essentially like replay, recover, audit, all of that. I told you if there's a crash, we want to find the last persisted event that happened and replay from there. That's where the sequence number will help us. After that, we have the timestamp. Timestamp, it's just understandable, a 64-bit unsigned integer representing time. One thing to note here is that the type does not specify which clock it comes from. It's just an integer timestamp. And you might be wondering, what do you mean which clock it comes from? Well, the project that we're building will deliberately distinguish between two kinds of timestamps, and it will use the same type for both. This timestamp will be used for two types of clock. One is wall clock, which is measured in nanoseconds since epoch. It will be used by transport liveness, like you're trying to do heartbeats. So like you want to check, has it been more than 5 seconds since I heard from this client, or have we logged off and we'll have to start some recovery process or something. And the second thing is logical timestamps that will count how many events have been processed so far. So these are two types of clocks that we'll be having. They have two meanings. And why are we using two clocks? Because wall clock, which is measuring nanoseconds since epoch, and you might have seen more about them overall, that's used because it is great for real-time operation. If you want to know, hey, has it been like more than 5 seconds since I last heard from this guy? You'll be using wall clock, the normal wall clock. Like, yeah, it's 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. Okay, I've not heard. Logical timestamps will not help us there. But the problem with wall clock is that they're not good for replay. You cannot rewind the wall clock, right? You can think of wall clock as literally the clock on your wall. You cannot rewind it. It will keep moving forward. And the matching engine prefers logical timestamps so that replay will produce the same output. And we've talked about that. In, let's say, about an hour, we'll be going into the clock. And that is one of the core infrastructures that we'll be creating. The next thing we have is the participant ID. Participant ID is the integer the gateway assigns at login time. It is not the username string. So let's say your username is something like Ranavat or like obviously you as the user will not be able to have a participant ID like that. It's most likely going to be a firm or a broker that's there. But let's just say for simplicity, you have this Ranavat Rivan username. That will be assigned participant ID 1. If there's some other firm, let's say firm A, that is also connected to the stock exchange so that they can earn some money, they'll have, let's say, participant ID 7 in the future. So those are participants ID. We are not storing the names or usernames or anything like that. The major reason behind that is if we know what the participant username is, there are chances of manipulating and giving someone else an unfair advantage. And we want to avoid that. So here we go. And why is this 32 bits? Because participant ID will live inside a struct that will already be aligned to 4 bytes. And shrinking it to 16 bits would not really save anything. The compiler would just add, 2 bytes of padding to keep the next field aligned. And actually, let me just explain this memory alignment in CPUs to you because it will just keep coming up and it will be good to have some idea when I'm talking about it, right? So the key idea that we have is that CPUs like data to be neatly lined up in memory, okay? Now, let's try to understand what I'm trying to say here. One thing to realize is that memory is just numbered bytes. You can imagine memory as, a long row of boxes. You might have seen multiple of those examples, but let's just say you have multiple of these boxes here, okay? And then you have address, like you have address 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's just say 10, 11, 12, 13, 14, and 15, okay? And let me just enlarge this so that we take up this entire space. Great. And now you want to store the bytes at these addresses, right? Each address here, 0, 1, 2, each of this address will hold 1 byte. So 64-bit integer will need 8 bytes, right? Because 64 bits means 8 bytes. So it will need these 8 bytes to store its entire space, these entire things. Correct? Now, suppose an 8-byte integer starts at an address 8. Okay? So we have a 64-bit integer that starts at this address. Let me just mark this with a different color. So this address 8, it will go and take up this entire space until 15, right? Because it's a 64-bit integer. It's an 8-byte integer. It occupies 8 bytes. So this address 8 is divisible by 8, correct? This is called 8-byte aligned. And the CPU can often fetch all those 8 bytes in just one operation. One read operation, one load operation is all it takes. And that's fast, right? You only need one operation to fetch 8 bytes. But let's say you have a misaligned access. Let's say, you're starting to store at this 12th position, okay? Now, if you have this 12th position, you'll go ahead and occupy 12 to, let's say, 19th, right? 12. And then you'll have 13, 14, 15, and let's say you also have 16, 17, 18, 19. So this value will span 2 chunks. You have one from 8 to 15 that will be fetched. So let's have 8 to 15 that will be fetched. And then from 16 until 23, all of that will be fetched because the CPU will fetch 8 bytes at a time. If you have a 64-bit machine, of course. So it cannot start at byte number 12. It will go ahead and start at 8 and go until 15, and then it needs to fetch the other thing as well, right? Because the bytes are also present from 16 to 19. So it will fetch those 16 to 23 bytes again, because again, it can only read 8 bytes. So it fetches this 8 to 15, then it fetches 16 to 23, and now you need 2 chunks, right? You need to do 2 load operations. The CPU will have to read the first chunk here, it will have to read the second chunk here, and then it will extract the relevant bytes, combine them, and it will return that. That's obviously more work. And if it's more work for the CPU to do, it's obviously going to be slower. So the compilers know this. All of the compilers, okay? All the compilers know that the CPU prefers aligned data. That's built into the CPU, so compilers will obviously try to build on top of that. And since the compiler knows that the CPU prefers these aligned data, when they're laying out a structure, they'll insert padding between bytes to keep these fields aligned. So let's say you have a struct. Let me just get into typing. So I have struct, let's say, I'm just going to call this example because I don't want you to confuse that with the order or anything else. Let's say I have an int 64 here, which is A. Then you have unsigned integer 16, which is B. And then you have integer 64, which is C. Okay. What does that mean? This is 8 bytes. This is 2 bytes. And this is 8 bytes again. Correct? So that means it's consuming a total of 18 bytes. So if you try to lay this out in the memory, what will you have? Well, let's say you start from 0 and you go until 7 and store them. Then you go from 8 and you go until 15 and then you store them. Then you go from 16 and then let's say, how many have I covered? Okay, I go until 18 or 19 or maybe 17. Okay. So to store this entire struct, you've passed in these memories. What is the problem here? Well, the problem is, first of all, the struct, how it stores it is that, A is present first. It will go ahead and occupy those 8 bytes. Then you have these B, which is 2 bytes. So it will go ahead and occupy this 8, 9. And now your C is starting at 10. So you go from 10 until 17 and occupy that if you don't add padding. And 10 we know is not divisible by 8. C is misaligned. And we know misaligning is a problem. So what does compiler do to optimize this? Compiler will insert padding. What does padding mean? It means that, okay, so here we had A stored. A is proper. It's taking those 8 bytes proper. Then you have B. B starts at 8, that's proper, but it only occupies 2 bytes, which is causing us a problem. So the compiler goes ahead and adds the padding from 10 to 15 as well. So this entire space that we have is occupied as padding so that our next variable, this C, can start from 16. And 16 is properly aligned because it's 8 bytes, correct? And that's why many of the times, if you do something like size of this struct example, you'll see that the answer is something like 24. It's not 18. You would expect it's 18, but it's actually 24. And that's because of the padding that was inserted. These 6 bytes of padding that was inserted was added in the real memory. We want to support this compiler feature because ultimately our goal is to get everything fast. And if that means the compiler will optimize these things for us so that we don't have to worry about where in the memory these things are being stored, padding is added automatically, I suppose that. So in our case, for the participant ID, we are using 32 bits here, but we could have used 16 bits as well because we won't have that many IDs. So even if you use 16 bits, that's fine. But the thing is, if you're just getting 32 bits for free, why won't you use it? Because where we use this participant ID, the structure we'll be using this participant ID in, that will have, the compiler is going to add padding for that as well. I'll point it out when we use participant ID later on in the struct, but I wanted to give you a feeling of how it's going to be. So in that structure, when we try to add it, even if you use 16 bits here, the compiler will add that padding, and the padding is going to be useless. It's of no use other than, for us to fetch, or not for us, for the CPU to fetch data properly or fast in a fast manner. So why would you change it to 16 bits? Why not have it at 32 bits if you're just getting it for free? I hope you understand. You'll understand it better when we see a real example. Having 32 bits here means, you can have over 4 billion participant IDs. That is more than any real exchange will probably ever need, but you never know. The next thing we have here is the match ID. The match ID is an unsigned integer, 64 bits. It identifies one trade, one buyer-seller pairing, that is match. So you set a price of, let's say, $150. The buyer buys it at $150. That is one match, one trade. And that's what this is representing, the match ID. Remember, this is 64 bits because a single incoming order can create many matches. Because if you place an order and multiple other people can place that order, each order will have multiple matches created and each match will get its own ID. So that's why it's 64 bits. It's the same reasoning as this order ID essentially. After that, we're going to get into the price scale. So price scale is an inline constant expression, price scale 10,000. Great, we've understood price scale. One thing I would like to tell you is that we've created this as a variable, but it's an inline constant expression. So when we compile it, we'll not be using this price scale variable at all. It will just be merged wherever we use this price scale. Let's say somewhere I use 1 into price scale later on. What will happen is the compiler will swap out this price scale with 10,000 and you'll directly have the 1 into 10,000 done. So the reason I tell you this is because this just optimizes the speed. Obviously, if you try to load a variable in, that could have just been 10,000 every single time. That would save us some time. So this 10,000 is just put in everywhere this price scale is used thanks to this inline constant expression. Now the next thing we have is the lifecycle state. So this is called the side. It is an enum that represents the side that you have. It can be a buy or it can be a sell. So a buy order says that, hey, I want to acquire shares. A sell order says, hey, I want to provide these shares into the market. So that is the entire meaning of the side in this code base. Pretty simple. You either buy or you sell. The underlying type of this enum is an unsigned integer of 8 bytes. So that 8 bits. So that's 1 byte. That really matters because side lives inside the order structure that we are going to create. So every event, every wire message that's passed in, everywhere that side is going to be present, and it occupies 1 byte. And it's purposely 1 byte and not 4 bytes, because that's what a default enum does. If you don't specify this, the side will automatically have 4 bytes assigned to this entire enum. But we are specifically saying that this is 8 bits, 1 byte only. So it saves us 3 bytes per occurrence. And, if you are having, a million orders, that is 3 megabytes that is saved. So 3 megabytes is quite a lot, considering, if you remember, the memory organization that I talked about. So we had that the RAM is the biggest thing, but it's the furthest away from the execution unit. Then you have the L2 cache or L3 cache, and that is bigger than the other things, but it's still further away from the execution units. Then you have L2 cache, that is smaller than L3 cache, but it's closer. Let me just make this smaller to give you a representation. And then you have the L1 cache, and in the L1 cache, it's separated out with L1I cache and L1D cache. But for now, let's just simplify things. You have an L1 cache, and L1 cache is the smallest. So there you go. And let's say this is your execution unit. Let me make that a diamond, because why not? So when I say that across a million orders, you're saving 3 bytes, so that's 3 megabytes. 3 megabytes could have been the size of this L2 cache, right? Or actually, it would be more than the size of this L2 cache. It would probably fit in this L3 cache. So we are saving storage in those terms. Also, it will help us later on in this explanation of memory organization and alignment that I talked about. But majorly, this is also a big concern, so that we can have more speed. Everything will revolve around majorly these two concepts, okay? And there's also going to be a third concept about storing on heap versus on stack, but we'll get to that. I also hope you've understood this. I just want to ensure we are on the same page till now, because what I'm trying to explain here is that this is the execution unit. To do execution on L1 cache, to fetch data from the L1 cache, it's the smallest amount of time because it's directly present on the CPU die, okay? It's the closest, so it's going to get the data fastest, but it can only store some amount of data here. I told you it's going to be like a kilobyte or something. Then L2 is bigger, but it's further away. L3 is even bigger, but it's further away. RAM is even bigger, but it's further away. And obviously below RAM, you also have those storage devices like HDD, hard disk drive, right? That is even bigger, but it's stored even further away from the execution unit. It's like a separate device altogether. So what you want to do is, if you have frequently used data, you want to keep it in L1 cache. If it's moderately used, L2 cache and L3 cache. And if it's rarely used, you keep it in RAM and you bring it whenever it's needed. Also, one thing to note here is I've used enum class here, not plain enum, meaning values do not implicitly convert to integers. So if you try to write, let's say something like, if the side is equal to 0, that will not work, because this is not implicitly converted into integer with the enum class. With enum, it would be, but with the enum class, it's not. You have to write side by like that, okay? And this is done on purpose because we just want to avoid this confusion in the code base. There's zero runtime cost of this. It's just a pure, compile time safety just for the developer. Another thing that I would like to talk about before we move forward is the 3 terms that you'll keep hearing. The first one is the bid. The second one is ask, and the third one is spread. So bid is the highest price someone is willing to buy at, okay? Let me just type it down. Highest price someone is willing to buy at, okay? Reasonable. You've put a bid of $100. So is someone willing to go beyond that? It's like an auction. You've put a bid of $100. That's the highest price you're willing to buy it at. And in the stock market, the bid is going to be at this price point. Is this the highest price someone is willing to buy at? The second thing is ask, which is kind of the opposite of this. So I said this is highest price someone is willing to buy at, right? This is the lowest price someone is willing to sell at. So in bid, you've bid that, yeah, I'm willing to bid like $100 for this. I really want this item. In ask, you're like, hey, I want this to be at the lowest price possible, right? Because like you want to sell it. And then you have spread, which is, ask minus bid. So this is quite simple. Ask minus bid. That is the spread. Let's take an example. Let's say we are trading with a stock that I'm not going to name. Okay. Then you have buy, and all of these bids are present here. So let's say you have bids that go like this. You have 100 shares that you can trade at $150.20. Then you have another one, which is 50 shares at, let's say, $150.15, and maybe 200 shares at $150.10. Not far from reality, right? I mean, prices cluster around a specific group. So you have 150.2, 150.15, and 150.1. Then you have the sell. Okay, so you have sell, and this is basically asks. So let's say someone is willing to sell at something like this, 150 shares at $150.25. Then there's 200 shares at $150.30. And then finally, something like 75 shares at $150.35. Correct? So this is what we have: buy, bids, and sell, ask. So what is the best bid that we have here? The best bid is obviously this one, right? 150.20, because let's go back to bid's definition. Highest price someone is willing to buy at. Highest price is this one. So this is our best bid. And what is the sell? The sell is the lowest price someone is willing to sell at. So the lowest price someone is willing to sell at is obviously 150.25. So what is the spread going to be? Well, you have the highest price and then you have the lowest price. So you do ask 150.25 minus 150.2. So your spread is $0.05. So let me just write it down. The spread is $0.05. So if you want to buy immediately, you pay the ask of 150.25, correct? Because if you really want it, you want to make sure that you are the one who gets it. So you'll pay the amount that they want, right? Think of it as a shopkeeper. The shopkeeper is like, hey, I'll sell this for $300. And you're like, someone else is bargaining that, okay, I'll buy it for $280. No, I want it for $270. And you'd really want to buy it immediately. You're like, okay, I'll match you. I'll give you $300 right at the moment. Okay. And if you want to sell immediately, you get the bid of 150.2, correct? Because let's say you are the shopkeeper and you're like, hey, I want to sell this item off and I want to sell it off quickly. I want to sell it right now. Obviously, I'm going to go ahead and find the person who's willing to pay me the most, and that's 150.20. So I'll pay that. The exchange itself here is not setting the price. The participants do with their orders. So that's a very important and interesting thing to keep in mind. And this entire thing that you see is called the order book. And that's why I created this very nicely so that we can refer to it later on. This is the entire order book, and we'll be coding that up later on once we've gotten our infrastructure, the supporting infrastructure in. The next thing we have is the order type. We're going to have multiple types of orders here, by the way. So again, this is unsigned integer 8 bits. So you have 1 byte instead of 4 bytes, which is the default one. And what are the order types? There's, I think, around 8 or 9 types of orders. So let's go over each one of them. It's a real concept on real stock exchanges. So I'll get through them. You might probably not even see most of these order types because the broker might just hide it from you unless you're on advanced settings. I don't really know. But yeah, I'll go slow here because, these are the foundational concepts. So the first one we have is limit. Limit, what does that mean? It just means that, hey, I want to buy or sell at this price or better. So a limit buy at $150 will say, hey, I want to buy this thing at $150 or less. If no one will sell that low, I will wait. I'll wait until someone will be able to sell it at $150 or less. I am limiting my expenditure to $150. So if the market is willing to give it to you, you trade. If not, your order rests on the book. It will wait. That's called a resting order, by the way. So you don't want to trade right now because there's no other order at 150. You'll put it at rest. As soon as someone is able to sell it at 150 or less, your order will go through. And most of the orders on real exchanges are actually limit orders. So this is quite an often type of order. The next thing you have is market. This means that, hey, I want to trade now against whatever is available. I do not specify a price. So what you're doing here is you're giving up the price control to get the speed. So if you want 100 shares and the best ask is 50 shares at $150.25, the next is a 50 at, let's say, $150.30, your market buy fills 50 at each price. You trade now. You don't care about the price. You just want speed. So you are guaranteed execution, but not at a specific price. In our code base, we are going to explicitly handle this. So the market order is rejected if the opposite side of the book is empty. That means no one is there to trade with, because in real stock exchange, obviously, it's so huge and so enormous that the market order is obviously going to go through. But in our case, it's so small, we have to handle this condition. And even in the real one, it would be handled. We are explicitly handling this. So it is rejected. The order is rejected if the opposite side of the book is empty. That means there's no one to trade with, because there is no defensible any price answer when there's literally nothing to match against, right? The next thing you have is IOC. IOC stands for immediate or cancel. So like a limit order, it is like a limit order, but there's a twist. You trade as much as you can right now at this price or better, then cancel the rest. In limit order, what did you say? You said, I want to buy these many shares at this price or better, correct? If it's not there, you wait. But in IOC, you're like, hey, I want to trade as much as I can right now at this price or better, but if not there, I'll cancel the rest of my price. So let's take an example. If you send a buy IOC order for, let's say, 100 shares at $150.25 and only 60 shares are available at the price of $150.25, you get those 60 shares. And the remaining 40 shares are cancelled. They're not resting on the order book like the limit orders do. You just cancel those 40 shares. And this is useful when you want to take liquidity but not provide it. So liquidity is just like how much orders are present in the market that are resting, right? So as soon as a sell order comes, the resting buy order can quickly get to it. And if there's a resting sell order, you can quickly assign it to the buy as it comes. But with IOC, what you're trying to do is that you're just trying to take liquidity from the market and you're not trying to provide any of this. So you're trying to take away any orders that are present there. The next thing we have is FOK, which is fill or kill. So it is stricter than IOC, which was, we trade as much as we can right now. FOK is like, hey, you trade the entire requested quantity now or don't trade at all. There should be no partial fills. I told you in IOC that, if you have, let's say, $150.25 and you sent a buy IOC for 100 at that price and only 60 of those shares were available, you got those 60, the remaining 40 were cancelled. In FOK, it's like, hey, you send a buy FOK order for 100 shares at $150.25 and only 60 are available, you just cancel it. You say, if I don't get 100, I don't want anything. There are no partial fills here. In IOC, you would still do the 60 shares and the 40 would be cancelled. Here, the entire thing is cancelled. You don't trade at all. So here, the book has to pre-scan the available liquidity before deciding whether to even start matching or not. The next thing we have is GTC, good till cancel. So this is like a normal resting limit order that stays on the book until either it trades fully or the participant cancelled it. So in this code base, GTC and limit behave identically inside the matching engine. Both will rest, neither will expire. The distinction will exist at the protocol layer because the gateway accepts a separate time and force field where IOC, FOK and GTC are siblings. We keep both names so the message types parse cleanly. So if you want, you can totally remove this field and not handle this part, but I'm just gonna keep it. The next one we have is a stop order. This is a conditional order, so it is invisible to other traders until the market reaches a trigger price. So let's take an example again. Let's say a certain stock is trading at or below $145 and we want to sell 100 shares at market. So it is a common protective device. What it will do is it will limit your downside if the market moves against you. So until triggered, the order is parked in a separate structure. It is not in the public book. And we'll talk more about that implementation. So what you want to do is that you want to check if this stock trades, at or below 145, I'll sell 100 shares at the market related to this. So it's like a trigger price. As soon as 145 or below, sell. So this is obviously de-risking you, right? If the market moves against you, it will limit your downside. After that, we have the stop limit. So it is the same idea as stop, but with a limit price as well. So we again take an example. If the stock trades at or below $145, then we place a sell limit at $144. So what this will do is this will avoid a stop market slippage problem. What that means is a stop market order, which when once triggered, can fill at terrible prices in a crash. The trade-off of this is that a stop limit might not fill at all if the market gaps through your limit while you are waiting. And finally, we have the iceberg. Or not finally, I think after that we also have post only. But yeah, iceberg means that this is a show only a slice order. So let's say you want to sell 1,000 shares at $150. Generally in the past, when I gave you examples, these were just 100 shares. But now we're dealing with massive things. It's 1,000 shares. And you don't want to telegraph your full size to the market, right? If you show like, oh, I want to sell 100,000 shares, that's not going to work for you. So what you do is you enter an iceberg with a display quantity of say 100. The public book shows 100 shares at $150. Whenever those 100 shares trade, the engine refills with another 100 from your hidden reserve. It will send that refilled slice to the back of the queue at that price level and so on until the full 1,000 is gone. Remember, I said it will go at the back of the queue. Later on, you'll see that the matching engine will talk about something like price time priority, and you'll understand more about why this will go at the back of the queue rather than the front of the queue if I've already placed 1,000 shares. But this is essentially you showing an iceberg, right? Only a small part is visible and rest of the big chunk is below. And as soon as, the visible chunk is gone, the other things will try to pop up ahead so that people can still buy and sell it. So you generally do this whenever, you want to sell a big number of shares and you want to sell it at a fair price. If you try to sell all of those 1,000 shares at once, what will happen is there's suddenly a lot of supply, but maybe the demand is not as much. So obviously the stock price will go down and you don't want to do that to yourself. After that, you have post only. What this means is that you do not take liquidity. So if your buy at $150 would immediately match against a resting sell at $150 or lower, the order is rejected. You want it to post, which means you want to rest. You don't want to take anything. There's sometimes a make or rebate mechanism on real venues. So what happens is some exchanges pay you to add liquidity and charge you to take it. So market maker uses post only to be sure that they never accidentally pay the taker fee. These 9 names are quite important. They'll recur in every almost later episode, and adding a new order type is going to be a frictional change in our code base. But yeah, we'll talk about that later on. You don't need to understand everything right now. I'm sure I've given you like 9 examples. You might not even be clear about what's going on. So when we get to handling each of these order types, I'll explain in detail about what each one of this does. But just to give you a good example, we have our order book here. Let's try to take an example and try to understand what's going on here. So let's say we have this order book, correct? We know what our bid is, what our ask is, what our spread is. Now a market buy for 200 shares arise. So let me just type it down. We have market buy at 200 shares that comes in. What does a market buy mean? Let's revise this market buy. Okay, there was the second thing. And the market buy meant that we want to trade now against whatever is available. I do not specify a price. And that's why I said we market buy 200 shares. We're not trying to buy, 200 shares at a specific price, just 200 shares. So I get whatever is present. So I want speed here. I want whatever is present. So what happens is you go ahead and try to evaluate. So let me just try to erase this off. This might be a bit confusing. Now, market buy 200 shares. So what will happen? Well, you buy these 150 shares at $150.25 because you try to go from the lowest price, because you're trying to give the best deal, right? If someone's trying to buy, you try to give them the least money option that's possible, right? That's the best deal that they can get. So you take 150.25, you sell these 150 shares, then you go ahead and have 50 shares of these 150.30. So this is completely eliminated from the process. And now you don't have 200 shares left. Now you only have 150 shares remaining, correct? So this 150 shares at 150.30 is happening, and you fulfilled this market buy order of 200 shares. You sold them 150 shares at 150.25 and 50 shares at 150.3. After that, a limit buy comes in. Let me just type that in now. So now after this, we have limit buy, and limit buy is for 100 shares. And here we have to specify a price. Let's say they say it's $150.10. Now, what was a limit buy, if you remember? Limit buy meant that I want to buy or sell at this price or better. So I want to sell or buy at 150.010 or better, right? So we go ahead and check that, hey, the best ask here is 150.3 now, because 150.25 is gone, right? So 150.3 is there, which is the best ask. The order rests on the book at 150.10 because 150.10 is lower than 150.3. So obviously, we're not going to buy at a much higher price than what we said. We're not going to buy. If we had $150, we would sell it off. We would buy off the 100 shares. But now, since we have 150.10 and the best ask, the best selling guy is 150.3, what we're going to do is store this in resting place. As soon as an order comes that's better than 150.10, we'll buy it. Great. So now this is still pending. It's in the order book. The next thing we have is, let's say, a post only buy comes in. So you have post only buy, and that's 50 shares at, let's say, $150.3. Okay. Now, what does a post only buy say? Post only buy says we do not take liquidity, correct? So this is going and checking that, hey, the best ask is $150.3. 150 shares remain here because rest of them was taken by this market buy. So our $150.3 here matches this $150.3 here. So post only says no, the order is rejected. So this order is rejected because this was only there to rest. It was not present to take. So this order is rejected, and actually it's never even made an order, right? So it's just straight up rejected. After that, let's say we have, let's just take this last example, IOC buy for, let's say, 500 shares at, let's say, $150.3, correct? IOC was immediate or cancel. So we try to see, hey, we want to buy, this guy wants to buy 500 shares. What's the best ask? The best ask is 150 shares at $150.3. So we take all of these 150 shares, correct? So we go ahead and take away all of these 150 shares. The next level that we have is 150.35 because it said 500 shares. We've only given 150, so 350 more remain. After that, we have 75 shares more, correct? But our limit here was $150.3. Here you specified 150.35. So this is not going to go through. So those remaining 350 shares that were present are cancelled because it's immediate or cancelled, right? They're not resting. Otherwise it would just be a limit order. But here it's like, okay, the 350 shares that are remaining, we cancel them. So the order is filled with just 150 shares. The remaining 350 shares are cancelled. It never rests in the order book. Instead of immediate or cancel by, had we had something like fill or kill, what would have happened is we would have gone and checked, okay, 150.35 for 150 shares. Yeah, well, we do have that. 350 shares remain. Let's go in the order book and check again. Well, it's at 150.35 and the user is not willing to pay 150.35. So this entire thing is cancelled and the order book still has those 150 shares at $150.3. And this is outright rejected. Nothing happens there with FOK. So that is the entire thing. I hope you're getting a sense of how this order book and matching engine is going to work. That was just a quick and interesting thing I wanted to share. Great. Now let's move forward with order status. So the order status that we have here is again, standard enum class. Then we have the order status. Is the order new, accepted, partially filled, or cancelled? And we've seen through this demo that I gave you that, what can each one of these mean? New means the new order came in. Accepted means the order was accepted. Partially filled means, you had something like a limit order where, or an IOC where you partially filled the order and then, you rested or you either just cancelled. Then you have filled, that means you've completely filled it, and cancelled means you've cancelled it, Cancelled means the fill or kill happened or IOC happened, whatever. If you want to get a more concrete perspective, you can have this. So let's say the person is standing here. There's a nice guy. He's standing here. He says, hey, I want to submit an order. Then there's an auth check that happens. You want to ensure that the user is correct. User is they say who they are and all of that stuff. Then you have the risk gateway check, which is you're just trying to check if the user is not doing any suspicious activity here. So you have this risk gateway. And by the way, if any of these result in a failure, then you just do order rejected. This is not a part of this order status because it was not even an order. It was just like, hey, we're straight up rejecting this. Now let's say the risk gateway check also passed. Then you go ahead and create a new order. And this order has the status of new. After that, the sequencer will go through. The sequencer will assign a sequence number. Okay. You remember the sequence number, the monotonically increasing number. After that, the order will be delivered to the matching engine, the main part of our entire system. It will match the entire thing. Matching engine is essentially like, the order book and the surrounding logic around it on how to decide where to give the order, whom to give the order, and all that sorts of stuff. After that, the matching engine will do all of these things, right? I mean, before it's delivered to or actually after it's delivered to the matching engine, the status of the order will be accepted. That, yeah, we have accepted, the matching engine has accepted the order. Then the order will match, or the order will rest on the book. And, the status will be either partially filled, or, it's just completely filled. Which one was it? And, if the user decides that, hey, I want to cancel, so the status of cancelled can also happen here. So either one of those, but this is kind of like the entire architecture. Doesn't say a lot. You'll get a beautiful diagram later on. This is just a rough diagram that I've created now. Generally, you also have another order status here called expired, but we are not including expired here in this order status because in our exchange, we're not implementing that time and force expiry, beyond what I've said about IOC or FOK semantics. Both of them just result in cancelled directly. Great. After that, we are going to have our symbol. So symbol is an array character of 8 characters. So here's an interesting thing. Symbols are 8 bytes. What that means is a symbol is a fixed with 8 byte array. So that means, let's say if you have a real stock, I was trying to not take the names of these stocks, but let's just take it. Let's have these things 1, 2, 3, 4, 5, 6, 7. I hope this is correct. I don't know. Yeah, this is a pretty messed up. Just ignore this part, okay? Just a terrible drawing. But anyways, you have these 8 slots created. Each one is 1 byte each. So you have an 8 byte array. And what that 1 byte means is that you can have 8 bits stored in it. 8 bits means you can have 2 to the power 8 characters stored. That means 255 or 256 characters stored here. So that means you can have English letters stored here. Cool. So let's say the stock is N. There's no investment advice I'm giving here. Okay. So you have N here. Then the next one is V. Okay. Then you have I. So let's just increase that as well. Then let's paste the D in. Then you have the other one, which is another I. And then you have the A. So what have we done here? Each slot of this array, this is 1 byte, 1 byte, 1 byte, 1 byte, 1 byte, 1 byte. So this is 6 bytes that were taken up by this symbol. Or actually the symbol is not correct for the company. It's NVD and A, my bad. So it's 4 characters and the rest 4 characters are passed in as \0. That means it's like a null empty character. So we are just having that placeholder kind of characters placed in here. So these trailing zeros are just padding the unused bytes. So this is, unusual if you worked with standard string most of the time. But what I want to tell you is why are we exactly using these fixed widths? And why are we not using the standard string that's already provided by C++? Why not just use standard string here? Why use anything else like an array? Well, that's because this is how standard string would work in memory. So let's say you have this entire thing, okay? Now in that you have a pointer that's pointing to the heap, okay? Or it's the inline storage. But anyways, let's just assume there's a pointer here to the heap because when you have standard string, you are allocating on the heap or the inline storage. So let's say it's heap and that's 8 bytes, okay? Because a pointer is generally 8 bytes long. After that, you also need to store the size. The string stores the size of the string and that requires 8 bytes as well. So you have size and that's 8 bytes. And then you have the capacity. What is the capacity of the string? And the capacity is 8 bytes too. So that means to store an entire string, you're taking up 24 bytes instead of storing, 8 bytes, what we exactly need for the symbol. Because no other symbol you'll be able to find, it's more than 8 bytes long. Every single one, even if you look at Apple, AAPL, I believe that's correct. Then you have Google, which is Googl. Meta is META, I believe. So all of these just fit in 8 bytes. Why am I using 24 bytes instead? In our thing, there's just 8 bytes. So it's a no-brainer not use this array. And what this shows is an inner detail about how standard string works. The standard string carries metadata. So it carries this pointer, this size, the capacity, plus, in the general case, a heap allocation that holds the actual characters. Even if you've implemented this small string optimization, which means like, the current modern standard string implementations, what they do is they stash short strings inside the metadata block to avoid the heap. So you're not using the heap, but still what happens with that is you still pay 24 bytes for what is essentially just, the 4 characters that we're trying to store. Or in general, we are allocating 8 characters in the worst case. So let's say 8 characters. So fixed array is obviously better than using the standard string. Also, the biggest thing here is that there's no heap allocation with array. We'll talk more about heap allocation because we are trying to avoid heap allocation. And the next thing we're going to get into is zero allocation infrastructure. That's kind of like what the phase is, where we're going to create 3 files where we are going to decide, hey, we are not going to use heap because it's bad. And I'll get to that. But yeah, the main thing is we're not using the heap here. The second thing is that this entire thing is trivially copyable. We'll talk about trivially copyable in a bit because it's also going to be present in our code. It's very important. And the second benefit that I want to talk about is that it fits the wire. What it fits the wire means is that the network protocol that we have, or not what we have, but the real stock exchanges have, like Nasdaq, they use exactly this kind of fixed width tickers in their binary protocols. So they use the same shape internally as on the wire, meaning that they can just do something known as a memcpy. And we'll talk about memcpy later on, but it's very powerful where it saves us some time. And this is also a benefit of trivially copyable. Trivially copyable means we can do memcpy. You don't know what trivially copyable means, but we'll get to that. Cool. So yeah, that is our symbol, an array of 8 characters. The next thing we have is make symbol, a function. So what we have is a constant expression, a function where we're going to return a symbol, and we make the symbol from a text, a string view text. And we're also telling that this function is not going to throw. This is essentially redundant because in our CMake list.txt, we had mentioned that we're not going to have any exceptions thrown at all. So obviously all the functions are going to be no except, but I've just manually set it over here. In this function, what we're trying to do is we're trying to make a symbol from a text that's given to us. And that means we're trying to create an array of 8 characters from the string that we've been given. So what we do is, first of all, just initialize the symbol array. It's just empty now. After that, we are going to calculate the length of the symbol, correct? Whatever is the minimum between this symbol and the text length that's popped up, because we want this symbol to be at max 8 characters long. And this text should not exceed that. So what we're doing is we take the length, which is the minimum of symbol.size and text.size. Cool. And you can see the nice autocomplete that we have. This is of the type of unsigned long constant. Cool. Fine by me. After that, we are going to loop over every character in this text, like in this text, as in assuming this text is 8 characters long, we're going to loop over every character in this text, and we're trying to put this in the symbol array. It's quite simple, an iterative process. So we have for standard size t, index is equal to 0, index less than length, plus index, and then we just do symbol at index. This array at index is equal to text at index. So we are just taking each character from this text, putting it into a symbol, and we're returning the symbol. As simple as it gets. We're just copying this text character by character. So if you call make symbol and then you pass in the text as something like NVIDIA, it will go ahead and create an array with NVDA as each of the elements in this array. Okay, great. The next thing we are going to have is the complete opposite of this make symbol. It's going to be symbol view. What this will do is it will take in a symbol and it will return a string view, complete opposite of make symbol. So let's have that symbol view, and then we'll have length is equal to 0 while the length is less than the symbol size and the symbol length is not equal to \o, because you remember that empty characters might be put in as placeholder values if our symbol is only 4 characters long and we've specified that the array is 8 characters long. So we are saying as long as the length is less than symbol.size and the symbol at length is not equal to this \0, we increase the length so that we find out what is the actual length of this thing, of this symbol. And then we just return a string view passing in the data and the length here. That's how simple it is. You can try to do symbol.size, but symbol.size might just give you this size, correct? We don't want this size. What we are interested in is the actual size of the text that's present within the array. So that's what we get here. Now you might wonder, what is the string view thing? I didn't talk about that. String view is just two things wrapped together, a pointer and a length. It does not own any memory. It does not allocate. It does not copy. It just remembers that, hey, the meaningful text starts at this address and has this length, or has these many bytes. So that's good enough for us, because in our case, there's a string view. It says, okay, n starts at this particular address and it captures these many bytes. That's good enough for us. We don't need any of the extra pointer and all of that allocation stuff, etc. needed. So it's not copying anything, and it is valid for as long as the underlying symbol is alive. So we have to be careful about that. If the symbol lives in a temporary thing that is about to be destroyed, the string view becomes a dangling pointer immediately, because string view is just a pointer to the actual data. It's not storing the data by itself. What it's doing is that, hey, we have n here. This is the pointer to n. This is where the address begins. And the size is 4. Great, that's it. So if the symbol from which it's built, because string view is pointing to a symbol, if the symbol is deleted, it's pointing to nothing, and that's bad. After this, we have symbol-less struct. It is a named comparator that we are creating. The operator that we're going to create within this is going to take a symbol LHS and an RHS, and what it's trying to do is lexicographical comparison. So we are trying to compare byte by byte, left to right, the two symbols. Why does this exist? Because some places in the code base need a map, and that map contains the symbol. And the matching engine, we're going to contain a books per symbol map. How many books are there per symbol, the order books per symbol. Because if you remember this one was for one particular stock price, right? We'll have multiple of these for each stock price. This is maybe for one stock, Apple, then we'll have another for Nvidia, and so on. So this will just help us lexicographically compare the LHS and the RHS. When we use it, it will get much clearer. We've just created it now since we're already in types.h. And the last thing we need is static asserts. So at the bottom of this entire file, we are going to paste in a bunch of static asserts. And what this assert is going to do is check if it's trivially copyable for this particular structure. So every structure or every type that we have, your price, quantity, we're going to check if they're trivially copyable. It's very important. Now, what exactly is trivially copyable? A type is trivially copyable if you can copy it by copying its raw bytes. And that's what memcpy is. Memcpy means you have something like this, okay? Where you have memcpy, where you do, you have a destination, you have a source, and then you pass in the size of the thing that you're trying to copy. So memcpy is going to help us a lot because the way it copies stuff is much more efficient than any other thing, because it relies on the fact that things are trivially copyable. Trivially copyable means that types that have custom copy constructors, custom move constructors, custom destructors, virtual functions, members that own heap memory, all of that are not trivially copyable. Trivially copyable means what you see is the truth. There's nothing else beyond it. There's no custom copy constructor created. There's no custom move constructor. There's no custom deconstructor. Everything that's created is by default. There's no heap memory owned by any of the members in that. For example, we are also going to check if this order status is trivially copyable or not. That means that had this order status had like a custom constructor destructor, that would have been a problem, because then it would not be trivially copyable. Why do we need this? Well, trivially copyable types can be stored directly in a fixed size SPSC ring buffer. We're going to talk about that once we get done with this. What is an SPSC ring buffer? Well, single producer, single consumer. It's like a queue, okay? Think of this as a queue. And trivially copyable types can be stored directly in this SPSC ring buffer. And when we do a push on the queue, we do a memcpy style write into the slot in an array. So that helps. The core point here is that trivially copyable allows this memcpy. For now, you can just think that memcpy is faster than, writing a for loop and trivially copying like every single element from the source to the destination, because the compilers just go ahead and optimize this thing. What they do is they use CPU specific instructions like SIMD, cache aware algorithms, all of that things. And the compiler specifically understand things. So they just go ahead and optimize it, and they can optimize it because of the fact that they're trivially copyable types. If they're trivially copyable, they're not going to have custom copy constructors, custom destructors. So all the extra stuff that needs to be done to unlink the objects and, do all of that unnecessary stuff, it's just removed. You just have to worry about moving bytes from one place to another as fast as possible without worrying about anything else. One thing to also note is that memcpy and the string, the standard string that we have, are dangerous together. Because, if we make a symbol using the standard string, it's not trivial, because what it's doing is, if we come back to our diagram, where it go? Yeah, it has a pointer pointing to the heap, then it has a size, it has a capacity, and it's not trivially copyable. So memcpy just naturally loves trivially copyable types. And if the pointer where the heap is allocated and, if the heap is just freed up, the pointer will dangle and it will cause all sorts of problems for memcpy, which will just result in corrupted data or potentially a crash, So that's why we are adding static assert here. We'll be using memcpy, as I said, it just fastens things. So that's the key point to remember here. And we're going to add a bunch of other copyable stuff for everything. We'll have price, quantity, order ID, sequence number, timestamp, participant ID, match ID, and all these things. Everything we've created in this entire file. So with all of this, what has happened is we've created the core types, and you have a high level understanding of how this matching engine and everything is going to work. The next thing we do need to get into is creating the zero allocation infrastructure. What do I mean by that? It's pretty vague. I know. What zero allocation infrastructure means is that we don't want to allocate anything on the heap. We don't want to allocate anything on the hot path. So we'll try to understand why, new keyword is actually a problem on the hot path. You can use new keyword and, unique pointer, shared pointer, all of those things outside of the hot path in the stock exchange. That's fine. If you're setting up or starting up something and you want to create an object, that's fine. That's a one-time cost offline. But when you're online, your system goes online and millions of orders are being placed through a specific path. That hot path cannot have the new keyword or the unique pointer or the shared pointer. So that's very important, and here's where we're going to get into the main part. So what we need to do is go to the source. In the core folder, we're going to create something known as a memory pool, just so that we have a file created here. And now I'm going to talk about why all of this is a problem. Why do we want to avoid the new keyword? So why have we created this memory pool that we have? What's the reason behind it? Well, to understand why we need memory pool and why this is a separate file and a separate class we're going to create, first we need to understand what is the problem with the new keyword, right? And what is this new keyword I'm talking about? Well, if we take an example, let's say you have a class order, or maybe you have a struct order, and it looks something like this: int ID, we have double price or something. And then you call order is equal to new order, correct? That will go something like this, let's say. Cool, so you've created a new order. Now, what have you done here? As soon as you've called this new order, you've told C++ two things. First, give me enough memory to store an order. Second thing is that we want to turn that memory into an actual order object. And these are two separate jobs that you've asked for. Giving enough memory to store an order, and then you turn that memory into an actual order object. So suppose an order is 16 bytes, okay? Before anything exists on there, what exists over there? You want a space of 16 bytes in the memory. Let's have this memory created, and let's say this is 16 bytes long. What's present in this memory? Well, this memory is just a bunch of random values that have been put in, correct? And it's just random 16 bytes present. Those bytes don't mean anything. They're just space. You can think of them as like an empty spot that's present. Now, whenever the operator new is called, the compiler roughly generates something like this. So it will go and do something like, let's say, void draw is equal to operator new size of order, something like this, and it will be a space. So something like this will be called. Notice it returns this void asterisk. It is not returning an order asterisk. Right now, it's just returning void asterisk. Why? Because at this point, there isn't an order yet. It's just a raw memory. 16 raw bytes of memory have been given to you. And what is this memory called? This is the heap, by the way. So you're not getting it randomly from somewhere. This is called the heap. Whenever new is called, memory from heap is allocated. Cool. So 16 bytes are given by this operation. So that was this part 1, right? You get access to the raw bytes. Step 2 is you turn that memory into an actual order object. And to do that, what do you have to do? Well, you'll have to run the constructor. And how is a constructor run? Well, it will go something like this. You'll call new, then you pass in the raw bytes that you got over here, and then you pass in the order object. So what this means is that you run the constructor at this address. So now those 16 bytes that we have that are basically random will store the values of ID is equal to 0, let's say, and price is equal to 0.0, let's say. They're not random empty slots. You've stored some value into this. And only after the constructor finishes, this part finishes, does C++ consider those bytes as order. So now these raw bytes that are present is considered an order. Now, why is this operator new expensive? That's because the computer has to answer one question, and that is a difficult question. The question is, where can I find 16 unused bytes? Sounds pretty easy, right? It isn't. So imagine you have memory. So let's also create another one. This is memory. And memory will look something like this. Let's say, you have, I'll translate this to English so that you don't have to think in binary and hexadecimals. You'll just have, let's say, something like this. You have occupied, and let's say you have more occupied, then suddenly you have a free, then you have more occupied, then you have another free, let's say after that it's occupied, and after that it's free again. Cool. So you have RAM that looks something like this, memory just looking like this. Now, whenever you ask for memory, something has to search for a free room, right? You have to search, there's a free room here, there's a free room here. That something is called the memory allocator. Now, what is the allocator doing? Specifically, the allocator is keeping track of which memory is free. Instead of checking every byte of RAM, it remembers these free chunks. Imagine, like, would it be a good choice to go over each of these bytes? I check here, is it free? Is it free? Is it free? Is it free? And then I check here, is it free? And then I find one, then I go over rest, and then I keep checking if they're free. That's like a linear scan, right? And we have so many bytes in our memory, correct? So keeping track of which memory is free is much better than linear scanning everything. So now you have kind of a hash map or a table that is storing something like this. It stores where is the free memory present. So you can store something like, 16 bytes. They're located at the address, and let's say the address is 0x2500, or let's just say 500. Then let's say there's 64 bytes that is present at address, and let's say this address is 0x8000. Then we have 128 bytes, and the address is present at 0x12000, let's say. Okay, these are just random values, but you get the point. A table is created that stores free memory of 16 bytes is present at this address. Okay. Now, whenever you ask for this new order, not this new order, this is step 2, but whenever you ask for the new order, like you're calling the operator new keyword, it looks for a free chunk that's big enough. So we told that our order is, let's say, 16 bytes. So it will go ahead and say, free memory, 16 bytes, that's present at this address. So it will give us access to this 0x5000 address that, we are free to use it. All of these free chunks, they're stored in a linked list. Why a linked list? Well, that's because, let's say you have chunk A that's free. It's connected to chunk B. Let's say you have A that's connected to B, that's connected to C. Each chunk here stores the next free chunk. So like you have chunk A, the next value of it, the chunk A is chunk B, and the next value of chunk B is chunk C. So the allocator walks from A to B to C. All of these are free chunks, and it just tries to find, if there's a big enough one. Now imagine if there are 2 threads. So I hope you've understood like all of these concepts till now. Now let's say there are 2 threads. One thread is thread A, okay? And then you have thread B. Both ask for the memory simultaneously for the same order object, all right? And let's say instead of A, B, C, now we only have one memory chunk that's available. Only one memory chunk is free. And let's not call this A because thread A is already A. So let's call this X. Thread A wants X. Thread B also wants X. And both call it at the same time. Now, what will happen if they ask it at the same time? Race condition, right? Thread A will try to access X, and thread B will also try to access X. And both will think they have access to X, or both will think they don't have access to X. And we don't want this race condition to happen. So we need some sort of protection here. Because if we assign the same memory chunk to thread A and thread B, both memory objects will kind of try to change each other's values, and the memory is just useless at that point. What do? What is the protection mechanism? Use locks. So thread A, if it, let's say, comes in like a microsecond earlier, it will go ahead and say, I've come in here, I want to take a lock. Once the lock is done, it will take away this chunk with it. And then it will say, I've done my job, let's unlock it. So now the lock is completed. Now you have unlocked, and thread A has access to X. And thread B that came in 1 microsecond later after thread A. Now thread B is like, hey, I want access to a memory chunk. Where is it? So it will also say lock, and then it will try to find a memory. It says, oh, there's no memory. That's so sad. And then it will just call unlock and it doesn't get access to that memory. So only one thread edits the free list chunk at once. Now, what if there isn't enough memory like we had with thread B? Or you just have every free chunk that is just too small. Maybe our order object here wasn't 16 bytes. Maybe it was like 1024 bytes and we only have access to these many bytes. Okay, nothing fits. In that case, the allocator must ask the operating system that, hey, you need to give me more memory. So I hope you've understood what I've said. This part is done. This was why we needed locks. Okay, now the other condition is that, let's say thread A comes in and it says, hey, I want access to 1024 bytes right now. And then you're like, hey, I don't really have access to 1024 bytes because, I only have access to these many bytes. That's like 208 bytes or something. So none of it is fitting. So the allocator says, hey, I must ask the operating system. It's not like we don't have more memory. We have more memory, but we don't have more memory in the RAM. This is the RAM. RAM doesn't have more memory. So what will it do? It will go and ask the operating system. It will tell the operating system, hey, listen, we don't have memory. I need more memory. Give me the memory. Why are we involving the operating system now? Well, I think I've answered that, but I'll make it more clear. Your program doesn't own all the RAM in the world. Let's take an example. Let's say you have an apartment building, right? So the programs are the tenants there and the operating system is the landlord. So you cannot simply decide, hey, I'll use the apartment 402. No, you cannot decide that. The landlord has to assign the apartments. Similarly, the allocator needs to ask the kernel because kernel is the one that manages all of the memory related stuff. So you're like, hey, now I don't have access to more RAM. Can I get more RAM for this program or process? And then the kernel steps in and the operating system kernel will assign you the bytes based on that. Now we get into the realm of Syscall. So the operating system, if it wants to give you access to memory, what will it do? It does what's known as a syscall. How is that different from a normal function call? Well, in a normal function call, you have something like this, right? You have your code, okay? And your code is calling some sort of function. So you have your function after that. And then you return from it, correct? So you just go ahead and you return some sort of value from that function. So everything stays inside your program. This is a normal function call. How is it different from a syscall? In syscall, you still have your code, okay? Now, after that, other step happens. You don't run your function or anything. What happens is your function gets replaced by CPU switching into kernel mode. After that, the operating system will run. So let's just have that. So operating system runs. After that, what will happen is the CPU switches back to the user mode. So let's say CPU switches back to user mode, and then the rest of your program continues. Okay. So let's have your program continues. This is how it looks like. This is a normal function and this is a syscall. Whenever your code is running, that doesn't require any privileged information. It will just simply run it. Let's say your function is just as simple like 1 + 1 = 2. In that case, the user mode is running. Similarly here, when you're at your code, the user mode is running. Then you're like, oh, I need to do a syscall. So the CPU switches into kernel mode. Kernel mode gives us access to some privileged instruction execution mechanisms. After that, the operating system will run. Once it's run, all of that functionality is completed. The CPU will switch back to the user mode, and then your code will run as it is. As you can see, to run a syscall, the CPU had to switch into kernel mode. it had to run the OS, it had to switch back to the user mode. This is crossing a particular boundary, like this is a step in itself. And since this is a step in itself, it obviously takes more time than a normal code would, because you need to do other things in the CPU. So we've understood how this syscall works, okay? And again, syscall is just a way to execute some kind of privileged information. Maybe you want to write to the screen, read a file, all of that comes under syscall because it requires privileged instructions or privileged permissions to run it. And that's where these things come in, okay? That's all good. The next thing we have is virtual memory. Now these are multiple concepts that I'm covering, and I'll get to the core part of the new keyword that builds on top of all of this, okay? So this is the syscall related stuff. This is how the new works at a high level overview. And then I'll get into all of these mechanisms that, I'm teaching you so that we can get a rough overview of what's exactly happening. So after this, we get into the virtual memory. And this is a pretty complicated idea. So let's go over it slowly. Suppose the operating system says, here, you now own address. Let's say the address is, let me zoom in. The address is something like 0x7000000, something like this. So it says the operating system is saying you can now own this address. You might think, yeah, great, that's RAM, right? Not exactly. That's called as a virtual address. This is not RAM. This is virtual address. You can think of it as a hotel room number or your apartment room number. This is room 402. The room number is in the room itself. The operating system is still deciding which physical room corresponds to room 402. That's what a virtual address is. Virtual address maps to a physical address. So this 0x700 is just digitally a number that's assigned. And there's a mapping created to the actual physical address that's present, and that would be the RAM. So whenever you see addresses spelled out by people like address 0x700, all of this is just virtual memory, virtual address. It's not the physical address. That is not the RAM. It is just a virtual address. The operating system maintains a mapping between the virtual address and the physical address. Now let's go to the next concept, which is page fault, okay? So suppose the OS reserves this memory address, okay? I'll just delete this virtual address. Suppose the operating system reserves this memory, but it doesn't actually back it with RAM yet. So let's say you do something like *p is equal to 5, right? You try to touch that page. CPU notices that, yeah, there is no physical RAM that's attached to this virtual memory address yet. So it interrupts itself. And this is known as a page fault. Whenever there's a page fault, the OS will go and find a real RAM page. It will fill it with zeros, and then it will connect it to your virtual address. And then your instruction of *p is equal to 5 will run again. Nothing crashes. It's just called a fault because the CPU needed the OS to resolve a missing mapping and it wasn't able to. But yeah, all of that runs fine. And notice I said the OS will find a real RAM page, a physical RAM page. It will fill it with zeros. Why will it fill it with zeros and then connect to virtual address? Why not just keep it like that? Why do you use zero fill? So imagine, let's say another program just exited. Its RAM contained things like password, let's say it contained the credit card details, maybe it contained some API keys. All of that was present in the RAM, and another program exited that. So if the OS handed that page directly to you, this page was directly given to you, what happens? The OS will have handed you another program's secrets. So it will give you another program's password, credit card, API keys. That's a problem, right? one program should not be able to access these things of another program. That's confidential details. So that's why the OS will wipe out the page first. So all of this will now become something like 000, 000, and 000. And now it's all safe, correct? So that's why v0 fell. I know I'm talking too much abstract here, but just understand these smaller concepts and then I'll add it up to be a bigger concept. After this, the next thing I want to talk about is the TLB. I'm quickly covering all of this so that I can get to the main stuff. So let's say, a page exists. The CPU still has to translate the virtual address to the physical address, right? I told you the virtual address exists and now you want to convert it back to the physical address so that you can store the information in the actual physical device. And doing that translation from scratch in every memory access, it would be very slow, right? Because you're trying to convert this virtual address to physical address for every memory access. So what does CPU do? CPU keeps a very tiny cache. That's called the TLB, Translation Lookup Buffer. What it does is that it notices that, let's say you have this memory address. This memory address corresponds to the physical page, let's say the physical page 54. So in the physical RAM page 54, your virtual address is mapping to. So in reality, your data is being stored in this physical page 54, but this is an identifier for the virtual addresses. And since this is stored in a very small cache that is very close to the CPU, this means it is very fast. So the first access has no cache translation, so the CPU must compute it and then it stores it in the TLB, okay? And then the TLB, whenever you need that address again, the TLB just has this quick lookup map that you can get to. And that is super fast because it's very close to the CPU. It's similar to that, cache memory hierarchy that I showed you, where, L1 cache, L2 cache. Let's see if I still have that. Yeah, this one. This is your execution unit. You have L1, L2, L3 RAM. And similarly, very close to it, you also have the TLB. And this TLB just keeps the mapping of the virtual address to the physical address so that you don't have to compute it every single time, because computing it is a bit slower than just looking it up in the TLB, which is very close to the CPU. So it can just go fetch it and you have access to the physical memory then. Cool. Now, why did I teach you all of these concepts? Why did I teach you TLB, page fault, like virtual addresses, physical addresses, and the syscall, and this, like the two-step process in the new keyword? Well, now we can put it all together. So whenever you write something like order asterisk O is equal to, let's say, the new order that we had in our C++ compiler here, whenever you type in this, what your code does is that it calls in something like this. You call in the operator new keyword, which says, okay, I need access to the 16 bytes that are present. Okay, so this particular part is called. Now, whenever this part is called, we know that the memory allocator comes in. The memory allocator says, I want to look for a free chunk. Now, to look for a free chunk, we know it will go ahead and say, okay, I want 16 bytes, but to get the 16 bytes, first I'll have to take a lock. And it takes a lock because this heap that's present, and by heap, I mean the RAM, okay? In the RAM, we are specifically looking on the heap, okay? We are not looking at the stack. You might have seen that in RAM, there are two components. One is you store it in heap. The other one is you store it in stack. We are storing this in heap. Whenever the new keyword is called, or you have something like unique pointer or a shared pointer, all of this underneath just call the new keyword. So these are all convenience functions for RAII. Underneath, they're just calling the new keyword. So in this new keyword, what happens is that, you have the memory allocator, it looks for the free chunks, it takes a log, and then it says, okay, do we have free slots in the RAM? And we know that because there's a linked list that's stored in the RAM that contains, oh, we have a free here. We have A that's free, it contains 16 bytes. We have B that's free, that's containing 24 bytes, 64 bytes, whatever. We have C that contains 128 bytes. But let's say right now you don't have any free memory in the RAM, just for the sake of our example. If there was free memory, you would directly give that to thread A. But now you don't have it. Everything is occupied here. So what you do is you go to the operating system and you ask for more memory. Operating system will reserve the virtual pages and it will return a pointer to those virtual pages. Then the constructor that we have here will run, and now you have a live order object. I hope you've understood what's happening. The step 1 is the part that's taking the most amount of time, finding 16 bytes of free chunk. If they're present in RAM, that would be great. If they're not present in RAM, you have to ask for operating system. The operating system will do its stuff. It will return a pointer, and then you construct on top of those 16 bytes your order object. Most of the time, the allocator will find an existing free block and it will return quickly. The expensive steps are asking the OS for more memory, handling the page fault. Just to remind you, the page fault was this part where you had the virtual address, you tried to store it to 5, but there was no associated physical address with it. So the operating system goes and assigns a physical address to that virtual address, and then you can store the value. So that was handling the page faults and also filling the TLB entries, because you want to store the mapping of the virtual address to the physical address so that it's pretty fast. So they happen very rarely because most of the time the CPU is very quick. Even while executing, it's very quick, but we are trying to optimize for milliseconds here. So obviously we cannot afford to have something that takes a little bit more time. So the expensive steps only happen occasionally, but they can dominate the cost when they do. And by the way, I've told you many times that there's this memory allocator. This memory allocator is basically malloc. You might have heard of this. Malloc is the memory allocator that does all of the main stuff behind the scenes for this operator new. Operator new is just calling this malloc, which does everything I specified. The surprising part of all of this is this new order part. This new order just looks like one operation. Behind the scenes, it's actually many layers of software that are working together to make this work. You have the C++ compiler, you have the memory allocator of malloc that manages the free heap memory, then you have the operating system providing more virtual memory when needed, and the CPU that's translating those virtual addresses, caches those translations, raising page faults when necessary, all of those things. That's why the new keyword is what we are avoiding. Because other than just, depending on OS many times, the other problem that might also arise is that you're relying on heap. Whenever you have to access the heap, you have to take a lock because heap is shared memory access. Many people or many components can write to the heap at the same time. So all of them need to take a lock one at a time so that they can write one at a time, and you don't have any memory corruption that's happening. So whenever you take a lock, obviously you're increasing the amount of time that we spend on a particular task. In our entire application on the hot path, we will never be taking a lock because lock is multiple nanoseconds. I think it's about 10 nanoseconds on average, and we cannot avoid that, or we cannot have that in our hot path because the hot path has to run multiple times. So I'll just go over this flowchart once again because it's the fundamental basis of why are we doing all the complicated stuff and not just using the new keyword. So whenever you do new order, the operator new calls the malloc. Step 1 in malloc is finding a free chunk. To find a free chunk, we walk the size class free lists, hope that something fits in there. What this step means is that we keep free lists. the linked list of previously freed memory blocks, and they're bucketed by size class. So you have something like this. You have 16 bytes that contains this address. Then you have, let's say, address 0x1000, something like that. Then you have 64 bytes. These are also containing something. All of this is linked list. 16 bytes at a specific linked list, then 64 bytes specific linked list, 128 bytes specific linked list. So the allocator picks the right bucket. Do we want 16, 64, 128, or any other sorts of bytes? Then it walks down this bucket in this linked list, and then it hopes to find a chunk that's big enough. Step 2 is it takes a lock. I told you the heap is one shared resource per process. So if thread A and thread B both call malloc at the same time and both touch the same free list bucket, you would end up with two threads writing into the same next pointer. So that's the same part as I told you before, thread A and thread B both trying to access the same thing in the heap. If they have a race condition, we have a problem, so take a lock. So in modern allocators, what we try to do is avoid the global lock by giving each thread its own arena. By arena, we mean a private slice of the heap with its own free lists. So you don't give the entire heap to both the threads. What you do is, oh, thread A came, let's give it this part of the heap. And if thread B comes, we give it some other part of the heap. We don't give the entire heap to both, because if we give it to both, we need locks. But we can avoid locks if we give slices of the heap to each one containing their own free memory. So that's great. But there's still a lock if your thread's arena runs dry and has to go to a neighbor's. Maybe the slice it gave you does not have any free lists. What it will do instead is it will just go to the neighbor and it will have to take a lock then. So that's the second part, take a lock. So the next part is there a free block available? If no free block fits, we want to ask the operating system for more memory. But if the free block fits and it is available, we return the pointer and it takes 30 to 500 nanoseconds typically. So that's good. Okay. But if the free block is not available, we have to ask the OS for more memory. When we ask the operating system for more memory, that is a syscall that's made. Syscall means like this mmap operation on Linux and Mac OS, and there's called something like SBRK on old Unix systems. And we've already seen how syscall is different from the normal function code that's run. The CPU has to flip from user mode, where your program runs, into kernel mode, where the operating system runs. It has to save your registers, it has to jump into kernel code, it has to run all of the allocation logic in the kernel and switch back. Even, if you have a modern machine, that is going to take hundreds of nanoseconds instead of just the 30 nanoseconds that would have taken if the free block was available. So that's step 3. Step 4 is the OS might have to fault in a fresh physical page. Modern operating systems, I've told you, use virtual memory. When the kernel hands you a pointer, the address is a virtual address that has not necessarily been mapped to a real RAM page yet. All you have is a digital thing saying, oh, we have an address, but if physically nothing is present for it. So the first time your program tries to write to that address, the CPU just runs a page fault. The kernel says, oh, there's a page fault. I need to find an unused physical page. Then zero fill it for security, attach it to the virtual address, and then resume the main instruction that the user had given before the page fault took place. And that can be tens of microseconds. Remember, earlier we were talking about nanoseconds, and here we have stepped into tens of microseconds. And the fifth one is TLB miss on first touch. So the CPU now, it did not have the mapping between the virtual address to the physical address. So what it needs to do is store that, and it stores that in the TLB. It has to cache that in the TLB, And once that's done in the translation look aside buffer, obviously brand new pages have no TLB entry yet. So the first read or write to them triggers a page walk. What I mean by page walk is that the CPU needs to traverse the in-memory page tables itself. It is tens of cycles. It's not too much. It would be like a nanoseconds, not on the scale of microseconds, but it still has to do that. And then you have the pointer ready. And obviously, in the worst case, it will take microseconds, not nanoseconds. And when our objective is to get a lot of speed, we cannot afford that. So obviously, we are trying to avoid the new keyword because it can potentially go down this bad path. And this also makes the new keyword very unreliable, right? Because now what you think might take nanoseconds can also take 100,000 nanoseconds, which is like, microseconds. And in stock exchange, performance is our biggest concern. We are running after getting more and more efficiency out of the system. Like if you're coming from, let's say, a web development perspective, you might say, yeah, if we have a web server that's rendering, let's say, a 50 millisecond HTML page, and it takes 100 microseconds for the malloc. It doesn't matter because anyways, 50 milliseconds, 100 microseconds, 50 milliseconds is so big that 100 microseconds is not visible. But in a matching engine, all of that is visible because you're dealing with real users' money. And it has promised every participant that your order will be processed, and in the order I received, it will be done under 1 microsecond or even smaller. And if you have hundreds of microseconds of stalling, that's pretty bad. So latency is obviously the biggest issue here, but there are also other issues. For example, fragmentation. So imagine you have this new and delete keywords that are running billions of times over a trading day. So over time, what will happen is the heap will become very weird. There'll be lots of free holes, each individually are too small to satisfy the next request, and eventually the resident set size, that is the real RAM your process holds, keeps growing even though your live object count is bounded. So let's say you bought a 64 GB server, you have 1 GB of live orders, and your process is using 40 GB. And where did the rest of the 24 GB go? These are just holes. There are lots of free small holes, but they are just individually too small, because the way new keyword works is that it finds free space anywhere possible. Over billions of orders, obviously you have, let's say you have a memory like this, and let's say you have certain memory taken out by these places, okay? There's small spaces left in the middle. So if you have these small spaces, you cannot fit 64 or let's say 128 kilobytes in this maybe. So maybe you go and store it over here, and maybe there's still some gap present here. And over time, this will just be like, oh, you have 24 GB of free space, but you don't really have the space to store that 24 GB. That's called fragmentation, and it can happen over billions of orders. Second thing is cache misses. So whenever you call the new order 10 times in a row, the allocator picks wherever it sees a free hole, right? And the 10 resulting order pointers might be scattered over megabytes of address space. So when the matching engine later on walks a price level, and what I mean by price level is something like this. Let's go back to our diagram of this order book. There'll be price levels, right? At 150.20, we have 100 shares. At 150.15, we have 500 shares, and so on. So when the matching engine later walks on these price levels, let's say a queue of 50 orders at the same price. So you have, like 50 orders at $150.20. Every single order is on a different cache line, and every access is a fresh load from the L2 or the RAM, because L1 is so small that you're not able to fit in. And if those 50 orders had instead been laid out contiguously in a pre-allocated array, the CPU's hardware prefetcher would have noticed that there's a linear access pattern and would have already loaded the next several into L1 by the time you got there. What do I mean by that? Well, in hardware, there's generally a component of hardware predictor or prefetcher. What that prefetcher or predictor does is that it tries to predict what is the next element that the user might need from a specific address. And it tries to prefetch that so that, like it just prefetches it from the RAM or from this disk, wherever it's stored. Like it will just try to prefetch it from the RAM and put it into L1 so that if you need it, you can get it instantly. There's no time wastage of, oh, CPU need goes to L1, L1 isn't there, so then it goes to RAM. That's pretty bad. Instead, the hardware prefetcher can just predict, oh, the user has been going linearly in an array. And we'll talk more about this. This is a very important concept. Let's say you have an array and you're going linearly in that array. So you have I plus 1, then you have I plus 2. What will the CPU do? It will just go and see, oh, you did I plus 1. It sees a pattern that you're just going one by one. So it will go ahead and prefetch this I plus 2, I plus 3, I plus 4, and so on. Because it notices that you're going linearly in the array. So it's very easy for it to predict the next item you might want is this. So that's called cache locality. In cache locality also there's two types. There's spatial locality and temporal locality. What we're talking about here is spatial locality. Temporal locality is, let's say you access I plus 1 100 times. By 5th time, the CPU will just notice, oh, this guy is just accessing I plus 1. So let's just keep I plus 1 in L1 cache all the time. So it's super fast. And spatial is that you go I plus 1, I plus 2. It's a predictable format. So it will just go ahead and prefetch that. Or you have I plus 1, I plus 3, I plus 5, I plus 7. It might even prefetch that, but if you just have it linearly, that would be awesome because it can just see your pattern and bring in the next 5 orders right there and then. So that's what I mean. If the matching engine works a price level of 50 orders at the same price and every single order is on a different cache line, every access will mean it has to go to the L2 cache or it has to go through the RAM. Instead of that, if those 50 orders had been laid out in this contiguous prefetched pre-allocated array, the CPU's hardware prefetcher would see, oh, you're going on I plus 1, you're going on I plus 2. Okay, let me just go ahead and prefetch all of these and put it into the L1 cache so that as soon as you need it, we are already there. You get a big performance hit there. And we want to optimize for that as well. So this cache miss that we have, the cache miss is just that if it could find it in L1, that would be a cache hit. But if it has to go to the L2 cache or the RAM, that is a cache miss because, yeah, you did not get it in L1, that's why you're going to L2. You did not get it in L2, that's why you're going to the RAM. You cache missed. We'll talk more about cache locality in the future because cache locality, this concept is going to be very important to optimizing our program. The main rule that we found out from all of this is that after startup, once you've set up the entire code and your matching engine is up, the hot code path never allocates or frees heap memory. After startup is the main part. We will still call new once in the constructor of each pool before the first real order arrives, and that is fine. Startup happens offline in a quiet moment, right? The cost is absorbed, like how much ever time it takes me to bring up the entire system, that's fine. But once the system is up, I want that path to be very, very fast, and we need to avoid the new keyword by never allocating or freeing the heap's memory after that. That's why we're going to create our first file. There's going to be another file called SPSC Queue, which we'll talk about in more detail once we get the memory pool done. But what the memory pool does is that it hands out fixed size object slots. In one sentence, what it is a bag of n pre-built buckets you can take from and give back in O of one time. So instead of, calling new or a delete keyword which allocates memory on the heap, what if you can just have one contiguous array that's containing, let's say, 1,000,000 slots, in which you can pass in the order and you can remove the order. That is the memory pool. Fixed size object slot. That's it. And this is not something that's very novel. Every serious low latency system will reinvent this primitive. Maybe it will use a version of this or something similar to this, but it will have this. So let's try to understand this very interestingly, okay? You can easily, in O of one time, remove an object out of here, push an object out of here. It doesn't allocate on heap. It doesn't have to do the new keyword. It is pre-allocated. Simple. Now let's go ahead and have hash pragma once, include array, C standard def, memory. What do each of these includes do? Well, the array is just giving us the standard array, which is just a C++ wrapper around a fixed size C array. We use it for the raw byte storage inside each slot. Then we have C standard def, which gives us size T and byte kind of things. So like if you notice size T, that's coming from this. Then you have memory, which gives us, the unique pointer, make unique, construct at, destroy at, all of those things. And now you might say, hey, unique pointer? Didn't you say unique pointer calls new behind the scenes? And that's true. I did say that. But I also said we'll call it once in the constructor when the system is being started. That's when we're going to use it. Otherwise, we're not going to use it. After that, we have this namespace of Exchange core. Remember, in types.h, we were also in Exchange core. This is also Exchange core. Simple. Now, let's go ahead and design how our memory pool is going to look like. And what exactly is the problem we're solving? Like, what is it going to do specifically? So matching engine is just the part where, the buy and the sell is just, given to each other. Like the sell orders come in, the buy orders come in, and they match to each other. That is the matching engine. So matching engine creates orders constantly. A busy exchange might process millions of new orders per second. Each new order needs a chunk of memory to live in, typically 64 bytes. So we have price, quantity, side, owner, status, all of that. And we're going to create an order later on. If you remember, we've already created all of the things here, like the order status, order type. All of that will be fit in within the order that we have. And will typically be 64 bytes worth of fields. So when the order fills or gets cancelled, those 64 bytes have to be reusable for the next order. Otherwise, we leak the memory and run out of RAM within minutes. So we need an allocator with 4 properties. Number 1 is we need O of 1 allocation, right? It should always be O of 1 allocation. We don't want it to usually be fast. Sometimes it can be slow. There should not be any variability. A constant number of CPU cycles every single time, no matter what the state the allocator is in. Second one is O of 1 deallocation. So if we want to remove something from the memory pool, we want it to be O of 1 deallocation. The third thing is going to be there's no call to malloc or free. So we have already discussed this. The main reason of creating the memory pool is that we have this no call to malloc or free. That means we don't use new keyword, shared pointer, unique pointer, any of those. And then we are going to have cache aligned returns. What this cache aligned returns means is that 2 orders never share a cache line in a way that will waste the bandwidth. What I mean by that is, let's say we go back to our example of where I explained to you how the cache alignment works, right? all of this, like this part will have a specific cache line. Then you have the other part that is a cache line. So each of these cache lines, should be aligned such that the two orders never share a cache line in a way that will waste the bandwidth. So that, like if one cache line would be fetched instead of two cache lines being fetched. If you remember this part about struct example and how this entire thing works of getting 8 bytes and then the other 8 bytes and so on. Like if you remember that, that's it. That's what we want here as well. So these are the 4 properties that we need. New or delete cannot be used, O(1) allocation, O(1) deallocation, and cache aligned returns. So we want to build the smallest, narrowest custom allocator that will satisfy them. Now, what is a slab allocator? The idea is pretty simple. Let's say you have these slots created, okay? You'll have a bunch of these slots, and I'm only going to draw in like 4 slots, okay? And let me zoom out a little bit. So you have these arrows connecting one to the other. So you have one line, then you have the second line, a third line. Cool. Now all of these slots are free. They are linked together as a free list. That is it. At startup, we carve out one big block of bytes. We'll divide them into n equal sized slots and link all of them together in a singly linked list called the free list. To allocate, we'll pop up the first node of the free list, that's O(1). To deallocate, we push the slot back onto the front of the free list, so that's O(1). There are 2 pointer moves, and there's no system call, no fragmentation possible because every slot is the same size. So any free slot fits any new object because it's free. It is fixed size, right? That's the main thing. How will fragmentation occur if everything is of the same size and it is cache aligned, right? And there's obviously no malloc to call. So this is the slab allocator. We have reserved a specific number of bytes. We've divided them into n slots, and we either remove this item off or we put it back in. Everything happens from the front. We are going to add a twist to this, which is we are going to make sure that this thing that we have is almost free in memory. What we are going to do is make this entire free list that we have intrusive. Now, to understand this, we'll have to understand what is intrusive and non-intrusive free list. So let's understand it. This is a very common trick in low latency code. So yeah, just pay attention. So what is non-intrusive? Let's start by understanding non-intrusive list. So each node in this free list is a small separate object that holds a pointer to a free slot. So let's say you have the same thing. I'll just copy and paste that in. Okay. Then you have, let's say, a head, and this head points to, let's say, this particular thing, and I'm unable to see it. Let me just go out and do something like this. Head points to a node pointer, and this node contains a pointer to a slot. Okay. So let's say it says that, yeah, it points to slot 0, and this slot 0 is free. And then this node points to the next node, and this node also contains a pointer to another slot. Okay, so it contains slot 1 and so on. So this slot 0 is currently free, slot 1 is also free, and then you can keep going. Okay, you also have slot 2 here, and then you also have slot 3 here, and let's say after that you have null, and then you just have a pointer to this null. So as you can see, there are 2 different data structures that are being used. The first one is the free list itself, and the other one is the slot where the actual storage occurs. The slots will contain the actual storage. The node objects that we have here are the free list itself. What's happening here is that each node in a free list is a separate small object that holds a pointer to a free slot. This is the non-intrusive list. And how is it different from the intrusive list? Well, I'll show it to you. I'll just copy and paste this in. So we have intrusive lists now. In intrusive list, you have a head that points to slot 0 directly. You do not have a node object as such. And then there's a next pointer after that, and the next pointer directly points to the next slot. So you have slot 1. And in that slot 1, you have the next pointer, and that next pointer points to the next one, where you have slot 2, which is, let's say, present and it's free. Then you have next, then you have slot 3, and the next for that is null. So what have we done? Instead of having a separate storage area here, you've combined that into the node itself. There's just one data structure here, the free list. And that free list exists only in the unused bytes of free slots. There's no extra allocation here. There's zero overhead happening. As soon as the slot becomes live, the next pointer disappears and that storage holds the actual object instead. In the non-intrusive one, for example, what would happen is there would be the node objects. We allocate them somehow, and then we are allocating memory to track free memory. So that is obviously extra allocation happening. So the insight here, and it sounds pretty obvious once we say it out loud, is that when a slot is free, nobody's using its bytes for anything. So we can borrow those bytes to hold a single next pointer. The moment somebody calls like an allocate and starts constructing an object into the slot, the next pointer gets overwritten by the object's fields, and that is fine because the slot is no longer in the free list. We already disconnected it. So in intrusive free list, what's essentially happening is the next pointer lives inside the slot itself. It borrows the slot's own bytes. Let's take an example to understand how this will all work. So in the initial state, what's there is you have a head that's pointing to slot 0 and it is empty as of now. It's all free slots. So slot 0's next pointer points to next of slot 1. Okay. And slot 1 is also empty. So the next points to slot 2. Slot 2 is also empty. So the next points to slot 3, and slot 3 is also empty. So next points to null. Okay. After that, let's say allocation happens. Now you want to take one slot and assign value to it. So step 1 is you take the slot, you move it out, okay, and also take slot 0 and next with you. And now you're just like, hey, I have certain memory here. So slot 0 now contains the value, and you have, let's say you store the value that ID is 101. And let's say, what is the other thing we stored? Let's say it was the cost or something. Okay. So the cost is, let's say 10.1. Cool. So you've stored it in this slot. Now what you do is this head will now point to slot 1. And this pointer of slot 0's next will not point to slot 1 because slot 0 now has elements. So you've taken one slot from this memory pool and given it a value. Now the first slot of head is slot 1 because slot 0 is no longer existing, right? Now let's say after that you allocate again. That time what will happen is slot 1 will be deallocated, or I mean not deallocated, but it will be taken away. Head will point to slot 1. Next of slot 1 is not slot 2, and slot 1 now contains the actual value. Maybe you have ID 100 and 2 and the cost is 10.1 as well. That's what's happening. So this is how the memory pool is going to work. And let's say after that you have deallocate, okay? And you've deallocated this slot 1, or let's say we deallocate slot 0. What will happen in that? Well, what will happen is it doesn't have this value anymore. Slot 0 goes back to this memory pool, and now you again have this next value, and the head now points to slot 0, and the slot 0's next value is slot 2. And let's say after that deallocate is also called on slot 1. In that case, you'll put it back over here. Slot 0 will no longer be actually slot 0 because now it actually is present in location 1 here, but still it's the previous slot. Its location has now changed because every allocation and deallocation happens from the front of this linked list. So when it's not in use, what happens is that, okay, let me just fix the arrows here. So you have head pointing to slot 1 and slot 1 pointing to slot 2, slot 0, and obviously slot 1 does not contain anything. You just have a next pointer. So the core thing here is that a slot cannot be simultaneously free and in use. So the same bytes that are present, so like slot 1 contains bytes, right? They can either be the next pointer when free, or they can have the object fields when alive. So right now they're free, so the next pointer directly points to the address. So this next actually stores the address of slot 0. But if it's not, if it's not free, in that case, there will be no next pointer. Instead, you'll actually be storing the slot data or the slot values. I hope you understand that. So this next pointer that we have can either be free or in use, but it cannot be simultaneously both. In non-intrusive, it was the other thing, because here you would have the next pointer pointing to the next node, but the actual storage would happen in the slot 0 storage. It did not take into consideration that a slot, if it's free, doesn't really have to store anything. It can just make use of this next pointer to store the actual data of slot 1. So yeah, that's pretty much what our memory pool is. We are using intrusive list for that. It's called intrusive because you no longer have two separate things. Next pointer and the slot data will be merged in. They'll kind of perform like a variant or a union. If you know C++, you can either have next or you can have the actual data values. But this trick that we have has one consequence. Every object stored in the pool must be at least the size of a pointer. Because, if you're storing next, it has to be storing the pointer of the next slot. And a pointer is generally 8 bytes. So you need to at least have every object stored in the pool of the size of the pointer. And the pool will enforce this with a static assert, and you'll see that when we write this code. Having understood this intrusive list, and that is pretty much what this memory pool is going to be, very simple. What we are going to have is this. So let's go ahead and define the class declaration, right? So you have a template of type T and a size T of size N. Okay. So what have you doing here? If you have never written a templated class before, whenever you have this template written out, you're telling C++ that, hey, this class that we have has two parameters that are filled in at compile time. T is the type parameter, like what is the type of object to pool? What is this memory pool going to be of orders? Is it going to be of levels? What is the type of this memory pool? Or is it of integer or a string? You can put in anything you want. And then you have a size N, which is what is the capacity? And it's going to be an integer. So that's why we've used a size T, unsigned long value. So later you will see we use memory pool where we pass in something like this memory pool where we have a type T where you've passed an order and then the size N, which is something like, let's say 1 million, correct? This is how we're going to have it. Let's understand why is N a template parameter. Why should this be a template parameter? I understand why type T would be, so that we can just make this memory pool reusable. It will work for orders. If we want to use it for something else, it can be used for something else. But why this N? Why can't we just take it from the constructor, right? Why can't we have something like memory pool where we take in, let's say, an int N and then use it over here? Why do we have to take it from the parameter, the template parameter? Well, that's because when n is known at compile time, the compiler can do real magic with it. So I told you that this template is a way to tell C++ that at compile time, not at runtime, at compile time, this class will have two parameters. So when you run the compilation part, n will be automatically filled in. But when you have a constructor, this constructor will run at runtime. At runtime, it cannot do the magic that compiler generally does. And what is the magic? So if this n is a power of 2, modular arithmetic, by modular arithmetic I mean, let's say you have an index and you do %n. If you do index %n, it can be replaced with something known as index ampersand n minus 1. This is bitwise operation. The benefit of doing index and n minus 1 and not index %n is that a modulo operation costs about 20 cycles on x86 machine. A bitwise AND costs 1. As you can see, we are saving the number of cycles. That's why we are taking this. And at compile time, the compiler can do this. At runtime, the compiler cannot. What if n is not a power of 2? In that case, it will not be really helpful. So yeah, but the compiler can do two more things. The second thing is that it can loop over fixed size arrays and it can be unrolled. So the compiler emits 8 or 16 copies of the loop body and it can run them in parallel. So that makes it really fast, right? I mean, just imagine you have for int I is equal to 0, or let's say, and then you do I is less than n, I plus plus. Instead of going over it sequentially, the compiler can just do like, oh, we need this 8 or 16 copies of this loop. Just run all of them in parallel because this is a fixed size array and we know about it at compile time. So we can just optimize that. So that's obviously going to be much faster because now you're not doing a linear scan. Behind the scenes, it's just splitting it up and running them in parallel. The third thing is that the size of the storage is baked into the type. There is no runtime indirection. However, in our case, the pool itself does not use the power of 2 trick, and the SPSC Queue that we are going to make next after this memory pool will use that, but the principle is the same. We want to make as much as possible knowable at compile time, and the compiler will reward us for that. That's a very important rule. I'll say it again. We want to make as much as possible knowable at compile time, and the compiler will reward us for it. The more the compiler knows, the better it is. After that, we are going to put in the two static asserts. First is that n is greater than 0 because the memory pool capacity must be positive. And the next thing is that the size of t is greater than equal to size of void asterisk, which means that the object storage must fit in an intrusive free list pointer. The benefit of having this is, like these two static asserts, is that if you type in something like memory pool and then you pass in, let's say, order and 0, you will get a clear message that, hey, what are you doing? The memory pool capacity must be positive. It should be greater than 0. And the second static assert will help us when we make use of the intrusive free list trick, right? I told you that if we ever try to pool an object smaller than 8 bytes, like an int32, the compiler will refuse because there would be no room inside a free slot to store the next pointer. So that's what we are doing here. Awesome. So having understood that, let's move on to the next one, which is the slot structure. So let's create a struct slot here. And what is the slot going to contain? It is just going to contain an array of bytes of the size of t. And let's call this storage, right? What's happening here? A slot is one bucket in the pool, one piece of raw storage that could become a t later. So we have a standard array of the the type bytes, and it contains these many, like the size of t, and the variable name is storage, right? This is raw untyped storage, exactly the size of 1 of t. So we are creating a slot where we have an array of bytes And this untyped raw storage that we have is the size of, let's say, the order, which is this T. And by the way, the standard byte is the C++ 17 version type. That just means this byte is storage, not a character, not a number. You can just use it to store whatever you want. When we use byte instead of character, we're just telling the compiler that, hey, this byte that we have, we're not interpreting it as character. We are not treating it as integer. We're not treating it as anything. What we want is bytes so that we can reinterpret it for any purpose that we want. And when we use this kind of initialization, we are zero initializing, which is, very optional, but it will just prevent undefined behavior if someone reads the bytes before we have constructed anything into them. So yeah, we have a slot that is just an array that contains bytes, and one slot is just the size of one order. So this slot that we have, its size is basically just containing, is it the size of order? Okay, I'll give you 16 bytes of free raw data. You can store whatever you want in those 16 bytes. So you can have a next pointer. You can have the actual data. Whatever you want, you have access to it. You got it. Also, one thing to note here is that slot is not a T. It is raw bytes that are placed in. One slot does not mean one order. One slot means you have bytes to store one order or to store the next pointer. You can interpret those bytes as anything you want. The next thing we are going to add to this structure is we are going to add align as. And this is a pretty good logic. We have align as align of T. If it's greater than 64U, then we align of T, otherwise we use 64U. This is the alignment specifier. What we are saying here is that we align this slot to whichever is bigger, T's natural alignment or 64 bytes. For most types, that is 64. And why 64? To understand all of that, I'll take a detour. We have to understand what is a cache line and why do we care about a cache line. I've been saying cache line here and there, but I've not specifically talked about it till now. So let's understand that. So we've already talked about that the CPU does not actually read memory 1 byte at a time, right? Let's go back up here and try to find in our thing. So here, when I was going through this part, I told you that the CPU does not fetch 1 byte at a time. It does not take this byte and fetch it. Take 1 byte and fetch it. That's not exactly what's happening. When you ask for byte, let's say 10, what happens is that the CPU will load a bunch of bytes, and I'll actually take a bigger example, okay? Let's say I have a much bigger thing, and in that much bigger thing, you have, let's say, slots 0 or bytes 0 to 63 bytes. Then you have 64 to 127 bytes. Then you have, let's say, 127 to something like 191 bytes. Or not 127, 128 to 191 bytes or something. So let's say you want to get access to byte 100. So when you ask for byte 100, the CPU loads bytes 64 to 127. A 64 byte chunk is called a cache line. And this is taken from the RAM and it is put into the L1 data cache. Okay. And in this L1 cache, you take these 64 bytes and you put it in there. And this is called a cache line, okay? Now let's say if you read byte 101 next, it is already there, right? It is free and instant because you've already transferred 64 to 127 bytes in this cache line. And if you want to read 126th byte, you still have it in the L1 cache. Now let's say you want to read byte 200. In that case, another cache line would load. It would take this cache line, or actually not, this 200th byte is not present here. So what will happen is you will have to go and do 192 to, let's say, around 255 bytes here. Then you will have to load that into this part. And in the L1 cache, now you have another place that stored then these 64 bytes. And now you can read the 200 bytes. And what would happen if an object is not aligned to 64 bytes? Well, let's imagine this case, and it's very similar to this one. We've already talked about this, but I'm taking a much bigger example. Let's say it is not aligned. So let's just copy this part and paste it in again. Now you have 0 to, let's say, 63 bytes here, but in the actual storage, how you've stored it is 0 to 49 bytes occupies something for you, and then 49 to 63 bytes store something for you. Then you have 64 to, let's say, 72 bytes storing something for you, and then 72 to, let's say, 127 bytes storing something for you. Just a random thing. But this is one data point, this is another one, this is another one. It's not cache aligned. It's not memory aligned. None of that is happening. Now, if you want to load, let's say, the order or the byte number 48, you go ahead and refer to this 0 to 49. So you load the entire thing into L1. So let's create the L1 cache again. And I pull this out and put it inside of this. Now 0 to 49 bytes is loaded within this L1 cache. After that, you need the 49th byte that's still present in L1 cache. After that, you need the 50th byte. The 50th byte is not present in the L1 cache, so you need to go and fetch this out and put it over here. That means 2 loads are needed. Had you aligned them properly, what you would have is 0 to 63 bytes containing one thing, so you would only need 1 load instead of 2 loads. And you wouldn't have to load 2 cache lines, only 1 would be enough. And this is called a cache line split. It is a real cost. With 64 byte alignment, we can start on a cache line boundary and avoid it. So for example, if you have 0 to 49 bytes, what you can do is add in a padding of 50 to 63 bytes here, so that the padding remains and you start at the 64th byte only. And that will help the CPU batch and get the next one, because the CPU will always fetch the next 64 bytes. So let's just ensure that when it starts at 0, it can get this entire thing in once. If it starts at 64th, it can get this entire thing. Same concept as what we've discussed, but I'm just making it more concrete. And this is what this struct align as is doing. It is just ensuring that the 64 bytes is used if this align of t is not greater than 64. Let's say something is greater than 64. Let's say it is 128 byte alignment. We do not want that t, which requires 128 bytes, to use 64 bytes, right? That would be memory corruption. That would just be overloading, and that's wrong. So what we do is, if something requires something greater than 64 bytes, we'll use that. Otherwise, we'll use 64 bytes. That will make our system better, because it will not be fetching 2 load instructions at a time. It will only be doing 1 at a time. So I hope you've understood this align as. All it's trying to do is add in padding if you don't have 64 bytes as it is, so that the CPU can fetch properly and only 1 load is required, so the cache line splits don't affect us. Or it will just respect the bigger one. But most likely in our case, we'll only be using the 64 bytes, because we don't use the memory pool when the align of t is greater than 64 bytes. Like, there's literally no use case. But just in case in the future you expand this project, your app won't crash. Sweet. Let's move on to the next thing, which is the free node structure. So this is the trick. When a slot is free, we will pretend the first 8 bytes of its storage are a free node. And this is the free node. The next pointer points to the next free slot, and we've already taken a look at that. I'll just go over to that. If this next is there, that means the slot is free. So this next is just storing the address of slot 2. That's what's happening here. You have a struct free node, and the next is just a pointer to the next free node that exists, right? So when a slot is free, we will pretend the first 8 bytes. This is just an 8 bytes because this is a pointer. Pointer is always 8 bytes. The 8 bytes of its storage are a free node. The next pointer points to the next free slot, and the free list lives entirely inside the slots themselves. And this is the part that makes intrusive free list possible. And like this structure is the reason why we had this static assert, if you've not already figured that out. If t were smaller than a pointer, you literally could not fit a free node inside the slot. Awesome. Having understood that, after that, we are going to go ahead and build up the constructor. Or before the constructor, let's just have a unique pointer to slot, and we have the slots, okay? Now notice, I've used a unique pointer here, which is a slot array. So you have this slot, right? Where did the slot go? You have the slot. Slot contains an array, which contains the raw bytes. And then this slot is also multiple slots, right? I mean, you have multiple slots, and within the slot, you have multiple bytes allocated. That's what's happening. And we've created a unique pointer to it because this will all be set up once we are starting up the entire system. It is not on the hot path. Cool. So this will all happen kind of offline. As soon as the system goes online and we start taking in orders, none of the unique pointer, shared pointer stuff will come in. Now let's go ahead and create the constructor. So in the private, we had created this variable attribute. And now in the public, we have memory pool, which is a constructor. And now you're going to assign slots their real values. Because right now, the slots are just these things. You want to ensure that the slots are of size n, right? And to do that, what we'll have to do is pass it in over here. So we have slots where we redefine them with the value make unique slot array of size n. All we are doing is populating them with values, and it is of the size n. After that, we will initialize the free list. Again, I'll tell you, this is the only call to the heap allocator in the entire file. This was the once at startup new that we promised was okay. After this, every allocate and deallocate is just pointer arithmetic that we're going to do. Another thing to notice is that we've used make unique, right? Because make unique returns a unique pointer, and unique pointer is just a smart pointer that will automatically free the array when the pool is destroyed. I've told you, unique pointer, it is just a convenience function over new so that we get RAII cleanup at shutdown. RAII, I hope you know that because that's the fundamentals of C++, but it stands for resource acquisition is initialization. We don't have to call the delete to throw away the slots. So we automatically get that cleanup at shutdown without writing a deconstructor ourselves. And third, the most important question you might have, why are we using the heap for the slot array at all? Why don't we put it on the stack? And that's because production-sized pools might hold 1,000,000 orders. Rn can be million. An order is roughly going to be 64 bytes. We'll write our own order structure in just a bit. Like we have 2-3 more files to write, and after that, we'll go on to order. And in order, it's going to be about 64 bytes. Now multiply 64 bytes for one order with 1,000,000 order pool that we have. That is 64 megabytes. Thread stacks that we have are typically 1 to 8 megabytes. So we cannot fit 64 megabytes in 1 to 8 megabytes, right? So we cannot use stack for that. We'll have to use the heap so that it doesn't blow up our stack. So we put all of it on the heap, but we do it once, exactly at startup time. So it doesn't matter. And then we will call initialize free slots so that we can link all of the slots together. I'll go into this initialize free slots function in just a minute, but before that, let me just create all of these functions, or like the destructor, the copy function, all of that. All I'm doing is deleting all of them. This is a very defensive declaration. So memory pool is a unique resource. It is going to be one big chunk of bytes that lots of live objects point into. Copying it would mean two pools believe they own the same storage. And that is pretty bad, because if two pools believe they own the same storage, we have double free and use after free bugs. We also can't move it because moving it would invalidate every pointer ever returned by allocate. Since we're not going to use both and we don't want to create confusion, we just call delete on them. Delete is just a way to say, hey, this operation like does not exist. Any code that tries it will fail at compile time. And like this is just the code that is there so that it's for the developer experience. You don't want to confuse anyone so that they don't use copy, move, any of these things. Having done that, let's go on to initialize free lists. So I'm going to create my own function called void initialize free list, no except. No except is just, hey, we are not going to throw any exception, but that's true for any function. So you can completely omit it, but I'll still keep it. After that, we build the initial free list. So the first thing we need to do is obviously have a variable that can keep track of what is the head, right? This head that we have, what is this head pointing to? Initially, the head is going to be a null pointer. For that, we will have to keep track of the variable. So let's create it as another attribute here. So we have free list head is equal to null pointer. Let's create it here. Free list head is going to be a free node pointer, and initially it is a null pointer. After that, what we'll do is we'll go over until n and we'll try to create an entire free list, right? I mean, the first step literally is there's no data in here. So we want to initialize everything to empty. So everything, this slot is not going to have 16 bytes. Instead, it's going to be next. And next, it's going to point to the next slot. And this will point to the next one and so on. So you have free list head is equal to null pointer. And then I have a for loop. The index is equal to 0. Index is less than n. Plus index, we go over until n that's present, maybe 1 million. So we go over 1 million. Then we have this node, which we reinterpret as free node. Remember, we have slots at index. The slots was this empty kind of slot that we had. These things. And these things have a storage attribute in them. And this storage.data contains the array of bytes that we're talking about. So what we are doing is slots at index dot storage dot data, and we're reinterpreting them as free node. So all they contain is the next is like, it's right now what we have done is we've just created these slots and all of them just have free node in them. The next that we have does not point to anything. It's just a null pointer. Even here, the next is just a null pointer. Next is just a null pointer for all of them. So we've just created a bunch of free nodes here, and now we need to connect their next values to each other. And that's what we're going to do. We're going to do node.next is equal to free list head. And then the free list head is going to be the node. So what we have is something like this. You have created a node first, okay? You've interpreted this as a free node. If you've interpreted that as a free node, then you have a next, right? Now this next will have to point to something. So this next is null as of now because the next thing has not been created yet. And then you said that the free list head that we have is a node. After that, you construct another one, okay? And that is another next. And now you set this next node to the free list node head. And remember, in the previous iteration, we had set this node that we created as free list head node. So you had something like head pointing to next, pointing to null, correct? So you had head pointing to this node and this node's next value was null. Now what you have is another node. You've created it. It's a free node. And now you're saying that this node points to this node because node.next is free list head. And in the previous iteration, we had set free list head to be this particular node. So now we have connected both of them. And then you say that this free list head is now the node. So whatever is the head is now pointing to this next. Or not pointing, this head, this next node is the head. And now let's say you have another one. So you've created next, then you've created an arrow to this next. and now the head is this node, and so on. So what have you done? You're always initializing from the very beginning, correct? If a new node is added, it's added on the beginning. If a new node has to be removed, then it's removed from the beginning. That's exactly what we wanted, O of 1. Great. So that's about it. I would just like to emphasize again on this line because this is a very interesting line. Remember, in slots at index, what we had stored, or in slots, what we had stored is a slot array. And in that slot array, we had one slot each. And in that one slot each, you had bytes array. And those bytes could be interpreted as anything. That's what we have done. Slots at index gives us one slot, and in that slot structure, we have a storage. So when we access that storage.data, we get access to the underlying all of these things, correct? So then we can do node.next because it's now interpreted as a free node. Those bytes can be interpreted as anything. So we just tell the compiler, hey, trust me, these bytes are a free node. Yep, that's it. Reinterpret cast, you might think, and you're right to think, is a dangerous operation. If you're using it, you should be careful with it. It does no checking, there's no conversion, it just relabels the bytes as whatever you tell it to. So just ensure that what you're doing is correct. Here we are extremely sure that the free bytes are free nodes, so it's fine. Cool, so we have initialized the free list, we have everything that's empty now. The next thing is creating allocation. We know how allocation works. We just take the slot at the very beginning, we remove it, we store data in that. Head will now point to the next node of this previous head node. Simple. So let's go ahead and create the function of allocate. See the return value of this, t asterisk allocate. It returns a pointer to the object that's being returned. So first of all, you're going to check if the free list head is a null pointer, then you return a null pointer. This can only happen when the memory pool is empty. Like, is the pool exhausted? If yes, return the null pointer. And the caller will have to check the return value as a result, because they'll have to check, hey, I've called allocate, is this a null pointer? If it is a null pointer, then the matching engine will have to deal with it. Generally, you would just have a raise function or a throw exception returned from here, but since we have no except and we are not using exceptions, we don't have that. Great. After that, we are also going to put in unlikely. What is unlikely? It might seem like a tiny attribute, but it has very big effects. The unlikely attribute is a hint to the compiler that this branch, that this if condition is rare. Do not optimize for it. Once you say that to the compiler, two things happen. First is instruction cache layout. Recall that earlier when we talked about types and CMake list.txt file, I told you that the CPU has an instruction cache, the I cache, which is typically 32 kilobytes of L1 sitting right next to the execution unit, and that an L1 hit costs approximately 1 nanosecond, while an L2 hit costs approximately 10 nanoseconds. The hot path of the matching engine has to fit in L1 if we want speed. Without the hint, the compiler typically lays out the assembly in source code. Let's go back to this part. When the compiler lays out the assembly in source code, what happens, and by the way, this is the one. So when the compiler typically lays out the assembly in source order, what happens is you have something like this. Maybe the assembly looks like this. Let's say this is the hot path, and what you're doing is you're trying to compare, let's say, the free list head, and you're comparing it to 0, and then you are just like, we jump if it is equal to handle empty, and then let's say there are some other things that are happening, and then you return from here, and then you have handle empty kind of thing, and what you're doing in handle empty is just XOR between RAX and RAX, which is just that we return a null pointer. So that's it. So this what happens when the compiler lays out the assembly in source order. The problem with this is that you're doing a compiler compare, and then you're checking if if the comparison value is equal, we jump to handle empty. With unlikely, this attribute that we've passed in, the compiler will move the rare branch out of the hot region entirely. What it will do instead is that the assembly will look something like this. You have hot path, then you have something like compare free list head to 0. Okay, and let me just move this a little bit. So compare free list head 0. After that, you have jump equals, and what you do here is cold handle empty. So what you're saying with this is that predicted is not taken. We branch to a cold section. Then there's some other operations as usual, and then you return. Okay. After that, there might be a huge gap, or possibly it can be on a different memory page. So let's just say there's a huge gap, or it's just in a different memory page. After that, we'll have cold handle empty, and then we'll do XOR RAX return. So the difference between both of them is that the hot path is now one dense block of instructions with no error handling code interleaved. There's smaller instruction cache footprint that's present here, and fewer instruction fetches are happening per allocation. And on a path that's running millions of times per second, this will matter, right? If this jump equals is a rare thing that will happen, it makes sense that all the other instructions are in line and you do not have to jump, because jumping also requires some time, right? You need to calculate which address to go to and do all of that. If everything is linear, you just have to go to the next instruction cache and then just run it. So that's pretty good. The effect number 1 is this. Effect 2 is branch prediction. So the modern CPUs execute instructions in a deep pipeline. They have to guess which way each branch will go before knowing the actual outcome, so they can keep feeding new instructions in. For this, they use a branch predictor unit. And this is actually very similar to, if you think about it, the hardware prefetcher unit. In hardware prefetcher unit, you're trying to prefetch the instructions that might be executed next based on the contiguous array, the cache locality that we talked about. Similarly, in branch prediction, you're just trying to guess which way each branch will go before knowing the actual outcome. So you're just trying to predict so that you can have the instructions quickly in there, and then you can just execute it very quickly. So if a branch usually goes one way, it predicts that way. A misprediction will cost 10 to 20 cycles, because the CPU must throw away all the speculatively executed work and restart. With unlikely attribute, what we have told our compiler is that you can emit the assembly in a shape where the branch prediction unit's default guess for an unseen branch, for a branch that's typically not taken, it will match our hint. So combined with this iCache layout effect, this will give us measurably fewer mispredictions on the hot path, right? Because the branch prediction is already predicting what's going to happen next. And if it doesn't happen that way, then it will throw away and it will cost us a bit more. But generally, there's always going to be space, right? I mean, we are storing 1 million units in there, 1 million slots. Obviously, there's going to be more and more space, and we're going to deallocate as soon as possible too, because as soon as the matching engine gets over, we're going to deallocate and go back and throw this in, like our slot, into the memory pool. We are going to deallocate. So obviously, there's always going to be there, but we're just handling this edge case that might occur. So that's why it's unlikely, and we get all of the optimization that's done there. So both of these effects, they just save us, let's say 10 cycles or something like that. It's very small, but when you calculate it over 1 million operations that might happen per second, they add up. After that, let's go to the real allocation logic. I'll go back to our diagram. I've been moving around a bit, sorry for that. So let's do this. What we want to do is, once we've checked the if condition, we want to get the head node, right? Because the head node is the front node that we want to store our data into. So we have free node is equal to free list head. Now we have access to that node. And now what we're going to do is the new head, the free list head, earlier this head was this guy, right? What we want to do is move this head to this guy. So we'll just do the current free list head that we have. Its next pointer is going to be the new head. So we're going to do free list head is equal to free list head dot next. So whatever is the current free list head, its next value is the free list head. Okay, so we have successfully made sure that this is present, but also head now points to this. The next thing we want to do is this node's next value should not point to slot 0. Instead, it should be removed, and now we store actual data in it. And since free list head's value has been changed, this node will help us out, because this node was basically holding the temporary value because we knew that this free list head is going to be reallocated, right? So the head is now the head.next. And now we'll take in the node value that we've deallocated. We are going to increment the allocated count because we have done one allocation more. And let's just create a count for that. Allocated count is 0. So we have allocated count. And now we'll reinterpret cast this node. So now this node is no longer a free node. It is a type of order or any other type that we had specified earlier on. We're again doing reinterpret cast for this. So these bytes that we saw, it's for no other purpose now. It's not a free node anymore. It is an actual order object. So this is now an order object, and whatever values we need to put in will be called in the caller function when allocate is called. That's great. So that is it about our memory pool. We don't really need allocated count. I had added it when we were doing some kind of diagnostics, like when I was doing unit tests or for benchmarks. It's all useful data. If you want to log it out, that's also pretty good, but we don't need it anymore. You can remove it if you want. So we've understood how allocation works. Now let's understand how deallocation works. And deallocation is, I've explained it to you. Allocation was just about getting the front slot, removing it, and storing all of the data in it. It's no longer a free node, it's an order object, so it doesn't point to slot 0 anymore. And yeah, so the next value is removed. By the way, when we do reinterpret cast this, the next value is removed, right? Because it's an order object now. Order object cannot have a next property. So yeah. Now let's go ahead and have deallocate. So let's have deallocate. You have an object that you take because you want to deallocate a specific object, right? Deallocate just means you go to the memory pool, you store the object back to the front of the linked list. That's it. So now we are going to do this. If the object is a null pointer, and that's also unlikely, and I've already explained why unlikely is a great thing to do here. It just helps us with our instruction cache. It helps helps the compiler write assembly code that will help us because it's an unlikely code to execute. Why should we waste cycles on unlikely code? So once we do need it, which is very unlikely, it will take a bit more time, but when it doesn't, it will save us a little bit of time. So yeah, reasonable trade-off. So once you've deallocated, what do you want to do? Well, the first thing I want to do is I want to remove all of the data that was present in this object. And to do that, I'll call destroy at. Destroy at just runs the tease destructor on the live object. So, if you have a trivially destructible type like order or most of our types, what is going to happen is this will compile to basically nothing because destroy at tries to work for non-trivial types. It will call their destructors and everything. Right now, order will not have a destructor or anything like that. So we're just future-proofing it. If you want, you can remove it. It won't really matter, but there's symmetry with the allocation because in allocate, I told you once allocated, the caller function is going to call construct at so that it can add the object related stuff into this function. Like you want to populate the node that you have with data, right? The slot you have, it needs to pass in the data related to the order, like the ID, the cost, all of that. So construct at will be called there. Deallocate, destroy at, destructor will be called. So there's symmetry. You're destroying whatever was constructing before. After that, you'll relabel it as a free node. Opposite of what was done here. Here, we reinterpreted it as a node, right? Like an order object or whatever it was. Here, it will be relabeled as a free node because it's free now. So you have auto node is equal to reinterpret cast free node object. So those bytes that we have, they're all the plain array bytes, they're now interpreted as free node, and now we just need to make the connection. So the symmetrical version of this is done here. After that, obviously, we need to go ahead and set up the next part. So this node that you have, auto node is equal to this. What you need to do is, let's take a visualization to understand this. So let's say you are deallocated here, right? So you want this new node, which is now having this next because, it's a free node now. So you want to make sure that this node.next connects to the current head, right? So the current head, whatever it is, slot 0 is the current head. I'll make sure that the node.next, so this node that we have, its next value will be this slot 0, which is the head of the intrusive list. So I can just do node.next is equal to free list head. And now the head has changed because the head is no longer this guy, slot 0. The head is now this node that we currently have because we have pushed this to the front of the list. So we'll just have free list head is equal to node. So deallocation is just the mirror of allocation. Simple. After that, we are going to have allocated count minus minus because we had allocated count plus plus. So now it's no longer allocated. So we decrease it. After that, you can also decide to have the diagnostic helpers, but I've removed it because these are empty capacity. If we need them, we'll add it, but I use them whenever I wanted to get access to it in tests or something like that. In the future, maybe if you want to know if the memory pool is empty or not, we can use it. One interesting thing though is just the no discard. No discard is a C++17 attribute. It just makes the compiler warn if you call the function and ignore the result. So if some, like a board programmer like me writes pool.empty thinking they typed if pool.empty, the compiler points and, maybe the compiler also laughs and it just says like, hey, like you've ignored the result. That's not good. The other thing is this capacity is a constant expression. It's a constant expression because the answer is n. And n is known as compile time. So calling it is quite literally free. Why not use that? So yeah, I'm going to remove it because it's of no use now. Unit test, benchmarking, all gone. So yep. So this is our entire memory pool. Few things to consider. First thing is this is single threaded. There are no locks. There are no atomics. There's no synchronization in the pool. If two threads called allocate simultaneously, they would race on this head of the list and they would likely corrupt it as well. The code base keeps each pool inside a single thread by giving each matching thread its own pool. Threads must own their pools. That's number one. It's single threaded. Second thing, and by the way, about the first thing, all of this is done on purpose because when you have locks, atomics, it just creates a lot of synchronization effort. And when your synchronization effort in stock exchange, where your goal is performance, it doesn't go hand in hand because you'll be spending time to acquire the lock, because of which other orders have to wait in line, and then you have to unlock the lock that you acquired. All of that synchronization, not worth it. The second thing is there's no automatic growth. When the pool runs out, you get null pointer. That's it. The matching engine will treat the pool exhaustion as a configuration error. We are saying that your n was set too low, you need to increase it. And there is no fallback we do on malloc. This is one of our core requirements as well, right? The next thing is there's no fragmentation by design. Every slot is the same size. There is no version of this where we say, hey, I need 100 bytes, but I only have 90 contiguous bytes possible. That problem is not there. Any free slot fits any new T that we have. The next thing is that slots are contiguous in the backing array. But as orders fill and slots get reused in free list order, the live and free slots interleave throughout the array. A more advanced pooler would be able to segregate hot and cold slots, but we do not do that because the gains are marginal and the complexity is bigger for that. And I don't want to talk about it in depth in this tutorial, otherwise it would be pretty big. The other alternatives that we could have used is number one, monotonic buffer resource. What is a monotonic buffer resource? It is a standard library bump allocator. Allocation is just advancing an offset, and it is even faster than ours. The problem with it is there is no individual deallocation. You can only free everything at once. So it's useless for our use case where we have an order book where individual orders fill at different times. So we cannot use a monotonic buffer resource. The next alternative we could have taken is a free list allocator with separate bookkeeping nodes. That would work fine, but you need to pay extra memory for the nodes, and the nodes live in different cache lines from the slots, hurting cache behavior. This design is the same as this non-intrusive list that we talked about, and we've already discovered the problem with that. The next is an index-based free list. So we just maintain a vector and we pop or push from the back. That would also work fine, but it would have slightly worse cache behavior because the index vector is a separate region of memory that competes for cache. Our intrusive approach keeps everything in one region. So we have achieved all of our constraints that we had specified earlier. We have O of 1 allocation, O of 1 deallocation, no call to malloc, and cache aligned returns. So all of that, all great. Let's take a final diagram to explain the entire memory pool. So let's say you have a memory pool, and this memory pool is created within, let's say, a heap. So let's have a heap memory, and this heap memory is allocated once. Let's make this black. So we have heap memory that is allocated once at startup, and the size of it is about 64 megabytes, right? Because there's 1 million slots that we're going to assign. After that, we have our design where you have slot 0, and then you have slot 1, and then you have slot 2, and then you have, let's just say you have these many, and then you just have a linked list, right? So now slot 0, all of these are 64 byte aligned. Each slot is either free or live. Free means that the first 8 bytes are a free node pointing to the next free slot, the remaining bytes are unused, and live means all the bytes are a constructed order object, for example. Allocate just means you pop the free list, O of 1, there's no syscall here. Deallocate means you destruct and you put it back into the list. That is the entire memory pool. And you can keep staring at it and keep looking at it until it stops looking surprising, because it is very important. It's one of the core infrastructure problems or things to consider. The matching engine will reach into this pool thousands of times per second. So the better you understand the pool now, the more transparent, it will feel like what's happening overall. Okay. Great. Now we've understood that. The next thing we want to build is the SPSC Queue.h file. What is this SPSC Queue? That's what we're going to discuss next. And we've spent too much time on that, and we're going to spend too much time on this as well. But I just want to ensure that you understand these two important critical infrastructure for our project. So before we get started with the coding of SPSC Queue, let's start understanding what is SPSC Queue and why we need it in the first place. What is the problem that we are trying to solve? Let's start with what is our exchange going to look like. So our exchange is going to be a pipeline of threads, and each one will do its job. Generally you would go ahead and have something like, let's say we have multiple components in our exchange, right? The first one is going to be TCP gateway. After that, we go to the risk gateway. After that, we go to the sequencer. Then we go to the matching engine. Then we have the market data. And then we have, let's say, a heartbeat. Okay. So what is each one of doing? TCP gateway is going to accept the socket data. It will parse bytes into orders. The risk gateway, that's going to pre-trade risk checks. We'll have position limits, all that kind of stuff. We'll get to it. Then we have the sequencer. Sequencer is going to assign sequence numbers and it will write to the journal. Then we have the matching engine. Matching engine is the order book itself. Then we have market data. Market data will publish the messages over UDP. We'll get to that. Then we have heartbeat. Heartbeat is going to be, well, network liveness supervision. So all of this are going to be there. In a normal system, what would you do? And in a very naive system as well, you just do, TCP gateway, risk gateway. Risk gateway goes to sequencer. Sequencer goes to the matching engine. Matching engine goes to market data, and market data goes to heartbeat. Well, in this system, you're going to have the same. But also in a nice system, other than this, what happens is this is called as thread 1. All of this logic happens in one thread. So that means you have one order which goes to TCP gateway, it goes to risk gateway, then it goes to sequencer, matching, market data, and all of that tasks. After that, the next order comes in. Then the next order comes through this. The problem with this approach is that, TCP gateway is done with the first order and then it's just blocked. It's not doing any work while risk gateway is doing the work. When these two are free, sequencer is doing the job, but no one else is. So at least one component out of the, let's say 5 or 6 components that we have is always working, but the rest 4 are not working. And that's problematic, right? So what we need to do is instead, or also market data won't publish to heartbeat. We'll just have heartbeat that checks each of these, threads. And what we are going to do is make each one of this a thread. So we'll have thread 1, then we'll have thread 2 where we have risk gateway. Then we have thread 3 where we have the sequencer. Then thread 4 where we are going to have the matching engine. Let's try to have that. And then thread 5, we'll have the market data. And heartbeat is going to stay in the thread 6. Cool. So this is going to be how we are going to structure. So this way, it gives us the flexibility that order comes in, or let's say network request comes in, we go through the TCP gateway. It converts it into the order, and TCP gateway is not blocked here. It will start processing the next one. And risk gateway will continue doing its job for the previous one. Now the natural question is, let's say, TCP gateway is operating independently of risk gateway. So TCP gateway's job is just to convert bytes into orders. So it's taking order at a time and just pushing it to risk gateway. What if risk gateway is working slower than TCP gateway? Because risk gateway, all it's doing is pre-trade risk checks. It's bunch of if conditions essentially. So, and this is converting data coming from the network. So obviously this can be faster, or actually this will be faster than this one. So let's take another example. Or for this example, you can consider, let's say TCP gateway is faster than risk gateway. So we have a bunch of orders coming up and we are just pushing it to the risk gateway. Now, obviously, if risk gateway cannot handle it, you're in a big mess. How will you store all of them? Well, you need a queue for that, right? And between each of these threads, we are going to have a queue, and the queue will store all of the data. Okay. Now this queue can be bounded or unbounded. Bounded means there's a specific size limit. It can either be, what the capacity of the queue is, or how many bytes it can store, whatever one you want. Let's say you have unbounded queue for now. So all the orders are being stored in the queue. Once the order is completed from the risk gateway, it goes to this queue and the sequencer will pull from this queue. That's what's going to happen. And each of this queue, the basic fundamental thing how this queue will work is something like this. You'll have 2 threads. You'll have a producer thread, and then you'll have a consumer thread, right? In our example, TCP gateway was the producer, and then thread risk gateway was the consumer. Similarly, when risk gateway is doing its job, risk gateway will be the producer and sequencer will be the consumer. And once, when sequencer is doing its job, sequencer will be the producer and matching will be the consumer. So this is the kind of way we are going to work. But as of now, let's assume we only have two threads, okay? Producer thread, consumer thread. Now, generally how producer thread code looks like is something like this. You have something like, let's say mutex, you acquire the lock. Let's say we are not using mutex, we are directly using lock guard. So that will manage the mutex for us and we do the mutex, okay? After that, we will essentially do our work and then we'll do our work beforehand. So let's say work done here. Then we have the lock that we got in. Since we have the lock now, we can push to this queue, correct? So we have pushed, let's say, some event to this queue. So this is how the producer thread will work. How will the consumer thread work? Well, consumer thread will also have a lock guard, right? Then let's say we have lock mutex like that. Then it will check if not queue.empty. Then it will go ahead and do something like this. You'll have event is equal to queue.front because it's a queue, right? You want to extract the event from the very first position and then you want to pop from the queue. So you've done that. This is how generally producer and consumer thread work. And this is correct. But it is also a problem. What happens here is, first of all, lock contention. When the producer holds the mutex, the consumer waits, and that keeps on happening. When the consumer is, holding the mutex, producer will have to stop. The two threads will not be able to work in parallel. They are serializing sequentially on the lock. The whole point of this pipeline is that each stage will run in parallel with the others, so the throughput is bounded by the slowest stage, not the sum of it, right? And serializing on a lock will destroy that. Another problem is that when a thread blocks on a mutex, the kernel may just put it to sleep and wake it up later. So let's say consumer thread blocks on a mutex. So the kernel may put this producer thread onto sleep and then it might wake it up later. So each sleep or wake transition here will cost 1 to 10 microseconds. And we are aiming for a system that is sub-microsecond. So this is also a problem. And another problem, the final one, is that we have used a queue here. I'm assuming the queue will be coming in from standard queue. If it comes from standard queue allocates. So standard queue is basically implemented on top of the doubly ended queue, and doubly ended queue allocates a new chunk of nodes whenever it grows. So we've already established that we don't want to do any allocation in our zero allocation infrastructure. So this is a problem. So what is our requirement here? The requirement is that we need a queue where producer and consumer never block each other. They never call into the kernel and they never touch the heap. This is our core requirement. Also, we want each of the threads to work parallelly, or kind of parallelly. They should essentially overlap. That while TCP gateway is working, risk gateway is also working, and sequencer is also working, and matching is also working. So maybe TCP gateway is working on order n minus, or let's say order n plus 1. Risk gateway should be working on order n, and sequencer should be working on n minus 1. This is how it should work. Or let's say, TCP gateway is the fastest, then you have n plus 4 or something like that. So anyways, they are all working, but they're all working on a different type of order, but they're all working overall faster. So we don't have to go through the sequential process. It's a lot like overlapping. And coming back to this design, where we want these conditions to be fulfilled, what do we create? Well, this is ring buffer. What is ring buffer? Ring buffer is basically a circular buffer. It is a fixed size array with two cursors. There's one for writing, there's one for reading, and they wrap around when they hit the end of the array. Let's go ahead and create it. A buffer is just some allocation created here, okay? Then we just go ahead and have slot here. So let's have multiple of these slots. So we have 1, 2, 3. Let's say we have 4. Then we have 5. And then 6, 7. Okay. So we have 1. I'm just going to label it again quickly. 2, 3. How is this going to work? Well, I would actually like to start with an 8 ring buffer because that is going to sound pretty well, you know. So let's have another slot created here, which is going to be 0. So we have an 8 slot ring buffer. Okay. And let's say we have 2 pointers here, as I said, 2 cursors. One cursor is going to be on writing. The other one is going to be on reading. So let's say this is called the start and this is called the tail because this is the ending part, right? So what will happen is when you try to push some data, let's say we call the push method here. When we try to call push, the tail will advance on push. And if we call pop, what will happen? The start will advance. So whenever we push an item, tail will advance. If we start, pop will advance. Simple. So what will happen is whenever we have this producer and consumer model, this producer will write at this tail and then advance the tail, right? Because when we push, tail advances on push. So let's say we write some data here. Let's say we write an XYZ data here, and then it will push or advance, sorry. When the tail advances, it will go to the next slot. So it will go to 8, but there's no 8 here. So what will happen? It will go to the 0 and the consumer will read at the start position and then advance the start. So whenever they hit this position 7, they will go to the next one and then that will be 8, index 8 or in total position 9. So it will come back to this, it will wrap around to 0 and this is called ring buffer. It's a circular loop. Whenever you go to 7, you come back to 0. So there's this imaginary pointer you can imagine that goes something like this. Something like this happens. So the benefit of this is that the consumer never writes to what the producer is writing and the producer never reads what the consumer is reading. They're always looking at different slots. They're separated by some distance in the ring and you can decide for yourself what that distance is going to be. And this simple concept will help us do everything because queue, where producer and consumer never block each other, well, if consumer and producer are looking at different parts, they're never blocking each other and they're writing to different slots all the time, or they're either writing or reading. And they never call into the kernel and never touch the heap. This is going to be pre-allocated. And then each of the threads will work parallelly. That's happening here. So all of the things are done. We'll come back to this example, but I just wanted to give you a taste of what we are building. So we have the head here. I'm going to rename it from start, and this is going to be the tail, and we remove this. It's not necessarily that head starts at index 0 and tail starts at index 7. You know, they don't necessarily have to be at the start and end. There just has to be a certain distance between them. The distance can also be 1 if you want. Awesome. Now that we've understood that, let's go ahead and build the class. So first of all, pragma once. After that, some includes. We're going to have array. We're going to have atomic. We're going to use atomic here. Then we have C standard def, C standard int, type traits. We're going to need all of that. After that, let's create a class, a templated class. So we'll have first of all, namespace. So we are building in the Exchange core again, similar to our memory pool. After that, we are going to have our templated class. So template is the same, type name T. We're going to accept a different type name. And then we are going to have a size N. And then we have a class SPSC Queue. Then we are going to have our static assert. So first of all, N needs to be greater than 1. That means SPSC Queue requires at least 2 slots, because if we only have 1 slot queue, it is a degenerate, right? I mean, the producer could only push 1 item before the queue is full. 2 is the minimum that would make sense because then we also have pointers or cursors at two different positions, at index 0 and index 1. So two threads are looking at two different slots. Then we have our second static assert, which is n ampersand n minus 1 u is equal to 0 u. That means SPSC Queue must be a power of 2. I don't remember if we did this in memory pool, but something along this line was explained to you that we use ampersand here instead of, anything else, because n must be a power of 2. That's what we are trying to calculate. And we're not calculating directly that, is the n power of 2, because that is more expensive. We can just do n ampersand n minus 1 u. So with this line, all we are saying is that the capacity, the n, must be a power of 2. Now, recall our design of this cursor here, head and tail. What did we say? Well, we did not say it, but what I implied here is that we need a single 64-bit counter that will monotonically increase forever. You know what monotonic means. It should always increase. It should not decrease at any point. What that means is that whenever we have 7 as the tail and we go to the next position, 8, I told you that instead of going to this position, we go to 0, right? But we're not actually setting tail's position to 0. We're not saying tail is equal to 0. Instead, tail will still be 8. But what we'll do is just percent it by n. So if our n is 8, that is our capacity, 8% 8 will equal to 0. So we land at 0. But in actuality, in reality, tail's value will be 8, not 0. At some point, the producer tail can also be something like 1,000,007, right? I hope that is 1,000,007, or you can assume with me it is, and it's not, so we can change it. That's 1,000,007. Now the actual slot to write into when we have 1,000,007 percentage n is what? Well, to calculate that, the CPU has to use the modulo operator. Whenever we are doing the modulo operator with integer division, it is going to take 20 CPU cycles. It is not very fast. What we want to do is instead, can we do this in just one CPU cycle? Modulo takes 20, that's bad. And that is slow. So what we can do is, instead of using n, what if we can just, instead of using an arbitrary n, what if we take an n that is a power of 2? When you have something that is a power of 2, you can replace this 1,000,000% n by something like this. You still have 1,000,007, then you take an and then you do whatever is the n minus 1. This is what we have done here. So what we're doing here is a single bitwise operation, and bitwise operation only takes one cycle, one CPU cycle. So we have reduced the CPU cycles by 20x by just using n that is a power of 2. And this works because, let's do the math. Let's say we take a smaller number, okay? Let's say n is equal to 8. In binary, what is 8? It is 1000, right? And then n minus 1, what is that? 8 minus 1, which is 7. And that is binary for 0, 1, 1. Now our goal is to compute 13% 8. What is 13 here? 13 is a replacement of 1,000,007 here, and 8 is the capacity n, okay? So we know the answer here is 5, because 13 divided by 8, 13 is equal to 8 plus 5. That's why the answer here is 5. What we want to do is something like 13 ampersand 7, right? Because what did we say? We want to do n ampersand n minus 1. So that's what we are doing here. N is 13, n minus 1 is 7. So 13 ampersand 7. Well, we'll get our answer. Let's try to put this in memory. And we are converting all of this into binary because that's how bitwise operations occur, right? It literally says bitwise. So obviously we're dealing with binary. So what is 13? 13 in binary is 1101. You can think about it. I mean, this is 1 plus 0 plus 4 plus 8. So 8 plus 4 plus 1, that's 13. And similarly for 1, we have 0, 1, 1, 1. So let's say you do an AND operation between them, what will happen? So the result of this is going to be 0, 1, 0, 1, right? I mean, you can do the AND yourself and you can see this is 0, 1, 0, 1, and 0, 1, 0, 1 is 5 in decimal. Yeah, 1 plus 2 square, that's 5. So it is the same answer that we get, but it's just one cycle instead of 20 CPU cycles. Now, why does this work? Well, let's try to notice something, okay? Let's say the n was equal to 8. What was it binary? The binary is, let's say, 1000. Then n minus 1, which is equal to 7. What was its binary? 0, 111. If you notice, n has 1 bit followed by zeros. N minus 1 has all those lower bits set to 1, right? Here 1, 3 zeros. Here we have 0, 3 ones. That means n minus 1 acts as a mask. So if you look at the binary of the numbers, here you can see 0 is 0, 0, 0, then 1 is 0, 0, 0, 1, then 2 is 0, 0, 1, 0, and so on. Now what if I mask every number with 0, 1, 1, 1? That is like the n minus 1 binary, okay? By mask, I mean you just do AND 0, 1, 1, 1, okay? So when you do it with 0, you get the result 0, right? When you do it with 1, you get 1. With 2, you get 2. With 3, you get 3. With 4, you get 4. With 5, you get 5. With 6, you get 6. With 7, you get 7. But when you do it with 8, you get 0. So these are exactly the same results as number %8. And the reason it happens is because a number is a multiple of n plus the remainder, okay? So let's say you have a random number. I'm not taking 13 now. Let's say we have 29, which is equal to 24 plus 5, okay? So multiple of n, right? 24 is multiple of n, which is 3 multiplied by 8. In binary, 29 is equal to, let's say, 1, 1, 1, 0, 1, and 24 is 1, 1, 0, 0, 0. And 5 is equal to 0, 0, 1, 0, 1, okay? If you notice, the multiple of 8 always has its 3 lower bits equal to 0. You can try it with anything. You can try it with, let's say, 16. For 16, we have 1, 0, 0, 0, 0. I mean, that's pretty easy, right? Because 16 is a power of 1. I mean, that is going to be the case. Let's say we have 32. 32, that means we have 1, 1, 0, 0, 0, correct? Because we have 24 plus 8, that's 32. The reason this happens is because multiplying by 8 is the same as shifting left by 3 bits. Remember this. Multiplying by 8 is equal to shifting left by 3 bits. So the remainder is stored entirely in the lowest 3 bits. So when you do any number ampersand 0, 1, 1, which I call masking, you throw away every higher bit, that is the multiple of 8, and keep only those 3 lower bits that are the remainder. And that's what the modulo 8 returns. It will not work with anything that's not a power of 2, because powers of 2 are the only numbers whose multiples align perfectly on a binary bit boundary. If you want a very mathematical statement, you'll have for 2 to the power k, every multiple has its lowest k bits equal to 0. So remainder is exactly those k bits. You can take out a paper, try to understand the statement. So, and I'll not misspell the statement so that it sounds cleaner. Okay. So you can sit with it, but I'm going to move forward. This is why we have power of 2. Cool. Let's move forward. After that, we have the is trivially copyable. We've already looked at this before. The queue copies items into and out of the buffer. So for trivially copyable types, that means it can do it with a single memcpy. We always want to use trivially copyable structs everywhere. We've looked into it. I'm not going to explain further. After that, we're going to go ahead and create a cursor. A cursor is just going to contain an atomic value which is an int64, right? So let's create a cursor struct. It is going to align as 128 bytes. So a cursor, I told you beforehand, I told you that when we have a cursor, it is going to be 64-bit integer, right? Why are we passing it out as align as 128? Why in the memory are we padding it out to 128 bytes? To understand why, we need to talk about false sharing. So let's say you have multiple CPU cores. Each one has its own L1 cache. If core A and core B both have the same 64-byte chunk of memory in their L1 cache, the hardware has to keep them in sync. Otherwise, what happens is that core A could read a stale value while core B has updated that value. So both of them obviously need to be in sync, otherwise there's problem. That synchronization is handled by a cache coherence protocol. And the most famous one is called MESI on x86. It's called Modified Exclusive Shared Invalid. So this protocol is implemented in hardware, and it runs over a chip internal coherence fabric and is fundamentally slow whenever two cores keep writing to the same cache line. This is the only detail we need to know about it. The two cores, if they're writing to the same cache line, the protocol that's implemented in hardware will be slow. And the problem is, let's say, suppose, like the head and tail, they live next to each other. And let's say they share the same 64-byte cache line. Actually, let's say this is the cache line, okay? Let's assume that is a 64 bytes cache line. Let's say head has 8 bytes, tail has 8 bytes. And remaining is the padding that's created. And let's say core A is the consumer. It modifies head, and core, or let's reverse the position actually, that would make more sense. So let's say we have head here and we have the tail here, and I'm gonna remove this item because I don't know where I sent my tail. Okay, so let's say core A is the consumer, it modifies head, and core B is the producer, it modifies tail. What actually happens on the hardware is that core A will write head, so core A will mark the L1 cache as modified. The coherence protocol will invalidate core B's copy of the cache line. So core B wants to write tail now, let's say. Okay, so core A wrote to the head, and core A's L1 cache line marks the line modified because we have written the head. So obviously the cache line is now updated. The coherence protocol invalidates core B's cache line because both of them were sharing the same cache line. And now since core A has modified, core B cannot read the tail value. Now let's say core B wants to write to the tail. It requests the line back from core A because it knows this line is now modified. That request crosses the coherence fabric, which takes 50 to 100 nanoseconds, let's say. Core A will flush the line, core B will receive it, and it will, do its thing and it will mark it as modified. So this cache line is again modified. Now core A has the stale value. And now if core A wants to read the head again, it will be the same request like core B, but in reverse, because now core A will have to request the line back from core B. That request will cross the coherence fabric again. Core B will have to flush the line, core A will receive it, and that will take another 50 to 100 nanoseconds, and core A will then make its changes and mark it modified. So this cache line will ping pong between cores on every push and every pop event. And if you're doing millions of operations per second, the throughput will obviously suffer. The problem here is that the two cores are not actually sharing data. Head and tail are different variables, but the hardware does not know that. The hardware operates on cache lines. They're not operating on variables that are present. And that is why this is called false sharing. There is no real shared state as such. Only, an accidental memory layout is present, which creates a sense of false sharing. So what is the fix? The fix is that we put each cursor on its own cache line. With 128 alignment, what's happening is, let's say head is 8 bytes, it will take on the rest of the positions. Then tail will be on a different cache line and it will take on the different position. So head and tail are now on different cache lines. Core A will write head and it will no longer invalidate core B, and core B will write tail and it will no longer invalidate core A. So the cores are working now in parallel and there's no coherence thing that I mentioned. And this eliminates false sharing. All we need to do is split them out into two different cache lines. And that's why we pad the 64-bit integer with 128-bit integer, or 128 padding. So the cursor will contain a 64-bit value, but we use 128 bytes of padding. Now, why are we using 128 bytes and not 64? 64 bytes is the cache line on most current CPUs. So one would assume if we want to do two different cache lines, we only do 64 bytes. So why are we doing 128? Well, some Intel processors do adjacent line prefetching. So when you fetch line n, the hardware will speculatively fetch line n plus 1 too. And the two lines will effectively act as 128 byte coherence unit. This also happens in some Apple Silicon configurations. And in some Apple Silicon configurations, the L2 cache line is also 128 bytes long. So both of them will be laid out together. So 128 is basically the safe upper bound that we have used, and that will basically guarantee the isolation across all of the kind of modern hardware that we have. So the cost is not that much if you think about it. We're using 240 bytes of padding per queue because we'll have two cursors and both the cursors have 120 bytes each. And if we get the throughput gain, that's obviously pretty good. Now in the cursor, we are going to have an int64, but it's going to be wrapped by an atomic value. Now, what is this atomic value? Well, we wrap a value with atomic so that the reads and writes to it are atomic. They are guaranteed to happen indivisibly. What that means is that there's no tone read where another thread sees half old, half new bits. All of the bits are going to be the new bits. That's what atomic means. On x86 and ARM machines, an aligned 64-bit load or store is already atomic at the hardware level for free. So the atomic wrapper enforces this alignment. It will prevent the compiler from optimizing across the atomic operation, and it will give us memory ordering knobs. And we're going to get to it in just a moment when we create the push and the pop functions. Also, we're using unsigned int64, not size T here, which gives us a guaranteed 64-bit width. And with a 64-bit counter doing 1 billion operations per second, it would take us a lot of time to overflow. So we can safely treat the cursor as monotonically increasing. So let's have a function here, but before that, let's create two cursor instances. We'll need head and tail. So let's go ahead and define in the private cursor head and then cursor tail. After that, we will also need a push function, right? So let's create that push function now. So this push function is going to return a Boolean value. If we are able to push successfully, it's going to return true. If not, false. Then the value we're going to push is going to be the templated type T. Like every other function, it's not going to return any exception. So the first thing here we need to do is fetch the value of head and tail. Now to fetch the value of head and tail, we need to extract the value from this cursor struct, this atomic structure. Here we run into the issue of memory ordering. Let me give you an example. Why does this memory ordering matter in the first place? This is the producer code, and let's say we also have the consumer code after that, okay? So producer code, consumer code. Producer code, we have buffer at 2 is equal to E, tail is equal to 3, and let's say for consumer, the consumer has, let's say T is equal to tail. If T is greater than head, we have something like V is equal to buffer at head and mask, okay? So let's say the CPU is allowed to reorder loads and stores within a thread as long as the single threaded result is preserved. From the producer's own perspective here, the order of buffer at 2 is equal to E and the tail is equal to 3. They do not matter. Both write to memory. So the CPU might reorder these operations. So let's say instead of executing buffer at 2 is equal to E and tail is equal to 3, the producer, the CPU might just reorder and it will do something like tail is equal to 3 and buffer at 2 is equal to E, because they're both essentially writing to the memory. So it does not matter what operations happen when, right? But in the consumer side, what's happening? The consumer is doing T is equal to tail and then it sees 3 for that, correct? That is the new value. That's good. But in the second operation, what happens is V is equal to buffer at 2. At 2, it sees the stale bytes because this has not executed yet. The producer, it wrote tail is equal to 3 to the memory before buffer at 2 is equal to E. And the problem is that the consumer saw the new tail, it looked at slot 2 and read whatever garbage was left before from a previous use of that slot. Because of this, we have data corruption. But whenever we have something like memory ordering, where we have different chances, like we have release, for example, if we use release memory ordering, what happens is that if we tell on the producer side, I want to do a release memory ordering, it will acquire on the consumer's load. So buffer at 2 is equal to E will take place and it will release store tail is equal to 3. So this means the reordering here cannot happen. The release will set up a one-way barrier on the producer side. Nothing before it can move after it. That's what release does. What if we want to do a reverse? Well, we can use another memory ordering operation called acquire. What acquire will do is it will set up a one-way barrier on the consumer side. Nothing after it can move before it. So the two barriers will compose into a kind of like a happens before relationship across threads. Because of this, we have no locks and no mutex, and C++ memory model will allow us to mention all of these state in the code. Let's take a look at it. So the first thing we are going to do is load up the tail value, because when we are pushing, I told you, where is our example? Whenever we push, tail advances on push. So obviously we need tail. We will also need head, but let's just say we have tail here. So we have constant uint64t, tail is equal to tail dot value dot load, because it's an atomic, and we use memory order relaxed. Again, all relaxed means is that the load is atomic, but the compiler and the CPU are free to reorder it with respect to other loads and stores in this thread. We do not need any ordering here because nobody else is writing tail. So any reordering is not a problem. So we use relaxed here. Next thing, we are going to load up the head. But in head, we do want the exact ordering. So we'll have head.value.load, but this time we'll use memory order acquire. So head is written by the consumer thread on a different core, right? When we are pushing the value, push is happening for the tail, like tail advances on push. So this is happening on one thread, pop is happening on another, because in pop, head will advance. So this head is written by the consumer thread on a different core. We need to read its latest value because we don't know what the latest value will be. But more importantly, we need to know that everything the consumer did before it advanced head is visible to us. Specifically, the consumer reads a value out of the buffer and then advances the head. We must now see the new head before we see the consumer's read having completed. Otherwise, we could be overwriting a slot that the consumer is still reading from, and that is what the acquire ordering will do. An acquire ordering will synchronize with the corresponding release store from another thread. So after this load returns, we are guaranteed that every write the releasing thread did before its release is visible to us. Again, let's try to visualize this. Let's say on a consumer thread, this is the consumer code, and on the consumer side, we add value is equal to buffer at head and mask, and head dot store. Let's say we store head plus 1 with release. And on the producer, what's happening? Well, on the producer thread, we publish, and then when we publish, we acquire the release pair. So what happens is head dot load acquire. Then we are like, oh, we need to see the new head and every write that happened before the release happened. So the whole point of this acquire release pairs is to define a happens before relationship, as I mentioned before. Cool. Now that we have the tail and head values, what we need to do is check if the tail minus head is equal to n, and that is an unlikely operation to happen because that means we have exceeded the capacity of the queue. The queue is full, so we cannot push more to it. We return false then. And this check only works because we have monotonic cursor. Tail, if it is on the index 1,000,007th, it will use 1,000,007. It is not saying, oh, I'm on index whatever. I'm not on index 0 or index 1 in reality. No, it will maintain its value of 1,000,007. Cool. If the queue is not full, which is very unlikely, what will happen? Well, we write the slot, right? So we have buffer at tail and mask is equal to value. What is this buffer? Buffer is going to be, well, first of all, what is mask? But more importantly, what is buffer? Buffer is an array which is going to contain all of the type T, and it is going to be of the size capacity n that we take as a template here. And well, yeah. And mask is going to be n-1u. And what are we doing here? Well, it's the same, operation that we have talked about. It is this thing. Oh, where did it go? Oh, this one. The n ampersand n-1u operation that we talked about. This is what's happening here. Tail might be, let's say, at 18th position, and mask is n-1. So maybe you have 1 million capacity. So this is 999,999. And obviously that's not true because n needs to be a power of 2, but just as an example, maybe it is 256. Okay. So tail ampersand mask is equal to the value. So we are putting in basically the modulo value. Okay. Basically what was the modulo of this n? So like tail %n is what we are doing here. And we are storing the value in that position. So we are writing to the slot. And finally, we will do tail.value.store tail plus 1, and we'll do it with memory order release. So this is the publication. So the release store guarantees that every write the producer thread performed before this store is visible to any thread that acquire loads tail and sees this value, or it will see it later. In particular, the buffer write from this step is now guaranteed to be visible to the new consumer once it sees the new tail. So without the release ordering, what would happen is the CPU would be free to reorder the buffer write to happen after the tail had been stored. And the consumer would see the new tail, but it will look at the slot and be like, oh, this is just some garbage random value. This is what I'm talking about when we have memory ordering. If we get the ordering right and the queue works, otherwise, if you get it wrong, you will get data corruption errors, and that's, it's very hard to debug as well. So yeah, the next thing we're interested in is pop. So let's have, oh, by the way, we'll also return true here because this was a success. If it's a failure, we return false. Very important. Yeah. After that, we have pop. Now, I hope you can write pop by yourself because I've given you the formula here. Everything is on the screen. Pop means head will advance. Push means tail will advance. So here, let's load up head and tail. We load up head with relaxed. We load up tail with acquire. Very, very opposite of what happened in push. We load the head relaxed because the consumer is the only writer of head. So relaxed is fine. Similar concept to what we had in push. The tail was the only write in producer, so it was relaxed. In pop, head is the only writer, so relaxed is fine. And we load tail with acquire. So the producer is the writer here, and we need to see its slot writes. After that, we'll again compare. If head is equal to tail, which is unlikely, we'll return false. What does head equal to tail mean? That means the queue is empty. Because when we are on push, we want to check, can we add another item here? If we can, well, that's good. How do we check, can we add another item? I need to check if the capacity is full, if the queue is full. In pop, I want to check, is there anything I can pop? So I need to check if it's empty. If the buffer is empty, well, that means head is equal to tail. That's the only reason why head and tail are on the same position. Otherwise, we'll copy the slot into the caller's value output parameter like this. Value is equal to buffer at head and mask. Earlier we were inserting the value, now we are removing the value. And notice we have taken t by reference, so we are able to update the value. And we're not even going to return that value because the value has changed, it's by reference. Then we are going to store this head value with released operation similar to what we had in the tail, because we want to tell the producer that, hey, I've read this slot, you can reuse it now. And then obviously we're going to return true. So that is the pop. Now, why are we, like I told you, we have this by reference, so we don't need to return it. Instead of using a Boolean here, what we could have done is also have something like this, right? Where we add standard optional and we return t. If null is returned, that means we have a problem. Otherwise, the actual value is returned. Well, why are we doing the Boolean one then? Because on the hot path, output parameters are cheaper. The caller stack slot for value already exists. So the compiler typically arranges for the assignment to write directly into that slot. If we used optional instead, the function would need to construct a temporary optional. It would have to copy the value into it, and it will have to return by value. And the caller would have to unwrap this. So the compiler can often elide some of that, but not always. And on the hot path, if we can avoid these operations, that would just make it faster, right? Because we're not building any temporary wrapper objects on the hot path. And another question you might have is, why exactly are we using this head as a monotonic cursor? Why are we not wrapping it at n? For example, like head is equal to 9. Why are we coming back to, let's say, position 1 or index 1? Well, there are some classic ring buffer implementations that you'll see online where they wrap head and tail at n. The problem with that is that if you have to check empty or full, you will have to waste a slot, check like if this is empty or not. We cannot just do head is equal to tail, because head is equal to tail can either mean empty or it can mean full. And if you really want to know which one, you would have to waste a slot. By keeping cursors monotonic, which means it's always increasing, we never wrap, we get size equal to the tail minus head always, and the buffer will be empty if head is equal to tail always. So that's the reason why we're trying to save on memory here, a simple 64-bit value, we're trying to save on that. Now we'll also go ahead and create one empty function. So boolean empty constant no except, and we're just going to return head.value.load memory order acquire is equal to tail.value.load memory order acquire. The reason we do this is because by the time you read them, the other thread might already have changed something, so we do acquire. And yeah, that's about the SPSC Queue. Now let's look also at why was this buffer an array? Why are we just using a contiguous plain standard array? Well, it is contiguous and it is in line with the queue object, and there's no heap pointer here. So, the whole queue that we have of buffer plus 2 cursors plus all the padding, it's just a one chunk of memory contiguously stored in the storage. That makes it very cache friendly, and that helps us. So it's a plain old standard array, nothing too crazy. Another thing you might wonder is, why are we using single producer, single consumer? Why are we not using something like multi-producer, multi-consumer? There, we'll be able to have multiple producers, we'll be able to have multiple consumers. That just means the overall throughput will increase, right? Well, here's the thing. In multi-producer, multi-consumer queue, the queue will have to handle the case where two producers push at the same time. To do this safely, it will either need a mutex, and we've already established that it's slow when it's contended, or we would need to have something like an atomic compare exchange loop. That means compare and swap loops, if you've heard of CAS, compare and swap loops. What that means is you will have to do something like while, not CAS, and then you pass in something like tail, the expected +1. You just keep on spinning and retrying, right? And this CAS is an expensive atomic read modify write on shared memory. So that means there'll be hundreds of nanoseconds even when uncontended, and it will be much worse when it's contended lock. And if two producers race, one of them will retry. And SPSC removes all of that because, it's not multi-producer. It is just a single producer. It is just a single consumer. And this is why we use this SPSC queue. It's great. Now let's go ahead and define our next file. And our next file is going to be clocks.h. So let's have clock.h. In this file, we're going to have two clocks for two different jobs. The first one is going to be a logical clock class with next, current, and reset functions. And the second one is going to be a free function called steady timestamp now, and its alias now in nanoseconds. So these two things have completely different uses, and we cannot conflate them into one because there might be a big common bug, and it's also common in trading system code. So let me make sure you understand why we need two clocks. Why can't we just have one? So your first instinct is probably like, when an order arrives, we want to just stamp it with the current time, right? So like as soon as the order arrives, we're going to say, oh, we want the date of, let's say 2027. Let's say today is 704, right? And then all the timestamps, let's say it's 2042 right now, 00, and all of that in UTC, let's say, correct? And then you can use this timestamp everywhere. And that instinct is just wrong for trading systems for two reasons. The first one is that the wall clock is not monotonic. So the system clock can move backwards. NTP, Network Time Protocol, synchronization periodically adjusts it. And admin can move a date before it. And daylight saving might or might not affect it depending on whether you use a naive or time zone aware representation. And if your event ordering depends on timestamps and timestamps can go backwards, your event order is broken because two orders that arrived in the order A, then B might just end up with timestamps B, then A, and we lose out on time priority that we are going to implement when we implement the matching engine. And we'll talk more about that when we create the levels and order structure. The second problem is that the wall clock is not deterministic. So imagine that the matching engine crashes and we recover by replaying the journal of accepted events. And we'll get to that much later in this series. So if we use wall clock timestamps, the replayed events would get new timestamps, and the current time at replay is what they would get, not the original ones. And any state that depends on timestamps, that is like order expeditions, rate limits, time and force calculations, all of that would just behave differently on replay. The engine would no longer be deterministic, and like we're saying deterministic replay, it would not be deterministic. And deterministic replay actually is very important in a trading system. It might cause issues related to audits, so we need to be sure about that. The other thing is that the C++ standard library offers something like steady clock that is coming from the Chrono package. This is always guaranteed to be monotonic. It never goes backwards. So it does solve problem 1, that we had of the wall clock knob being monotonic, but the problem too is that it still measures real elapsed time. So replays can still differ. So we need to separate these two completely different ideas of so-called time. The first one is logical time. Logical time is just that a number that captures the order of events. Event 1 happened before event 2. That is all we need to capture. There is no relationship to seconds, milliseconds, or anything in the physical world. It's just for our reference. The second thing is the real time. That is the actual elapsed time in nanoseconds since some moment. This will be used when we need to talk about, like, is this thing still alive? Like heartbeat checks, or how long did this event take? All of that. So let's go ahead and implement logical time. Real time is quite easy to do. So let's just go ahead and have the pragma ones. These include, one is chrono, then is core types.h. From types.h, we'll be using the timestamp parameter, this one. So yeah, from chrono, we'll be using it for this real time. Cool. Now let's create the exchange core namespace. Within that, we are going to have the class called logical clock. This is the first type of clock. And we're going to implement 3 functions in it: next, current, and reset. All of them are just going to increment the timestamp that we are going to maintain. So what we can do is have a class that just maintains, an integer structure or like an integer value. And then we can use that integer value to increment, to reset, or to just return the current value that's being maintained. Correct? So let's have public or private timestamp. Timestamp is just referring to the unsigned integer 64, and that is the current value. It is 0. Then we are going to have a public no discard. So this function has timestamp. It's called next. What it will do is give us the next timestamp. And all we're going to do is return plus plus current. We're doing pre-incrementation. So we are doing plus plus current. So the current is incremented to the next value and we're returning that value. So the first call will return 1, second will return 2, and so on. The next function we're going to create is the current value. What is the current value? And we're just going to return this current private variable. After that, we're going to have the reset value or the reset function, and it's going to do current is equal to 0. We are resetting it back to 0. Nothing different. Not a lot going on, just 3 functions, as simple as it can get. We're just maintaining this current variable in this class. The next thing we want to do, or actually before we move forward, you might be questioning, why is there no atomic used? Why is there no clock? Can 2 threads not simultaneously use this logical clock? And that's a good question. So this clock, where is it used? This clock will be used on the matching engines thread, which is single threaded by design. We do not need any concurrency control there. There'll be a single thread incrementing a single integer as fast as we can. That's why we do this. All right, let's move on to this real-time clock now. That's basically the chrono thing that we're going to implement. So we're going to have an inline timestamp, steady timestamp now function, and we're just going to have 2 lines here. The first one is what is the current time. To get that, we can do constant auto now is equal to steady clock now. So from chrono, we get the steady clock and we ask the steady clock, what is the time now? And this is monotonic. I've already told that to you. The next thing we're going to do is this monotonic standard steady clock now returns to us a time point, correct? What we want to do is first get this duration relative to the steady clock's epoch. Epoch means some moment in the past that it's relative to. I think generally it's January 1970 or something. So yeah, so let's convert it. So we'll have dot time since epoch. After that, what we're going to do is return this by rounding it up to nanoseconds. So to convert it to nanoseconds, we're going to do this. Return static cast timestamp. So this converts it into integer, and then we're going to round this to nanoseconds, this now value. And to do that, we can do chrono duration cast nanoseconds now. So this will return the chrono duration, and we'll call count function on it so that we can convert it into the raw integer value. And that's how we have this entire steady timestamp now function. One important thing to note here is this inline keyword. This inline keyword is telling the compiler that, hey, I expect this to be called from many translation units, so please do not multiply define it. So in a header only function, inline is the standard way to avoid linker errors. Now, why are we using a steady clock here instead of a system clock? The system clock measures wall time and can jump. That's dependent on NTP, manual adjustment. Heartbeat timers based on it would be flaky because an NTP correction could delay a heartbeat by minutes. Steady clock is monotonic. It briefly pauses while the computer sleeps, but it never goes backwards. And that's exactly what we want, right? We want to know if the connection is still alive. We're also going to create an alias for this function, and we're going to call that now nanoseconds. It's just a short name because, some callers read more naturally with now nanoseconds. So that's pretty much it. If you want, you can still call this, not a problem, but I'm just doing this for readability of code. So we'll have inline timestamp now nanoseconds, and we just return whatever value this function throws or returns, sorry. This is our entire clock.h, nothing more than that. Who uses which clock? Who uses logical? Who uses the real time? So this logical time is used by the sequencer because the sequencer will be stamping each accepted order with a logical sequence number before journaling, correct? The second one is the matching engine. The matching engine will use logical timestamps for time priority and for tie breaking. We'll understand both of these concepts, but the high level overview is that if two orders come in at the same price, then who gets the priority? The order that comes in early. So that's time priority. And this will be used for tie breaking when the matches or prices are equal. The second thing is real time, okay? In real time, where will this be used? Real time will be used by, let's say, the TCP gateway heartbeat supervisor. This will basically say if I have not heard from this client in 15 seconds, the connection is dead. Cool. And it will also be used by the journal flush policy. The journal flush policy is going to be something like if it has been more than 1 millisecond since the last fsync that we did, flush now. We'll get to it later on. So these are the two things. This concludes our entire zero allocation infrastructure: memory pool, SPSC queue, and clock. We learned here that the heap allocations during this entire hot path will include all of these three things that does not touch the heap. There are no mutex locks during these three and the entire flow of the stock exchange on the hot path. When the order comes in and then the order, like the trade occurs. So that is the entire thing. And we've understood everything here. Slab allocator versus general allocator, SPSC versus MPMCQ, the power of two buffer sizes, then the 128 byte cursor alignment, the logical clock for, all of the kind of business logic, and wall clock for all the transport logic. So I hope you've understood a lot from the zero allocation infrastructure. It was one of the most important things to cover. Now, the next thing we're going to do is go on to the level and the order structure. So what we can do is close this core folder. We're done with it. Now we can create another one, which is called matching. Everything related to the matching engine will go here. And within here, we're going to describe our first one, which is order.h. After order structure is defined, we're going to get to the level. How is our level going to look like? And then we'll get into the matching engine. So the matching engine will include the events, order book, and the matching engine itself. So let's quickly get done with all the order and the level now. So before we get started with the order.h file, let me just make sure you understand this order book, because if you remember in the very beginning, we had created something like an order book, but this is not the complete picture. It's a very, very high level overview, you can say. So we had our buy, bids, and our sell, asks, and we had these shares listed, and we calculated the spread, which was the ask minus bid, and bid is just the highest price someone is willing to buy at, ask is just the lowest price someone is willing to sell at. Great, we know that. Now, how is this order book going to work? Well, I just told you that we have 100 shares at $150.2, but that's kind of a high level overview, right? Because the 100 shares can be by one person, it can be by two people, or it can be by three people. It can be by n number of people, right? So different people can put in price at different times, and the price can be the same price, right? So let's take an example. So let's say we have this buy, and let's say there are 100 shares at $150.2, right? Now at $150.2, that's just how it looks on a high level overview, but when we go deeper, there is one more layer within it. And this layer is known as a price level. Let me just shift it over here. So this is a price level, and this is a price level for what? It's price of $150.20. So everything within this box is going to be of the same price of $150.2. What is the total quantity that we have? The total quantity we have is 100 shares. What is the order count? Let's say the order count is 3. That means there are 3 orders that are willing to buy at this specific price point. Cool. So now, how are we going to store these orders? We have 3 orders. How do we store them? Well, the way it works is that we also maintain a FIFO queue here. That is the first in, first out queue, basically a standard queue. Okay. And this is not going to be our SPSC queue. It doesn't matter, because SPSC queue is needed when we have a producer and consumer both writing from different threads, and we want to avoid locks and stuff. But here it doesn't really matter, because all we're trying to store is basically create kind of a linked list to store our orders. So here we have a FIFO queue. In the FIFO queue, we are going to have oldest order at head, newest at tail. Now, just take a moment to understand why would we have oldest at head and newest at tail. That is because whatever order that comes in the oldest, that means the order that comes in first, is going to have the topmost priority at the same price level. So let's take an example here too. Let's say we have a FIFO queue wherein we are going to maintain a linked list. Okay, so we have our order A. The order A has, let's say, quantity equal to 40, and let's say the time it came in at is, let's say, 1001. Then we have order B, which is quantity, let's say, 35. The timestamp here is going to be 1003. After that, we have order C, which is, let's say, quantity is equal to 25, because all these quantities should essentially match up to this 100 shares, right? So yeah, and the time it came in at is 1007. What this means is that order A is going to be the head, and this order C is going to be the tail. That's because the timestamp 1001, the monotonically increasing timestamp, is going to be like the first order that's present in this queue. So we take that off, because think of this in terms of real people. 2 orders were placed. One guy placed it before the other guy. The first guy is going to get the priority. This is called time priority. This is what I've been talking about the entire time. So now whenever an incoming sale at this $150.2 price trades against, let's say, this price level, order A will go through first, then order B, then order C. So we have FIFO here, first in, first out. And time priority is within the price only. There are price levels at each one. So 150.15 will have its own price level. So there maybe the quantity is 80 shares, the order count is, let's say, 2, and both the orders are, let's say, 25 shares. So each one of these is going to have their own price levels. And this is what we're trying to create within the order. Okay. So there's going to be an order and there's going to be a level. Whenever I say level, we're talking about the price level. Maybe I should have named it price level, would be easier, but anyways. So this is what we're trying to build. So now let me give you a more formal definition of what it means. Basically, a market is fair when for every trade, there's price priority and time priority. Price priority means that, let's say someone offered a better price than someone else, you trade first. So better here just means that, someone is willing to pay a higher bid for buyers and lower ask for sellers. So like, it's quite obvious, right? If someone is willing to trade you a better deal, that will go through first. But within a better deal, we will go through this time priority. So if two offerings are present and they're at the same price, then the one whose order came in first will be taken in. So first, price priority, anyone who has the better price is going to be offered first, and then the time priority. Cool. And together, this is called price time priority. And this is the most important matching engine rule we are going to follow as well. When you research about it, you might also see that some venues use pro rata matching. That means the same price orders will share a fill proportional to the size. And there might also be some hybrid rules for these order types. But price time is the default, and it is what I'm going to cover in this tutorial. The main thing here to recognize is that the engine needs to remember two things. First, all the resting orders should be organized so that the best price on each side is easy to find. And the second thing is that within each price, the arrival order should be present so that we can pick the oldest order first. Cool? And that is related to the order book. The order and the level that we're going to create are basically structures, and then we'll incorporate them into the order book, which will then be used in the matching engine. Awesome. So we are essentially creating the data now. Let's go ahead and understand why do we need this order structure in the first place. Now you might realize where we might be using this order structure. I told you that we will be receiving data over the network, and the TCP gateway is the one that's going to, take a look at it. So what happens is we get some data over the network. The TCP gateway is present. The TCP gateway will take those bytes and convert it into an order. That's where the order structure is going to be used. The raw bytes that will come from the network are going to be shaped a bit differently from how the order structure that we have is going to be shaped. The main difference is that when the wire message comes in, it is going to contain things like new, cancel, modify the order, because we want to give those instructions from, let's say the user is giving instruction and they're giving the instruction to our stock exchange. So it's going to be, hey, I want to create a new order. I want to cancel this order. I want to modify this order, right? And each of these operations is a different shape with different fields. So they will share a header byte, but otherwise they will look nothing like each other. So each shape that will be present when there's an inbound wire message will be different. But in our order, what will happen is there will be only one order struck. So every order, like the limit, market, immediate or cancel, iceberg, stop, all of this will use the same fields. And most order types will just leave several fields at 0 once. This is why we're not just reusing the raw bytes that come over the network. It's just because they're of different shapes and of different purposes. They contain different sorts of information. So what we're going to do is we build the order once when we have admitted the raw bytes that have come over the network. And after that, the engine will mutate that order in place so that, based on whatever is happening, let's say there's a fill, so we bump the quantity down, or if there's an iceberg, we will have to rewrite the display quantity, all of those things. Cool. Now let's get started with writing this order.h. Obviously, the first thing is pragma once. After that, we have the C standard def, type traits, and core types.h. From core types.h, we're going to import multiple things, right? First of all, we'll need an order ID, which is just an integer, and we'll keep using that. Okay. So like all of these things, we're going to make use of them, and I'll go over it one by one. So let's get started with the first thing, which is creating the structure or creating the namespace. After that, we're going to create our structure. And this structure is going to be of 64 bytes. We'll get to that 64 bytes number later on, but for now, let's understand this order structure is just 64 bytes. The first field that we have here is the order ID. So this is the thing that the client will pick it. Okay. This is not something that's going to happen on the server side. The client is going to pick it. And this is obviously going to be a 64-bit unique identifier. And every cancel, every modify, and every trade report will reference this ID. And the design choice of client picking the ID, not the exchange, is the real convention in most exchange protocols. And there is a reason for it. So when the client, let's say, sends, let's say something like, oh, I want to buy 100 Apple shares with ID, let's say 12345. They can immediately use 12345 in their own tracking. So every response from the exchange, like accepted, rejected, filled, cancelled, all of that will reference the ID 12345. The client will never need to wait for an exchange assigned ID before issuing a cancel. That makes it very instantaneous, right? Because they are the ones who selected the ID, they placed an order, and that is being processed. And in the meantime, they're like, oh no, I don't want this order. Let me cancel it quickly. So they can cancel it. Otherwise, what would happen is we would have to send a request to the server picks the ID, and then the server will have to return that ID back to the user, and only then can they cancel it. So that's obviously pretty bad because we're operating in a time sensitive manner. Obviously, the cost of this is that the client now has to produce unique IDs themselves. And if they accidentally send, 2 new orders with the same ID, the second one will be rejected. Here, the default value is 0 because it's just, let's say, an uninitialized value. Real orders will get a non-zero ID at admission time. Otherwise, we're not going to accept it. Also, by the way, if I've not already talked about this is the brace initialization. So whenever in C++ we use something like a brace initialization, it is just a safe way to say, ID is equal to 0. It basically disallows, narrowing conversions. So you cannot convert an int from a double and silently lose out on decimals. Or I should say an int from a double, because you're converting from a double to an integer, right? So you will not lose decimals when you do this brace initialization. So a very small thing, but it will catch bugs. This is surprisingly common. The second thing is the side. The side, if you go back, is an enum of do we want to buy or do we want to sell? And by default, it is buy. And this is just 1 byte. We've already talked about this. Obviously, in an order, we need to know, are we buying or are we selling? All right, on to the next one, which is price. Price, again, let's take a look at it, is just an int 64. And the price is initialized to 0. And this is the order's limit price in fixed point integer units. If you remember from our very first talk, where I said if we have something like 150.20, that in the order structure, it will be stored something like 150.2000. So there we go. This is our price, the limit price. For most order types, price is the limit that participant agreed to. So for a buyer, this represents, oh, I am willing to pay up to this much money per share. And for a seller, this will be reused. For a seller, this will mean I will sell down to this much per share. I'll say that again. For a buyer, I will buy up to this much per share. For a seller, I will sell down to this much per share. For a market order, price will always stay at 0 because market orders have no limit, right? For a stop market order, price is also 0. The trigger goes in trigger price instead. So if you don't remember them, you can search it up. But if not, if you do, you already understand it. Take a moment. I'm purposely not going over it right now again with you because when you search it yourself, you'll be able to remember it better. The matching engine will treat this price as the bound it uses when comparing against opposite side prices. So buy at $150 can trade against any sell at $150 or below, and we already know that. Just making sure you understand that again. After that, we'll have our quantity fields, and there's going to be 5 different types of quantities. The first one is going to be quantity. This quantity represents the current remaining quantity. So as the order trades, this will count down and eventually hit 0. So when it hits 0, the order is fully filled and the engine will retire it. After that, we have the original quantity. So this is the size that will be filled at submission, and this will never change until you have cancel and replace. But anyways, this original quantity exists so that, the trade reports can say, oh, you submitted for 1,000 orders and filled at 600 so far, and you don't have to remember the initial value elsewhere. Okay. After that, you have the display quantity. The display quantity is the publicly visible proportion right now. So for a limit order, this quantity and display quantity is always going to be the same thing. But it's not the same when you have an iceberg order. In iceberg order, display quantity is the small visible slice, and the rest will hide behind hidden quantity, which is our next thing. So this hidden quantity is the iceberg's hidden reserve. Yeah, right? So when the visible slice is fully traded, the engine will pull this fresh quantity from the hidden quantity to refill this display quantity. I mean, a lot of words to just describe the iceberg order. Iceberg order is basically what do you see at the very surface, that's display, and what's hidden, that's basically what's going on. We have another quantity here, but I've not added it to the next line for some reason. So I will come back to it. It's called peak quantity, and that is just the iceberg's configured peak. So it is basically the participant's choice of how much should be visible at once. And when the engine replenishes it, it pulls the minimum between hidden quantity and peak quantity. When we get to iceberg order implementation, you'll understand it better. So why do we have these 5 quantity fields instead of having, one quantity and reusing that for different purposes? And especially most of these quantities come in because of iceberg orders. Why is that? Well, there's 2 reasons for it. The first one is that there's 0 overhead when it's unused. So fields will default to 0. So a non-iceberg order will pay for the bytes, but it will never read or write the iceberg fields on the hot path. So there is no branch in the matching loop saying, oh, we want to check whether this is an iceberg before reading display quantity. It will just read display quantity. So we are saving on one branch condition, right? The second thing is polymorphism. There is no polymorphism now. The alternate of this structure would be something like we have class order, then we have, let's say, a virtual function created or a virtual attribute created, and within that we'll have iceberg order that will implement the order, and that means we will have to create polymorphism, and basically we'll have all of those vtables that we talked about earlier in the tutorial. We don't want that because a vtable pointer will be wasting 8 bytes every time, and in heap layouts where different order types will live, there'll be different sized objects, and we might not get the cache friendliness that we need. It will also kill the pool based allocation and all the 0 allocation stuff we've created. Okay. Now, I'm not going over the iceberg order again because we've already taken a look at it, or actually I can, because this is a new concept, let's say. So let's just do it quickly. So let's say I have an iceberg order, and the iceberg order is something like I want to buy 10k shares, let's say at $150.25, and the peak value is 500. What does that mean? That means the quantity is equal to 10,000 shares. Then we have the display quantity. The display quantity is equal to 500 because it says, peak 500. That's our display quantity. Then we have our hidden quantity, which is equal to 9500, because whatever is displayed, quantity minus the display is going to be the hidden quantity, right? Or something like that. Then we have peak quantity, which is equal to 500. So the public order book will see that, oh, we have buy of 500 shares at $150.25. Except, like this, nothing else is visible. These 9,500 shares, they're not visible to anyone except the iceberg's owner. So now let's say a seller will submit something like, oh, I want to sell, let's say 500 shares at, let's say $150.25. And then we see, oh, 500 shares at $150.25, that's a match. So 500 shares will trade. So let's say match was there and 500 shares trade. After that, the engine will do these things. First one, it will reduce the quantity by 500. So this quantity that we have is now 9,500. Okay. After that, the next thing that will happen is we reduce the display quantity by, let's say, 500, because 500 shares were traded. That means the display quantity will now become 0. After that, since the display quantity is gone, it is 0. The iceberg order will check, oh, is the display quantity 0? Well, we want to replenish. So replenish means we'll pull, and let me just write it here. C's display quantity is equal to 0. If it is, then what's going to happen? Well, we are going to pull, which is equal to minimum of hidden quantity and the peak quantity. So what that means is we'll have a minimum of 9,500 and 500, because hidden quantity is 9,500, peak quantity is 500, because at any time 500 orders should be the peak number, that peak quantity that should be visible to anyone outside of the user. So this will mean that we pull 500 shares. Then we'll have to obviously go ahead and cut this hidden quantity down to 9,000, because we took away 500 from here. And then the display quantity is back to 500. So after this replenishment process, we have 9,500 shares. The display quantity is 500. The hidden quantity is 9,000. And the public book will still show 500 shares trading at $150.25. One thing that's not captured in this process is that the iceberg order has lost its place in line now. So iceberg replenishment will lose the time priority. It will come back to the end of the FIFO queue that we are maintaining. Now you might just think, why do we need this iceberg order? And we've already talked about this. We need iceberg order because if you want to buy 1 million shares and you show the entire 1 million shares to the public, every seller will see it and immediately raise their ask. So the very information that someone wants 1 million shares is very valuable, because there's a lot more supply than probably the demand. So obviously the price will go up because the demand is probably higher than the supply, and every supplier is like, oh, 1 million shares at one time, let me raise my price, I'll get more profit on this, because someone wants 1 million shares. So if this information is given out to the public, you might be paying the market to move against you. So an iceberg just lets you participate without telegraphing your size to the public. You will pay a price, but you do not have to pay the much larger price of moving the entire market against you. Okay. After that, we have the timestamp. The timestamp is the logical, not the real timestamp. The logical timestamp is the one that we also had in our order book, right? Like the monotonically increasing timestamp. That's what we have here. Not going to spend much more time on that. Now we go to the timestamp or type, sorry. So type just says what kind of order is this? It can be one of the 9 order types, and we already know those order types: limit, market, IOC, FOK, all of those. So the matching engine will branch on this value at a few specific decision points. So the first question the matching engine will ask is, should this order be allowed to rest on the book, right? There are only a few order types that will allow us to rest on the book. That is limit, GTC, iceberg, post only, stop limit. And the ones that are not allowed are market, IOC, and FOK, because they either fill immediately or they get rejected or cancelled. They don't have the ability to rest on the book. Second question matching engine will ask is, should this order be allowed to cross immediately? And all will be done except post only, which is rejected if its price would cross. The third question is this a stop order? So stop and stop limit, they sit in a separate parked stop until the trigger fires. So we need to ask that. And the fourth question is this fill or kill? If it's fill or kill, then we reject the order if the entire size cannot be filled atomically. We'll get much deeper into it when we get to the matching engine, but for now, good enough. Now the next thing is the status, order status. Where in its life cycle is this order? Well, it can be new, accepted, partial, whatever. We've already gone through this. Next is the participant ID. Who owns this order? Well, it's the 32-bit ID of the trading firm that submitted this order, and the matching engine itself does not use this for matching because matching is purely by symbol and price. The engine does not care who you are. Otherwise, obviously, this is a big regulatory issue because you might be favoring someone, and that's obviously a very bad situation in a fair market. The next thing we have is trigger price. This is only for stop orders. So for stop and stop limit orders, the trade price that once reached activates this order is the trigger price. So the engine will watch the last trade price, and when it crosses trigger price in the right direction, it wakes up the parked stop and pushes it into the regular matching flow. And this is 0 for non-stop orders, and it will be non-zero for stop orders. Great. After this, we have the peak quantity. We've already talked about this. Then we have the things that will link to the engine. We will have a previous, next, and a parent level, all of the type of order. So I told you we're trying to create a queue here essentially, right? So we are trying to create a linked list over here. So whenever we have an order, that order will be linked to another order. Order A will have next to the order B and will also have a previous. So it will be a doubly ended queue. So we'll have order A will have connection to order B, and order A also has a pointer to null because there's nothing before it. Then order B will have a next pointer to order C, but it will also have a previous pointer to order A. It's a doubly ended queue that we are going to create. So let me just write down these three things: previous, next, and parent level. The level structure is not created yet. We will create it, but let's just understand why we need these 3 pointers, because it is pretty confusing, right? Previous and next are linking this order to its neighbors at the same price level. That's basically the gist of it. But why do we need these 3 pointers over here? Why are we not handling this in the matching engine or something? To understand that, first we need to know what does the matching engine need to do constantly. So the matching engine, the main thing is enforcing price time priority. To do this, the engine will have to do 3 things on every single order, potentially millions of times a second. So the first thing is that we match from the front of a price level. So as soon as an aggressor crosses, we have to consume the oldest, that is the highest time priority resting order first. And we need to do this in O of 1 time. That means we have to tell it, hey, give me the front of the order of the queue. The second thing is that we should be able to cancel from anywhere in a price level. So a trader can cancel any of their orders at any time. The cancel message gives an order ID. I've told you that's what the order ID is about. You can use it to do anything very quickly. So we need to look up the order via a hash map and have to remove it from wherever it sits in the queue. So it can possibly be in the middle of a long FIFO queue. And we need O of 1 in this as well to remove this specific node. And the third thing we need is we need to append to the back of a price level. So a new resting order joins the line behind every order already at that price. And we need to push that O at O of 1 to the tail. So these are the three things. Match from the front of a price level. That's pretty easy. It's front of the queue. That's obviously going to be O of 1. Second thing is cancel from anywhere in a price level, which could potentially be the middle value in a very long queue. And we cannot go over it sequentially because otherwise we are essentially O of n. We want to do this in O of 1 because the user requested cancel. We want to do it as quickly as possible. The third thing is we want to append to the back of a price level. So whenever we need to push to the end of the queue, we need O of 1. Now, how would we make that happen? The first option is we have something like a vector. Let's say we don't use a queue. I've already mentioned we'll be using a queue, but let's say we're not using a queue or a linked list, like we have a vector. A vector's property, what is that? If you want to match from front, so front is going to be O of 1 because front of a vector, that's easy. Pop from front. If you want to pop from the front in a vector, how much time will that take? Well, that is going to take O of n because when you pop from the front, the remaining elements need to readjust themselves. That's O of n. Then we have cancel from middle. When we have cancel from middle, that is also going to take O of n because we'll have to traverse and remove the problems, right? Like whatever order we want to remove. And if we want to append at tail, this is O of 1 again. This is bad because cancellation is O of n. So we cannot take this approach. What's the next approach? Let's say we have a standard list, which is of the type of order. And this is basically a normal non-intrusive doubly linked list. You already know what non-intrusive means. I'm not going over it now. So if you want to match from the front, that's going to be O of 1. Popping from the front is going to be O of 1 again. Cancelling from the middle, that is also going to be O of 1. But it will be only O of 1 only if you already have an iterator. Okay, only if you have iterator. After that, we have append at tail, which is also O of 1. And this will always be O of 1. No problems. The only problem is cancelling from the middle. The standard list will allocate a separate node on the heap for every element. And the hot path is forbidden from touching the heap, right? So this is obviously bad, but also the second problem is that an iterator into a list is not the same thing as an order pointer. So given an order pointer alone, you cannot remove it from the list directly. You need a separate map of order ID to iterator, and then we use that iterator to do the lookup. So that is another container, that will be another lookup, and there'll be another allocation per order. So this is bad. The third one is we use the intrusive doubly linked list. In intrusive doubly linked list, we match from the front in O of 1. We pop from the front in O of 1. We cancel from middle in O of 1 because we are given the order and we rewrite the previous or the next pointers. And then we have append at tail, which is also O of 1. And we just rewrite the tail and the new order's previous value to append at the tail. The way this will work is that the previous or the next pointers will live inside the order. So there is no separate node wrapper like, a wrapper around this order that contains, oh, this is the previous value, this is the next value, this is the current value of the order. No, it directly lives inside of the order. That's why non-intrusive. The order is the wrapper node itself. Okay. And the list is just a head and tail pointer stored in the level. So this way we don't have heap allocation per element and the orders will come from a memory pool. And this is perfect for us. Oh, sorry, this is intrusive. I think I said we have a non-intrusive approach. No, we have intrusive approach. No, and intrusive approach is basically you have something like this where you have, let's say, order A, then we have previous is equal to null, let's say, next is equal to order B, and then maybe there are other fields that we don't really care about now. Then we have order A, let's say this is order B. The next of order B is, let's say, or null. I'm going to make it short. And the previous is order A. So this is the head. This is the tail. There are no separate nodes. The order is the node. And if we want to remove an order, what we can do is, let's say someone gives us, oh, we want to remove this order pointer. What we can do is just 2 pointer rewrites. We'll just set orders previous. So this order, let's say this order needs to be removed, or let's say this one. So order dot previous dot next. So this order's previous value is order A. So orders A next value is going to be the next value of this order. Or let me just make this clearer. Let's have head, and then we have a link here. Then we also have a link that goes backwards, and then we have a link that goes here. Cool. So now this order needs to be replaced, and this is null itself. So this will be, oh, order B needs to be removed. So we go to the previous order. The previous order's next value is going to be the next value of the order we want to remove. Okay. After that, we'll set order dot next dot previous value. So this next, the null, its previous value is going to be order A. But let's say instead of this, maybe we had order C, then the order C would basically pass it over here. But anyways, this previous pointer is removed, this is removed, and this essentially order is removed. And now we have mapping between this and this. Let's say this was not null, then there would also be a previous connection made here. But since there isn't, I mean, there isn't one. But this is how it essentially goes. Very easy. All of this operation is an O of 1. So the trick here is that we put the linked list pointers inside the data type itself. This is called the intrusive free list. And we did the same thing in the memory pool. So now that we understand previous and next, what is level? What is this parent level? So this parent level is that, what price level is this under? So many operations will need to update the level that contains this order, right? Let's go back to this one. So let's say, we are in this level 150.20, total quantity 100 shares, order count is 3. Let's say we have a cancel operation. When there's a cancel operation, we decrement the total quantity because now the order has been removed from this price level. So we'll have to update this quantity. If there's a partial fill, we'll have to reduce the display quantity, and that will be within the order, but we'll also have to update the level's total quantity then. If we have a full fill, we'll have to remove the order, and we'll also have to possibly empty the level. So without this parent level sitting within the order, we'll not be able to identify, oh, what level does this order belong to? Because if we would have to do that, if we have to find out what level this order will have to go into, we'll have to search across all of the levels, and that's, pretty bad. All the levels, we'll have to go and check, oh, does this order exist? Does this order exist? And we'll have to iterate through all of them. Instead, we can just maintain a separate map. So with parent level, we already know what order this, what level this order exists in. So we can go to the map, find out, oh, this is where it lives. Okay, let me just remove it. And yeah, we've removed the operation with just over 1 time. And the cost of this is just we need to add 8 bytes. Not a lot, correct? Now, this is our entire structure. We also have one function that we'll create, but it's a very trivial function. But before that, I want to get to this align as 64 bytes. Why is this 64 bytes? So align as 64 will ensure that every order starts on a 64-byte boundary, no matter where the pool slot array lives in memory. And every order will be divisible by 64. The first 64 bytes of every order will occupy a single cache line and never be on two cache lines. Okay, cool. Having understood that, let's move on to the next function that we're going to create, which is the is stop, or before that, actually, let me just go ahead and have a forward declaration of struct level. We're going to define level in just a bit once we've completed this order structure. But yeah, this is a forward declaration that we're doing so that, we resolve the error. And if you're not familiar with forward declaration, well, that's C++ fundamentals. You should, that's a prerequisite. But anyways, we are just telling the compiler that, hey, listen, there is a struct here called level somewhere. You do not need to know its fields yet, just its name. And why exactly do we need to do it? Well, we are using level here, right? And order knows about level, and level will also know about order. So if instead of doing a forward declaration, we did something like hash include level.h, what will happen is that order.h includes level.h and level.h includes order.h. So we have a circular reference. That's compiler error. And to avoid that, what we need is a forward declaration that here, you don't need to exactly know that a level fields, what are they, all of those things. You just need to know that somewhere a struct level exists. That's enough. And a pointer is the great thing to do about it, because pointers do not need a complete type definition. It is just 8 bytes on a 64-bit machine. So it doesn't matter what it points to. The compiler can lay out an order containing a level pointer field as long as it knows that level is a type. It does not need to know levels fields until somebody actually dereferences the pointer. Okay, after that, we are coming back to our function, the is stop order. We're just creating a helper function for us to know if it's a stop order or not. And the way to do that is just to create a function, no discard. I've already talked about this. Is stop order, and we return if the type is equal to order type stop or order type stop limit. Great, that is stop order. After that, we will also have a static assert here that the size of the order should be less than equal to 128. And the reason is that order should stay compact enough for cache friendly access. Now, why is this 128 present? So size of order less than equal to 128 is the size budget. So with align as 64, what we have done is said that the struct occupies at most 2 cache lines, never 3. Okay, we're trying to fit it in 1 cache line, but at most we have 2 cache lines. We never go on to the 3. And that matters because, every match that we have will touch the previous, next, all of these order types, right? And these fields are scattered throughout the structure. So if a future contributor adds a field that pushes size of order to, let's say, 130, suddenly we have some accesses near the end touch a third cache line. So that extra line is another potential L1 cache miss on every order. And the static assert is just catching that growth at compile time. And it just forces a conversation that, hey, you either need to justify the size growth or we need to rearrange or shrink fields to stay under budget. And the size layout is not as simple as it seems. Let's understand what would happen here by an example. So we have an order first. It starts at offset 0. It takes in 8 bytes because order ID is uint64. Correct? Great. After this will start at 8 bytes, but it only occupies 1 byte because side is only 1 byte. So it goes until 9. Now this starts at 9 and it goes until, let's say, or actually 0 to 7 would be the case, 8 to 9 would be the case, then 10 to, let's say, 17 would be the case, right? Well, that's wrong. That's because this price cannot start at 10. It needs to be cache friendly. That means we will instead have some padding over here. this padding will be of the size of 7 bytes. After this, it will start at 16 because everything needs to be a multiple of 8, right? We've already established that before. So we have 16, then it occupies 8 bytes because price, so we have 24. After that, we have 24 and 4, which is 28. And this will keep happening until we get to status. Status is 49 and 1 byte, which is 50 bytes. And well, if we have 50 bytes here, we'll have 2 bytes of padding so that we can start at 52 and so on. So like this thing will continue happening. So it's not laid out perfectly in our structure. So, and the total of this is probably going to be around 96 bytes, and align as 64 will round the total to the next multiple of 64. So that's 128 bytes. And that's why down there we have added size of order should be less than equal to 128 bytes. Also, I told you that I don't know why for some reason I've added these 4 quantities together and peak quantity later on. Well, there was a reason for it. The reason is cache friendliness. This is very cache friendly. Let me explain this to you. So let me undo all of that. So the first cache line is going to contain bytes 0 to 63. That includes ID, which is 8 bytes, then 9, and then it goes until 16. Then you have price, quantity, original quantity, display quantity, hidden quantity, timestamp, then the order type, order status, participant ID, and the trigger price. All of these are most of the fields you will read on a matching engine. All of that will come under the first cache line. The second cache line includes the peak quantity, the previous, the next, the parent level. And these are the linked list pointers and, well, the iceberg's peak. This comes under second cache line. So in the first cache line, we have everything that might be required for the matching engine and would be frequently required because every matching engine will require a price quantity, right? So they're laid out perfectly in the very beginning, type, status, all of that. And in the second one, iceberg specific thing, then the previous and next, it's not going to be as often updated as, like if there are a million orders, how many of them do you think will need previous and next update every single time? Now, you can make a case that if you really wanted to squeeze, you could split the iceberg and stop only fields out into a side table that would be keyed by ID. However, we are just choosing simplicity here over micro optimization. You should do it. That would be a good next thing to do after this tutorial. See how you can make it more performant. I'm just going with the simpler approach here. Yes, you can split out iceberg order and stop orders into a separate thing of their own and ensure that we have faster performance there. After that, we also have another static assert here, which is standard layout V. So standard layout type has a predictable, portable memory layout. Specifically, that just means we have no virtual table pointer. That means we have no virtual methods, no virtual base classes, no mix of public or private fields, no, like the multiple inheritance stuff. All of that is not there because all of that requires vtable. And the order is exactly the fields you typed in. We want the exact declaration order because we have decided that very cleanly. We want deterministic padding. We've decided that. The compiler is not allowed to silently shove, like a vtable pointer at the very front. We've already understood vtable pointer and its problems, so I'm not going over that more. So this is our entire order structure. You might be getting a feel of how the matching engine is going to work. Now let's get into the level.h. After level.h, we'll be getting into the order book because order book contains the entire, price level, all of the entire thing. And that is going to be a very big file compared to everything we've built till now. And then we get into the matching engine, which is much simpler. It just uses the order book. Cool. Now let's get started with the level. Very simple. Level, what does that contain? Price, quantity, order count, and the queue, right? What is the head of this queue? What is the tail of this queue? And what is the, like the functions to add an order to this queue, to remove an order from this queue. That's pretty much it. Now, I don't want you to confuse this order previous next parent level with this level. This was the order structure. In the order structure, we stored, what is the next order in our thing, okay? But in the level, what we are storing is what is the head order. And this order is going to be the order structure itself. And it will have a doubly ended thing, right? So it will have like a next pointer, the previous pointer. Then order B will have its own thing with a next pointer and the previous pointer. And then there will be order C, which does the same thing, correct? So each order will have its own previous next thing. And level is going to contain what is the head of this order, what is the tail of this order. So a level just represents all the resting orders at a specific price point. An order is one thing that might be present within a specific level. Now we just need to get through the fields. This is going to be super fast because we've already understood the entire structure, so that we can get quickly into the order book. Let's get to it very quickly. As usual, we are going to have our pragma once. After that, we are going to have our include statement. We are going to include this order.h file because, as I mentioned, each level is going to contain an order. After that, we can go ahead and have our structure or namespace. After that, we'll have our structure. One thing to notice is that the namespace is the same as this order one, exchange matching. Cool. After that, we can go ahead and have a structure now. Structure align as 64 level. We'll talk more about that align as 64 after we're done putting in all the fields. But the first field that we're going to have is price. Obviously, even if we go here, there's a price, right? The fixed point price that this level represents. So it's going to be 150.2000 instead of just 150.20 because we're not storing in decimals, right? We're storing integers. So that's the price type. Great. Next thing we need is the total quantity, as we have described here again, how many shares are present for this level. After that, we are going to have the order count. How many orders do we have in this level? Great. Easy. After that, we're going to have our head and our tail. Great. Everything we've discussed. This is the head of this level. This is where we start this particular part, and this is going to be the tail of where it ends. Now, the next thing we need is two functions, one to add the order to this queue and one to remove the order from this queue. So to do that, what do we need? Well, we need two functions, or add order and remove order. So let's create the add order function first, which basically appends to the tail, right? So we have our add order. Whenever we add a new order, we add a new order over here to the tail. So how do we add a new order to the tail? So whenever we want to add a new order, we'll go ahead and take the new order that we want to add and put a connection in, right? Let's say I want to add an order D. So I'll go ahead and have order D. After that, when the order D is here, I want to take this order D and put its previous value to this order C because we're creating a doubly ended linked list, right? Or like a linked list that has pointers both the sides. I'm not sure exactly what it's called, I forget. But anyways, we have our orders previous value to the previous tail, okay? And then what we want to do is set this order's next value to null because there's nothing after this. So we go ahead and have a null value. Also, we'll update that the order's parent level is equal to this particular thing that we have, right? If you notice, we have a parent level here. What is the parent level? Well, the parent level is the structure that we are inside of. So we need to set it to that. And then we need to update this tail's next value to order D so that there's a pointer here. So that is going to be our process. And then obviously the tail value is going to be this. And I'll remove this indication because it only points to null. So there's no need of pointing it anywhere. So we have created it this way. So we know the steps. Let's get it coded. So we want this orders, the order we want to add to the queue, its previous value should be the tail. After that, order's next value, the next pointer should be at null. So we go ahead and set order.next is equal to null pointer. After that, we'll set the parent level. The parent level, what is this order belonging to? What level does it belong to? Well, it's this level that we are inside of. So we can just set order parent level is equal to this. Great. After that, we want to set this next pointer. As of now, we only have this done. But what we want to do, also this tail points over here. What we want to do instead is have this tail, the current tail that we have, take its next value and point it to the new order. And to do that, we'll first have to check if the tail value even exists. If the tail is a null pointer, well, we cannot just set tail.next, right? So instead, we'll have an if condition. If the tail is not equal to the null pointer, tail.next is equal to the order. But what if the null pointer is present on tail? So tail does not really have anything. That means it's something like this. Head and tail pretty much point to the same thing, which is null. In that case, we'll just set the head to the order because the queue was essentially empty. There was none of these orders. I can remove it for demonstration and add it back later. So what I mean is you have nothing like this. Okay, so or actually something like this. There's an empty queue and head and tail point to nothing. They're both null pointers. So what we want to do is ensure that the head is equal to the order and tail is also equal to the order. So here, else case will be head is equal to order, and after that, we anyways want to set tail to an order, right? Even if the queue was empty, we wanted to add, let's say, a new order. Let's say we added order A after this. Even if we added order A here, the head points to null, tail also points to null. But if we have some other elements like we had previously, let me just go back to that scenario again. Even if we have something like this, our tail was pointing at order C, we added order D, and now we want to update the order C tail or the tail to order D now. So that's what we have done. After that, like after this, it doesn't matter if the tail is null pointer or not. Regardless of that, we're going to set tail is equal to order. Then obviously we need to update all of these fields as well because a new order is added. So the level's total quantity has increased, the order count has increased. So we'll do that. Total quantity plus equals order or display quantity. And then we'll have plus plus order count. We're using the display quantity here, not the hidden quantity. Obviously that makes sense, not the original quantity, because even if there's an iceberg order, we only want to replenish whatever is the original quantity, not the display quantity. Otherwise that would be, we want to do display quantity instead of original quantity, because original quantity will just give us the entire original quantity, and that will not work well for our case in iceberg orders. And obviously not the peak quantity either. So yeah, that's that. Then we just increment the order count and we're all set. So we've understood add order. Let's understand how to remove the order. To remove the order, all we need to do is unlink from anywhere. Let's say we try to delete order B. So to delete order B, what do we have to do? We want to remove a pointer from here. So we want order A to directly go to order C. Okay, so order B's previous value will change. Let's put that in and then we can move on to the next condition on how to unlink the orders. And I've not even created the function, so I'll create that first. We have void remove order. There we go. No except. Great. I mean, you can put it or not put it. We know that. Now what we need is an if check. If order's previous value is not a null pointer, then we want to set the order's previous next value to order.next. What I mean by that is, again, we have to remove order B. To remove order B, there's a bidirectional arrow here, correct? Order A points to order B points to order A. What we need to do first is remove order A's pointer to order B. And instead of putting an order pointer to order B, we'll put it directly to order C. So instead of the pointer looking something like this, it will point to something like this instead. How do we do that, considering we only have access to this order, because that's what we are getting from the parameter? Well, to do that, we will first have to access this order, and we can do that by accessing order.previous, right? Because this order's previous value is order A. So I'll check here if order.previous is not equal to the null pointer. If that is the case, that means we're not at the head, okay? If we're not at the head, what do we want to do? Well, if you're not at the head, then we want to basically take this previous value, this is order.previous. We take order.previous and then we set its next value to order C. And to do that, we'll do order.previous, which gave us access to order A, and its next value, which is order C, and we set it to order.next, right? I mean, we take this pointer of next. I mean, just imagine we have an order structure. Order structure has the next pointer to it. So we have order A. So the way to go to order A is order B dot previous and order. So we are on order A. This gives us, let's go back. This gives us order A and then its next value. So order A's next value is order C. Well, how do we contact order C? Well, order B's next value is order C. So we can just set it to order.next, right? So this is order A. Order A's next value is order B's next value. So we have removed the pointer from here and instead put the pointer here. However, this connection still exists. To totally unlink it, we also want to ensure that order C's previous value is order A. But before that, what if order.previous is a null pointer? If order.previous is a null pointer, that means we are at the head, because just think about it. Order B's previous value is order A. Order C's previous value is order B. And if there's order D's previous value is order C. So that means the only time we don't have a previous value is when we are at the head, because order A does not have a previous value. So if we are at the head, what should we do? Well, we just want to set the head to order.next, right? Because if we are at order A, we want the head to point at order B if we want to remove order A. So we can just set head equal to order.next if we are at head. Awesome. Great. Now that we have understood this, we can go ahead and remove the pointer that I was talking about over here, the next pointer essentially. And it follows a very similar case. If order.next is not equal to a null pointer, then we take order.next.previous and set it to order.previous, similar to what we had before. Let's say we want to remove order B. So there is a connection going out over here, right? What we want to do is ensure that order C's previous value doesn't point to order B. And to do that, first we have to contact order C. So we have order B, which is the current order. Order.next will give us order C. So if that is not a null pointer, well, it's not in order B's case. So we'll have order.next, which gives us again access to order C. We'll set its previous value. To, well, not order B, right? Because it already has it. We'll instead set it to order C. And to do that, we'll just set it to order.previous. Great. So we have that done. Okay. So now we've removed this connection as well. There's no backward connection from order C to order B, and there's no frontward connection from order A to order B. All that exists is order B's previous value is order A and order B's next value is order C. But both of them point to other things. So what will we do? Well, it doesn't really matter if you do anything with it or not, because this is already out of the queue. Order B's next and previous value is set to anything. That doesn't matter to us. What we care about is it's unlinked from the queue. However, if you want a safe case, what you can do is set the previous, next, and parent level to null pointer for this order. But before that, we have more important work to do. We have removed an order from this level. So we want to update the total quantity and the order count, correct? Let's do that quickly. Oh, also we have an else condition. I forgot about that, because what if we only have order D, right? I mean, if you want to remove order D, it does not that we can do order.next.previous value, right? I mean, because there's no order.next for this order D, it's the last. It's going to be a null pointer. So in that case, we just want to take this tail and put it to order C. Great, we have understood that. These are the edge cases. Now let's update the total quantity, which is minus equals order display quantity, minus minus order count. Very simple. And now we can do what I talked about. Because coming back to the order B example, what did we have? Let me remove some arrows and then we can explain further. So the first thing we did, if you want to remove order B, is instead of having a connection like this, we only have a connection that goes like this. Order A directly goes to order C. Order B still points to order A. And order C, instead of pointing it this way, order B still points to order C, but order C points to order A. So order B is out of the queue because imagine you're traversing over this queue. You go over head, which is order A. Then you go to the next value, which is order C. Then you go to the next value, which is order D. Or if you want to go previously, what you have is order D goes to order C goes to order A. There's no order B here. But if you specifically, let's say, land on order B, it still contains the link of previous and next values to order A and order C. We can still clean it up. It doesn't really have any effect on our case, but it's just clean code because we essentially want to remove it and isolate it because it's no longer a part of us. So we go ahead and have order.previous is equal to null pointer, next is equal to null pointer, and parent is equal to null pointer. What that does is removes this link, and it does not belong to this parent either. So we completely remove it. And now we don't have order B at all. Awesome. So that was our add order and remove order. Now we can also have two functions, two trivial functions that we will use later on. You'll see its use case. What we have is front. What is at the front? Just a helper function. So we have order returned front. It just returns the head. So that can be a null pointer that's returned when, the queue is empty. So the caller has to handle that. And yeah, it's just the front of the queue. So that's the head. And then we have is empty, which is the queue empty? Well, to check that, all we need to check is the head null pointer? If the head is a null pointer, we don't have anything. Or you can check if the tail has a null pointer. Even that case would be fair. So you just have this. Return head is equal to null pointer. So that's all for the level. That's all we need. And this will really help us a lot. Both of these, order and levels. Now, before we move on to the order book, let's understand how the order book works, right? Also, I'll remove all of these scribblings, doodlings that I did because we want a clean start when we go to the order book, right? Okay, great. So now coming back to this order book. So we know that we have buy and sell parts where we have all the orders listed. Now, what happens if, let's say, for a particular stock, the bit side of that stock is not a single FIFO. It's a collection of price levels as we have here, right? I mean, 150.20 maps to this level. We'll also have another one that will be for 150.15. We've covered that, correct? For each price point that you see over here, you have a level. For each price point in cell, you also have a level created, correct? What does that mean? That means we need a map, right? A map kind of structure that will help us create a mapping of, okay, this price has this particular level. This price has this particular level. This price has this particular level, and so on. So you have sort of a mapping that's created. So naturally, you might just think, why not use a map to create this? We'll have a map where we have, let's say, a price and a level pointer, correct? Whatever is the price will point to a particular level. One thing to note here is we don't have a structure just like this, even if we do that. The reason for that is, well, think about it. The buy and the sell, as you can see, are arranged in descending and ascending order. In buy, highest prices are listed out first, then you have the lower prices later on. In sell, you have the lowest prices first, and then you have higher prices down there. That's done because the highest bid in bid is the best bid. So that's where the matches will start, correct? And in ask, everything is ascending order because the lowest ask is the best ask. That's what we want to maintain here. So even if we do use map, we still need a greater here. What this will do is ensure that it is ordered in the bid side, because bid side is the one that will require a descending map. And we will be using an ordered map here instead of unordered map because we will have to iterate in price order. So whenever, let's say, a marketable order comes in, the engine will have to look at the ask side from the lowest ask and upward. When a sell comes in, it will have to look at the bid side and go from the highest bid to the lowest bid. Think about it. That's literally how exchanges will work, right? If you want to satisfy a user's requirement, you give them the best deal. If someone wants to buy, you'll give them the lowest price possible. If you want to sell to someone, you will get the highest buy price possible. So that's what we are doing here. That's why we have descending and ascending. Now, since we will have to iterate through the price order, we cannot use an unordered map. We do need an ordered map. Map is ordered. We know that. If you want more details, it's basically a balanced binary search tree. If you are using libc++ or something like that, it would be a red-black tree. So whenever you call something like .begin, it will give us the best price on a side in O of log n time. And if you just cheapen it out, it will be O of 1 because like the value will be cached and so on. And if you try to insert or erase an order, those are O of log n as well per level. And per level is the key point. They're not O of log n per order. It's O of log n per level because we typically only create a level when the first order at that price comes in, right? Why would we create multiple levels if we already have a level at that price point existing? But we do have a problem with using a map. One of the major problems with map is that it allocates on the heap. We don't want to allocate on the heap on a hot path, and this is directly coming in on the hot path. It's touching the order book, and order book will be updated millions of times. So we can't have map allocating on the heap. And to avoid the map allocating on the heap, we will be creating our own structure called PMR, Polymorphic Memory Resource. And we will see that when we get into the order book. But before we get into the order book, there's another file that we'll have to create, and it's called events.h. So here, whenever we are matching, we're also going to have events.h. For each event that happens, we're going to create those types over here, and then we'll get into the order book. So after events, we're going to get into the order book.h as well. All the events that we have will be defined here, and order book will use those events later on. Another thing I would actually like to talk about before we get into the order book is basically the invariant, the specific kind of guarantee of the property that we get because of the matching engine. And actually, before we get into that, I would like to talk about one other thing, which is basically the invariant that the matching engine maintains. By invariant, I mean the fundamental property because of which the matching engine basically works as efficiently as it does. And that is the bid side's best price is strictly less than the ask side's best price. So if the best bid is greater than or equal to the best ask, the book is crossed. That means there is a buyer that's willing to pay more than the seller is asking for. And that cannot persist for a long time. The engine will have to immediately match the trades until the cross is resolved. So the steady state, what you see between events, is always uncrossed. So it's kind of like a transient issue that the engine will have to eliminate before returning. So let's just take an example to understand that. This is basically a book that's uncrossed. We have 100 shares at 150.2. That is a best bid, and the best ask or the best sell is 150 shares at 150.25 because, this is unmatched because if the best bid is less than the best ask, the book is uncrossed. And that is the case here. The best bid is 150.2 and it is less than the best ask, which is 150.25. So that's good. But what happens if, let's say, a new order comes in, a new buy order, which says, okay, I want 200 shares at $150.30. Okay. What happens in this case? Well, buy is structured in a descending order. That means it will climb up at the top. So we have this done and we can remove this circle. It's no need of that circle. Okay. When this order comes in, it just means that a buyer is now willing to pay up to $150.30. If that is the case, the current best ask is the current best bid is 150.3. What is the best ask? 150.25. Well, that means the best bid is greater than the best ask. And we've reached a cross because, well, that is how cross is defined, right? Someone is willing to pay more than what the seller is asking for. So how do we resolve this? Well, to resolve this, what we'll have to do is first look at the best ask. Well, it's 150.25 with 150 shares. What we will have to do is trade 150 shares at $150.25. So we'll resolve it. We'll go ahead and say, okay, we don't want this. We want this. So 150 shares is gone. But this buy requires 200 shares. That means 50 shares for this buy is still required. Well, how do we satisfy that? We'll go to the next cell and we see, okay, 150.3. Let's trade 50 shares at 150.3. So we'll have 150 shares at 150.3 and this will essentially go away. So all the order here is fulfilled. And now we're reaching back at the position where it's uncrossed because you have someone who is willing to, or not someone, the best bid here is less than the best ask. Pretty straightforward, but this is how you'll go ahead and resolve it. So the buy order that came in, the best bid, what happened in that is that 200 shares were traded where 150 were at 150.25 and 50 shares were traded at 150.3. So a few things to notice here is that the aggressor never rested because its full 200 shares were traded. If it had been something like, oh, I want to buy 500 shares instead of 200 shares, let's return back to our initial order or order book. So we have 200 shares here, right? Let's say the guy said, I want 500 shares at this price. We have a problem here because the total number of shares that we have is 350 plus 75, 425 shares. We don't have 500 shares to capture all of them. So what will happen is once these 425 shares, let's say, are traded, or let's say these 350 shares are traded, because then the buy and this 150.35 is bigger, right? If someone is only willing to pay 150.30 at best, you can only share these two with them. 150 shares at 150.25 and 200 shares at 150.3. You cannot do 75 shares at 150.35 because they're not willing to pay that much. So what will happen? Well, after you've traded those 350 shares, 150 shares will rest in the order book. And after resting, 150.3 will become the best bid and the book will still be uncrossed because the best bid is 150.3 and after that, so you'll only be left with 75 shares at 150.35. Now, what do you have? Well, you have 150 shares at 150.3, so that is the best bid and the best ask is 150.35, so your spread is now again $0.05. We don't have to change that, but that's what happened here. Now, what would happen if this aggressor was post only? Let's return back to our normal condition where we have something like this. Okay. Now, what do you think would happen if this order was post only? For your recollection, post only order is just like a limit order, but your trade is added directly to the order book rather than being executed immediately against an existing order, right? You just do it for maintaining the liquidity. So what would happen in that case? Well, if it was post only at 150.3, it would be rejected instantly because it would have traded, right? 150.25, it would have traded. 150.3, it would have traded. It'll just go ahead and reject itself because post only refuses to cross. That's the main thing here. Now, what would happen if, let's say, an FOK order was placed for this, which is fill or kill? And, as we know, only 425 shares are available. And out of that, only 350 shares are available at the price that we want, of 150.3 or below. Well, in that case, the entire fill or kill would be rejected because no partial fills are allowed there, correct? Now, what would happen, or actually, I guess you get the point. I won't discuss every order now, but these are the main things here. The order can get rejected. If the order gets rejected, it will not stay in the order book. Just remember that order will come into the order book if it's coming to rest. That's the point. Also, remember that with each thing that happens, the total quantity is updated, okay? So if we add an order, we remove an order, the total quantity is updated thanks to our level file that we had. Add order and level order, or remove order, that handles all of these cases. And this is why, the aggregate quantity lives on the level. If it hadn't lived on the level, like the total quantity and all of that, what you would have to do is go through this entire order and then calculated the aggregate total quantity. Okay, order A has 50 shares, order B has 200 shares, order C has 300 shares, order D has 100 shares, and you would have to add them up. Instead, you can just maintain a value here at the top of the structure so that you can look at it in O of 1 time. Okay, we are at level this, and I know if I go at 150.3, how many shares do I have available? Well, I have 100 shares. I only have to look at this instead of going over the FIFO queue again and again. O of 1, you can basically think of this as a cached value. Another thing to look for here is that the order belongs to two structures at once. One is the FIFO queue, the price level FIFO, where you have the answer of, hey, where is the oldest order at $150.2 on the bid side? And we get access to that answer in O of 1 time. Because if I want to know what is the oldest order at 150.2, I can just go to this map of 150.2, which will lead me directly to the level. And in level, I know there's a FIFO queue because like in the level, I've stored the head and I can just access the head to get me over there. Now, another place where order will exist is, let's say you want to answer the question that looks something like this. Given an order ID 12345, where is it, right? You want to know where a particular order exists. Well, you cannot know without traversing all these levels and going over each of the FIFO queue, correct? I mean, that is the most brute force way to find that out. Because if I want to find a specific order, I would have to go to 150.3, then go to head order A. Okay, is that order ID? Maybe, maybe not. Order B, order C, order D. Okay, it was not in this level. Then I go over here. I go over each of the things over here. Check, nope. Then we again do the same for each of the level. And let's say it existed, this order ID existed at this last 150.10 and the very last thing. So in worst case scenario, you are taking so much time. You have to go through each level. You have to go through each queue of that level. That's bad, right? We want to do it in O of 1 time. Because at any given point, we will not just have 4 levels. That's the best case scenario you can say. We'll have multiple because we want a stock exchange to be functioning, right? So that's one thing. Now, how do you solve this? Well, to solve this, one of the things you could do is that each of these structures, you could go ahead and store a set that, yeah, I have these orders available in this. So you go through each level and you have a set where you can just check in O of 1 time. Is this order ID available? Then you do for this level, this level, this level, and so on. So that will still take you the amount of time that is something like O of n, where n is the number of levels, because you'll have to traverse over each of the levels and see if it exists in the set. Another thing that you can do is maintain a map. A map which is an ID indexed lookup map, where you have an order ID and it will tell you exactly where it is in the order book. And that is why on each of the order, we have the parent level. Right? So you have kind of a structure where you say, okay, 1, 2, 3, 4, 5 order ID that's present at this particular order address. And the order address is basically 0x something like this, okay? And you have a map that maintains this. So you can go to this order ID. You'll directly go to that order structure. Let's say It's present at 150.10 order D. So you are able to go to it in O of 1 time. That's great. And then you are able to find out what level it's in by looking at order D's parent level attribute. That's O of 1 as well. So we just took and diminished all of the time instead of storing extra details over here. That's awesome. Now let's imagine a scenario where instead of using a queue here for the FIFO queue, we went ahead and had something like this. Okay, actually, let me push it up. Okay, for the FIFO queue, instead of using a linked list, we would be using something like a list, a standard list. And then we have an unordered map for the lookup. That means every order would be heap allocated as a list node, and the map would have to store iterators that dereference back to that node. That means we'd have to do like 2 layers of indirection in 2 heap allocated structures, and it would be very complicated because what would happen to the iterator if the list invalidates it. And that's why our intrusive design is so good, because with our intrusive design, we can have one order structure participating in both structures, this FIFO queue and this map, without copying or wrapping. So what's happening here is in the ID index lookup map, we have our order 1, 2, 3, 4, 5 order ID. That's to an order address, right? And the same order address is directly in this order price level. So all of this is just 4 O of operations. If you wanted to remove something, for example, you don't have to scan anything. You don't have to copy anything. There's no sort of allocation going on. So this is awesome for our use case. I hope you understood the entire order level and how it all plays out, and this imaginary map that you've only seen over here, but we'll create in the order book. But first, let's get into the events. I think you've understood how the order book is going to work. So we can get directly started by introducing all of the events that are going to be present in the matching engine and more. And then we'll use those events within the order book so that we can send out the events. Events are like, okay, this order was rejected. That is basically what events are. So let's just do that. A kind of a notification system. So before we touch any code, let's just understand the idea of events, because obviously, why do we need events at all? Well, the matching engine, in our case, will not mutate any private state silently. So what it will do is that every important decision that the matching engine will make will be an event. Event is basically a small immutable record that will describe what happened. So let's say an order was accepted. For example, an order rested on the book. A trade occurred between order A and order B at price, let's say 150 for quantity 100. And all of those will be converted as events. And even if there is an order rejection, that will go through the events as well. Now, why is this present? Well, this is a pretty popular pattern. This is not something novel that we're doing. This is called event sourcing. Basically, the event log will be the source of truth. The current state of the engine, like the order, the levels, all of that is basically just a projection of the events, right? If you replay the events from the start, you reconstruct the exact same state. That's the core idea. And why is that useful in our system? For reason number 1 is crash recovery. As I've mentioned many times previously, if there's a crash, we want to replay the journal of events to rebuild the order book. So we'll be able to do that. Second one is audit. If we want to know, or the government wants to know, or any regulatory authority wants to know why a specific order was rejected, the event will carry a reason code that will tell you why the order was rejected, why every decision was made, because the event log is going to contain every decision in that. The third reason is decoupling. So the market data publisher that we're going to take on later on in future videos, the journal writer, all of that consume the same event stream. None of them will have to peek at the orders book private field, or order book's private field, the engine will produce, the consumer will consume. So the market data, publisher, the journal writer, all of those are decoupled. They can just look at that event data stream and get their answer. They don't have to continuously use some private field that is present within the order book that we need to make public. The order book state should be within order book. If someone wants to take a look, they can look at the event state. That's a benefit that we get, and it's a pretty good design. So with this, the events are basically not an afterthought or something that we are logging for convenience. They are basically the way the engine is going to work. If you want to consider it as an API, this is kind of the engine's API. So yeah, let's go ahead and quickly add the pragma ones. Then we are going to have C standard integer, type traits, core types.h. I'm not going to explain each of them. We can move forward. Then we're going to have our namespace exchange matching. Here we've used a different kind of formatting for C++. If you notice here, let's say level, the brace is over here. Just a fun thing. If you want, you can put it over here. I don't know why suddenly my cursor editor wants to format it this way. I'm not going to debug further. It's fine with me. Let's move on to the next thing, which is having all of the using statements. So the using statements that we're going to put in are from core match ID, order type, price, quantity, sequence number, side, symbol, and timestamp. So these are all standard types that we are pulling in using the using keyword. Why are we doing that? That's because the using declarations will pull the core types into the matching namespace so that we can write to order ID instead of doing core : order ID. This is basically just a styling choice that I'm having. If you don't want to do this, you can keep writing core : match ID everywhere. I just want to write match ID. Cool. On to the next thing. Then we have the reason code. This is basically the structure which will decide what are the ways in which an order can be rejected. So there are 12 possible reasons here, and each one is going to be a 16-bit integer. That's because it's small, it's stable across process boundaries, and it's easy to test against if you want to add tests later on. Why are we using integers and not strings here? Because it's a reason code, right? I mean, code is going to be something like, oh, this is a negative price, or the book is empty, or we did not find an order. What is the reason to reject an order? All of that can be a string format. Why are we using an integer for that? Well, that's because integers are cheap. 16 bits is 2 bytes. 2 bytes versus a string, and a heap allocated string can be, let's say, 24 bytes as we've discussed before. Also, integers are stable. A string can change phrasing in a future release. Like, let's say it's changed from this is an invalid display to you change it to, let's say, iceberg display invalid. The string has changed, the value has changed. With an integer, the integer code is definitive. It is going to last forever, right? And also in testing, integers are just much easier. So you can keep it if you're going to do testing as well. But let's move forward. The first field we're going to have is none. There was no error. So we don't need a reason. That's 0. And we've mentioned 0 over here because that's what we're going to start with. After that, it will automatically take up 1, 2, 3, etc. All right. Then we are going to have 0 quantity. As the name suggests, the user has passed in, oh, I want to trade 0 shares. Well, unfortunate, we don't do that. The next thing is negative price. As it says, the price was negative. How can a price be negative? It's always going to be positive, because what does it mean to trade at negative prices? The next is book empty. The order book is empty. Specifically, this is the rejection a market order gets when the opposite side is empty. So the engine is just refusing to invent any price execution out of thin air. There has to be a counterparty, right? If you want to buy 150 shares at $150.1, there has to be a sell on the other side at that price. Otherwise, we cannot just trade, right? So the book is empty, you get a rejection. After that, we have duplicate order ID. Somehow the order ID is duplicate, so we've prevented that. Obviously, each order ID should be unique, otherwise you're conflating between two order IDs. Next is order not found. As it says, the order was not found, we throw an error. The next one is order not active. And this is where I would like to point out the difference between both of them. Order not found and order not active might sound like the same thing, but they're not. So whenever you cancel an unknown ID, the engine will distinguish between, oh, I've never heard of this ID, from, oh, I knew this ID, but the order is already filled or cancelled. The order book will remember every ID it has ever seen, even after, let's say, the order retires, okay? Exactly, so it can tell those apart. What we are telling apart is, oh, I've never heard of this ID ever before. That's order not found. And this one is that I knew this ID, but the order is already filled or cancelled. After that, we move on to FOK insufficient liquidity. This is basically if there's a fill or kill order, which is basically all or nothing. Just to remind you, if we can fill up everything, that's great. We want that. If not, we're going to kill the order. We are not going to rest the order. We are not going to do anything else about it. So if the engine cannot satisfy the full quantity in one shot, it will reject without trading anything by saying there's insufficient liquidity. There's just not enough shares to help us match this order. Great. After that, we have post only would cross. So this is for a post only order, which is a maker only order, which means it must reset. It should never aggress. If just to remind you, post only, we've talked about this previously as well. Post only is an order that's just posted to the market just to provide some liquidity. If the order can match, it will just be removed out. It will be rejected. Otherwise it will cross, right? That's why we have would cross. So the post only order's job is to add liquidity to the market, not actually trade. So a post only order is make or only. That's why I said that. And it must rest. It should never aggress. It's just adding liquidity. So if it would cross immediately, the engine will have to reject it instead of either trading or silently changing its price. Because if it trades, it would betray the maker only intent that this post only order has, or you're silently changing the price because of which you would betray the requested price. So we don't want to allow it to cross. That's why we reject it if that happens. After that, we have invalid modification. You're just invalidly modifying. Maybe you're not the participant and you're trying to modify the order or some other reason. So all of that. Then we have invalid iceberg display. This is pretty straightforward. If the iceberg display quantity or display part is invalid, it returns that. And finally, we have order pool exhausted. Not finally, or I think it's finally. Do we have 12? We should have 12 reason here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 12. This is the last one where we say, okay, the order pool has exhausted. Remember, when we talked about zero allocation infrastructure, the pools were bounded, memory pool. So when the order pool runs out, the engine will reject with this code. The right reaction to this in production system should be that you just run an alert that, hey, the config is just too small so that anyone else can change this limit because we were wrong with one of our assumptions. But we are not doing a runtime fallback to malloc here. Because if we do with malloc, I've already described the negative consequences of that, and we don't want to do that. Awesome. We have all of the reason codes. Now let's move on to the next thing. And these are all the enums and structures that we're going to create, and then reason code will be within one of these structures that we create here. It will be part of the event, and it will be very helpful. So the next thing is the event type. This is going to be what the engine reports. Was the order accepted? Was the order rejected? what was the reason. Okay, or what was the event, sorry. Reason is over here. Why, if an order is rejected, this is the reason. But there are different types of orders that are present as well, right? They can be accepted, they can be rested, they can be rejected. If it's rejected, we have reason code. They can be reduced, or they can be partially filled, they can be completely filled, all of that. So we have event types for all of them. So we have an enum class again, event type. This is an 8-bit integer, 1 byte for each of the types that we're going to have. And some of these distinctions between all of the events might look redundant, but trust me, every one of them will carry some information that some downstream consumer will need. From a diagram that I mentioned in the introduction, you remember there are downstream consumers of the matching engine as well, the market data publisher and all of that. So they'll be looking at that and it will help them out. So the first thing is order accepted, and I'll also go ahead and have order rested. What is the difference between both of them? Because they might seem similar or actually not based on our explanations. It's just that order accepted is you've accepted the order. Great. Order rested is you rest it on the order book. And they are different events created, not combined into one. You could technically combine them into one event and call it a day. Because when the order is accepted, you just say, okay, yeah, it's rested, the order is rested. But no, they are different events because acceptance and, in the book, you're inserting and it's visible to everyone. They're not the same thing. A market order, for example, can be accepted and immediately filled without ever resting. A stop order can be accepted and it can be parked, which will become visible only after its trigger fires, right? To differentiate between all of them, we have order accepted and order rested. The basic difference is that the subscribers that care about visible depth want order rested. The client confirming the exchange got my order wants order accepted. Awesome. We've understood that. Now let's move on to order rejected. Straightforward. Order reduced. This is fired when a resting order's quantity is reduced in place. We're going to have a function like a modify order that will lower quantity at the same price. So this is not a trade. This is basically an event. This is not a trade because no execution occurred here. There's no match ID that exists. You only match, or you only call it a trade if it's matching, right? You generate a match ID that's matching, and then you've gone ahead and called it a trade. But order reduced is that the resting order's quantity is reduced in place. So essentially, the quantity is reduced, so you can say a depth is reduced, and yeah, that's not a trade. Just to keep in mind, this is not a trade. After that, we have order partially filled. I think you already know what that means because, the order is just partially filled. It's not completely filled. And then we have order completely filled. This is related to our order types. If you want to go back, not over here. Okay, yeah, over here. We have all of our order types like limit, market, IOC, FOK. So you have this order partially filled when, let's say, you have a market order and you're like, oh, I want 200 shares at $150.2 price. And if those are available, you will partially fill it, and then your buy order will rest on the order book. But if you have something like FOK, fill or kill, it will just be, okay, fill this order, otherwise I'm getting out. I don't want any of it, or I want all of it. So in that case, partially filled will never get triggered. So in that case, partially filled will never get called. Only order filled or order rejected or something like that would get called because order should be completely filled or not. After that, we have order cancelled. The user went ahead and cancelled the order. After that, we have trade. This is the market facing event. This means that the trade happened. You have a match ID. You have the two order IDs like the buyer and seller one. There's also a price and a quantity for this trade to ensure like this is a single trade that happened. And by the way, this is also the price discovery moment. So the exchange tape, like the ticker that you see on financial news websites or financial news broadcasts, you'll notice that there's like this ticker of, Apple or someone is trading at a specific price point. If that is what you see, well, that's changing or flickering because of the trades that are happening here. All of these events don't contribute to that. The trade contributes because think about it. I mean, you completed the entire order. Someone's willing to buy it. Someone's willing to sell it. You match them. So you have a trade now. Great. So the exchange tape is made of these trade events, nothing else. None of them get outside. These are all private internal information for us. Now you might wonder, why do we have both order filled and trade? Well, that's because order filled only describes what happened to one specific order. The order filled for this particular order. Trade describes the entire matching itself. That there are two order IDs, there's a price, there's a quantity. So that's why we have two events here. Okay. Now let's move on to the next thing, which is we're going to create one structure per event payload. What that means is that each event type here is going to have its own structure with exactly the fields that it needs. So let's go ahead and have struct order accepted. What is this order accepted going to have? Well, you can refer to the types here and find out what will an order accepted order need. Well, obviously an order ID, a sequence number, a quantity, a price. That all of that sounds reasonable, right? Then we have, let's say, match ID, for example, is not going to be needed because why do we care if it matched or not? The order itself, if it's accepted, doesn't have to have a match ID. Also, match ID is going to be null because the order is just accepted. It just came into our system. We need to match it in later process. So why do we have to do this? So that's all we're going to have, and we're creating a struct for each one of these events. You could, in theory, go ahead and have one struct which satisfies for everyone, but most of the fields will be nullable in that case. And overall, in like when you're trying to broaden the stock exchange, it's not a good experience. Instead, if we only have 8 event types, it's better to have 8 structures. It makes our system more extensible, but there is more code. So yeah. So let's go ahead and have the sequence number first. Every event is going to start with 2 common fields. The first one is a sequence number and the second one is a timestamp. Sequence number was the monotonically increasing counter that's assigned by the order book. And the timestamp is the logical time at which the event was emitted. We've already learned about logical time in clocks.h. So let's move forward. Then we have order ID. What is the order that we've accepted? Then we have the symbol. What symbol does this order stand for? Is it for, let's say, APPL, or is it for NVDA? What is it for? Next, we have side. Side is this part. Let's go to 2 types again. Is it a buy order or a sell order? If that's answered, that's side. Awesome. The next thing is price. What price are we trading it at? What is the quantity? What is the order type? Order type is, if we go to types.h again, is it a limit, market, IOC, FOK? What is it? That's also helpful information because the order was just accepted. Awesome. We've understood that, and now I'll go very quickly with all the other structures. Okay. The next one is order rested. As I mentioned, these 2 fields are always going to be the same. So we have sequence number, we have timestamp, we have order ID, we have symbol, we have side, we have price, quantity. And yeah, that's pretty much it for order rested. Notice, in contrast to this one, what is present? Well, order ID, symbol, side, price, quantity is all present. But order type is not present over here. Why is it not present? Well, that's because when the order is accepted, we need to know what kind of order it is. But if it's rested, we don't really care what kind of order it is because it's rested. If it was, let's say, an IOC, FOK, it will never rest. But if it's an order that allows us to rest, that's why we have here. The next thing we have is order rejected. Again, sequence number, timestamp, order ID, reason code is going to be present here, the one that we defined earlier. Very simple reason. If the order is rejected, we want to know why. Otherwise, it should not be rejected. So yeah. After that, we have our order reduced. Also notice in order rejected, we did not have price, quantity, any of that stored. That's because the order has been rejected. We only want to give out useful information. Sequence number and timestamp, we need to know for each one of them because this will give like downstream consumers a total ordering across all the events from this bug. But anything else like price, quantity, the order is rejected. We don't really need it. Order ID is also fair, which order was rejected, and the reason is also fair. We're not adding anything that we don't need over here. Because if we wanted to add that, we might as well just have one structure where you can have nullable pointers, right? That's why we have this. Then we have order reduced, where we take in a sequence number, timestamp, order ID, awesome, quantity. What is the new quantity? This is important because when an order is reduced, I mentioned that the quantity will decrease. If the quantity is decreasing, what is the new quantity that is decreasing? Like 2. Right? I mean, there's an old quantity, which is the current quantity, and the new quantity comes in, that is going to be the reduced quantity. So if you want, you can also name this reduced quantity, but since we're already calling the struct order reduced, I call this again reduced quantity. This is more specific that it's new. Okay, then we have order partially filled. If an order is partially filled, I want you to take a moment, go through these types and see which one we'll need. Okay. So we'll need sequence number, we'll need timestamp, we'll need order ID again, then we'll need quantity or filled quantity. How much quantity has been filled? Then we have remaining quantity, how much quantity has not been filled. That is what we want to fill again, like if the order allows that. So if the order allows that, right? So we have price so that we know if the order is basically price. What price should the order trade at for the remaining quantity? This will especially help us when we have the iceberg order. But even when we have normal orders, this will obviously not get filled when we have an order type that does not support it. And that's why we do not have an order type here. If it's already partially filled, that means the order allows it to be partially filled. As a result, we don't need the order type at all here. Then we have order filled. If the order is filled, we have sequence number, timestamp. Then we have the order ID. Then we have quantity, filled quantity. How much quantity has been filled? Then we have the price. And then we have the order cancelled. After order cancelled, I believe we just have the trade that's left. Yeah. So we're very close. So order cancelled has a sequence number, timestamp, order ID. Quantity is going to be cancelled quantity. How much quantity has been cancelled? If the order is cancelled, how much did it already trade? How much did it cancel? We don't really care about how much quantity was traded here because the order has been cancelled. Why do we care how much quantity was left to trade? Our objective here is to trade or help our downstream consumers. It's not helpful for the downstream consumers if you're providing how much quantity is left. It only needs to know order was cancelled. Okay. How much was cancelled so that it can display to the user or do some other kinds of things that we'll talk about later. That's why it helps. Then we have a struct trade. Again, timestamp, sequence number, timestamp, and then we have unique structures now. If there's a trade, I told you there needs to be a matching ID. So we have a match ID now. Only one struct has this. No other event struct has this match ID because a trade is only there when there's a matching ID. Then obviously also the symbol at which the trade happened. Did it happen for NVDA or did it happen for APPL? Which one did it happen for? Then you have the order ID for buy order ID. What is the buying side order ID? What is the selling side order ID? And what price did they trade at? What quantity of shares were traded? This is the trading structure. One thing to remember here is that each trade will get its own matching ID. It is possible that one inbound order can match against many resting orders, which will produce many trades. So each trade here will get its own matching ID. Just imagine that. Let's say you place an order of, let's say I want to sell 150 shares at, or actually let's just take this example. I want to buy 500 shares at $150.3. And you're like, 150 shares at 150.25 is available. Do you want that? So that's one trade. 150 shares were traded at price 150.25. And yeah, so that's one trade. After that, you still need to satisfy this part where the user now wants 350 shares and this is no longer available. So you go to the next one where you have 200 shares at 150.3 and that works as well. So you have a second trade happening here. You have another match ID because the order ID has changed. This cell has a different order ID compared to this cell, which has a different order ID, right? So you have 200 shares, you sell that, and that's the second trade. Now you have 150 shares, and after this, we have already discussed what happens. It will not proceed. So we have that spread of $0.05. The next thing we need is an event structure. What will this event structure contain? Think about it. You have all of this payload for our event, right? It can be any of these events. So we need one field essentially that can contain any of these structures, and we can use a union for that, right? So that we have one, let's say, payload which can have details of order accepted, order rested, order rejected, anything. But it will only have one data for each one. And we also need to specify the event type. That also needs to be stored. And both of them will be stored in an encapsulating structure called event. And this is specifically called a tagged union. A tagged union is a fancy term for basically a struct with two fields. There's going to be a tag, which is the event type tag, and a union payload. Union is just, you can have either order accepted or order rested or order rejected details within it. You cannot have for both of them. The tag is needed because it will tell you which member of the union is currently valid. So yeah, let's just go ahead and create this tagged union quickly. So we have a structure event. This is going to contain our tag. The tag is event type. By default, the order is rejected. If it's accepted or anything, you'll change this. So that is the tag. This just tells us which member of the union is currently valid. The next thing we have is the payload. So you have union payload like this. Union payload. Payload is the variable name. And then it's a union, right? You can have either one of these fields present in the union. So let's say you have order cancelled and trade. Both cannot be active at the same time. It's either a trade or the order is cancelled. That's why we have a union here. So let's go ahead and have order accepted, order rested, order rejected, order reduced, order partially filled, cancelled, trade. So we have all of the participants of the union present here, and in any case, one of them is going to be true. So if order is rejected, the order cannot be accepted, right? If the order is rested, the order was accepted. Now we are back to the latest event that we need to send out, correct? So in any case, payload is going to contain either order accepted structure details or it's going to contain order rested detail, but it will never combine both of them or have two events that are used both the times, like have a combination of these fields. That's not allowed, or just have both of them true at the same time. So that's what we have. And some C++ experts might be wondering, why are we using a union here and not a standard variant like this? And the reason for that is variant is the modern C++ 17 type safe choice, and it would technically be the nicer choice, but there are two things that favor union here. First one is variant carries its own discriminator and runs no except checks. The union does not have all of those checks. It is leaner. The second thing is union keeps event trivially copyable, which means we can memcpy it through SPSC queues with no constructors or destructors running. Variant is trivially copyable only when all of its T's are trivially copyable, and that is fragile to maintain over time. That's why we're using union here. Okay. Awesome. Now the next thing we need within the structure is something like this. How I imagine everything is going to look like is something like this. So whenever the user wants to, by user, I mean the producer code, whenever an order needs to be made, an event needs to be sent, the producer code will be called, right? The producer code is basically the producer consumer that we have talked about before. So whenever the producer code calls something like making the event, what it will do is event make something like this. And then it can specify some sort of trade here. And if it specifies some sort of trade here, it will get back an event whose type is trade, for example. It will return this trade details, and then it will also have the type set to trade. So this payload.trade is going to contain the trades data, and type is going to contain the trade. Okay, so that's what I'm envisioning here. One make function that will make the event for anything. If, let's say, for example, instead of some trade, you say, okay, I want to do an order filled event. So it will make an event out of this order filled. So it will go ahead and populate the details of this order filled and return the type of this. Was this order filled, order rejected, what was it? So that's what I'm envisioning here. And to do that, we'll have to create overriding functions, right? Basically static factories that we'll have to create them. We'll have one for each event type. So we'll have one make for trade, one for order accepted, one for order reduced. It will take that through the parameter, create the event internally, and return the event. It needs to be static because we are returning the event here. Okay, so let's go ahead and create those functions. The first thing we have is starting event make order accepted. Notice we have constant order accepted value. It's constant. We're not changing the value of order accepted here. What we are trying to do is create an event out of this, populate the details, and also attach the event type. So let's go ahead and create an event here. The event will be, we have an event object. Now we need to populate its payload and its type. So we'll populate the type as order accepted, and then we have the payload.order accepted set to a value. Now we do the same thing for literally every order. We return the event, by the way, but then we do it for every event. So similarly, we have it for order rested, where we are like, okay, I have an event. This type is rested. We set the value here and we return the event. Might all seem like too much boilerplate code, and it is, but it will help us later on when you'll see we do event : make, and it will just make our lives easier instead of writing this every single time. Because if you write this every single time, you have 4 lines and we'll have to create events in multiple places because we have 8 event types. Accepted might happen in one place, rested might happen in one place, and it's all over the place. So we have one standardized place to do all of this and just abstract away the logic. Also, this is all centralized. So if you want to add a new event later on, all you have to do is follow the structure. As I said, makes it very extensible. Now quickly, let's do it for other events. We have order rejected. Cool. Order rejected payload is set. Let's quickly move on. I'll not explain any further. So we have order reduced. Then we have order partially filled, then we have order filled, then we have order cancelled, and finally the trade. And all of them constant, we're not updating them, and we've taken that by reference so that we can directly point this trade to the correct place. In every single one, by the way, we've taken by reference so that we can directly point it at that particular address. Because the compiler will usually just elide the copy and construct the event directly in the caller slot because of return value optimization. Nothing you should know about, but yeah, that's cool. Now let's just go ahead and have static asserts so that we know that each of these things, like the reason code, the event structure, the order accepted, the payload, basically, all of them are trivially copyable. Okay, so static asserts trivially copyable for each one. Reason code, event type, all of the events that could happen, and then and then the event structure itself. Great, so that is our entire events.h file, and suddenly Cursor formatted everything correctly. So now it's all on the same line. Okay, anyways, we have everything created now, and that sounds like a great thing to do. By the way, if you didn't want to write all of this, you could just copy it from GitHub. The link is in the description. So yeah. Also, one thing before we get into the order book, finally, yes, is we'll be returning in the order book itself. This is like a preview, but in the order book, what we'll have is something like this. So instead of having anything else, we'll have something like standard span constant event, and then we have or add order where you'll have some fields. And similarly for cancel order, you'll have the same thing. Similarly, you might have something for modify order, which will modify order reduced, all of that thing. Okay. Here you'll notice that every event or every operation here returns a standard span, which is basically a non-owning view over a contiguous array. Now, why are we returning the span, not a queue? The reason is that the event themselves live in a single reusable scratch buffer inside the order book, which is pre-allocated at construction, right? Each call here will clear the buffer, it will run, fill it with how many ever events the operation produced, and returns a span of length event count. So instead of having a queue, we just have a span here. And why exactly are we doing this? Because first of all, we have 0 allocation per call, because if you, instead of returning a span, you return a vector would either allocate per call, which is forbidden in our case, or it will force a custom allocator kind of thing onto the callers. We don't want to do that. The second thing is single ownership. The book owns the events, the callers borrow them until the next call. That just makes this lifetime obvious. If you don't understand it, don't worry. If this looks like standard C++, how else would you do it? Don't worry about it. This is just for people who are curious and they know a lot of C++. But yeah, we'll be returning span over the events because, as I told you, how the engine works on a very high level is you get an inbound order, you put it through the matching engine, and what you get here is an output order plus the event. So inbound order and output order is basically the same thing. What the matching engine is doing is mutating the state of this inbound order. That is the output order. And then it basically returns the event out of the order book. So output order is not really returned. It's coming in. They're modifying the state in the order book or the matching engine. And then the events are what's returned. And that's what we did with span. We are returning the events to the callers, the downstream consumers of order book or matching engine, so that we can have this entire event-based journaling and event sourcing that I described earlier to you. So yeah, having understood all of that, let's get into the big chunk of this tutorial, which is the orderbook.h file. There's a lot of things over here. The first thing that we're going to add is basically all the include statements up top, because I don't want to bother you by moving around in this huge file. And then we'll build up small helper types. Then we'll create our own monotonic buffer. We'll talk more about that. And then we'll get into building the order book and all of the related things so that our matching logic and everything is smoothly present in this order book. So let's get started. We'll quickly cover them one by one. Not quickly cover them, but we'll cover them one by one. Let's go. So let's get started by coding up the order book. Obviously, as things go, we're going to have our pragma ones first. Then we're going to have all of our include statements. So the first set of include statements that we have are related to C++ features. We have unordered map, span, optional, memory and memory resource. We have map, limits, functional, C standard lib, C standard int, C standard def, and algorithm. Now you might be wondering, why do we need unordered map and map? We'll talk about that in a moment when we get into initialization of the fields of the order book. We'll be using both map and unordered map, and there's a specific reason for that. Then we also have span. We've already understood we'll be returning the event span from the public functions. Then we're going to have memory and memory resource. We'll get into that when we talk about monotonic buffer. And that's just the next thing that we're going to work on after we create small helper functions. So the next thing we need is the files like level.h, events.h, types.h. We need all of that imports over here. So let's have them. Memory pool, events, levels, types, all of that over here. Okay, we've understood why we need all of these. There's going to be a memory pool of order and all of those things. Okay. The next thing we need is a namespace. Within this namespace of exchange matching, remember I told you there's going to be a mapping that we're going to create between the order book and the order and the order ID, correct? This mapping is going to be present. Well, this mapping is a bit of a lie because we're not going to directly store the order address. What we're going to have is the order ID that is going to map to something known as an order record. And what the order record contains is the order itself and the order status. Order status represents the last status of this order. So it will carry both the live pointer to the order object, and if the order object is not present, it's going to be a null pointer because let's say the order has retired, and it will also contain the last terminal status the engine had assigned. Let's quickly code that up. So we have struct order record. It contains an order pointer, null pointer by default when we're starting out. We'll populate it when we need it, and we'll set it to null pointer again if the status or if the order is not active anymore. Then we have last status, which represents the last terminal status the engine assigned. This second field is needed because it will power the order not found versus the order not active distinction that we talked about in types.h or events.h, sorry. So here we had order not found and order not active. I told you there's a difference between both of them because here we simply do not have the order ID. Here we have the order ID, but it was not active for some reason. And there can be multiple reasons. We've talked about that. Let's take an example to understand this. Say we have a cancel that comes in for an ID that has already filled. So let's say we have this 1, 2, 3, 4, 5, and we only have this order just to demonstrate why we need the second field. Let's say we only have this order, okay? And the order ID exists, and this order is basically a null pointer, okay? That just means that the ID exists, the order ID exists, but the order in reality is a null pointer. If this is the case, we will report that the order is not active. The order is not active because we knew this order ID 1, 2, 3, 4, 5, but the order itself is gone. If the lookup failed entirely, let's say the request for cancel 1, 2, 3, 5, 6 came in, the lookup here will fail because there's no ID with 1, 2, 3, 5, 6. Since it will fail, the order does not exist. The order is not found. We never heard of this ID. So that will happen. But if we have 1, 2, 3, 4, 5, we'll go ahead, do a lookup. The order is a null pointer. The order is not active. And this will only happen when the order has already filled. How do we know if the order has already filled or not? Well, that's done through order record, because order record contains the order. It also contains the last status of this order. And the last status can be filled. So we'll have to check that, yeah, the order is filled. The ID has already filled, for example, which just means like the order status is now filled. And then we'll be able to say, okay, yeah, the order is null pointer, the order is filled, and the ID does exist. So it's order not active. That's how it's helping us. Also, we have understood this. I'll move on to static assert of is trivially copyable for order record. You can do it at the end. You can do it over here. Doesn't matter. So we have done that. The next thing we have is price level view. So we also need a read-only snapshot of a level, right? So we need of a level, what kind of price is present for that level? What is the quantity present? So we'll have a struct for that too. We have struct price level view, a price and a quantity. This is basically a read-only snapshot of a level. We just want the price and the total visible quantity. The engine will expose a function like copy levels, which will fill a caller provided span with these views, and it will just help the external observers to inspect the depth without depending on an internal level layout. It's basically just a nice separation that we have, because internally when we are representing levels, it's an intrusive doubly linked list, right? External view should just be two things, because the external callers don't really care about, okay, do you have a linked list? Do you not have a linked list? Doesn't matter. What we do need is a price level view. That, yeah, this is the price, this is the quantity, this is what I care about. So we just get that out. And then we have a static assert for is trivially copyable of price level view. And actually, now that I think about it, this is only helpful in tests. So you don't really need this in our code because we don't have tests. Because in tests only, we are trying to expose out, okay, this is a price, this is a quantity, right? This is not going to be a part of map or anything. So if you want, you can just go ahead and remove it. I will do that once I've written down the other things, because I have like this Control-Z format which shows the code. But yeah, go ahead, remove this. This is only helpful in tests, because this is basically a nice separation, right? We are not exposing out the internal representation of doubly linked list. We just expose out a price level view that can look at a certain thing and give us the answer. That's helpful in tests, because why should I bother looking at the internal linked list and traverse over it and do all those kinds of nonsense when I can just look at this thing and get my answer? Okay, so feel free to remove it. This is just extra code for tests. All right, the next thing we want to get into is the monotonic buffer. And this is where you might start getting confused. So let me just explain it from the very start. What is the monotonic buffer and why do we need it? Let's start with the problem. Say you want to use a standard map for the price, correct? And let me zoom it in a bit. So we have this map, and in that map, what we need is something like a price to level mapping. That for this price, this is the level. The natural choice here would be something like standard, map, price, and then you have a level pointer, correct? The key is the price, and then you have a level pointer if you want to do this. The problem is whenever you try to insert a new price level value here, what will happen is it will allocate from the global heap, and every erase will return one from the global heap. And we said that we don't want to touch the heap, because maps by default, when they have insert or anything, they go and touch the heap. We do not want to touch the heap, and we've already understood the reason behind it. So what do we do instead of that? Well, we can use something known as a PMR, which stands for Polymorphic memory resource. The idea is very simple. These containers like map or any containers like vector or anything can be told that, hey, I want you to allocate from a user provided memory resource, basically a region that you can control instead of from the global heap. So whenever you use something like standard map, instead of that, you can use standard PMR, and then you can have something like a map here, or you can have an unordered map here, or you can even have a vector. Any kind of container can be passed in here. We're going to use a map and an unordered map. And then you can specify the allocation of the memory. Where should the allocation come from? Should it come from the heap, which is by default, or you can specify your own allocation of the resource? Okay, you can just go ahead and say, I want 1,000,000 slots that are available here, and this map should allocate on that 1,000,000 slots all the time instead of going to the heap and doing that thing that I talked about. So essentially, we are handing the map an arena that we own. So every insert or every erase will pull from or return to our arena, not the heap. And because of that, the allocation latency will become predictable because it's our arena. We can control it. And on heap, it's not predictable because of the reason we've already talked about. All the fragmentation, all the complex things that happen behind the scenes to make this thing work. Where did our thing go? I think it was this one, yeah. All of these complex logics that makes the heap non-deterministic and non-predictable. So to do this, we use the PMR, and it's pretty neat. It's a feature given by C++, so it's very easy to implement. Instead of using map, we just add standard PMR map, and then we can keep using anything that we want. What it does is it accepts a PMR memory resource at construction time. So we can just create our own memory resource, pass that in, and we'll always use that. The specific thing that we are going to use is called a monotonic buffer resource. So this is polymorphic memory resource, okay, PMR, but in that we are going to use the monotonic buffer resource. And it is the simplest possible PMR resource. It is basically a bump allocator. Essentially, every allocation just advances an offset pointer. So allocation is O of 1 and cheaper than even using our own pool. And the catch here is that it does not free individual blocks back into the arena. So when you call something like erase from a map that is backed by a monotonic resource, the map will call deallocate, but the resource will ignore it. So the memory is only reclaimed when the whole arena is destroyed. And this is an unusual property. It shapes basically how we use the maps, because in our case, for example, what happens is when a price level becomes empty, we do not erase its map node. We do not erase the key and the value associated with it. We leave the node in place with value set to null pointer. And we'll reuse it next time someone creates an order at that price. And we look at that later when we get into the deactivate level. This is what we're going to do. Instead of removing the node, let's say you don't need this node, you won't go ahead and delete this node, which is anyways not possible, or it is possible that you remove it from the node, but the actual allocation still exists in the arena that we are going to have, the memory allocation that we're going to do. It's still going to exist there. But in our case anyways, we just set this to null pointer instead of doing anything else. And whenever someone else creates an order at this specific price, we'll go ahead and update the level again. So anyways, in our case, this is going to exist. We don't need to free up our allocation. Now let's go ahead and define this class of owned monotonic buffer. You can just call it monotonic buffer, but yeah, I'll just stick with owned monotonic buffer. Within this class, we have a constructor which takes in the bytes. What are these bytes? We'll get to that. But other things that we're going to have in this is, first of all, this, a private unique pointer containing the storage. This owns the underlying bytes. So what will happen is that the constructor will allocate this byte array once and will construct the resource on top of it. What is a resource? Well, we are also going to have our resource. But before that, we have a storage here. Like the private variable is going to be a unique pointer, standard byte array storage. And what we do here is call make unique standard byte, and we're storing these number of bytes in that storage. So this just owns the underlying bytes. Then we are going to have our monotonic buffer resource that views those bytes as an arena that we can allocate. So we are going to create another variable here called PMR monotonic buffer resource. So these bytes that we have allocated now, just think about it. You have a storage, or let me just visualize this. You have a storage here. Within that storage, you have all of the bytes, and you said, okay, I want, let's say, 1 trillion bytes. So in this storage, you've stored, let's say, 1 trillion bytes. But this is just raw bytes array, correct? The storage is just a raw bytes array. What you want to do now is convert this bytes into a monotonic buffer resource so that you can pass it into the PMR, correct? Or you can use this as an allocator essentially. Because right now you just have raw bytes. You want to transform it so that you can use it within the allocator. So let's go ahead and initialize this resource. First property is going to be storage.get. So .get just gives us the bytes. The next thing we need is the number of bytes. So we pass that in because this is size t. The number of bytes have been passed in. And then the third argument is to the resource constructor. And then we just go ahead and set the standard PMR null memory resource. So what is this? Well, storage.get, you understand that is our buffer space, all the bytes. This is the number of bytes, which is the buffer size, standard C++. But this upstream is the upstream resource. So when the monotonic buffer exhausts its bytes, because for example, here we have passed in 1 trillion bytes to this polymorphic memory resource, correct? Okay, let's say this is the polymorphic monotonic resource buffer. I'll just call it MBR, monotonic buffer resource. So here, this is basically a wrapper around the storage of bytes that we get. You can think of it that way. Now what happens is the storage is of 1 trillion bytes. What happens if the monotonic buffer exhausts all of the bytes that are present in the storage? Typically, it would just fall back to the upstream, which is the global heap. If it cannot use any further, it will go ahead and ask the heap, oh, I want more memory, please give it to me. Instead, we say, hey, you cannot access the heap. You're going to have null memory resource here, which is basically saying that, hey, the fallback should fail loudly instead of silently allocating. If the arena fills up, we want a hard error, not something like a quiet heap allocation where it's just going to the heap, slowing down our entire process. We've already said there should not be a fallback to the heap whatsoever. So we said that. So now if we run out, we just throw an error instead of going to the heap and asking for more data. Awesome. So this is our monotonic buffer resource. Whenever we want to get access to the allocator, we're going to use this resource. The next thing we're going to have is the deleted instructions. So we are going to have our deleted copy, move, and equal to operations. All of those are deleted now. It's basically the same as before, whatever we have done. The arena will own the memory. Copying the owner would just lead to double freeze, and we don't want to allow that. Just a good developer experience, just in case that never happens. After that, we are going to return this resource because it's a private variable, right? I want this private variable to be exposed out, and I'll create a function that will just return the memory resource. Because as I said, if you want to do allocation, you have to get access to this resource. So we go ahead and have standard PMR memory resource returned. It's just resource getter kind of thing where we just return the resources. That's it. So this is our owned monotonic buffer. Again, just to recap, because this is very important, and we're going to create multiple instances of this monotonic buffer. How this works is you have a buffer resource, you have an allocator, your own arena that you control. You give it the number of bytes, you give it how it should construct. Right now, we are constructing the memory resource by using a very simple monotonic buffer resource that the PMR itself goes and gives. But later on, let's say if you find some problem with monotonic buffer resource, it's maybe slow or it doesn't satisfy your requirements, maybe you need more data than it can handle or something like that, you can just go ahead and swap this out with another resource. The external API still remains the same because you will be returning out some kind of memory resource, and then you can swap that out. It is your custom allocation that you control. As simple as that. We'll not allocate on the heap when using map. So now obviously, whenever we create the order book and we have something like map or we have unordered map, we'll have to pass this monotonic buffer resource or this owned monotonic buffer essentially, so that we can pass in the custom allocator to this, because the map still does not have a clue about, okay, do I want to go ahead and have the allocation on heap, or do I want to have allocation on our own arena? We have to mention that somehow to the map, and that's where we'll use this memory resource. Now let's get into the order book and specify all those details. So the very first thing is going to be the class template. So we have a template class order book. This template is going to contain multiple things. The first one is an order capacity of 1 million. At most, 1 million live orders will be present at any moment, and that is bigger than most single symbol books that will ever need, okay? After that, we'll have level capacity, which is 10,000. At most, 10,000 distinct prices are going to be present. Real books typically have a few hundred to a few thousand, so that's all right. Then we have our event capacity of 262,144. Basically, the Scratch event buffer can hold up to 256,000 events per request, and that is enormous. Even a market sweep through 1,000 levels with one trade each plus aggressor summary produces about 2,000 events. We are on the safe side because the buffer is shared across all the requests on this book, and a too small buffer would basically just abort the process, and we'll see why later on. The next thing we need is a stop capacity. At most, there'll be 65,000 parked stops. So these are our capacity constraints. These are more than generous, so we should be fine. The next thing we need is this, a bid map. What is a bid map? Well, bid map is basically a map that will sort the bids from highest to lowest. Let's get back to our order book. Remember, we are in the order book now. And in the order book, I told you there's going to be a bid map, which contains from the highest price, 150.3, 150.2, 150.15, to the lower price. So we need a map. And map is going to have a greater comparator because the map should sort, right? So let's go ahead and define bid map. Generally, we would just have a map of price to level to greater because greater is just a comparator. But now, since we're using polymorphic memory resource, we're going to have PMR map instead of just a map so that we can mention our custom allocator. So we have using bid map is equal to standard PMR map instead of just a map. The key is going to be a price. Then we are going to have a level as the value, and the comparator is greater because we want to sort the map from highest to lowest. So begin, whenever you try to do bid maps or bids.begin, it should give you the highest bid first. That's what we have here. Okay. So we have price to level, this price 150.3 mapping to this level, 150.2 mapping to another level, and so on. Great. Then we need an ask map similar to a bid map. So let's have that quickly. Ask map asks, and then you have using ask map is equal to basically the same thing, but instead of greater, you have less, because the map should sort from lowest to highest, because 150.25, 150.3, 150.35. We've explained that a lot. So let's move forward. The next thing we're going to have is a stop map, and stop map is something we've not talked about. Stop map is going to be stop buys. It's going to be a multi-map because there'll be multiple parked stops that can share the same trigger price. Basically, the stop map is basically this. Okay, let's say you say I want to do a stop buy of 150 shares at a specific price. What does that mean? That means you specified your trigger price of 150.10, and it just means that if the price rises to, so as soon as this trigger price is hit and it's below that or something like that, the stop buy will execute. And the point here is that you have a trigger price here and you want to store that somewhere in this order book, right? Because you do need a mapping between, okay, this was the trigger price and this is my actual buy order, correct? So this stop buys is going to have that. You're going to have a mapping between the price, the trigger price, and the order itself. Now, the thing here to note is that we don't need this to be ordered, so we don't really need to use a map. It can be unordered, but we don't really care about that either. The main point here is that map and unordered map, they can just store one key to one price, right? I mean, they can have one key to one value. They cannot have n keys mapping to one value or something like that. My point is that let's say you have a stop price at 150.1 for a specific order. Okay, someone else can also have 150.1 for a specific order. It doesn't necessarily mean that you need to override it, because in a standard map, what would happen is that you have two prices, two keys with the same key, like there are two keys that are the same, they cannot exist. So this order would just go ahead and override this order. Well, we cannot have that because the previous guy's order has just disappeared. So what we need is a multi-map, not just a map, because we can have multiple parked stops that can share the same trigger price. So in this multi-map, we are going to store the trigger price to stop order mapping. Simple. So let's have that. We'll have we'll have stop sells. We have stop buys. Obviously, we'll also have stop sells. And then we have using stop map is equal to PMR multi-map core price to order. That's the main difference. We have understood why we need this map. Just to summarize, we need this map because in the order book, we'll have to store somewhere that this is the trigger price at when we are going to buy. And we'll also have another map that just contains, okay, this is the price that we are willing to sell at. So if the price drops down to 150.1, we'll quickly go ahead and sell it out. Or if it rises to that occasion, whatever be the case, the trigger will happen at this specific price point. So this is for the sell, this is for the buy. These just contain the triggers. They're not really buy or sell. I mean, they will be there because you're buying or selling at a certain point. But the main part here is to store the trigger so that we can check with every order that comes in, oh, are we satisfying any of these conditions? If we are, let's just go ahead and do the stop buy, stop sell. Otherwise, we can go ahead and look at the rest of the things. So that's kind of the main logic here. And since multiple keys can have the same price and we don't want to override one value with another, we'll store multiple keys to multiple values. And there can be two duplicate keys there, but they can have different values. Okay. Or they can even have the same values. It doesn't really matter. But in general, it will be different because there'll be two different orders, right? Okay. The next thing we need is an order map. This just contains all of the orders that we have talked about, right? This mapping of order ID to order record. And we've talked more about that. So I'm just going to skip and I'll just get to the explanation of why this is an unordered map. That's because we don't need any order. If we don't need any order, we can just use unordered, because the main point that we need here is that the ID based lookup should be O of 1. In standard map, it's not really O of 1. In unordered map, it is O of 1. So we use that order map so that we can quickly get to the order. Okay, great. The next thing we need is some compile time computed constants. So what we need is basically the byte budgets for the PMR arenas. Literally, we want to answer the question of, hey, how big should each slab of memory be? Remember what we just decided. Every map and every multi-map and the unordered map in this book gets handed a monotonic buffer resource that's sitting on top of a fixed slab of bytes. Remember this thing that I talked about. And if that slab ever runs dry, the null upstream makes it fail loudly instead of quietly reaching for the heap. So getting these numbers right is very important, because if we don't, we'll start failing the order bug. The next thing we want to get into is how much allocation in terms of bytes should be given to each of these things: the orders, the stops, and the level, right? Because as I mentioned, this monotonic buffer resource stands on top of a storage. If you run out of bytes, it will fail loudly. And even though that is a better choice than heap in our case, it's not elegant. It will fail your entire application. You don't want that. The stock exchange should never go down. So what do we do? Well, we can make our best calculations to find out how big should each slab of this allocation memory be. Well, let's think about this. One thing to know is that map and multimap are implemented behind the scenes in C++ as red-black trees. You can search that up on Google. An unordered map is implemented as a hash table. The reason I say this is because basically all three of them, even if it's map or multimap, if you have map, multimap and maps are both implemented the same way, and unordered map is a bit different. Map and multimap are red-black trees, and unordered map is a hash tree and a hash map, you can say, kind of thing, a hash table, so to say. Okay, so red-black trees, you might not know them, you can search them up. Hash table, you already know them, it's just a mapping between the hash and the table. Good. Now, the thing to know is, despite both of them being, or three of them being a bit different, despite that, all three of them are node based. That means every time you insert one key, the container will ask its allocator for a small chunk of memory to hold that one node. So a tree node is the key, it will be the value, it will be the 3 pointers that stitch it to its parent and the 2 children. Because think about it, if you have any kind of tree, what you have is a structure that looks like this, right? And within that, you have another circle here, and then you have another circle here. Let's take this tree, for example. Okay, this is not a red-black tree. In red-black tree, there'll be another thing that I mentioned. But in a normal tree node, what do you have? Well, you have the key, you have the value, and there are 2 children, correct? And then you also have a reference to the pointer, because this guy also has a parent, right? Or this guy has a parent. So that's also stored. Also, you have a color bit because of the way red-black trees are implemented. There's red and black. So those are color bits. Realistically, it will be around 40 to 64 bytes in them on a 64-bit build. What we are going to do is we are going to use 128 bytes per node. The reason we keep this kind of like a big fat chunk of memory is that it has to swallow the allocator's own per chunk bookkeeping and alignment rounding. Plus, if there's any difference between how map and unordered map lay their nodes out. And we still have some room to spare. So we are very generous with what we have. And what we are going to do is say, hey, we want to reserve a room of, let's say, n nodes that will have 128 bytes each. So we'll have something like this. We'll have order index bytes, level index bytes, and stop index bytes. As you can see, stop index bytes is stop capacity into 128U. Stop capacity is 65,536. So each node here is going to have 128 bytes for them. We're very generous. Level capacity, we have level capacity 10,000 multiplied by 128. So we have level indexed bytes that many. And the reason stop index and level index bytes are, just 128 and this looks a bit more complicated is because look at it, level and stop. Stop is an unordered map. Oh, sorry, stop is a multi-map and the level index bytes is these two normal maps. And as I mentioned, they are basically red black trees. The way they store their data, they do not need an extra thing. Over here in order index bytes, you'll notice we have order capacity into 128. So that's the same as this kind of format. But we also add order capacity into 16. Because in unordered map, it's a hash table. Whenever you have a hash table, you have something like this, right? You have some sort of hash here and it refers to some sort of value. Hash and then value. So this is our hash table. A hash table just means that you need two separate pieces of memory, not one. The first piece is the nodes, the value, which is the same case as the red-black trees. But a hash table also needs to keep a bucket array, which is just a flat array of slots where each slot points at the chain of nodes that hashed into it. Whenever we call something like orders.reserve, and let's say in our case, we're going to do this, we have something like order capacity. What happens is that we're telling the map that, hey, we want to size that bucket array to comfortably hold 1,000,000 entries now. So you never have to grow and rehash later. So that bucket array is a whole separate allocation that we have done. The 128 is per node allocation, similar to what we had for the red-black trees. And this 16 is for the bucket array for our hash map or hash table, okay? And you might notice that none of these numbers are computed from a precise value. Like we're not doing size of node and we're just putting in rough values here. The reason for that is we are being generous, and we are being generous very intentionally because there are two failure modes that can happen. The first one is that the slab is too small, which means there will be a hard crash in the middle of matching a trade. And another error that can happen is that the slab is too big. That means a few megabytes of virtual memory that just sit there unused. So given that choice, we just round up and move on. Now let's go ahead and define the constructor where we just reserve everything. Remember, we've created our maps. We still don't have our monotonic buffer resources created. So we'll have to create them. And initialize them in the constructor. So we'll have, also we have a symbol. I forgot about that. What symbol are we trading for this order book? And an order book will have one symbol and we'll have multiple order books. And each order book will be for a symbol, right? I mean, you cannot have an order book that contains data about NVDA and APPL at the same time. Like in the same order book, you cannot have both of them. It's just messy. What you have is one order book for one symbol, then you have another order book for another symbol where you maintain all of these things like the bids, the asks, the stops, all of that. Otherwise, there'll be confusion and you might just interchange what's trading for NVIDIA and Apple. Now let's go ahead and have the constructor of order book, or even before that, I forgot about it. We need the owned monotonic buffer where we have the order index buffer. Then we need the bit index buffer. Then we need ask, stop sell, all of those things, because you have a map here. Each map will have its own monotonic buffer, which we'll assign, and you'll see how we assign that. I hope this is all clear to you. These are all memory allocations. These are all maps, and these memory allocations will go within this map. Another thing we need is the event storage scratch space. I told you that we're going to store all of our events within an event storage. We need that. So we have a unique pointer of event array, which is the event storage, our scratch storage where we store all of our events so that if you want to do auditing or any of those things I talked about, you can do it. Now it's all coming together, I hope. Now finally, we'll get to the constructor. So the constructor goes like this. You have a public explicit order book. It takes in a symbol because you need to know what order book you've initialized for, like what symbol have you initialized this order book for. And then you can go ahead and assign the values. The very first value is going to be symbol of symbol. So this symbol value gets its value. The next thing is the order index buffer. We are trying to create a monotonic buffer, right? Now imagine this monotonic buffer requires a byte size, the number of bytes that should be assigned. And we have calculated that byte size over here because we have our order index bytes, level index bytes, and stop index bytes. So what we're going to do is order index buffer and pass in the order index bytes, whatever we calculated. And notice, this order index buffer will go within this orders map because this is for the hash table. Then we have the bid index buffer, which has the level index bytes, which will go within this bid map. Then you have ask index buffer, which again has the level index bytes, which will go within this ask map. Then you have the stop by index buffer, which will go within the stop, which has the size of the stop index bytes, and it will go within the stop map. Then you have the stop cell index buffer, same thing, not getting into that. Now we need to go ahead and have the maps having this memory resource passed into them, correct? We have our map, we need to assign these memory resources to this map. So we have bids where we specify that the first thing we have is greater core price. This is just the comparator. The first argument is always a comparator. The second one is the memory resource, the PMR resource. Where should it pull its memory from? The next thing we have after this is the same thing for all of the maps, right? This is the same pattern. Comparator, if there is, and then you pass in the PMR resource. Then we have ask where you pass in less and then you pass in the PMR for ask index buffer. Then you have stop bys where you have stop by index buffer dot resource. We have not specified the comparator here because stop bys is an ordered map, or sorry, stop map is a multimap, and here we do not really specify how we want to sort it. We don't really care about sorting this map. Then we have stop cells, same thing. Then we have the orders where we just pass in the order index buffer dot resource. And finally, we're going to have our event storage, where for only in the constructor of this order book, which is being initialized before the hot path starts, you can call make unique, and you have a small scratch space where you can write the events. And this event storage will be used by downstream consumers to look at the events and all that sorts of things. Now inside this constructor body, we are also going to call orders.reserve order capacity. So this orders contains the number of bytes that we told it to. So we have something like this, where we have a monotonic buffer resource for this specific orders. Okay. Whenever we want some data, it will be pulled out of this storage. Another thing that we're doing is calling reserve of order capacity on it. So we are pre-sizing the hash maps bucket array so that the growth will never reallocate. Yes, that's true. Even with the PMR arena, unordered map will internally request more memory if its bucket count grows past the load factor threshold. So reserving it upfront prevents all of that case. And we only do this for orders because order is the only one that is an unordered map. Only in unordered map, it will internally request more memory if the bucket count grows past this specific threshold that we have. So we have just went ahead and said, hey, I just need these many orders reserved upfront. So after the constructor returns, the book is ready to receive its first order. Everything that the hot path needs is allocated. So you don't have any more heap, you don't have that arena growth, you don't have any surprises, it's all predictable. And similar to our owned monotonic buffer and all of the classes essentially we've created, we'll have our move, copy, deleted completely. Because a book is uniquely owned by exactly one matching thread. Remember that, a book, an order book, is uniquely owned by exactly one matching thread. If we copy or move it, it would invalidate every pointer and iterator that we hold, causing problems. Okay, so we went ahead and created everything, so we are ready for the hot path. Now, what are the operations that are possible in the hot path? That just means what are basically the public APIs that are offered from this class. And those are add orders, cancel orders, and modify orders, correct? If you have an order book, what would you like to do? Well, I would like to place an order to this order book. So you add an order. You would like to cancel a specific order, or you would like to modify an existing order that you've already placed. So yeah, we'll start with that. The very first thing we'll start with is add order. Whenever we add an order, what should happen? And this is going to be pretty big, but you'll kind of get the whole idea of how the order book is arranged. And then we can get into the other functions, which might seem very similar to this, have similar logic, but you'll get kind of the mindset of how it should be. So let's get into the add order function. Before moving on to the add order function, the one thing I forgot to do is add a private. All of these variables, they're going to be private. So let's just add that private here. And then we can go ahead and add our first public function called add order. All it does is adds a new order to our order book. Let's go ahead and add that. But before that, we need these variables: best bid, best ask, order pool. So this best bid is going to be in the level, what is the best bid? We'll go back to our order book. Here we have a bid, right? What is the best bid order level? Correct? That's what we are storing. What's the best ask level that we are storing? Though all of that is going to be present. And then there's going to be an order pool. It's going to be of the type of memory pool. And from here, we are going to add or remove the order. And that's why we had created the memory pool in the first place, so that we could add and remove the order from the order book in O of one time. And the size of that is order capacity, which is 1 million. Okay. So we're all set with the variables. Now let's just go ahead and add that function. You'll see how these are used, but we just have those variables in now itself. The next thing we have is also event count. We are going to reset the events because we have the event storage here. We'll also have a variable that keeps track of all the event counts, the number of events that have taken place. We increment it by 1 every single time. And whenever we want to reset the events, we'll just set the event count to 0. That's all. All right. The next thing we want to do is create the function, add order. Like every other public function we're going to create, it's going to return a standard span of event. It's called add order. And it's going to take all of these things: order ID, price, quantity, order type, timestamp, participant ID. Trigger price by default is 0 because it's only present when there's a stop order. And then there's display quantity for iceberg orders. So we are accepting all of those information pieces from the parameter because the user will have to specify that so that we can do some kind of work. Cool. The next thing we want to do, the very first thing, is clear the scratch event buffer. So as I told you, we are going to be using one event buffer for every call that's present. Before we add an order, what we're going to do is ensure that the event buffer is empty so that we can add more orders to it, correct? And to do that, all we need to do is reset the event count variable that I created at the very bottom, okay? So coming back to this function, what we're going to do is create a function called reset events. It's going to be a reusable function because it's going to be used many places. And there, we're just going to set it to 0. So let's have reset events function. And then in the private part, we can create this reusable function. In the public, we're only going to have our 3 functions: add order, modify order, cancel order. In private, we're going to have all of our helper functions. So we have the events created. Events is basically something that we're going to use in the very next if statement. What it does is it returns a standard span of events. It's just, creating a span from the event storage. So if you notice, event storage is a unique pointer event array, right? We want to convert it into a span. So what I've done is created standard span of constant event, passed in event storage.get, and the number of events that are present in it. That's why we needed event count. And now what we can do is just set the event count to 0 by creating this reset events function. And we do that using this void reset events, event count is equal to 0. So with this, we've set the event count or reset all of the events that are present. And now whenever we want to return a span of events, all we need to do is event storage.get event count. And event count will be reset to 0. So if you have reset everything, events will be empty. Otherwise, it will be of the specific, number or the capacity, whatever. So yeah, we have that in place. All this is doing is converting the event storage array into a span. And again, the reason we needed reset events here is so that we could remove the old events from the previous call because they're garbage values. The buffer will override them as the new events will get appended. So once we have set this to 0, what will happen is we'll go ahead and in the next add order, we'll try to add the event. Okay, so event count at 0 will be filled. Then event count at 1, event count at 2, let's say. All of those are filled. Then add order is again called. So we reset the events. So its event count is 0. And now we'll do, let's say we again store through the event storage as event storage at event count. And since we have resetted it to 0, it's going to be event storage at 0 is equal to some event. So we have overridden the previous value and we only get the values that we have recently modified because event count will be incremented or decremented based on what we have added, right? And we only create a span out of those. So we don't need to call .clear on event storage array because that would anyways take a lot more time compared to what we're doing right now. Just overriding and only touching the values that we need. The next thing we want to do is validate that it's a new order, right? So how do we go about doing it? Well, we can create a helper function that's called validate new order. And if the order is new, it is going to return a null pointer. But if it doesn't return something, it's going to return a reason code. The reason code that we had defined in events.h, the rejection reason, right? Because if the new order is not validated, that means it's rejected. So we want to emit a rejected event. So let's have that created. We'll have an if condition of if constant auto reason is equal to validate new order, and we pass in the order ID, side, price, quantity, order type, trigger price, and display quantity. We're not interested in the timestamp or the participant ID because to validate a new order, we don't really care about these two things. All we care about is these things because they are related to the order. So if this reason has a certain value, it will get into this if condition and execute what we have further. If it does not, that means it was returned a null pointer and therefore we do not have any rejection. It's a new order, so we can proceed further. Now let's go ahead and have a validate new order function created, and its return type is going to be optional because it can return a null pointer, right? And it is also going to have the reason code return. So that's going to be the return type, okay? Let's go ahead and create that function, validate new order. It returns a standard optional reason code. Then we have the validate new order. We'll have the order ID, the side, everything that we accepted above. We're going to have all of them over here. All right, now how do we know if it's a valid order or not? So the first thing we'll have to check is the quantity equal to 0? Because if the quantity is equal to 0, it's never a valid order size. So we can skip that, right? So that's the time we'll go ahead and return 0 quantity. So essentially we need to have checks for all of them. Let's go ahead and check it. If quantity is equal to 0, we'll return reason code 0 quantity. Next thing we have is, let's say, duplicate order ID. Duplicate order ID means if we already have an order with this ID, it doesn't matter if the order is live or retired. If there's a duplicate order ID, we want to reject it because it's not a new order. It's an existing order, so you cannot call add order on it. What we need to do then is check if the orders, this is the orders map that we had, and if the orders map contains the order ID, then we just go ahead and return duplicate order ID. Make sense? On to the next one. Next one is specific to limit prices. So the thing about limit prices, if it's a limit order, if it's an IOC, FOK, GTC, stop limit, iceberg, post only, all of them require a price. What don't require a price is market and stop orders. So that means we need to check if they have a limit price set. That means we need to check if their price is greater than 0. If the price is greater than 0 for the types that I just mentioned, then it's valid. Otherwise, it's not valid. So let's have a variable that contains all of these orders. We'll just call it requires limit. So we have constant boolean requires limit price. So obviously limit requires limit. IOC requires limit because you'll immediately fill it or cancel it at a certain price. Then you have fill or kill. Similarly, you will either fill or absolutely kill that order. Then you have good till cancel, same as the above two. Then you have stop limit. It itself says stop at a specific limit. You have iceberg, which goes on until a specific listed price. That's the kind of the display price. And then you have the post only, which is just to provide liquidity to the market at a specific limit price. And then you'll just remove it from the order book, but still it requires a limit price. So let's go ahead and check if these things have a limit price set. So we can check if requires limit price is true, that means it's any of these orders, and the price is less than equal to 0, we'll return negative price. That means that the price should be greater than 0. It cannot be 0. It cannot be less than 0, obviously. And if that's the case, we can have negative price. Awesome. The next thing we need is that the stop orders must have a positive trigger price. So we have checked the price. What about the trigger price? So stop orders should have a positive trigger price. We'll check that. So if the order type is equal to order type stop or order type stop limit, and the trigger price is less than equal to 0, we'll say negative price. This is a bit confusing because negative price is like given to 0 as well. If your price is 0 or trigger price is 0, you still get negative price, but that's fine. If you want to be more correct in a way, you can just go ahead and add that extra condition, also add the reason code in events. Better auditing, obviously. So this gives us the condition that the stop orders have a positive trigger price. Other ones do not need to have a positive trigger price because positive trigger price would mean that there's 0 that's present, right? I mean, negative price in our case includes 0 and negative values, and positive price means it's always greater than 0. But if you do not have stop orders, what will happen is by default, the validate new order will get a trigger price and the trigger price will be 0. And you might run into some sort of error, or you will run into an error because if you have, let's say, a market order and the trigger price is 0, you just return a negative price error, and that's not correct. Awesome. The next thing we want to do is have a display quantity for the iceberg order, because we know iceberg orders always have a display quantity which gets filled and then you refill the price or refill the quantity. So we'll have iceberg's display quantity and it should be within a specific group. It should be 0 till quantity like this. That means it must show something, but it cannot show more than the total quantity that you have. Okay. So let's have that. We'll have if order type is iceberg and the display quantity is 0 or the display quantity is greater than the quantity itself, we say invalid iceberg display. Because think about it. Let's just imagine an iceberg. Let's say this is kind of the sea level where you have an iceberg, correct? A small part is visible here for the iceberg, correct? When you have the small price that's visible in the iceberg and then you have the rest of the things underneath, what's happening is that if you specify the display quantity to be more than the actual quantity that you have, this is the actual quantity. And if your display quantity is more than the actual quantity, that's wrong. So that's the check we are trying to have. Okay. So let's just remove this and come back to our order book. Cool. We've understood that. The next thing we need is that we need to mark it against empty opposite side. So that means we need to look into the book empty, that the order book is empty. Okay. And to do that, we'll have to add another if condition. If the order type is equal to market order and the opposite best side is a null pointer, then we have a book empty. Because think about it, what does a market order mean? Market order means I want to buy 200 shares. It does not guarantee that you'll have the best price that's available, but it will ensure that you will have everything filled out very quickly. So it's just a fast way to buy or sell things, correct? And to do that, we first have to ensure that the opposite best level is present. That means if your buy order is present, there needs to be a sell side. If you have a sell market order, then there needs to be a buy present. Because if it's not, that means you have an empty side, an empty opposite side. So if you have 150.3 or market shares do not have that market bias, let's say you market buy for 200 shares and there's no sell side that's present, you will give out an error, correct? So that's what we're trying to do. Let's just create this opposite best level. And the way to do that is just checking. If the side is equal to buy, then the opposite best level is sell. And if you are at sell, then it's going to be buy, okay? Let's create that function. It's going to return a constant level pointer. What's the opposite best level? And then we just check this side. And then what we'll do is return side is equal to buy. If it's buy that your side is, that means you want to buy something. The best opposite level is going to be the best ask, correct? Let's say you said, I want to do a market buy of 200 shares. What's the best opposite level that you're going to get? Well, the best opposite level. To find that out, you need to find what is the opposite level. The opposite level is sell. And what is the best sell? Well, we're tracking that. We're tracking that in this best bid and best ask. That's what we'll do. And these are null pointers initially, but we will update it in add order, in update order, in cancel, all of them. Okay. So don't need to worry about it. You can guarantee that it's going to contain the best ask and the best bid. We'll see that when we add an order, because when we add an order, we'll have to update what is the current best level that's present, right? So we have the opposite best level now. And if we go back to our thing where we said if order type is equal to market and the opposite best level is equal to null pointer, that means there is no opposite best level, the side is empty. Because only when the side is empty, you don't have a best level because you don't have any level. And in that case, we'll just go ahead and return the book empty reason code. The next thing we need is post only that would cross. That means you have a post only order. Post only orders are meant to add liquidity to the market. They're not actually allowed to execute and trade against the system. So we'll reject it if there's a post only order that would cross the system. That means there's enough liquidity in the market that the post only came in and it could instantly be traded. So we are like, oh no, you cannot trade it. Let me just reject you before allocating anything, just to be sure that the trade never happens. And to do that, we can just check if the order type is post only and it would cross, we'll have to create that price, or we'd have to create that function. Then we'll go ahead and return reason code post only would cross, right? Because if we let it execute, it would cross, and the entire point of post only is not to trade. We're giving that guarantee. So we have that would cross function, and we'll have to create that would cross function for post only. It's actually a pretty simple function. Let's create that function. We have Boolean would cross. We take in a side, if you're doing a buy or a sell, which one is it? And at what price is that happening? Now, how would you go about checking if the post only would cross? Well, think about it. If you have a buy coming in at $150, it will cross if there's an ask at $150 or below. If there is a sell coming at $150, it would cross if there's a bid at $150 or above, correct? So to do that, what we'll have to do is check the best opposite level that we have, right? If you have a post only order for buy, let's say you have let me write it down. You have post only buy of, let's say, 100 shares at $150. That means you're willing to buy at anything that is 150 or less than $150. So what we will have to do is check if what's the best opposite level. If the best opposite level is even present, then you can check if the price is less than equal to that price. Correct? That's all you need to do. So let's have that condition in. First, we need to get the best opposite level. That means we'll again use that function of opposite best level that we created. And we'll have something like this. Constant level, best opposite level that we have is equal to opposite best level. So if you have a buy of, let's say, stop buy 150 shares at 150.10 or $150, sorry, what you'll do is find out the best sell level that's present. Once you have that, you want to check if it's a null pointer or not, because it can be the case that it's a null pointer. If it's a null pointer, then we want to return false because it wouldn't cross, correct? So that's good for us because the post only is giving us liquidity to the market, right? So we'll have if best opposite is equal to null pointer, we return false. If the side is, let's say, buy, then what we want to do is grab the best opposite price and then check if it's less than equal to this price. Because again, think about it. If I'm saying I want a post only buy at $150, it will only cross if there's an ask at 150 or below. So all I need to do is check this. If the side is equal to buy, that means I'm willing to check if it is less than equal to 150. If it is less than equal to 150, that means we have a crossing. If it's not, then we don't have a crossing. So we just return that true or false value based on this, correct? Otherwise, the side is equal to sell. And if it's sell, then we'll do the complete opposite. We'll do if it's greater than equal to the price, right? So we'll just do if it's a sell, return best opposite price greater than equal to price. Because a sell at 150 would only cross if there's a bid at 150 or more. So if the best opposite price is 150 or more, then it would be true. But if it's not, then it's false. I hope you've understood this. This is the concept of crossing. And we instantly reject it if post only would cross. Okay, awesome. Now we can get back to the next one, which is checking if the new order is validated or not, because here we've completed our validate new order, right? We've checked for post only would cross as well. Or actually we have one more thing we need to check, which is that the fill or kill market or fill or kill order that's present cannot be filled in full. So what you want to do here is, let's say you have an FOK order of, let's say $150.3. It's a buy order. And let's say you want to do it for 400 shares. So it goes here, checks, oh, is there 150.3 or lower price that I can get? So it sees 150.25. Okay, that's good, 150. Then you have 200, so 350 shares. And then it's 150.35. You cannot do 150.35. And that means you only have 350 shares, not the entire 400 shares that you asked for. That means the fill or kill cannot be done because you either fill it or you kill it. So since we cannot fill it, we need to kill it. And since it cannot be filled in full, what we need to do is reject. So to do that, we'll have to create another one. If order type is equal to FOK and the available liquidity is less than the quantity, we just reject. So we need to create a function that will check what is the available liquidity given the side and the price. The side is required because if you have a buy FOK, you'll check the sell side. If you have a sell, you'll check the buy side. And based on that, you'll try to find out what the available liquidity is. If it's less than the total quantity that's present, we'll reject it. So let's create the function available liquidity here. What it will return is a quantity because of course we are comparing with quantity even above. And then we'll have available liquidity, we have side, we have the limit price that's passed in. Now, as I mentioned, the next thing we want to check is what is the side, right? If it's a buy order or a sell order. And even before that, we need to return a quantity, right? So we'll have to create a variable that keeps track of the quantity. So we'll have a variable called available. What is the available liquidity or the available quantity that's present? And it's an unsigned in 64 value. After that, we'll just go ahead and check if the side is equal to buy. If the side is equal to buy, we'll go over all of the asks that are present. Now in the order book, where are we storing all of the asks? Well, if you scroll down, we have created an ask map that keeps track of all of the ask prices to their levels, right? So all we need to do is traverse over this asks map and check if we have enough quantity. So let's go back up where we have the available liquidity function, and here we'll go over each of the price and level in the asks map. So for constant auto price level, price is the key, level is the value. In asks, we'll try to check. Well, what are we trying to check? Well, first of all, is the level equal to a null pointer? Because as I've mentioned before, whenever we are storing in this ask map, let's say we are storing a map, right? In that map, if we do not have any level value for that price, let's say the quantity was exhausted, the level is now gone. I told you that what we'll be doing is storing a null pointer instead of completely removing this key. The reason we'll do that is because of our PMR, right? The way our monotonic resource buffer works, remember that you can just go behind and watch it again where I mentioned that we'll be storing this level and what the reason for that was. So yeah, we'll check if the level is equal to a null pointer. If the level is equal to null pointer, we can continue. There's nothing at this price point. Let's go to the next price point. The next thing we'll check is if that price that we have, if it's equal to, if it's greater than the limit price. That means you have, again, a filler kill for $150.30. So let me type it out. Filler kill of buy 400 shares at $150.3. That means you go over this 150 shares at 150.25. Well, that's available. How do I know that's available? Because the price that's listed in this map of 150.25, that should be less than or equal to this price that I've listed, correct? 150.25 is less than 150.3. That's good. Or we have 150.3, which is less than equal to 150.3, which is also fine. But if we have something greater, then we have a problem. So what we'll check here is if the price that we have in this map is greater than the limit price, then we break out because that's invalid. This is basically the end of it. Because remember, asks is an ordered map, correct? When it's ordered, let's say 150.25 filled, 150.3 filled, 150.35 filled. Well, 150.35 cannot fill for 150.3 because it's greater. We break out. We calculate there's only 350 shares. Because we know even if there was a 150.4, it wouldn't satisfy the conditions of 150.30 because it's always increasing order, it's ascending. And that's why we check this. If the price is greater than the limit price, okay, we have exhausted the available quantity, let's break out of it. And let's say if these two conditions are not satisfied, that means we have a valid thing. Let's just add the available quantity from this level into this available variable. So we'll have available plus equals level dot total quantity. So whatever is the total quantity listed, 150.25, let's say it had 150 shares, 150.30, 200 shares. We add both of them. Available is now 350. We'll check later on about the main thing. But yeah, we are just calculating the available quantity here. So this was for the buy side. Now what happens if a fill or kill for sell of 200 shares comes in? That means we'll have to do the complete opposite. So we'll have an else condition here and we'll do pretty much what we have here, except instead of having asks here, you have buy. Instead of having greater than limit price, you have less than limit price. So we'll have else and then this thing. So for constant auto and price level, we go over bids. That means all of the orders that are listed here. Then we check if the level is equal to null pointer, classic, we continue. If the price is now less than limit price, we break. Because if you have a FOK cell of 400 shares at 150.30, you're like, okay, 150.3 compared to 150.3, that is equal to, we're fine. But if we had something like 150.40, that would also work because you're selling at 150.3. What you want is something greater than you because you want a profit, right? So you'll be like, okay, 150.3 and someone is willing to pay me 150.40, that's good. But when you go to the next one, you go to 150.20, you're like, okay, 150.3 compared to 150.2, someone's giving me lower than what I want. Well, we reject it. That's what's happening here. If price is less than the limit price, we break out. And then we add to the available if these two conditions are not satisfied. Okay, we have all the available quantity now. If it's a sell or a buy, it doesn't matter, we have it. The next thing we want to do is give out the available liquidity that's present. Now the thing is, available liquidity is of the type of uint64t and quantity is of the type of uint32t. To fix that, what we're going to do is return static cast quantity. We'll take the minimum. So the static cast is pretty much, okay, like whatever is present here, you anyways just convert it into quantity. Then we are taking a minimum value of the available and the max quantity limit that's allowed. So quantity is uint32, right? Whatever is the minimum value of the uint32, we're going to take that so that we don't have an integer overflow error. And whatever is the minimum between these two, we'll take that. If available essentially exceeds the uint32 limit, we'll just return the uint32 max level. That's very unlikely to happen, but it's just a case where our stock exchange does not crash. So we've handled that. All right. So we have the available liquidity as well. And if there is the available liquidity less than quantity, that means we just don't have enough liquidity. FOK needs to be shut down. So we'll return FOK insufficient liquidity. Otherwise, we'll return the null OPD, and null OPD not null pointer because we are anyways returning an optional value. So null optional is returned. Awesome. So we have validated a new order. Now, what if the validate new order is false? That means like the reason is present. That means it was rejected. If it was rejected, what we want to do is emit a rejected event in our scratch event buffer. So this event storage will now get a new rejected event to it. And then we'll return out all of the events, right? Because this is not necessarily the first time that something's happened. So what we'll have is emit rejected. We'll have timestamp, order ID, and we pass in the reason. And then we return the event. But before that, let's just create the emit rejected. It takes in a timestamp, the order ID, and the reason of why it was rejected, because we have to add it to an event, right? To our event buffer. Now within emit rejected, we are going to call a function called push event, and this push event is going to be reusable function. So this is just the emit rejected event. We'll also have emit accepted event. We'll also have other events that we have specified here, like rested, reduced. Now whenever we have all of those events, we'll be pushing to our scratch buffer, the event storage that we had. Now, whenever we do that, what we want to do is do the same thing, right? I mean, you'll be storing to event storage and increasing the event count. So why not just extract that into a reusable function? And in the push event, all you need to do is pass in the event with these details passed in. Okay. So let's have push event here. It just takes in an event. So here you'll have to create an event object and pass that in. And what it's going to do is event storage at event count ++ is equal to event. What does that mean? Well, event storage at 0 is equal to event, and then you've incremented. So the next time push event is called, it's event storage at 1, and then 2, and then 3, and so on. Now, another thing you'll have to do here is check if the event count is greater than or equal to the event capacity. If it's greater than this, that means we cannot have more. Let's abort. It's an unlikely condition, which is doing all of our optimizations that we've talked about. Then we'll just abort. So that's all. Now let's call emit rejected here, and we'll pass in the event make. Remember this event make where I mentioned that all you need to do now is just create this thing. So event make will, and then you pass in, let's say, order rejected, order accepted. You just pass it in and it will create all of these things. And since it's overloaded functions, that's great for you. So let's have order rejected here, and order rejected, what does it require? Well, sequence number, timestamp, order ID, and reason code. We don't have a sequence number. We'll create that in sequencer. So what I'm going to do is for now create a function called next sequence, and that will be created within the sequencer. And we'll remove this error once we get to the sequencer in the next tutorial. So let's have sequence number equal to next sequence, and I've added it to do here that we want to add the sequence number when the sequencer is added. Then we'll have a timestamp, and then we'll have the order ID, and then we'll have the reason code. Awesome. So we have pushed the event, and that just means we have emitted the reject thing. Now we'll go back up and return the events buffer, because yeah, we rejected the event, we've added it to a scratch buffer, and now we just want to return this span of event. So we are returning this event of span event storage.get event count. Done. The next thing is, well, we validated the new order is present or not. We only move forward now if it is a new order. If it is a new order, I want to construct the order. And to do that, I'll have to do order is equal to order pool.allocate. That means from this memory pool, we are adding one order. So let's go back to the main thing where I had described what the pool is going to be like. And it was this thing, intrusive lists. This was the memory pool. You take one element when you allocate, and when you deallocate, you put it back into the memory pool. So that's what we have here. And when we call order pool.allocate, we are taking one slot out of that intrusive linked list, and that's our order. And I told you that in allocate, what we are doing is just giving out a node, and that node is going to be cast as whatever is the T. And in our thing, the T is the order object. So right now, the order object does not really have anything, because remember, this was a free node. And what we did is just casted it as an order node, but it does not really have the content of the order. So we need to construct at that specific point. And I told you that the caller of this order pool.allocate is the one that's going to pass in the order details. So what we're going to have is if order is equal to null pointer, which is highly unlikely, we'll just emit rejected, pass in the timestamp, order ID, and the reason is that the order pool is exhausted. Cool, that's a preventive measure, unlikely to happen, as we have discussed many times before. Then we return the events, and then we go ahead and calculate the peak quantity, because it's required when we try to create an order object. Because when you try to allocate and create an order instance, you need to pass in all these things. We have majority of them. What we don't have is peak quantity. So we have that. So the peak quantity is defined as this. If the order type is equal to iceberg, then the peak quantity is going to be the display quantity, because you can only share orders of that much quantity. And if it's not iceberg, then it's 0, because it's anyways useless and won't be used in any of our calculations. Now let's go ahead and construct the object. So we have order is equal to construct at, then we pass in the order. So all we're doing is construct at order, and then we're filling in the details of that order. And this construct at is going to return an order that contains the filled in order details. So we'll have that passed in here. And then we can have order like this, where we pass in all of these things. So look at the values here. You have ID is equal to order ID, side is equal to side, price is equal to price, quantity, original, display, hidden, timestamp, type. The status is set to new because it's a new order that's come in. Then the participant ID, the trigger price, and the peak quantity we just calculated. What I want to focus on is this display quantity and hidden quantity, because these are just placeholder values that we've passed in. Display quantity is equal to quantity and hidden quantity is 0. Now we're going to create the next function that will prepare the visible slice for the iceberg orders. What it will do is do the iceberg split as we know it, because we want to ensure that the display quantity, hidden quantity, and the peak quantity, original quantity, they're all set to the correct thing for our iceberg orders. So let's have that function created called prepare visible slice, where we pass in this order. Now let's create the helper function of prepare visible slice. We'll take in an order reference, and now we can check. Well, the first thing we want to check is, well, if the order is iceberg or not, because if it's not an iceberg, why are we doing any of these? Because display hidden quantities only matter when it's an iceberg order. They're not used anywhere else. Anywhere else, they don't have the concept of display or hidden quantities. So we'll have if order type is not equal to iceberg order, then we'll just have order.display quantity is equal to the order quantity. That sounds good. Okay. And the hidden quantity is going to be set to 0. It does not really matter what you mention here, but we're just ensuring that it's set clearly. If you want, you can just return from here. I've still ensured that it's set to these values, but if you want, you can just do return and it will still work fine, because above we have set this to display and hidden quantity to 0. Okay. So we've returned. Now, if it's an iceberg order, what do we want to do? Well, the display quantity is just the minimum value between the actual quantity and the peak quantity. So we can set that in. Order.display quantity is the minimum between order quantity and the peak quantity that we've already cleared off above when we created the order for the first time, right? Let me go back to this peak quantity. Yep. So we have had the peak quantity set up properly, and we can use it over here. So if you have, let's say, a 10,000 share iceberg order with the peak of 500 shares, that just means that you are willing to trade 500 shares in this particular order. So the display quantity is just the peak quantity. But what if the peak quantity is always constant, right? Let's say you have 10,000 shares that you're willing to do in the entire lifetime. Entire lifetime is the total quantity, correct? So you have the quantity, which is the total quantity, and 500 shares is the peak quantity, which just means that at any given point, the order will only be able to trade 500 shares. Not 501, not 600, not 400. 500 at its peak. So when you have a trade, it will be that you have 9,500 shares more, right? And then you have another 500, so 9,000, and then 8,500, and so on. Towards the end, you'll start going to 500 shares, right? And when you're at 500 shares, you can only do peak quantity of 500 shares. But what if you are at 499 shares? Right? There can be a situation that exists because let's say the entire lifetime is 9,999 shares. At one point, you'll have 499 shares that you can trade. That is the quantity. And you have 500 shares as the peak quantity. So if you always set it to order.peak quantity, it just means even though you only have 499 shares that you're willing to trade, you'll have to pass in 500 because you've always set it to peak quantity, and that's incorrect. So what we do is take a minimum value of 499, which is the total shares that you can trade, and 500 shares, that is the peak quantity that you can trade at any given time. So that is the display quantity that's displayed to the user. The next thing we have is order.hidden quantity. And hidden quantity is the same as whatever is the total quantity minus the display quantity, right? Because let's say I have 10,000 shares, 500 shares is our peak quantity. Well, the hidden shares are going to be 9,500 shares because the display quantity will be 500 shares, the peak quantity, and the total quantity is 10,000. So you're displaying 500 and the rest 9,500 are hidden. There you go. So you have order.hidden quantity is equal to order.quantity minus the display quantity. So we've prepared the visible slice for our iceberg order. All right, now let's get back to the top. We've done our thing for the iceberg split. The next thing we want to do is insert into the ID index. Remember, this is the part where we had our order book. Let's go back here. And I told you we'll be maintaining the order ID index, right? The order ID mapped to a specific order record. And we want to maintain that as well. And where were we maintaining it? Well, if we scroll down, there we have our order index. And here we have it, order map of orders. So we'll have this order map, which was an unordered map, and all we needed to do was store the order to the order record, or the order ID to the order record, sorry. So to do that, we'll go back to our add order function, and here what we're going to do is orders.insert or assign. We're just adding the order to the hash map, okay? Nothing more than that. So we're doing insert or assign, and I'll talk more about insert or assign, what it does. Here, we need to pass in the key and the value. You can look at it by hovering over it, key and the value. So the key is going to be order ID and the value is going to be order record. So we'll have to create a new order record object. And the thing is, order record accepts an order and the last status. Well, we know the last status of the order is the new. So you can either pass an order, this order dot status, or you can just pass an order status new, doesn't matter. I'll just pass an order record. Order is equal to the order. We know that's last status. I've just set it to order status new. Or if you want order.status, same thing. All right, so we have added the order to the hash map. This insert or assign is basically the absurd version of insert. What it means is if the key already exists, we override the value. In our case, after validation, the key should not exist because we've already checked for duplicate ID above. So this is basically an insert, but we're just using insert or assign as a very defensive mechanism. Doesn't give us anything. We don't lose out on anything, so it's fine. If there is a stale order record left over from a retired order with the same ID, we cleanly will replace it, but that should not happen. So we have added the order. That's all well and good. The next thing we want to do is match the order. So we have done everything we could to add an order to the thing, right? We have resetted the events. If we validated if it's a new event or not, or new order or not, we've rejected it if it is. We've allocated the order, we've constructed the order object, and we've done it for all types of order, iceberg, market, limit, everything. And we've updated our thing of ID index to order record. The thing we've not done is added to this order book. The reason we've not added it to the order book is first, we'll have to match it. Because let's say you have an order, let's say a market buy of 200 shares that's coming in, we don't directly place it in the order book. What we do is first try to match it against an existing order. So we'll have to run the matching logic, and if the matching logic fails, that means we'll have to either rest or kill, retire. What do we want to do with the order? We'll have to do all of those things, because if it's, let's say, a fill or kill, we'll try to match it with all of these things. If it doesn't match, we'll have to reject it. And the same with market buy. If there's 200 shares, we'll quickly do the matching, and if it works out, then what we're going to do is do the matching and update the existing order book events. So the key point here is we'll have to run the matching logic here. because it will do the actual matching, resting, and all the other events that need to be emitted, because here you notice we have other events that can be emitted as well, right? Like order accepted, rested, rejected, reduced, partially filled, etc. So we'll have to emit those events as well. And for that, we'll just create a different function called execute inbound order. I'll pass in the order object that's obviously needed. Then we also need the event timestamp, and then we'll set it to true. The true is standing for emit accept event. If it's set to yes, this is a fresh inbound order. So if we emit order accepted before anything else happening here, because if you're getting into the matching logic, the order is now accepted and you want to emit that event, correct? So you're setting it to true to update it, or like in our execute inbound order, we'll check if this value is true, then we'll first emit the accept event and then we'll move on. We'll also have execute inbound order called in, let's say update order or something like that. The reason for it is, well, if you update an order, you want to match it. So yeah, why not? And there it will be set to false because it's not a new order that's been accepted, right? So we won't emit that accept event. All right, awesome. And finally, we'll return the events function here. It's just a span of event. Great, we're all done with the add order. The next thing we need to do is ensure that this matching logic runs properly. It's the shared lifecycle essentially between the add order, modify order, and all of those things. So after this execute inbound order works, the event buffer will be fully populated and we'll run a span over it for this events so that we can return all of the events that took place over here. Assuming all of that makes sense, now we'll get into the main matching logic. Just remember, this function, this execute inbound order, is going to be a shared lifecycle for 3 different starting points. The first one I mentioned is going to be a fresh inbound order. That means this is set to true. We emit the accept event. This is a fresh new bound order. The second one is a stop order that just got triggered by a trade. That is called with false because acceptance was emitted earlier when the stop was parked, correct? So this is just execute inbound order when it will be called when there's a stop order that got triggered by a trade. And the third one is modify order, and we've talked about that. That will also be set to false. So we have centralized this matching logic behavior in one helper function, and we will ensure that all the 3 paths that we have behave identically. So there's just one matching logic in our entire code base, not 3. And if we got it right once, it will be right everywhere. That's our logic here, okay? So let's go ahead and create this execute inbound order. All right, so before we get started by creating this function of execute inbound order, what we need to do is create some variables. So the first thing we want to create is we have an order pool, correct? From this order pool, we'll be able to, we were able to allocate and deallocate the orders. Similarly, we need that for levels as well. So we are going to create a level pool as well. So we'll have a memory pool, the zero allocation infrastructure. The type is going to be level. Capacity is level capacity, and we call it the level pool. Simple. Then we also have 2 other variables. The first one is next match ID, which just represents what is the next match ID. It will be a monotonically increasing ID that we're giving it. You can also generate unique IDs, but I find this to be much better because it's just continuously increasing all the time. And we've given it the type of match ID, which is uint64. Awesome. And the next one we are going to have is last state, but we'll create it when we actually need it. For now, let's just go ahead and create the execute inbound order function. So we have void execute inbound order. We take in the order reference, the timestamp, and then the Boolean emit accept event, which is going to be true or false depending on the 3 scenarios that we've talked about before. Alright, within this execute inbound order, the first step we want to do is optionally emit order accepted event if this emit accept event is true. I told you that whenever we come to this execute inbound order, we want to first check, is this a new inbound order that's being created. If it is, we'll emit an order accepted event, and then we'll push it in the events buffer. So let's just check that. If the emit accept event is true, then we are going to set the order status to accepted. We'll change the previous status, which would most likely be new, and we're changing it to accepted, that the order has been accepted by this matching logic. And then we are going to emit accepted. Similar to emit rejected, we are also going to have emit accepted, and now we'll create this emit accepted. So here we have emit accepted. I've done it in the same private block as this emit rejected one. The structure is going to be quite similar. We just take in the arguments that we need, and then we'll just push event. So the push event is going to be event make. We pass in the order accepted, then we pass in the sequence number. Again, we don't have the next sequence. Once we have the sequence, we are going to add that. Then we have timestamp, order ID, symbol, side, price, quantity, and order type. Awesome. So we have emitted accepted event. The next thing we want to do is check if it is a stop order, because the thing here is that if it's a stop order, we don't want to put it into the matching engine directly. Whenever you have stop orders, they will never enter the matching loop directly. Remember that they will enter at some point, but not directly. They will be parked within the stop buys or the stop sells maps that we had created. This part, stop buys, stop sells. The reason we had created them is because we'll have a trigger price based on which the stop order will get triggered, and then they'll enter the matching engine logic. They don't directly enter the matching engine. So key thing to keep in mind. So coming back to our execute inbound order. So if this order is a stop order, what I want to do is make them sit in a stop buy or stop sell depending on the order side, correct? If it's a buy order, then we'll put it in stop buys. If it's a sell order, we'll put it in stop sells. So we'll just create a helper function to help us do that. We'll call it park stop order, because essentially we're just parking this stop order. We are not putting it into the matching engine, right? So now let's go ahead and create this park stop order. Well, we take in an order reference, and as you would expect, all we do is check first if the order side is buy, then we put this order trigger price in the stop buys dot map. Okay. So mplace is just a way to put it into a map. What we have done is stop buys dot mplace, and then we have passed in the key as the trigger price and the value as the order itself. And if it's a sell, we'll just do the same thing, but in reverse. We'll just have stop sells here instead. So else, if it's not a buy, it's going to be a sell order. If it's a sell, we'll put it into the stop sells map and do the same thing. The mapping is between the trigger price to the order, right? At what price is it triggering and what is the order for that? And this is the reason why we had created a multi-map within stop buys and stop sells, because you can have multiple trigger price that are the same. That's why we had that. Awesome. So we have parked the stop order. If that's true, the next thing we want to do is update the order index to reflect the post acceptance status. So we'll just have orders at order.id.last status. Remember, this orders map that we had created, I told you, or not orders map specifically, but this last status specifically, because this orders map is containing the value as order record. And when we were creating order record, I told you we'll be updating the last status, because that will help us know and distinguish between two different order types, right? So this last status is updated to reflect this post acceptance status. So we are saying, hey, the orders at order.id, its last status is accepted now. We're good. Again, this orders at order.id gives us the record, the order record, and order record is just a wrapper over the order, and it also pushes in a last status. This last status is used to help us know and distinguish between two similar order types. And we've set this to accepted so that we can update the last known status. The last known status was accepted. So we do that. If it's not a stop order, Then what we want to do is get into the actual matching logic. We want to try to match the order, because if it's not a stop order, then it means that we want to match it. So we get into the matching logic. But before that, we'll have to store and record the original quantity, because first we are going to record the original quantity before the matching logic happens. Then we'll match it, within which, the original quantity will change. Because think about it. If you have a market buy of 200 shares, you're going into the order book. What was the original quantity? Or 200 shares. And then when you go into it, the quantity will change to 0 because you no longer have to buy it. So the original quantity has changed. What we need to do is store it so that we can have some sort of logic to understand how many shares were totally filled, right? To calculate the total shares that were filled, what we'll have to do is, okay, there were 200 shares originally. You went here, maybe 150 shares you received it, rest 50 you did not. So you only have 50 shares as the quantity now, because the matching engine will decrease it. And then when you come out, you're like, okay, original was 200 and you only have 50 now. That means 150 shares were fulfilled. That's what we're trying to do here. So we'll go ahead and store, or before that, actually, let's return it, because if it's a stop order, we do not want to get into the matching engine logic. And after that, we can store the original quantity. Then we'll go ahead and have the last fill price. This last fill price is updated by reference inside the loop. It will record the price of the most recent trade that has happened. And what loop am I talking about? Well, let's get into that. So we have the match function here, where we pass in the order. Obviously, we want to match a specific order. What's the event's timestamp? And what is the last fill price of this? It will be updated by reference inside the loop within the match function. Now we'll get into probably the most important thing of this entire stock exchange, the actual matching logic. Just remember this, the actual trading will happen within this matching logic, the match function. And how this match function behaves is that it will early exit if there's no liquidity present in the market. Cool, that sounds reasonable. So how do we go ahead and find out if there is no liquidity in the market? Well, we have created a function for that. The best opposite level, if that's null pointer, then we're going to return, because that is going to help us decide if there's liquidity or not. So let's go ahead and create this match function and also do the best opposite thing I'm talking about. So we'll have void match. We get the aggressor, we get the event timestamp, and the last fill price. Aggressor is just the new order that's coming through that needs to be matched. I'll always call it the aggressor. Okay. Now let's do the early exit check, where we just want to check if there's liquidity in the market. So we'll have constant level best opposite is equal to opposite best level. What is the side? Are we trying to buy or are we trying to sell? If you're trying to buy, we just want to look at the best opposite level that has sell. And if it returns a null pointer, that means there's no opposite best level. If it does return a level, that means there is an opposite best level. What we want to check for our early exit is if the best opposite is equal to null pointer. That's very important. If it's null pointer, then obviously we cannot match because there's no liquidity. If there's no liquidity in the market, what are you matching against? And the second thing we check here is this marketable? What does is marketable mean here? Well, is marketable is just a way to know if the aggressor's price might even cross the best opposite price. What that means is, let's say you had something like FOK sell 400 shares at 150.3. You had 150 shares at, just assume that this order went in, okay? The early checks that we had previously did not happen and we've somehow got into this order book. So what we're trying to do is FOK sell of 400 shares. Oh, sorry, let me do FOK buy of 400 shares. So what we're trying to do here is 150.3. Okay, that's a good one. So we'll take the 150 shares. This is a good one. We'll take the 200 shares. And let's just say instead of this, we had 350 shares, not 400 shares, because 350 shares can be satisfied here. 400 cannot be because this one is bigger than this price. We've talked about that. But anyways, let's see. These 150 shares can trade. These 200 shares can trade. So it is marketable. How did I know that this is marketable? Well, that's because the aggressor, the new order that came in, its price could cross the best opposite price that's present. It could cross 150.25. Then it could again cross at the next best price, 150.3. And that's why we were able to fulfill this order. That's what we're going to do here. Let's go ahead and create this function of is marketable. What this will do is check if the order is marketable. That means it will first check if it's a market order, because as you remember, if this is a market order, there's no limit on the price. It can match with anything. So market orders are always marketable. That's why it's called a market order, right? It doesn't have a limit, so it can match with anything. The next thing we want to check is if it is, a buy order. If it's a buy order, then the price of the new order coming in should be greater than or equal to the price that's already present here. And if it's a sell order, then the price coming in should be less than or equal to the resting price that's already present here. Let's create that function. So we have static boolean is marketable. We'll check if the order type is market order. So we'll have if aggressor.type is equal to market, then we return true. If it's not a market order, it's other types of orders. In that case, we want to check with this resting price. And this resting price is just the best opposite price that's present here. Makes sense? Because if you're coming in with FOK buy 350 shares, the best opposite price you get is 150 shares at 150.25. Awesome. So 150 shares satisfied. So you're just looking at the best opposite price, the first price in this sorted sell up or asks map. So let's go back to our is marketable. If the order type is buy, what are we looking for? Well, if the aggressor side is buy, then the aggressor price should be greater than or equal to the resting price. Think about it. I put in a buy order. This 150.3 is greater than or equal to this 150.25. That's why we were able to do this marketable order. Another thing, let's say 150 shares is done. We want to do 200 shares. Well, 150.3 is greater than or equal to 150.3. It is marketable. So we are done that way as well. So this logic is basically what I've said right now. And if it's a sell, we just do the reverse of it, correct? So we just do return aggressor price is less than equal to resting price. If FOK sell of 350 shares at $150.3 comes in, you look over here and you're like 150.3, that is greater than, or sorry, that is less than or equal to the resting price. That's correct. So we do just 350 shares. But if you try to go down, you have 150.2 and you do, let's say FOK buy the next 100 shares at 150.3. You're like, okay, so 150.3, the aggressor price is less than equal to 150.2, and that's obviously false because 150.3 is not less than equal to 150.2. 150.2 is less than equal to 150.3. So this will fail, and therefore this order is not marketable. So this way we are preventing the lower order to not trade with this higher order because there's no way this matching happens. Awesome. So we have is marketable. If either of these cases are true, we will not match. Perfect. All right. The next thing we'll do for this matching logic is, well, we've done the early exit checks. Now we actually need to match. How does actually match work? Well, your aggressor will come in. Your aggressor will say, okay, give me the best, give me the second best, as long as my 350 shares is not done. So what we are doing is matching against the levels. Correct? What we are trying to do is say, okay, 150 shares at 150.25, that's great. We'll exhaust that. Then we'll do 200 shares at 150.3. That's great. We'll exhaust that. So we're just going over each of the levels and seeing if it satisfies, and if it doesn't, we'll break out. This is going to be a for loop. And that's the for loop I've been talking about when I'm talking about this, where did the value go? Well, this last fill price essentially. But this logic is going to be pretty much the same for buys or sells. If someone says, okay, FOK buy 350 shares, it will be the same logic compared to FOK buy 350 shares at 150.3. Basically the same, right? Buy, sell, same thing happens. It's just that the map changes. Here I'm looking at the bids. Here I'm looking at the asks. So only that part will change. So again, we'll have to do that. We'll have to put an if condition here saying if the aggressor side is equal to buy, then we're going to call match against levels. Then we'll pass in the aggressor. We'll pass in the asks map, because when you have a buy, you're looking into the levels of asks. When you have a buy, you're looking at sell asks. That's what you're looking at. And if you have sell, then you're looking at bids here. And also the side will become buy, and rest of the two things are going to stay the same. But that's our logic here. Let's go ahead and create this match against levels. We have a templated function where we have match against levels. We have an aggressor, we have a level map, we have a resting side, event timestamp, and last fill price. First question, why is this templated? This is templated on the map type because the same code will handle both bid and ask maps. They differ only in their comparator, which lives in the type, which is the level map, correct? This level map can be the bid map or it can be the asks map. So we have just templated it and put that in so that the user or the developer essentially can pass in asks or bids here. It's just a way to pass in asks or bids, because if you pass in ask map here, you can always only pass in ask map all the time. If you pass in bid map, you'll only be able to pass in bid map all the time. So we've passed in a level map. This way you can pass in both bid map and ask map. That's good. All right, let's get moving. How exactly will this work? Well, I've already told it to you. Whatever map we get access to, this level map, we'll iterate over it and we try to check what is the best level marketable here. Well, the best level is obviously given to us because we are iterating, right? If 150.25, we are in buy, okay, FOK buy 350 shares. We are in the buy side right now. And then when we have sell, you already know the process will be reversed. I won't go over it. But anyways, buy or sell, the case is that you go over each of the levels. So let's iterate over this levels map. To do that, we'll do for auto level iterator is equal to levels.begin, and we'll go until level iterator is not equal to levels.end and the aggressor quantity is greater than 0. This is an important condition. We don't always want to go till the end, because think about this case. 350 shares at 150.3. We satisfy 150 shares, we satisfy 200 shares. Why should we go to the third one? The quantity of the original order has been satisfied. That's what we're checking here. If the aggressor quantity is greater than 0, we keep going, otherwise we don't go. And yeah, plus level, because we want to, increment between the levels. So yeah, this is just a way to keep iterating until the levels is empty or the aggressor quantity is empty. Okay, now we are at a specific level. If we are at a specific level, what do we want to do? Well, we know a specific level has its own FIFO queue inside of it. And within that FIFO queue, we'll get access to each of the orders and try to match it, because that's how it goes. That's how the matching works. Because remember, here the oldest one is at head and the newest one is at tail, and we are looking into the price time priority again. If you are at the same price, then the time the order came in at is going to be the most prioritizing order or most prioritized order. So here, let's just go ahead and calculate the level we are at, because, well, this is a level map, right? Level map is a mapping between this. Let's go back to this level map here, or actually let's just go to ask map. When we go to ask map, we see that the price is the key and level is the map. That means we want to get access to that particular level, the value. And to do that, what we need to do is call this level is equal to level iterator dot second. Second just gives us access to the value that is the actual level. The next thing we'll have to check is if level is a null pointer. Because remember, if level pointer is null, it is a deactivated placeholder. That means it is a level that was once active but is now empty. So we want to skip it. That is not the level we want to match at, right? Because that was one of the polymorphic memory resources limitation that we talked about. So yeah, that is a problem. Let's go ahead and check that. If level is null pointer, we continue because we don't want to match at a deactivated level. The next thing we want to do is check if it is a marketable order or not. Because when we are again trying to match against the levels, okay, maybe the first level that we had is not marketable. We've already checked for that in this case. Where did it go? Is marketable was called in match. But it was only checked for the best opposite level. So we know that the best opposite level is marketable. But what about the second best? Is that marketable? And since we are looping through all of the levels, it is the case that this is not marketable. So we want to check that. So again, we'll go ahead and check. If it is not marketable, we want to break out of this loop. Because if it is not marketable, it just means that 150.3 is greater than or equal to the other thing. That means you had 150.3, correct? It matched with 150.25. You had 150.3, it matched with this. Let's say you had FOK by 450 shares. Now you reached 150.35. This is not a marketable order because 150.35 is greater than 150.3, so they should not match. Therefore, you break out because even if you had something after this, it would not match with this. The reason for it is simple. This is a sorted map. Since it's a sorted map, if 150.35 does not match, 150.4, 150.45 will not match. That's why we just break out of this loop directly. We don't want to proceed any further. Now, if it is marketable, then we want to start matching. But how will we match? Well, we'll keep going until we can match all the orders within this FIFO queue. And how we decide that? We decide that because we'll again have a while loop where we go and probe into a specific level every single time until the quantity is greater than 0. And the level is not empty. That's also important. The level should not be empty because it can be the case that either the new order that comes in is fully filled and that's great, or the level itself empties out. If the level empties out, there is nothing for you to get from it. So just move on to the next level, right? So we'll have a while loop here because now the orders are marketable, and you'll have while the aggressor quantity is greater than 0 and the level is not empty because your objective is to fill all of the orders. That means the aggressor quantity should be brought down to 0 and the level should be turned into empty. Because yeah, that's how it goes. The level should be emptied because that's how the matching works. So we'll go ahead and create another helper function called match FIFO at level. We'll pass in the aggressor, we'll pass in the level, we'll pass in the event timestamp and the last fill price. And within this match FIFO at level or some function within it, we'll go ahead and update the last fill price. Just to be clear, all match FIFO at level is trying to do is trade against one level's FIFO queue, one level's this particular queue that we had, because we'll go over the orders and say, okay, order A, can we trade? Good. Order B, can we trade? Good. Order C, can we trade? Good. And so on. So let's go ahead and have match FIFO at level function created. There's going to be an aggressor, a level, an event timestamp, and a last fill price, as we've already passed that in. Now, how is this going to work? Well, as I mentioned, we keep going as long as the level is not empty and the aggressor quantity is greater than 0. And now that I think about it, since we are already creating a while loop within that function, we can remove this part of while loop and just have something like the while loop inside of it. But I'm not getting into that because I have this all control seed. If I mess that up, it's not going to work. But I encourage you to remove it out. This is dead code essentially, because within match FIFO at level, we are going to have while loop, which does the same thing. So the outer loop does not really make sense. And now what we are trying to do here? Well, whenever we are trying to match FIFO at a specific level, let's say if we are matching at this queue, we want to take a look at the head, that is the front of this FIFO queue. And to do that, what we'll have to do is level.front, correct? Because if you go to level, we have stored this front, which is just returning the head. That's what we'll use. So we'll have, well, the passive order, which is level.front, it is passive because the other one is aggressor, right? And this is the potential order, but it's passively sitting there. That's why we call it passive. Now, if passive is a null pointer, we just break out, because that just means that the entire FIFO queue is empty. If it's empty, we want to get out of it, because this level is not empty, but this passive is a null pointer. Ideally, we should have the case where if this passive is a null pointer, that means the queue is empty, that means the level should also be empty. But in our case, we've already established that it cannot be the case sometimes. So yeah, this is one case that's handled here. The next thing we have here is the actual matching logic. Now, in the actual matching logic, one of the things we need to be concerned about is the iceberg order. Other orders would just go ahead and quickly satisfy it by just checking, okay, order A, what is your quantity? Okay, order A's quantity is, let's say, 50 shares. Cool, I'll give it to you. Order B is 50 shares again. Cool, I'll give it to you. Order C is 50 shares. Okay, cool, I'll give it to you. But this is a normal, proper order. If there's an iceberg order, we'll have to do all the display quantity and hidden quantity checks. What we'll have to check is if the display quantity is 0 and the hidden quantity is greater than the 0, well, it is an iceberg whose visible slice has been consumed and it is waiting for what's known as replenishment. What does replenishment mean? Well, again, think about this. You have this thing and you have your iceberg order. This entire part is visible, but this part is not visible, right? And let's say you consumed this part out, then you consumed this part out, and then you consumed this part out. So essentially, you have traded all of these shares. That means you have actual display quantity as 0 and your hidden quantity is a lot present. As we know it, the iceberg order just means that you take a chunk of this and you put it as the display size. And what is that chunk going to be? Well, whatever is the peak quantity, correct? Whatever is the peak quantity of that iceberg, we have to make sure that we use that and replenish it. And that's why we want to go ahead and check that case. What are we checking again? If the passive display quantity is 0, not the aggressor. Remember that. We are checking for the passive one, because if the aggressor is 0, what we try to do is just say, okay, you're done. This order is done. It's on the other side where we'll go ahead and check, okay, this was an iceberg order. Okay, cool. We are going to replenish that and do all that sorts of things. But in this case, we are only concerned with matching one order. We're not concerned with taking an iceberg order and converting that into multiple orders based on the replenishment, because that will violate the priority that I talked about. Because as soon as you replenish it to an incoming order, it is no longer an incoming order. It goes to the back of the entire matching queue. It will be given the last priority, not the first priority anymore. So yeah, let's just go ahead and check for the passive one. The one that was resting in the book, this one if this was an iceberg sell order, only 150 shares were there, then 50, then 100, and so on. And let's say all of them are now violated. That means like violated as in this is all 0 now. It just means that we want to replenish it because there's more available at 150.25 possibly. So yeah, let's just go ahead and do that. So if the display quantity is 0 for the passive order, and if the hidden quantity is greater than 0, then we want to replenish the iceberg and continue. Because as soon as we have to replenish the iceberg, we'll go over this aggressor again so that we can see what is at the front. Because as I said, the iceberg order has 0 now. We take a chunk of this and we put it at the top. But this chunk is no longer guaranteed to have the same price as what was present over here. The user can have the ability to set that, okay, the first 100 shares, they trade at 150.3, the second one is 150.4, and then the next chunk is 150.6. They have the ability to do that. So obviously we want to continue and again check what is at the level dot front. What is the order that is the newest for this specific price point. Also, this order, even if it's at the same price, will be given to order C, then order D, then order E. It will end up as order E. It will no longer be at the very front because we're not going to trade it, correct? Because this is the last order that came in. We're not going to give it the opportunity, even if it's a passive order, right? Even in an aggressor, when let's say if it's an iceberg buy order, it comes in, it only trades for the first chunk, and then the second chunk is going to be put at the end. Similarly, for the ask one, even if it's a passive order that's just sitting there, we look at it, okay, the quantity is 0, okay, good. We'll just take it and push it towards the end. It's no longer going to be towards the front of this FIFO queue. So we maintain the priority on both the aggressor order and the passive orders. Now let's go ahead and create this replenish iceberg function. We'll have this. Again, the entire point of this function is to refill and lose the time priority because it is no longer the newest order. Earlier, it was at the very front because of which we were matching against it, but it's no longer the new order. It will now be towards the end, or that means it will be at the tail because newest orders are at the tail. Now let's go ahead and have the parent level. To replenish the iceberg, we need to know what the parent level is, and if the parent level is a null pointer, we return. We've covered that case. It will happen most of the times whenever you're trying to check for a level. You have to check for a null pointer because it can be a deactivated order or level, sorry. And the next thing we want to do, think about it. Well, you are at this level. You want to take this order and you want to remove it because it's fully filled. There's no point of keeping it now. What do? Well, this level structure, if you go here, has a property called remove order. If you remember, this level, what it does is adjusts the linked list so that the head can now be order B. And all of that logic is taken care of. I'll not get into that because we've already covered that before. So now we can go ahead and remove the order. Then what we want to do is update the order's timestamp because this is a new timestamp. This is essentially an order that has updated quantities, but it also has a new timestamp. So we'll update the timestamp. Then we'll go ahead and calculate the replenishment, how much it should happen. Well, how do you calculate that? I believe we've done that somewhere where we had something like the minimum value between the hidden quantity and the peak quantity. This one, prepare visible slice. Here, we just calculated that the display quantity should be the minimum between the actual total quantity that's present and the peak quantity that the iceberg allows. And we already discussed why that's the case, so I'm not getting into that. So we're going to calculate that replenished value similarly. we'll take a minimum between the hidden quantity and the peak quantity, and we'll minus it with the hidden quantity, because think about it. If you have an iceberg order where you're taking a chunk, let's say you have this chunk, you're taking this off, you've calculated how big this chunk is going to be by taking the minimum of the display quantity and the peak quantity that's allowed. Again, we discussed that, not getting into it. And then we are refilling it. So what do we want to do? Well, we want to set the display quantity to this new quantity, and also the hidden quantity should be subtracted by this one, because what you've done is taken this portion, put it out at the top, and this portion no longer exists. So the hidden is smaller now. It's not as big as it used to be. And this is now the new one. So for that, we've calculated the replenished. Replenished is how much is going to be deleted from the hidden quantity, and the display quantity is going to be set to the replenished value. So we do both of them. The next thing we want to do is, well, come back to our level. We removed this order A, and now head is order B. What we want to do is ensure this order A is added at the very end. So let's go ahead and add level, add order, and we add the order. After that, we're going to emit the rested event, because what have we done till now? We rested this iceberg order. The whole point of doing all of this, by the way, is just to maintain the price time priority, or the time priority that we discussed. Replenishment loses time priority. Awesome. Let's go ahead and create this emit rested event. There we go. And it will be like push event. There we pass in order rested. The sequence number, again, next sequence we'll create it later on. Timestamp, order ID, symbol, side, price, and quantity. So emit rested is done. Replenish iceberg is also done. Now coming back to our original part. So if the display quantity is 0 and the hidden quantity is greater than the 0, we replenish the iceberg and then we continue. Remember, normal orders will not go through all of this because their hidden quantity is not going to be greater than 0. Perfect. Now let's go ahead and check this. So we've continued it. Now let's say it was an iceberg order, it reached its quantity as 0. So we now again go through this queue, and now the front is order B, and order B is proper. What proper means here is that you want to actually execute the trade. But before that, one thing I see is that what if the display quantity is 0? What that means is if the display quantity is 0 and the hidden quantity is also 0. If that's the case, we just want to break out of this match FIFO at level because this level is no longer present, it's empty. So we want to break out of it. So if display quantity is 0 and hidden quantity is equal to 0 or it's less than 0, which is highly unlikely, you just break out. Awesome. Now, having all of those conditions in place, if it's a normal trade, we want to execute the trade slice. Even if it's an iceberg order, but if it has actual display quantity, we want to execute it. If it's a normal order, we still want to execute it. So let's go ahead and have the trade slice. Well, how much do we want to trade it for? What is the trade quantity going to be for? Well, that is essentially just the minimum between the aggressor's quantity and the passive order that's sitting, its display quantity, correct? You either want to trade at as much as what this guy wants. Let's go back to our example. FOK buy 450 shares, 150.3. That means you have 450 shares and this is 150 shares. Since 150 is less than 450, what you'll do is trade completely for this 150 shares. Then you have 200 shares. 200 shares is less than the 300 shares because 450 minus 150 has happened. So you have 300 shares and 200 shares. 200 is less than 300. So this will also execute. Correct? So we want to do that. So we want to calculate how much quantity is this trade happening for. So we'll have quantity, trade quantity is equal to minimum between the aggressor quantity and the passive display quantity. And then we'll go ahead and execute the trade slice. I call it the trade slice because it is probably just a small part of the big trade, because this one is going to be 150 shares, this one is going to be 200 shares, or actually we're not even dealing at the level part, we're dealing at order A part. Sorry about that. What I mean is this order A is willing to do 50 shares, order B is willing to do 50 shares, order C is 25, and this one, order D, is 25. So order A has 50 shares willing to trade, and the original quantity you have is 450 shares. So you do that. Then you have 50 and 400. You do for 50 again. You have 25 and you have let's say you are at 350. So you do again, you have 325 and then you have last 25, 300. Then you go over here and you again do the same thing. So you essentially want to do the minimum trade between the aggressor's quantity, which is this part, and the order's quantity, which is this part. Sorry about the confusion about levels, because levels we iterated over and now within each level we are going over the trade, correct? Sorry about that confusion. Now how does this execute trade slice look like? Let's go ahead and create it. You have an aggressor, you have passive, then you have trade quantity, event timestamp, and last fill price. This, I believe, is the place where we'll have the last fill price done, if I am correct. Now let's go ahead and have the details passed in. This is going to be the function that does the actual update of the order. And there'll be multiple parts to it. So part number one is you have a trade price. What is the price happening at? So you have this passive.price passed in. Remember, this is the passive.price, not the aggressor.price. Why? That's because the resting order's price should always be the trade price. This is basically the standard price time priority outcome. The maker will get the benefit of their better price. The taker simply agrees to it. So if you place a buy at 150.3 and there's a seller resting at 150.25, you trade at 150.25. You got price improvement on your buy by 5 cents. Taking back our example, you have 450 shares at 150.3 and this is dealing at 150.25. Do you trade at 150.3 or 150.25? You trade at 150.25, right? You sell this or you buy this stock at 150.25 and this is the resting order's price that you're getting. So passive.price is the one that is going to set the price. The resting order is the maker's order. Cool. So this is going to be the price at which the trade happens. Now we'll go ahead and update this last fill price here because this is the last price at which this trade occurred, right? A fill occurs here and this is the trade price at which it happens. Then you go ahead and decrease the aggressor's quantity, the passive order's quantity, the passive display quantity, all of that, correct? So you have you set last trade price to trade price. Last fill price is about when did the full fill occur, and trade price is when did the last trade occur, and we're going to create that variable over here. So we have price, last trade price, it is set to 0. I told you we'll be creating another variable, that is the other variable that we created. So we've also stored the last trade price. Why are we doing that? We'll realize that later on when we take a look at how this last trade price helps us. Now let's go ahead and subtract off the aggressor quantity, the passive quantity, all of that. So you have aggressor quantity minus equals trade quantity, understandable. This quantity is decreased. Then you want to decrease this order's quantity. So you go ahead and passive.quantity minus equals trade quantity. Then you go ahead and also decrease the display quantity if that exists. So you do that as well. So if this was an iceberg order and it had 10,000 shares in total, but it only had 500 display shares, 500 is, or let's say 50 shares that would display because the total quantity is just 150 shares at this level. So let's say 50 shares is present. So what you do is take out this 50 shares. Now you have 0 shares. The display quantity is 0 and the total quantity is now 9,500. The total quantity should also decrease, right? Because total quantity is just the hidden quantity plus the display quantity. So you minus that as well. The next thing you want to do is also subtract the quantity that's present for this level, correct? Because this level had 100 shares, or this level especially, this had 150 shares. So you want to subtract that because this level no longer has 150 shares. You traded 50, so you have 100 shares now. So you update the passive.parent level.total quantity minus equals trade quantity. And that's why on a level we stored, or on an order we stored what is the parent level. That just helps us quickly update these total quantity things. It will be especially useful even in update order. So that's good. The next thing we want to do is emit a trade, because a trade has happened now. So we emit a trade event. Now we have to go down and create one, this emit trade function. So we have void emit trade. We take a timestamp, aggressor, passive, price, and the quantity at which we emit the trade. Then we go ahead and have the buy order ID. What that means is if the aggressor side is buy, then we use the aggressor ID. Otherwise, we'll use the passive ID, because we want to know what is the buy's order ID. If you have a buy, let's say you placed a buy over here, right? FOK buy 450 shares. That means you are the aggressor is the buy order ID. But if you are doing FOK sell, that means you're looking at this passive order. If you're looking at this passive order, that is going to have its buy order ID. Similarly, we'll do it for sell order ID. So you'll have aggressor side is equal to sell. Then we use the aggressor ID, otherwise the passive ID. Similar thing. Then we go ahead and emit this event. So we push event and have event make trade, pass in the sequence number, and all of these things. For match ID, we've passed in next match ID plus plus. So initially match ID is 1, then 2, then 3, and so on. You could start from 0 as well, I don't know, but I just started from 1. Then you have the symbol passed in, because what symbol did this trade happen for? We are having that within this order book, because this entire order book is for one symbol. We've already established it, so we can just refer that. So that is our emit trade. So a trade has been emitted. What else has happened? Well, we fulfilled the passive order, correct? That is another event that we want to emit. So we'll have emit passive fill state. We went ahead and filled the passive order. So let's create that function, emit passive fill state, pass in the timestamp, the passive, the filled quantity, and the price. If we go back up, event timestamp is passed in, the passive is whatever is the passive order, the filled quantity is the trade quantity for which that happened. You know, like how much quantity did you fill for this passive order? And then you have the trade price at which it happened. So let's go ahead and fill that out. Here we'll check if the passive quantity is 0, that means we fully completed the passive order. So we'll push the event saying event make order filled. Then we have the sequence number, timestamp, order ID is going to be the passive order's ID, filled quantity, and the price. However, if the passive quantity is not 0, that means the passive order was not fully fulfilled. That means, let's say instead of 450 shares, you had something like 50 shares. Okay. So you went, or let's say it is 60 shares actually. So let's say you had 60 shares here. Order A was 50. So you fully did that. Then you have order B that you only did 10 shares of that. The rest 40 are not fulfilled. So what you're saying here is that for the first order, the passive quantity is 0. So you push this event of order filled. If it's not, then what you do and you also return, by the way, so that you don't continue with this further execution. And then you just go ahead and push the event, because this is a partially filled order. You only had 10 shares here. And then you just say sequence number, timestamp, passive ID, filled is this much, the remaining quantity is the passive dot quantity, because already when we had our passive fill state, we passed in the trade quantity, which is the filled quantity, and the passive order is passed in. Its quantity reflects the remaining quantity that's present, correct? Because initially it was 50, then you subtract it from the trade quantity, which was 10, so you only have 40, which is the partially remaining quantity. After that, what we need to do is, well, we've emitted the events now. What we want to do is check, do we want to retire the passive order that's present? Because think about it, this order A is 0 now. Let's say this was not an iceberg order, but still it's 0. If it's 0, that just means this order A should not exist in this queue. It will just be wasting our queue's length, because we'll first go over order A, check if it's there. Well, it's 0, no. So let's go to order B. Well, maybe even that's 0, so no. And then at order C, we'll get some value. So obviously we want to avoid that. So what we'll check here is if the passive quantity is 0, then we retire this order. We'll pass in the passive order, we'll say that it is of the status filled, and we'll set it to false. What are we setting to false? Well, let's look at it in retire order. Let's go to retire order, and you'll see we have the order status, the refresh best is equal to true. So refresh best is set to true by default, but in our retire order, we set it to false. What this means is, do we want to refresh the best order that's present? So let's just go ahead to retire order, and we'll also track a variable called removed best level is equal to false. That just means, are we removing the level that's present here, the best level that's present? So initially it's false, and we'll set it to true if certain conditions match. Here we just go ahead and check if the order.parent level is not equal to null pointer. That means, let's say order A, it's not equal to null pointer. That's good, because even if your parent level is null pointer, then it doesn't make sense to do any of this. Now let's go ahead and have the order.parent level here. That is your level. Then we'll remove this order. Obviously order A is fulfilled. Let's remove it. Then we check if the level is empty, because if the level is empty, that just means we want to remove the parent level. That just means we want to remove this thing. So what we do is set removed best level is equal to, well, it depends. Is it a buy or a sell? If it's a buy, then we check if the best bid is equal to level, or we check best ask is equal to level. I hope you understand this. If not, let me just explain really quickly. What we've done here is, well, we're keeping track of this Boolean value removed best level. It's set to false initially. And if the level is empty after removing the order, it just means that, we essentially want to remove the level. But now we want to check if we are removing the best level that's present. How do we know if it's a best level or not? Well, if your order, this order that's present, if this order, the passive order is buy, then we check the best bid. So we check if this particular thing, this level matches the level of this parent level. Well, if it does, then we are removing the best level, otherwise we are not. Similar for sell. If this side is equal to sell, then we are checking the best ask. This level doesn't match with the level that we are talking about. Cool. Having understood that, let's move further. The next thing we want to do is deactivate the level. Because if the level is empty, all we need to do is deactivate this level and set it to null pointer in this map that we've been keeping track of. So let's go back to our deactivate level function here, which takes in aside the price and the level. And here we'll check if the side is buy. Then we want to remove, or first we will find the level iterator in the bids, obviously, because it's a buy, right? We want to find the level that we are removing. Let's say we're trying to remove this level, 50 shares at 150.15. So we find that out. Okay, this is the level. So we have the level iterator with us. Then we check if the level iterator is not equal to the bids.end. That means the level iterator is not out of this bids map. Then what we want to do is level iterator.second is equal to null pointer. All that means is that you have bids, correct? In this bids, you have bid map. Well, there's a mapping between the price to the level. So you get access to this level and you set it to null pointer. So let's say at 150.15, we find that out and we're going to set it to null pointer. I told you that we essentially want to update the map, correct? So that's what we're doing here. So here we just go ahead and check, well, in the bids, if the level iterator is not equal to bids.end, that just means we want to go ahead and set it to null pointer within this bids map, because this level iterator that we got is going to be a part of the bids map. Awesome. Otherwise, let's say it is a sell. If it's a sell order, then we want to do the same thing, but for asks map. So we'll have auto level iterator is equal to asks.find price. If the level iterator is not equal to asks.end, we will set level iterator.second to a null pointer. So this way we went ahead and deactivated the level. There's obviously one more thing to do here, which is, well, we have updated this map of buy or of sell. But what we have not done is deallocated from the level pool that we have. This part, because we want to deallocate as well. So we just go ahead and have level pool dot deallocate, and we go ahead and deallocate the entire level. So it's no longer a part of the level memory pool. Now you might be wondering, where did we go ahead and even allocate in the memory pool for this level? Well, we'll get to it in a bit, but first, just understand that we have deallocated the level because somewhere we allocated as well. We are specifically going to do that when we try to insert a new order into the order book. Because whenever we are trying to insert into the order book, that's the time we'll be updating the level as well, correct? You have a new order passed in, it updates this level that's present. All right. Now, moving forward, what we need to do is go back to where this deactivate level was called in the retired order. We noticed that if the level is empty, we remove the best level, we set it to true because let's say we removed the best level, or we did not, so we set it to false, and then we deactivate this level. Then we want to check if the order is a stop order. That means, let's say the parent level is null pointer. The order does not have a parent level. That means the order is most likely a stop order. If it's a stop order, we want to erase the stop reference because that's what the retire order is about, right? If the order's parent level does not exist, that most likely means it's going to be a stop order. And if it is a stop order, well, we want to retire this order, so let's just remove its reference from our stop maps. So let's go ahead and create the function erase stop reference. And then what we want to do is first get access to the specific stop map, correct? So we'll have stop map stops is equal to, well, if order side is buy, then we get access to the stop buys, otherwise we get access to the stop sells. And that's why we've called it stop map, not a specific type, or actually both of them just refer to stop map. But either ways, yeah, that's what we're doing. We want to get access to the specific stop map that we essentially have access to, so that we can remove the reference of the stop order from there because this order has been retired. So let's go ahead and do that. For that, what we need to do is first get access to all the stop ranges in the specific price point. Whatever is the order's trigger price for that specific point, what you want to do is erase the reference from the stop map. So let's say this is our stop map. we had 150.1 order number 1, 150.1 order number 2, and so on. So what you'll do is find out all the ranges where 150.1 exists. So you only need to look at a very specific price point. You have, let's say, X number of orders. You look at them, not the entire map, just a specific part of this map. And then you go ahead and find out, okay, for this 150.1, does this order match with the order that I'm trying to remove? No? Let's try for this one. Let's try for the other one, and so on. So pretty much a brute force solution where you're looking over each of the orders, but the optimization we're making here is finding for 150.1 only. So we have stops.equal range that we'll use. Let's just take a look at it. Constant auto first and last. So what is the first stop order that we found? Let's say this one, and the last one, in two orders it would be this. In one order, first and last both would be this. And if you had a third one, the last would be this, the first one would be this. So you iterate over all of them essentially. And we obviously pass in the trigger price because we want to remove the stop reference. And now for auto, iterator is equal to first, iterator is not equal to last. We keep on moving forward in this iterator and we check if the iterator.second is equal to order, because you have a stop map essentially, right? In the stop map, the second price is going to be, or the second value is going to be the actual value. The first one is a key. So the second one is the actual order that you have, and you check if it matches the order you're trying to retire. If that is the case, you remove that order. So stops.erase, and then you return out of it because you found the order you're trying to remove. You don't want to remove anything else other than that. So yeah, we've done that. Let's move forward. So what you want to do in here is just update the order status now, because orders at order.id is now equal to order record. You pass in the order as a null pointer now because the order does not exist. You retired it. And the last known status is the terminal status, which is best received from this one. And this one is just the order status filled, or, if you have another one, which we will have, you'll have order status partially filled or something like that. But when you're trying to retire the order, most likely you just have filled. Okay. And yeah, we've updated this orders map here, which contains the index, or the key is going to be the order ID and the order record is going to be the value. We've talked a lot about this, skipping over it. Then we just go ahead and deallocate the order from the memory pool, because obviously if you've exhausted this and you want to retire this order, let's just get rid of this thing from this order pool in the very first place. And then we check if the refresh bet and the remove best level is true. What we want to do is refresh the best level. What that means is if you've set this to true, that means you want to retire the order, but as soon as you retire the order and the order that you retired made you remove the entire best level that you have, then you want to refresh the best level. That just means that you want to ensure that the best level refers to this one, because this one is no longer the best level because it has been exhausted. This is the next best level which has some orders in it. And same for ask side. This one is no longer the best one because you exhausted it and you go to the 200 shares one. That's what we are trying to do here. Okay. So let's go ahead and create the function to refresh the best level. Cool. We just have access to the side. And again, we'll check if the side is equal to buy, then we set best bid equal to the first active level. And if it's ask, then we set best ask to the first active level within asks. Same thing. We say that this is no longer the best, so we give this the best. If this is no longer, we give this. So we want to find the first active level. Remember the word active is the first active level. Now let's go ahead and create this function of first active level. Again, this is a templated function because you're either passing in bids or asks, which is both of the type of level map. So how do you find the first active level? Well, you just go over each of the levels and try to find if the level is not a null pointer so that it is not deactivated. If it's deactivated, it's not active. If it's not deactivated, you have an active level. So good. Well, we'll check here. Well, we'll first of all do void price. This just means that this price thing that we have is of no use. So we are just chucking that value off. This is a way to tell the compiler that, hey, do not give me like a compiler warning saying, okay, the price does not exist, this variable does not exist, which will show up when we use w_all, which is a setting that we have enabled in our CMake list.txt file, if you remember. So we just do void price. This is a value of no consequence to us, and we are explicitly saying that out loud here. Then we check if the level is not equal to a null pointer. If it is not equal to a null pointer, it is the first active level, so we return it. Otherwise, we keep going. And if we still don't find after looping anything, we return a null pointer that there's no active level here. Sorry about that. And therefore, the best bid will be back to null pointer and best ask will be null pointer. And that's why everywhere where we've used best ask or best bid, we try to check if it's a null pointer or not, because as I told you, even the initial values, when we said it's a null pointer, I told you it just means that there's no best bid, that the entire order book is just empty for buys. Or if best ask is null pointer, entire sell side is empty because there is nothing best about it. Cool. So we have refreshed the best level here. Let's go ahead and add the other if condition, else if condition in execute trade slice. Remember what we've done. We've retired the order when the passive quantity is 0. To retire the order quantity, we removed the entire order, we deallocated it. If the order ensured that the level no longer exists, we remove and deactivate the level. And if it's a stop order, we handle all of those cases for all of the order types. Mainly stop orders and iceberg orders are different from rest of the orders. There's also one other type, which is the orders that are allowed to rest, and we'll take a look at that. But these are broadly the things that are giving us concerns. Rest of the orders, they're quite straightforward. So now we have retired the quantity order if the passive quantity is 0. Now what if the passive display quantity is 0 and the passive hidden quantity is greater than 0? That just means that we want to replenish the iceberg, correct? Because we went ahead and executed this order. Let's say it was for 50 shares. We took all the 50 shares from here. So the display quantity is 0 now because we took away all the 50. And the hidden quantity, let's say, is greater. This order has 10,000 shares or something like that, some absurd amount, okay? So what you do is replenish that iceberg order. The last time we had used replenish iceberg was when you wanted to match FIFO at a particular level. You were matching at a level initially and you just checked here. But once you execute the trade slice, and after executing the trade slice, if the iceberg is over, even then you want to replenish the iceberg, correct? So you do that because you might argue that something like this happens where you execute the trade slice, correct? So even if you don't fill it, well, you are in a while loop. So you again go over it, and at this time the iceberg will be replenished, correct? So why do you want to do that? Well, the thing is, level.front will change because we retired the order at that specific point in time because the quantity was 0. So we just retired the order, and if we retired the order, it will no longer exist. If it no longer exists, the iceberg's order's importance will go away. Because let's say you had order A, 50 shares, you executed it and you retired it. This function only runs in the very beginning, correct? But not after the trade happens. So after the trade happens, order A is out and only order B exists. So this guy will just think level.front is order B, not order A. And order A was an iceberg order and we did not take into account. So our order book starts to have a divergence over time and it violates the rules. So what we want to do is first we do this before a trade happens, and we also do it after a trade happens. And that's why you have the replenish iceberg over here. Otherwise, if none of these happen, what you do is set the passive status to partially filled. Make sense? And then we set this passive status within the orders map that's present. This order map was a mapping between the order ID and the order record, and we set the order record to have the last status as the passive status, and the passive status is partially filled now. Once we have done all of that in execute trade slice, we are completed with the match FIFO at level as well, and we are back at the match against levels. This is how deep we were, and all of this seems very straightforward, that the idea is very simple, but you need to take into account multiple factors because of which the code is growing. And match FIFO at level was done. And this was essentially like, if the aggressor quantity is greater than 0 and level is not empty, keep doing it. But yeah, as I said, you can just remove this while loop and you'll still be fine, because match FIFO at level keeps this while loop intact. So this is just unnecessary while loop. Now let's go ahead, and once this while loop is over, so that just means we keep going until this entire logic is over. So after this entire for loop is over, what do? Well, we refresh the best level, because after we match against all of the levels, it's possible that some of the levels are retired, etc., etc. Just ensure the refresh best level is intact. And now we'll make use of the last fill price that we have. So here we're going to check if the last fill price is not equal to 0. 0 is the default value. If it's not equal to 0, then we trigger the stop order. Why though? Well, that's because if the last fill price is not 0, you have a last fill price, correct? Like, at what price did the last fill occur? What this trigger stop order does is it basically starts triggering the stop orders, nothing much. And how does triggering the stop order works? Well, you go over all of the stop buys map elements that are present, and then you try to find out if any of the order was greater than the last trade price at which it happened. And if it did, you just break out of it. Because think about it, what is a stop order? A stop order is inactive until the market reaches a specified price, correct? So stop buy just means you want to trigger when the market price rises to or above the stop price, and stop sell occurs when you want to trigger when the market price falls to or below the stop price. And once they are triggered, they typically just become the market orders or limit orders. That's the point. So now if we know that what price, at what price did the last fill occur, at what price has the market fallen. If the market has fallen or risen above a specific stop price, then you just go ahead and convert the stop buy orders into into a marketable order, or you just go over stop sell orders and you convert them into marketable orders. So all you're trying to do here is trigger the stop orders to convert them into a normal orders, because the specific trigger price has been hit, because you have the trigger price with you. That is the last fill price. So now you just go ahead and create that function of trigger stop orders. All you need is an event timestamp. Everything is in the variables. And then what you're going to check is, well, create a do while loop. Or first of that, you want to check if you've triggered any of the stop orders. If you have triggered any of the stop orders, you stop, correct? And also now you'll have a do while loop. Why do you want to repeat this? Because activating one stop order may submit a market order, which then executes a trade, which will change the last trade price, which causes additional stop orders to become eligible. And this essentially just creates a chain reaction, correct? Think about it. If you have a price, let's say at 100, and you have a stop buy at 101 and another stop buy at 102, a large buy order might just come in and push the price to 101. So the current price has changed from 100 to 101, which means stop buy A triggers, which becomes a market order, and A buys aggressively, so the price moves to 102, and now B should also trigger because it triggers at 102, all a chain reaction. That's why you have a do while loop here. And within this, you'll have to do something for stop buys, and then you'll have to do something for stop sells. So now we'll check while or triggered any is now set to false here, because if you're in this loop, that just means you've triggered once. So you set it to false, and if any other order triggers ahead, you set it to true again so that this do while loop can run, so that we can check for the chain reaction. So now we have while the stop buys is not empty. If that is the case, while the stop buys map is not empty, that means you have a map that contains the trigger price to the order, I believe it was. Let's just go back to stop map. Yeah, we had priced the trigger price to the order. If that is the case, now let me just go back to where this error came from. Here we go. We have trigger stop orders. So while that stop buys is not empty, then you try to find what is the stop iterator, where does the stop buy begin, and then you check if the stop iterator dot first value, the trigger price, if the stop trigger price is greater than the last trade price at which it happened, then you break it. Why? Because think about it, what does stop buy mean? Stop buy means that you trigger when the market price rises to or above the stop price. In this case, what has happened is the stop price that was already existing, let's say it was, as I mentioned, let's say the stop price, I'll not use this 150 example because it gets very complicated, but I can just explain this to you. If we have current price of 100, then you have a stop buy of A at 101 and stop buy of B at 102. What's happening here? Well, the current price is 100, stop buy is at 101, and no other buy has come in yet, okay? So now the market price is less than the stop buy price, correct? That means the stop buy price is greater than the trade price, right? 101 is greater than 100. So we just break out. Nothing has happened, so we don't want to trigger any of the stop orders. So we break out of this loop, this while loop, okay? But if it did happen, then what do? Well, we get access to the order that triggered it, and we remove it from the stop buys because we are converting the stop order into an actual order. This is no longer a stop order. And then, yeah, we just call activate stop order. One thing to notice here is that the order is removed before activation. This avoids triggering it twice, some recursive issues that might happen, or some sort of iterator invalidation if the activation modifies the stop book. But yeah, now what we want to do is activate this stop order. We'll take in the order and the timestamp, and then we set the order's new timestamp to this event timestamp, and then we check if the order type is a stop order. In that case, we'll set the order type to market. As I mentioned, we are going to change the stop order into a market order. Then we set its price to 0 because it's a stop order. Remember that. Stop order gets converted into market order, and market order does not have a price set. All it has is the number of shares. It doesn't have a limit. But if you have an order type that is stop limit, then you'll convert it into a limit order where you'll set a specific price point. So here we have an else condition where the else is most likely going to mean it's stop limit because you don't have any other types of stop orders. And then you just convert this order.type to limit. And by the way, we are not changing order.price here because order.price is already what it should be. Here we set it to 0 because it's a market order. It does not have a specific price point. Now we go ahead and execute the inbound order. And executing the inbound order just means you run this entire loop again. Remember what I mentioned, execute inbound order is a shared life cycle. It will be executed when you have a new inbound order. When you want to convert the stop into and execute it. So that's what we are doing here. We have a stop order that we want to execute because we've converted it from a stop order to a market order, or a stop limit order to a limit order, because the price has been triggered. And remember, we only trigger the stop orders when we match against a level and we know that the last fill price has changed because it's no longer equal to the default value, which was the case before we went into match against levels. All right. And also we set triggered any to true here within this while loop of stopbuys.empty, because yeah, if we activate the stop order, if we've not broken out of this, that means we have triggered a stop order. Cool. So now we'll run again so that this chain reaction keeps on happening. So this is what we have done for stop buys. We need to do it for stop sells as well. So now we just go ahead and have while true. So that is an infinite loop, and we check if the stop iterator, what is the stop sells lower bound of this at this last trade price. And this looks a bit different from this one that's present. The reason for that is because stop sells trigger when the price is less than equal to the stop price, correct? So let's just imagine, let's say the stop sell prices are something like this. You have 110, 105, 100, 95, and let's say 90. Or we can remove 90, just 95. And let's say the current price, and we'll remove the stop buy. I hope you've understood that. Let's say the current price is 102. That means the triggered stops are 105 and 110, right? Because the price 102 is less than equal to the stop price. That means it's less than 110. 102 is less than 110. It's less than 105, but it is greater than 100. So these are the two things that are triggered here. Now, since the market has fallen below those trigger prices and the container is sorted ascendingly, then lower bound that we do here will return the first element. So if you have the last trade price of 102, it will return to you 105, which is the first element. And what we want to do is ensure that everything from 105 to above keeps on happening. So 102 is there, the lower bound is 105 because it's sorted in ascending order. So you have something like this done, if you can mirror this, but yeah, you have 102, and since it's in ascending order, the lower bound is 105. So you have that match in place. Then you want to do it for 110, and that's why you have this while true done. That's what this loop does. And now you check if the stop iterator is equal to stop sells.end, which is pretty much similar to what we have over here. If we've reached the end of stop sells, we want to break out of it, and then we get access to the order, which is stop iterator.second. Then we want to do stop sells.erase, stop iterator similar to this one. Then we go ahead and activate the stop order, and then we just go ahead and set triggered any to true. So all these lines are similar to what we had over here. Instead of stop buy, we have stop sell. And this logic is different from this logic because this one was only concerned with iterating over the stop buys and it's empty or not. And the logic completely fell in place with how this is sorted. But this one requires you to use this lower bound because, as I said, for stop buys, you have trigger if the stop is less than equal to the price. So if you start at the beginning and stop once, the stop price is greater than the current price. For stop sells, however, the trigger is if the stop price is greater than equal to the price. So if you jump directly to the first qualifying stop, you have to use lower bound at this price and activate everything after it. And this is much more efficient than scanning the entire container. The entire complexity of this function, ignoring this activate stop order, becomes O of k log n, because you have k number of orders that ultimately trigger, and n is the number of stop orders in the book. And when you try to erase something from stop cells, which is a multimap, I believe the time that it takes is log n, but correct me if I'm wrong about that. Let's get back to our code where we had trigger stop orders. So we have that logic in place. Everything about it looks good to me. So now we can go ahead and go to the function where trigger stop orders is called. Match against levels is also done because now you've refreshed the best level. You've activated any trigger or you've activated any stop orders if they are present. So match against level is also done. And now you're back to this match function. We're getting close to completing this giant function that we've taken in, but this is the core logic of our order book. Cool. So if it was a buy side, we did match against level for asks. Now, obviously, else condition will come in. If it's a sell, then we want to match against this bids. Everything else remains the same. So let's do that. And we're all set. This is our match function. Pretty simple, right? Yeah, it was actually very complicated. But you get the entire concept. It all revolves around updating this order book and updating this price level that we have. So now we have completed the match function and we're back to the execute inbound order function. Now we want to do post matching whatever is present. I told you we want to know what is the actually filled thing that we've done. So we take this original quantity and try to find out what is the total filled part that we have completed. So we have constant core quantity, total filled is equal to original quantity minus the order quantity. And I told you order quantity will be subtracted, and we already subtracted it if we were able to fill something. Partial fill, full fill, doesn't matter. If we were able to fill, we decrease the quantity and we handle the iceberg order stuff in it as well. That's great. Also, check now. If the total filled is greater than 0, that means we want to emit the aggressor side fill state, correct? Remember, we have done emit passive fill state, but we have not done emit aggressor fill state. We want to do that as well. So let's go back to our function of execute inbound order. And here we'll check if the total filled is greater than 0, that means the aggressor has now filled. Passive already did. Aggressor is now going to happen. This aggressor has been filled. Partial filled, full filled, that we'll have to look into within this emit aggressor fill state function. So you have emit aggressor fill state where you take in the timestamp, aggressor, total fill, last fill price, and then you check if the aggressor quantity is equal to 0, similar to what we had in the passive fill state. We'll push the event of order filled, pass in the sequence number, timestamp, order ID, filled quantity, price, etc. And then we return, obviously, because we don't want to execute any further. If it's not 0, it's partially filled. Then we go ahead and have the partially filled, similar to the passive one. It's basically the same function, but instead of having passive, we have aggressor. We could just have emit fill state and use it in aggressor and passive. That's my mistake. Should have thought of that. But I just wanted to make it a bit clearer for separation of concerns that this is aggressor, this is passive. And if you want to create a new type in the future called aggressive order filled or something like that, it's much easier. But yeah, over-engineered, agreed. If the total filled is greater than 0, we have emitted the event. Now still, we have to look at the order quantity. If the order quantity is 0, we want to retire this order as well, right? If we cannot retire the order, then we want to check if it can be rested. Same concept as the passive one. Remember, whenever we try to retire the order as of now, we only retired the order that were passive. The orders that were sitting in this level, this order B, this order C, this order A. We did not do anything with the aggressor order that came in. The order that was like, hey, I want some stuff. That was not the order that did anything. So we want to retire this order. Let's say this FOK buy, 450 shares, everything was done. Let's assume that it was 0 shares. We want to retire this order. So we'll have if order.quantity is 0, we retire this order. So we pass in the order, the terminal status is entirely filled, and we return. Now, if the quantity is not 0, that means there was partial fills. Whenever there's partial fills, for example, what would actually happen if you tried to do, let's say, something like 400 shares at 150.3, because when you come in with 400 shares at 150.30, what's actually happening is something like this. You have 150 shares done, 200 shares done, 75 shares not done because it's at 150.35. So only 350 shares were given, 50 shares were not done. It's partially filled. 350, even though it's the majority, you have still only partially filled this. You've not completely filled it. So what will happen in that case? Well, this will come and rest over here within the buy, and it will rest somewhere over here. Since something already exists at 150.3, you'll go to this level and you'll try to attach this order somewhere at the end, because newest should be at the tail. That means the new order that came in, which was this one, and the oldest one is resting here. And whenever a cell comes in that's able to sell, it takes from the front, and this guy will be towards the end. I hope you've understood this entire process. This is the entire matching logic. So what do we want to check? Well, is this order allowed to rest? Well, no, because this is an FOK buy. In reality, FOK would just get rejected early on, because if you remember, we had put in some logic earlier on that we just check if FOK buy can even be executed here. Otherwise, we just return it. Let's say we had FOK insufficient liquidity, this one, where we validated new order. So this is a bit of an invalid case, but let's say there was some other order that does not allow resting. Let's say it's post only buy. It does not allow resting, right? But even that would technically get rejected because it was able to cross in the very first place. But just imagine any other order. I don't want to spend much more time on this, but any other order that would be able to, trade partially, but it doesn't allow to rest. So you have a problem. So first you want to check if it allows resting in the first place, correct? In execute inbound order, you've retired the order if the quantity is 0, but if it is greater than 0, it's partially filled, then you want to allow the resting. And how do we check if it allows resting or not? Well, based on the order type. What allows us to rest the order? Well, that depends on the order type, and we have that function. So these are the things that allow. Limit orders allow you to rest the order. Good till cancel allows you to do that. Iceberg, post only, and stop limit do. Rest everything does not allow you to rest the orders. Remember that. If you have a market order, it cannot rest. If you have some other order like IOC, FOK, they will not allow you to rest. You immediately trade whatever is there or you cancel it. Oh, the good example I just remembered is of IOC buy. Instead of FOK, if you have IOC, it will not get rejected earlier on, and you have 50 shares, but it cannot rest. It cannot rest over here because it's immediately fill whatever is available or you cancel it. So you'll just cancel this order. But if you had a limit order, it would be able to rest over here, or an iceberg order that would be able to rest over here. That's why we are only concerned about limit, iceberg, post only, and stop limit whenever we are dealing with orders that are present over here in this level, FIFO Queue. Because if you're getting to the level FIFO Queue, that just means these orders are resting. They were partially fulfilled, they were completely filled. In that case, they wouldn't exist. But if they were partially fulfilled, then they're present over here. And partially fills can only be these things. Other orders are not resting. So I hope this entire circle is coming into your brain and you're able to understand it. So now, if the order allows you to rest, what do you want to do? Well, first of all, if it's an iceberg order, I want to prepare the visible slice. If it's not, then it doesn't matter because prepare visible slice will just do it for iceberg orders. Then we just go ahead and insert the order. And now we have to create the insert order function. What insert order does is insert the order into the order book. Insert order is where we are going to allocate the level to the memory pool, as I described earlier. The order to the order pool. I think we've already done that, but anyways, yeah. This insert order is where we're going to do all of that stuff. So let's go ahead and create this insert order function where we are going to first find or create a level, because when you're trying to insert the order, it can be the case that buy or sell is completely empty. If that is the case, you want to create a new level. If a level already exists, you want to find the level and insert the order within that level, right? For example, when 150.3 came in for a specific price point, I forget where did it go. Yeah, this one. When this IOC buy 50 shares at 150, let's just change this to limit buy now. So limit buy was 50 shares, 150.3 came in, the level already existed. So you went to this level and you try to append it. But if 150.3 does not exist, you go ahead and create your own new level. That's what this function does. Let's go ahead and create this function. Obviously it takes an aside price because you'll create a level within asks or bids. So you take in the side and the price, well, at what price point are you going to allocate? So I pause here and give you a moment to go ahead and test out if you're able to do this by yourself, this function only. So I hope you were able to do it. Let's just go ahead and check if the side is equal to buy. You find or create level implementation. And obviously in the else case also you'll have the same thing, but you'll have asks here and price passed in. There we go. That's what I've done here. If it's buy, bids. If it's sell, asks. Okay, let's create this find or create level implementation. Obviously, you want to find the level implementation if it already exists. If it does not, you create it. So you go ahead and do levels.find, as simple as it gets. And if the level iterator is not equal to levels.end, that just means that you were able to find a proper level. So you want to create an order object within it, within that specific level that you found. So what you're going to do is check if the level iterator.second is not equal to a null pointer. That's an important thing. As I mentioned, if at any point you access a level, you want to check if that level is not a null pointer because it can be a deactivated level. If it is not, then you've found a level. So let's just return the level, correct? Because the entire point of doing this is finding or creating a new level. If you find a new level, instantly return it so that this level is populated. Otherwise, you create a level and then return it. So yeah, we found it. Now let's say we weren't able to find it after all of this. What do we do then? Well, create a level. So we have level, recycle level is equal to allocate level, and you pass in the price. Why do I call it recycle level? Well, you'll get to know in a minute. Let's go ahead and create allocate level, and then we'll do level pool.allocate. This is where we call our memory pool to allocate a new level, because levels are also stored in an intrusive linked list and they're able to be added like this. Okay, this is a slot that we need. Okay, let me grab one from the memory pool in O of one time and then allocate a price to a level thing. And you keep doing that. And once the level is over, you deactivate that so that it can be passed back into the memory pool. Great. Now what you do is check if the level is null pointer, you return the null pointer because let's say it was exhausted, right? Because allocate can return a null pointer if the entire thing is exhausted, which is very unlikely. But yeah, we handle that case. I've mentioned that the caller is the one that will handle that scenario. Now let's go ahead and construct at this level. I also mentioned in order pool, in level pool, and anywhere else where you create memory pools, you will have to construct yourselves. So this is the level and this is the values that you're passing in. Price, the total quantity is set to 0 here because you don't have any orders within it right now. The order count is 0. Head and tail is null pointer. So you've just instantiated a level that has nothing but a price passed to it. Other values are placeholder, and as soon as an order comes in, or as soon as orders come in, this head and tail will be updated appropriately. Because that's the time you will have this insert order, inserting the order, or wherever else you had level, remove order, which is what updated the head and tail, or you had add order, which went ahead and added the order, which would update all of the things like quantity, price, etc. Not price, but quantity. You've understood that. Now, this is the allocate level you've constructed at the specific point, and you've returned that level. So this raw bytes that you had access to, it's an actual level now. And this is a recycle level. It's a recycle level because it's a level pool.allocate. You have a recycle level that's coming to you. And you just set level iterator.second equal to recycle level. Level iterator here stands for this level's map value. So this level's map value, it had the key at a specific price point and the value as a level, correct? So the first value, you already know what is the price point. The second value is going to be this recycle level that you just created. And then you just return the recycle level. So if the level already exists, you return that. Otherwise, you go ahead and return the recycled level by allocating it. So yeah, we're done with this, but what happens if the level iterator is equal to the levels.end? If that is the scenario, well, then you again want to allocate the level, right? So you have level is equal to allocate the level. Also, this was called recycle level also for the reason that if the level iterator is not equal to levels.end, that means you were able to find the level even though the level was deactivated, correct? Because if it was a null pointer, that's the time you're allocating a level and returning it. And that means it was a deactivated level that you've activated again. That just means you had something like this where, you exhausted 150.2 everything. So it was matching to a null pointer. And then you went ahead and created a new level because a new order came in at that specific 150.20 price and you were able to add it again. So it's a recycle level. You're again adding a level for which the price point already exists. Now what happens if the level does not exist in the levels map at all, right? The price does not exist, nothing happens. It just means that the price level for that level does not exist. If that is the case, then you just go ahead and check if the level is null pointer, return the null pointer. Otherwise, you have levels.emplace price and level. So you added to this levels map the price and the level, both of them. Pretty straightforward, right? I'll just go over it again. You try to find in the level, if you are able to find a price point that exists in the levels map, you return the level. Otherwise, you're not able to find the level. It is not a null pointer. It is a null pointer, sorry. So you go ahead and have a recycle level. That means you take it off the memory pool. You set the level iterator to recycle level and you return it because the price point already exists. You already had 150.20 and you reallocated the level. But what happens if the price point does not exist in the levels map? Then you have to create the price point yourself. Maybe you have something like $150.05. You have to create your own price level at that point. So you go ahead and allocate a new level. You check if it was exhausted or not. And if it wasn't, then you update the levels map to have this new price and level key. So at 150.05, you had another level which contains the price as 150.05 and initial the quantity is 0, order count is 0, the FIFO queue is empty. Awesome. So that's our find or create level implementation and our find or create level as well. Now what we do, actually before that we also have to return the level, obviously, because if we allocated the level, we have to return the level. And then we're done with all of these functions. We come back to insert order and we check here. If the level is null pointer, which is very unlikely, we'll abort because rest of the things here are also unlikely. Whenever we try to return a null pointer, it just means that the memory pool has exhausted, and the memory pool exhausting is unlikely. So this is also unlikely, just optimizing the compiler assembly instructions we talked about earlier. So we abort if that's the case. Then what do we want to do? Well, we want to insert the order within this level. So level.add order. Then we check if the order.side is equal to by. If it's a by order, we want to update the bids. So we check here if the best bid is equal to a null pointer, or that just means that, the best bid is waiting to get its first bid, or the level.price is greater than best bid.price. That means the new price that has come in is greater than the best bid price that already existed. So you have, let's say 150.30, a new order came in at 150.40. That is supposed to be the new best bid that's come in, and it's a new level that was created. So you have 150.40 at the top, and 150.3 is no longer the best bid. So best bid gets changed to this new level. Now else if best ask is null pointer or level.price is less than best ask.price, you set best ask to level. This just means that the order.side is cell and best ask is null pointer, or the level price is less than best ask.price. That just means, a new ask or a new cell came in at $150.20 and 150.25 is no longer the best ask because there's something lower than that. That's what this logic is about. Straightforward. So that marks the end of our insert order. We inserted the order, we found or created a level, and updated the best bid and the best ask depending on what we inserted, correct? Because best bid and best ask is just what's at the top in both of them. I mean the level, what's the level that's at the top for both of them. And it just gives us the best bid or best ask based on which we can quickly deny or give out the information. So that's pretty cool for us. It gives us everything in O of one time. And we've seen everywhere we use best bid and best ask. If you notice, we try to get the opposite best level multiple times. We refresh the best level based on whatever is present. And we also use it when we try to remove the best level or not. So yeah, it's pretty helpful. We already know that. So we just get all of that in O of one time. So now let's get back to our execute inbound order function. I believe that's where we were. Execute inbound order function. So we inserted the order. The next thing we want to do is emit the rested event, because the order has been rested, right? You inserted the order into the order book. If you're inserting it into the order book, you're done. You're just resting the order now. And then you want to update the order status so that the order record contains the latest status possible. So you have order.status is equal to total filled is greater than 0. If that is the case, that means you've partially filled it, or it's been accepted. Because if total filled is greater than 0, that just means the last event was partially filled. But if it's not greater than 0, that just means the last event was accepted because it cannot be filled. If it was filled, you wouldn't rest this order. Now let's update the orders map. So the last status is this order status, and then you return out of this so that it doesn't execute any further. Now, if in none of these instructions pass in, that just most likely means you have to cancel this order. So let's go ahead and emit the cancelled event if that happens. Let's create the void emit cancelled for this. It's just push event make, we pass an order cancelled and all of these details as we know it. Next sequence, timestamp, order ID, cancel quantity. Awesome. And once we have emitted the cancelled event, we want to retire this order because this order no longer exists. Because, yeah, it is either IOC, FOK, any of these orders. If it's any of these orders, we want to retire this order. So we cancel it. And that is our execute inbound order function. I would recommend you to pause the video here, go over this entire function again, understand that you understand this order book, this entire thing. This was the major chunk of this tutorial. This is what we had been looking for. And we have looked at how we are optimizing everything. Now, I agree that we have not optimized everything, and you can optimize this further. So once this tutorial is over, take your chances, see where you are able to ensure that we get faster code quality. As I mentioned, the performance, you'll have to ensure that you do the benchmarking, then you go ahead and do some performance optimizations, then you pause it, do the benchmarking again, and see if it improved or not by a substantial amount. There might be multiple times that you just get random noise, which doesn't equate to anything because we're dealing with microseconds, nanoseconds, and milliseconds here. Your computer is running multiple tasks at the same time, so it's difficult to do this benchmarking. So just ensure that. But yeah, we are done with this execute inbound order, which just means you should be able to understand what all the order types are doing. We've already looked at stop orders. Stop order gets converted to market. Stop limit gets converted into limit once the trigger price is hit. Then you have the market orders. That limit orders at a specific price point, they come in. Then you have the good till cancel, IOC, FOK. Those were anyway straightforward from the very beginning, but I hope you understand that too. And that was the major chunk. The next thing we want to get into is canceling the order. Should be quite straightforward because canceling the order just means whatever we have done before, we just have to do this. We just have to look for the active order that's present. We have not created the function for it, but whatever is the current active order, you find that if the order does not exist, you reject it because, well, if the order does not exist, you do not really have to cancel it. Then if the order does exist, then you're going to change its status to cancelled. You're going to retire the order, and yeah, you're just going to return the event because it's a public function similar to what we had earlier in our add order function. We executed inbound, we return the event. So yeah, in cancel, we are not going to execute inbound orders because you just canceled an order. Why do you want to execute anything? So let's have cancel, and then we'll work on modify, which will again help have you find the active order, emit the rejected in case, you'll have to reduce the order quantity, etc., etc. So, and you'll also have to execute the inbound order perhaps. So we'll have to take a look at that, but let's quickly get done with cancel order. So as usual, what we're going to do is similar to add order, we are also going to create a private class and a public class, and the public one is going to be cancel order. It's going to return a span of events, and it's going to take in an order ID plus a timestamp. By default, the timestamp is 0. Yeah. After that, what we're going to do is similar to add order. We want to clear off the scratch buffer that we might have. So let's just call reset events here. After that, what we want to do is just ensure that the order is found. Right? We want to ensure that the order exists in the first place. So what we'll do is auto order is equal to find active order. We know that orders can be non-active as well. They're deactivated. And to find that, what we need to do is pass in the order ID. We have the orders map that will allow us to find the correct thing. Cool. Now what we're going to do is create the find active order function. So let's go into the private part and create the find active order function. In public, as I've mentioned previously many times before, add order, cancel order, and modify order are going to be present. All the helper functions are going to be in private. So let's create a find active order. It's going to return an order pointer where it takes in an order ID. After that, we are going to find the orders in the order map, correct? If the order exists, then we have an active order, otherwise there's nothing. So we check if the iterator is equal to orders.end. That means the order does not exist. That means we return a null pointer. We do not have an active order. Otherwise, we'll go ahead and return iterator.second, because second will give us the value, which is the actual order record, and order record has the value of order in it. Order record also has the last status, but we are interested in the actual order. So we return that order value from it. Coming back to our find active order here, since we already have the order now, we found the active order, we'll check if it is a null pointer, because if it is a null pointer, we want to emit the rejected event. Makes sense? Because we don't have an active order, what are you even trying to cancel? The order should exist for you to cancel it. Then we also pass in the reason. The reason is a helper function which is called lookup reject reason. Essentially, when you're trying to reject an event from cancel order, there can be two reasons for it. The first one can be, is the order not found? And the second one can be that the order is not active. If the order is not active, that means it should be present within the order's map that we've added, right? If we go to this find active order, if the order is found within this thing, the iterator will have the order, but it will not really have the value in it. So we're just trying to find the reject reason based on the existence of order ID within this order's map. And we had discussed that before when we were talking about something else. I don't remember where we discussed it, but we were discussing about this. Oh, actually when we were creating the order record, because when we were creating the order record, we went ahead and found out why we need the order and how we are going to distinguish between order not active and order not found. Similarly, to find active order, we are also going to create lookup reject reason. So if the ID exists in the order's map, we are going to we are going to say that the order is not active, and if it is not found, then it is order not found. Awesome. Let's create this lookup reject reason. It's going to return a reason code, obviously, because we are rejecting it, and that's why we are passing it as the reason. And yeah, let's just check if this order ID exists. So we'll do something like auto iterator is equal to orders.find, very similar to find active order. Here we are going to check again, similar to this. If iterator is equal to orders.end, we are going to return reason code order not found. That means the order ID does not exist in the order's map. And if it does exist, then we say the order is not active anymore. That's why it's present in this order's map. So this is our lookup reject reason. Moving forward, let's say the order is present, it's not a null pointer, so we don't need to emit rejected. And also before that, we need to return events, because if the order is a null pointer, obviously we don't want to continue any further, so let's just return events. However, if the order is not a null pointer, then what we want to do is cancel the order. And we know how to cancel the order. All we need to do is call retire order, because immediate or cancel, fill or kill. In that, we also had execute inbound order, within which we went ahead and retired the order, correct? Emit cancel, retire order, same thing. But the different thing here is that, let me just scroll up. The different thing is that we need to change the order status here, because we still haven't changed it, right? And to change it, also when we emit the cancelled event, we will need the cancelled quantity. So we need that as well. So let's go ahead and have quantity, cancelled quantity is equal to order.quantity. Essentially, what is the quantity of the order that we are cancelling? We store that in. Then we change the order status to cancelled, correct? Then we emit the cancelled event, where we pass in timestamp, order ID, and the quantity that we cancelled. Cool, because that's what it requires. If you notice here, cancelled quantity is passed in. Cool. The next thing we need is retiring the order. We can just call that function. It's a reusable function we've already created. And we pass in the order, the terminal status, all good. The next thing we need is return the events, and this way we are done with cancel order. That's how easy it was. We had basically all the pieces there. We only had to create find active order, but that was pretty trivial because we already know how the orders map is laid out. It is just a mapping so that we can find the orders that have been active or non-active so that we can distinguish between order not found and order that is not active. Awesome. So with this, cancel order is passed in. Pretty much the end part is pretty much similar to what we had for immediate or cancel, because in both cases, you're just trying to cancel the order, right? Makes sense. The next thing we want to work on is modify order. And similar to cancel order, it's also going to be a public function, and we'll create all the helper functions needed for it, but should be pretty straightforward. All update or modify order is trying to do is update the order. And to update the order, we need to take in the new quantity, the new price if there is, and the current timestamp that's present. And then we can go ahead and update it, but we'll also have to do some kind of validation checks, because if it's a stop order, then we need to do some kind of rejection. If the new quantity is 0, the new price is less than or equal to 0, something like that, we'll have to emit rejected in all of those cases. So once we do that, we can easily go ahead and then update the orders present, because all we need to do is update the values in here, then update the specific price level, and we've already looked at how we can update those values. So let's get into that. Let's go ahead and create a modify order function. We're going to take in an order ID, new quantity, new price, and timestamp. We're not going to take anything else like, modifying the status of the order, because status of the order is changed within this order book and within our exchange only. We don't need that from the user. We also do not need something like what is the order type. That's the new order type. You cannot change an order that was initially something like iceberg to FOK or IOC. No. All you can do to modify it is pass in a new quantity or a new price, or both of them. So that's what we're trying to do. Now, how do you go ahead and modify this order? As I mentioned, with every single public function we have to do the first thing, which is reset the events. We'll do the same thing here as well. Once we have resetted the events, what we want to do is find the active order. How do we find the active order? We have a function for it. If we search for find active order, here we go. Now, find active order requires an order ID. We have an order ID, and if the order is active, it's going to return the order to us. If it's not, then it's going to return a null pointer. That's awesome. We would like that, because if the order does not exist, we want to go ahead and say, okay, we do not have this order. Just reject this modify order request, because if you don't have an active order, what exactly are you trying to modify? So let's go ahead and find out the active order. Once you have that, you need to check if it's a null pointer. If it is a null pointer, you emit rejected. The reason is lookup reject reason, and it can be the order was not found or the order was not active. Cool. The next thing we want to do is check if it's a stop order. We want to reject the stop orders as well, because we don't want to allow stop orders to be modified. Now, this is not an inherent requirement of a stock exchange. We're doing this in our stock exchange. The reason we're doing that is because stop orders are not in the active order book, right? So stop order is stored in a separate stop book that we looked at. We created a map that had all the stop things. So if the stop price hits, we take one from here, convert it into a normal market or a limit order, and paste it into the order book. So if you try to modify the price of a stop order, it will require reordering within that stop book if the stop price changes. Many engines, or actually some of the engines, simplify the implementation by just making these stop orders immutable. So what you need to do is cancel and submit a new order instead. And we're going to do just this. What we're going to check here is if the order is a stop order, we emit rejected event, pass in the timestamp, order ID, and the reason is that it's invalid modification. Great. The next thing we want to do is a validation of this new quantity that's being passed in. So we want to check if the new quantity is 0, because if the new quantity is 0, that just means you want to remove the order, because like what are you even trying to modify, right? So we have to handle that edge case. We'll check here if the new quantity is 0, we emit rejected, timestamp, order ID, and say that the reason is 0 quantity. Awesome. The next thing we need is if the new price is negative, right? The new price can be set to 0 because someone just wants to sell it for free. We don't care about that. What we do care about is new price is not less than 0 because it's negative. So we handle that case as well. So the reason code here is negative price. Next thing we want to check is if the new price is equal to the old price and the new quantity is less than the previous quantity. In that case, we want to reduce the order quantity, right? Imagine you already had something like 200 shares at 150.10 and now you sent in something like modify this order and then you pass in this order ID. The new quantity is no longer 200 shares. Maybe it is something like 150 shares. If it is 150 shares, what we can do is go ahead and see, okay, 200 shares, you want to just reduce 150 shares. The price is the same, 150.10. Okay, great. All I can do is go ahead and remove this and change it to 150 shares at 150.10 instead of 200 shares. I'm talking about a specific order here, not a level, but just consider this as one single order. Okay, like in this level, there's just one order and that is 200 shares. So I'm just simplifying that. But yeah, the price is the same in that case. The quantity is reduced. If that is the case, we don't need to do anything else. We can simply reduce the order quantity over here. Nothing else to do. But if we run into other cases, like if you have something like same price and same quantity, in that case, it's a no op. You just return an empty event set because nothing happens in that case. But let's say if you have something like the price changes and the quantity or the quantity increases, then you just go ahead and do cancel and replace. So 3 conditions here. First one is you have same price and smaller quantity. If this is the case, then you do an in-place reduction. This just means that the order keeps its time priority. There'll be no new ID created. There'll be no FIFO Queue movement. All you have to do is shrink the quantity based on, if it's an iceberg order, you also need to do the stuff with display quantity and all of that. But the point is you just shrink the quantity and then you emit an event saying order reduced because you just reduced the order. Another one is you have the same price and the same quantity. If it's the same, what are you even modifying? So it's a no op. You don't do anything. The next one is price changes and let's say the quantity increases. It's not really an and, it's an or. So if the price changes or the quantity increases, what you do is cancel and replace. So first you will have to emit a order cancelled event. You'll have to retire the old order. You'll have to allocate and admit a new one with the same ID. And the new ID will have to go through the normal admission path where, it may trade immediately if the new price crosses, then rest if, there's a residual that's left around. So all of the things that we discussed about in execute inbound order, that will happen here. So these are the 3 things. The first thing we want to handle is this part, same price, smaller quantity. If that's the case, we want to reduce order quantity. Let's go ahead and do it. So we'll have if the new price is equal to the order price, that means the new and the old one is the same, and the new quantity is less than the order quantity, that means the order quantity has been reduced. We don't have to affect its time priority. The reason for it is earlier you was doing 200, now you're just doing 150. That should not really affect the priority of your order. So what we'll do here is create a function called reduce order quantity. We'll take in an order, new quantity, and a timestamp. Now let's go ahead and create this private function called reduce order quantity. As we know, it takes in an order reference, a new quantity, and an event timestamp. Then we'll go ahead and store the old display quantity. This is just order.display quantity. Then we have the reduction. How much do you want to reduce the order by? So that's order.quantity, the previous quantity, minus the new quantity that's coming. So earlier maybe you had 200 shares and now you've placed an order of 150 shares. So that means there's a 50 share difference. That is the reduction. Then we go ahead and set order.quantity to the new quantity, understandable. And then we want to check if it's an iceberg order. Because if it's an iceberg order, we also need to update the display quantity stuff. And we've already looked at how the iceberg order works. There's nothing unique going on around here. We'll copy basically the same logic we've discussed multiple times before, where we'll have the remaining reduction equal to this reduction. Then we find out the hidden reduction, which is the minimum of this remaining reduction, and the hidden quantity. Then we'll just set order.hidden quantity minus equals the hidden reduction, and the remaining reduction minus equals the hidden reduction. This is the same logic we had seen previously when we had to calculate the hidden quantity. If you don't understand it, draw the iceberg, try to figure out what is the hidden quantity, what is the remaining reduction, all of that, and you'll be able to understand it much better than I could again explain the same thing to you that we did before. Cool. The next thing we need is if the remaining reduction is greater than 0, in that case, we'll minus off the remaining reduction from the display quantity. And then we'll check if the parent level is not equal to null pointer, because if it is, then we have an inactive level, because obviously levels can be deactivated. We've already established that multiple times before. Then we'll have order.parentLevel.total quantity minus equals remaining reduction. So once you've cleared out what the order is going to be, you're also going to update this particular part of the level. Then we go ahead and check if the remaining reduction is not greater than 0, which is most likely less than 0 or equal to 0. In that case, you just set order.displayQuantity to the new quantity, and then you check if the order.parentLevel is not null pointer, then you again do order.parentLevel.total quantity, and this time you minus it with the reduction, not the remaining reduction. After all of this if condition, we'll go ahead and just set the last status of the order to accepted, because yeah, that is the last known status. The new order quantity came in, we accepted that order's quantity. And then we'll check if the order parent level is not a null pointer and the old display quantity does not equal to the new display quantity. If that is the case, we'll emit reduced event. That just means we'll create a new event which emits reduced quantity. So let's create that function. We'll have emit reduced, where we have a timestamp, order ID, and new quantity. So we'll push the event where we pass an event make, order reduced. The sequence number is there, timestamp, order ID, and new quantity. So that's good. So once we have emitted the reduce order quantity from here, like this part we emitted reduced, what we want to do is, well, we reduce the order quantity. So let's go back to this function and return the events array or span. So we do that. So first case is now handled. We reduce the number of shares and we establish that it works for normal orders and also iceberg orders. And we handle those cases where we adjust the display quantity based on the remaining reduction that's present. Because if you want to reduce by 100 and only 50 is available in hidden quantity, you obviously don't want to take away 100, right? You have capacity of 50 hidden or quantity, not 100. So that's what we do here. And yeah, the rest of the thing is updating the display quantity based on whether the remaining reduction that we have is greater than or less than equal to 0. Having understood that, let's move on to the next part, which is within modify order only, we have the second type where, the price is the same and the quantity is also the same. So it's a no op, and we just return events there. So we'll have this condition: if the new price is equal to order price and the new quantity is equal to order quantity, then we return events. No op, nothing done. So this case is also handled now. The last thing is price changes or quantity increases. And I mentioned that if this is the case, what we want to do is cancel and replace. That means we will have to cancel this order, meaning retire the order, allocate and admit a new one with the same ID. That's the key part, with the same ID. It will not get a new ID. It will be the same ID, but it will go through this normal admission path where, it can trade immediately if the new price crosses, and it can rest if there's some leftover quantity that's not been traded yet. Let's go ahead and do cancel and replace. The entire point of doing cancel and replace is so that we have price time priority. The order that came in newly should have less priority than the order that already exists. That's why we are doing this. It's almost like we have a new order coming in. So we cancel the old order and make this new order come in fresh. Because otherwise it's very easy to game the system, right? Somebody can just say, okay, $150.3 and 250 shares. So they increase the number of shares, they increase the price, and suddenly they don't even have this price time priority and they can trade faster than the one before it. This is a loophole. So what we do is cancel this order and put them back into this FIFO queue. Let's go ahead and do that. So what we'll do is emit cancelled first of all, because we're going to retire the order, and then we'll call retire order, and the last status is now cancelled. Then what we want to do is allocate and admit a new one with the same ID. So what we'll do for that is call it replacement, where we call the order pool and allocate a new order, which is replacement. And then we know whenever we call allocate, we have to do certain things. The first one is you check if the replacement is equal to null pointer. If that is the case, which is unlikely, that means the order pool, memory pool has been exhausted. In that case, you reject, return events, but unlikely, let's move forward. Then what we want to do is construct at this replacement, because we have a free node. We want to convert it into actual order object with all of its properties placed within this order. And to do that, we can just do replacement is equal to construct at, pass in replacement, and then we pass in the order, where the ID is now the same order ID as the previous one. The side is what we need to decide. The new price is the price, quantity is the new quantity, original quantity is the new quantity, display quantity is the new quantity, hidden quantity is 0, timestamp is timestamp, type is type, status is new because it's a new order, then the participant, trigger, and peak quantity, all of that are left. Now, how do we pass these in? Well, the side, the type, the participant, trigger price, peak quantity, all of them are simply the remaining or the attributes of the past order, right? So we can take the past order, extract its attributes, and then paste them over here. And we need to do that before we retire this order. And therefore, what we're going to do is create these variables. So the side is going to be order.side. Before we retired the order, we just calculated the attributes, and then we have order.side, order.type as the type, participant ID is order.participant, trigger price is order.trigger price, and the peak quantity is order.peak quantity. So we extract all of these elements before this emit cancelled is done and the order is retired, because when the order is retired, we deallocate the order, so we won't have access to it. So we've stored these in separate variables, and now we can pass them in over here. So that's what we did. we've allocated a new order with the same one, and now it needs to go through the normal admission path. And to do that, we need to do, well, first of all, prepare visible slice. It's pretty much similar to the last time we used prepare visible slice, or yeah, it was somewhere over here where, we constructed this and then we did the prepare visible slice because if you remember, the display and the hidden quantity were set to be placeholder values. And prepare visible slice goes ahead and updates these values to have the actual quantity values to be present, because we want it to work for iceberg orders, right? And that's what we did. That's what we do in modify orders as well. We do the replacement, we construct it. There's placeholder values passed in. So what we do is pass in the prepare visible slice here, and it will do the relevant things for iceberg orders. Now, obviously, once prepare visible order is done, we need to execute everything else. For example, over here, when we had add order, we did prepare visible slice, then we did insert or assign into our orders map, and then we execute the inbound order. Same things are going to happen here as well. We go ahead and have orders at order ID is equal to order record. The order is now replacement and the last status is new. Remember, this order ID is the same as the previous one, so we are just updating the value over here. That's why we are not doing dot insert or assign, because we know we are updating the value because order ID already exists in the first place. It's just a new order, but the order ID is still the same. So we have updated this, and then we do execute inbound order. We pass in the replacement, the timestamp, and the except event is now set to true. Remember, this emit except event is true, not false, because now a new order has come in. The order's last status is new, so we still want it to emit accepted event. So this new order is modified. We cancel the previous order. New order came in. We say, okay, new order has come in. Great. We have accepted this order. That's why we have this set to true, because remember, in execute inbound order, we set it to emit accepted when we have this to true. In another one where we used execute inbound order, we had set it to false, which I believe was this one. Yeah, inactivate stop order. And that was because this was an already existing order. We just had to take it and place it into our order book. We have done that. Now let's go back to our thing. It was called modify order. So here we go. Execute inbound order is also done now. And then we go ahead and return events. And that is our entire modify order. We handled 3 cases here. Same price, smaller quantity, does not lose out on time priority. This one is a no op, and this one gives us price time priority because the price or quantity has increased, and we've handled all of those cases over here. So that's pretty much it for the order book entirely. It was a lot of stuff that we learned in this. We have 3 primarily functions that are going to be used by outside world, and yeah, that's pretty much it. Now, one thing to remember is that this order book is for one symbol. If you scroll down, you'll notice that there's this symbol we are storing, right? This order book is for a single symbol. So we need a wrapper over order book that is going to handle all of these symbols. In real engines, I think there are over 4,000 symbols. So yeah, we need to handle for each one of them. So an order book handles one symbol. We'll have n order books for n symbols. And that is going to be our final file for this part of this tutorial. And we're going to call this matchingengine.h. So this is pretty much the symbol router. What it's doing is just creating a thin layer over this order book, and it will route to the correct order book based on the symbol that's received. If you have NVDA, it's going to route to this order book with NVDA symbol set to it, and all of the things are going to be related to NVDA. Then there'll be another order book created just for APPL or for GOOG and so on. So what we're going to do is very simple, barely 100 lines or 150 lines of code where we add a symbol router over this order book, a thin wrapper over this order book. Let's get into it. So let's go ahead and code it up. What we need to do is first of all import everything. We're going to have a map because, as I mentioned, this file is going to be a symbol router, right? It's going to contain the symbols and the order book related to it. So that's the map. Memory, as we know, we always need it. The span, we are going to deal with span of events because we're trying to call in to the order book, which returns a span of events. Then we have types.h, contains all of our core types, and the order book.h itself. Great. Now let's go ahead and have our namespace. Then we'll have our templated class called matching engine, or actually before that, what we're going to have is a request action where, what is the action that the user is requesting? Is it to add an order, cancel, or modify? Based on this enum class, we're going to decide which function to call from this order book, right? Do we want to add the new order, or do we want to cancel the order, or do we want to modify the order? Based on this enum that will be present in a new structure, we're going to call that inbound order, and this is how it looks. It's going to take in a request action, which is of the type of, by default, it's going to be, well, you want to add a new order, and then it can be like the user can shift it to cancel, modify, whatever they selected, right? Based on this enum, we're going to route to the correct public function that's present here. Then obviously the symbol, what does the inbound order symbol represent? Then the order ID, the side, price, quantity, order type, timestamp, participant ID, trigger price, and display quantity. As you can notice, hidden quantity is not present over here. Peak quantity is not present over here. And also, if you notice, this order is not of the type of the things that are presented in these parameters, like order ID, the side, the price. All of them are not present. The reason for it is this is just a structure for us and for the upstream consumers or the upstream components like the TCP gateway, which try to pass in the inbound order to us. So this is just for the upstream. In the downstream, we are going to decompose all of these individual attributes and pass them through the parameters of this function, like order ID specifically, quantity specifically, and so on. Cool. Now let's go ahead and create the templated class, and actually even before that we need to check if it's trivially copyable or not so that it can pass through correctly. Everything here should be trivially copyable. So we have the request action and inbound order both trivially copyable. Then we'll now finally have the templated class. As usual, we're going to take the order capacity, level, stop, event capacity, all of them. Then we are going to go ahead and create our order book namespace or order name using line, which means if you notice this order book that we have, this is also a templated class, right? And you can pass in an order capacity, event capacity, stop, and level capacities each. And if you want to pass these templates through to this order book, what you need to do is write in a big thing. Like you'll have to do something like this, where you have order book and then you have something like this. Okay, I want to pass in the order capacity. Cool. So my order capacity is this. So you have order capacity, and then you need to pass in level capacity. As you can see, the size of this line is increasing. So what I'm going to do is use a using statement here so that we can just call it a book instead of order book, order capacity, etc. And now we can have something like this done, where we can create a private variable of a map which has a mapping between the symbol and the order book, and we compare using the symbol list. Let's go over it one by one. The key is the symbol. We understand that. I've already mentioned that this matching engine is going to create a mapping from the symbol to the actual order book. Cool. And what is this comparator? Symbolless. If you remember, when we were in types.h, I told you that we're going to compare the order books using a lexicographical comparison. That means N will be after A, and B will be after A, C will be after A, and so on, right? So this map, as we know, is going to be an ordered map, and the order is maintained using this lexicographical symbol. If you want, you can use any other comparator here, but we're using this lexicographical comparison. So this is our books map, and we use the symbolless here so that we could definitely clearly compare these things. Okay, on to the next thing, where we have something like this. We'll have to create a function to prepare the symbols, and it's going to be a first public function that will be used by the exchange runner. Exchange runner is going to be something we create in future tutorials, and what it does is it gives us a span of symbols, and we need to prepare that symbol. How do we do that? Well, we just prepare the symbol by going over each of the symbol and updating our books here. That's all. So if you have 4,000 symbols, it will go over all of these 4,000 symbols. It will add this to this books map, and it will create a new order book for each one if they don't already exist in this books map. So if our exchange wants to support one more order book or one more symbol, all we need to do is update this books map. That's all. That's how easy it is. So let's go ahead and loop over this symbol. We get a reference to it, and now we'll call a function called book_for symbol. So what it does is this function is going to do two things, by the way. Book_for is going to return the order book for a particular symbol. That's number one. And if the symbol does not already exist in the order book, it's going to add it to the map and then return the book. In our case, we are just interested in adding the symbols to our book. Think about it this way. You have a map, okay? And you have, let's say, your symbol. And if you have your symbol, you need your specific order book here. But what if this is a symbol you're adding for the first time? So what will happen in that case? In that case, the symbol does not exist. So if the symbol does not exist, you need to add it. And to add it, what you need to do is paste this in. Right? You need to pass in the key and the value. That's what we're doing here. Now, another thing book_for will do is, let's say you want to know what is the order book for a particular symbol. What is the order book for NVDA? Well, you can look over this map. So you'll have this symbol already exists. Great. So we have the order book returned. But if, let's say, I'm asking what is the order book for Apple, for example, I'll just go ahead and have something like, okay, APPL, and then I'll have to create a new order book here because Apple does not really exist, and then I'll return this order book. That's what this function does. Two things. Direct lookup, and if the lookup does not exist, it will create it and then return the order book. Cool. Let's go ahead and create this private function, book_for. It returns a book reference. And then whatever I mentioned, we're going to put it in code. So we're going to have, well, the first one, books.try emplace, add that symbol, and the value is a null pointer. So if there's a first call for a new symbol, it creates the book. Now, if the inserted value here is true, then we want to do bookIterator.second and we pass in the book value, right? And remember, we're doing make unique here. We do not need to do anything else because it's fine if we allocate this on the heap, because remember, this is related to the allocation. The hot path hasn't started yet. You're preparing all the symbols so that you have the books ready. The order books for each of the symbols is ready. So none of this is on the hot code path. This is all setting up thing. So here you check if the inserted value is true, you'll check bookIterator.second. So you have bookIterator, which gives us this part, something related to this books. And then you take the second value, which is the actual value of the map. bookIterator.first or something like that would only give you the symbol, which is the key. What you're interested in is the value. So you have book iterator.second, and then you go ahead and do make unique, add the symbol in if null pointer was inserted for the first time. Now, if inserted is not true, that means the value already existed, so we don't need to bother with anything. So either ways, if it's inserted or not inserted, we have a specific value. If it's not inserted, we inserted it, so book iterator.second has a value. And if inserted was false, then we did not insert anything because some value already existed. So we're going to have book iterator.second with a value. So in any case, we want to return book iterator.second. So that gives us book for. Now, why did we call this particular function, which seems like allocating the book over here? Well, that's what our goal was, right? All we needed to do is make space in the map so that we could store our symbol and the order book for that symbol. Now the value here does not really matter because all you're trying to do is prepare the symbols. You're just trying to allocate space into this order book. So you can just pass in void here so that the compiler does not argue anymore. The value here, we're not interested. It's okay. We'll use this book for somewhere else where it will help us to actually know what is the order book associated with it, which is the next function we're going to create. And the next function we have is this process order. We take in an inbound order. Inbound order is the structure we just created above, where we take in an action, and based on the action of this inbound order, we are going to decompose all of these individual fields into this function of the order book, like add order or cancel order or modify order. Let's go ahead and do that. So again, we have to check if you're trying to process the order, we're going to call relevant functions from this order book. The first thing we need to check is what is the order book for this symbol. So we'll call this book for again in process order. So we'll have book ampersand book, you have a reference to a book. So you have book for, you pass in the symbol. So you get a relevant book for this symbol. And now for this inbound order that has come in, you're going to use this book and call the specific functions on it, because at the end of the day, this is an order book, right? We had the using over here. So what we'll do is switch order.action. If the case is you want to do and add an order, then we'll do return book.add_order. We'll decompose all of the attributes in here. Order ID is passed in, side, price, order type, timestamp, quantity, participant ID, trigger price, display quantity, all of that is passed in. Now we need to do the same thing for cancel. We'll do the same thing over here, book.cancel order. And we do the same thing for modify order. And we do the same thing here. There's one edge case that we need to handle here, which is what if the order action is none of them? In that case, we just want to return an empty span over the events because this book for or this order.action was something invalid. So just an edge case we are handling here, we just return an empty span. And that's all. With this, we've completed the entire matching engine. Although there's one other function that we can create which will help us downstream or upstream actually, which is find order. You have this prepare symbols, which is first called so that you can allocate something on the order book. Then what you want is process order so that you can process all of these orders that are coming in and direct it to the relevant functions in the order book. And the third thing is finding the relevant order. And to do that, we'll create another function. And the last function we are going to have is find book. What we need to do is given an order, we want to find out what book does it belong to. So we have this. We are given a symbol and we want to find what book it is. And it's very simple for us. All we need to do is books.find for a symbol. If the book iterator is not towards the end, we are going to return a value. If it is towards the end, we'll return a null pointer. And then we just do book iterator.second.get. So if the book is not found, we return a null pointer. And if the book does exist, we do book iterator.second, which gives us the order book. And then we call .get on it. That will give us the actual order book value. the pointer to the order book. So yeah, that's all. This find book will be used by the publisher, I believe, and it is downstream, so it will be helpful there. We've just created it as of now. So yeah, that is part 1 of the stock exchange tutorial. In the next tutorial, we're going to cover the upstream, which is the TCP gateway majorly. And if time permits, we'll also cover the downstream in that, which is the publisher. And that's it for this part of the tutorial. We covered a lot. We created zero allocation infrastructure, like the memory pool, the SPSC queue, the types, all of that. Then we created events.h, which was containing all of our events, the level structure, the order structure. Then we used all of them in order book, and then created a wrapper around order book so that we could have multiple symbols mapping to multiple order books. In the next tutorial, we're going to cover the upstream, which is going to have the TCP gateway majorly, and it will also contain downstream if time permits, which is the publisher, the market liquidity bot, and putting all of this together into our stock exchange and actually seeing a visible output on the screen. So let's see how many tutorials we divide this into. However, the core part of stock exchange was this logic within the order book. How do you handle different types of orders, and how do you do that extremely fast? Now, obviously, even if the order book is fast, you need the other parts of the system to be fast as well, so that during the hot code path, even if order book is not the bottleneck, other components are not the bottleneck as well. So we'll figure that out in the next tutorial. Thanks for watching.